Hi guys, if you are viewing my channel first time, please subscribe to my channel for more updates on embedded systems. Okay, today we'll mainly discuss about an embedded system introduction. Okay, first we'll see the definition of embedded system. An embedded system is a combination of hardware and software designed for a specific function. Let us take the example of washing machine. Okay, it has hardware and also software, and it is designed for a specific functionality like washing the clothes. Okay, washing machine is a one of the embedded system. Okay, we'll take the another example, fan in our home. Okay, it has only the hardware, it does not have any software. That's why it is not a embedded system. We'll take another example. Fire alarm is an embedded system. It will sense only the smoke. Okay, alarm has some hardware and also then some specific software. Then only we are designing this fire alarm. Okay, whenever the fire detected or the smoke detected, it always gives us alarm. Okay, it is one of the embedded system. Okay, we'll see the for the next slide. An embedded system has three components. It has hardware, it has application software. As we discussed in the definition of embedded system, it should be have hardware and also software. And the third point, this one RTOS is a optional one. Real time operating system is a optional one. Okay, a small scale embedded system may not require RTOS. That's why in the definition we are not mentioning this RTOS. Okay, in the small scale embedded system means 8051 microcontroller, we does not require any RTOS. In case of big scale or sophisticated embedded system, we need this RTOS to schedule our application functionalities as per our plan. So we can define an embedded system as a microcontroller based. If I want to design any embedded system, it should be we have to use the hardware as a microcontroller based, and the software driven. We need to write the specific software to the specific application. And reliable, the software, the execution, it should be always consistently, the system should work as per the plan. And real time, we need to achieve our targets as per the real time. Okay, next we'll see the characteristics of embedded system. Okay, if I want to design any embedded system, we need to consider these characteristics. Okay, requires less power. If I want to design any embedded system, it should requires less power. That way we need to design. Okay, next, low cost. We need to select all the hardware and also software low cost manner. And highly stable. Okay, it should work any environment, the always stably. Okay, next one, task specific. It should perform only specific tasks if I want to design any embedded system. Next one, highly reliable. Okay, it should execute the all the tasks consistently, and also performance also it should be very high. And time specific, we need to complete a specific task within this time. That's why this should be a time specific any embedded system. And highly efficient, it should be 100 percentage we need to achieve our goals, whatever the task we need to achieve 100% efficiently. And minimum user interface, if I want to design any embedded system, the interface should be very less. Okay, we need to consider these characteristics before designing any embedded system. Okay, I just given the all the just subheadings here. And we'll see the types of embedded system. Okay, first one is a performance functional requirement, and second one is a performance of the microcontroller. Okay, embedded system we divide into the two types based on performance and functional requirements based on the performance of the microcontroller. The first one, real time. Okay, we need to do all the tasks in a real time manner. Okay, in the real time embedded system we have two types, hard real time and soft real time. Hard real time, nothing but aerospace, air control or the medical. Okay, we need to reach the targets effectively in case of hard real time. Soft real time, it may delay a little bit. Example, multimedia player. Okay, next one is standalone. Okay, it should not depend any other components. For example, fire alarm is one of the standalone embedded system. It does not depend on any other systems. Okay, it is a one specific system. It won't depend on any other systems. That's why it is a standalone. It will take some inputs and it will give us some specific output. And network based, we need to use some internet based or connectivity between the module. We need to use the connectivity. This is a network based embedded system. The last one, mobile based embedded system. Okay, it is a multi functionalities we can implement by using the mobile based. We have the Android and also iOS. By using that we can design this mobile based embedded system, and based on the performance of the microcontroller, and we have the three types: small scale, medium scale, and sophisticated. And performance mainly based on the 8-bit or 16-bit or 32-bit controllers, right? And in case of small scale, our controller is 8-bit. In case of medium scale, 16-bit and 32-bit microcontrollers comes under the medium scale, and more than 32-bit it will be sophisticated microcontrollers. Here based on the performance, how much our processing speed, we are dividing our microcontroller types here. Here these three types our embedded system types. Okay, here mainly we just divide into the based on the performance and function requirements are four types, and the based on the performance we have three types. Okay, the just similar way I just given the just same explanation here, and we'll see the application of embedded system. Okay, the first thing, consumer electronics, we have televisions, digital camera, and computer printers, video games, and home entertainment like PS4 we have, right? That is also one of the embedded system. And household appliances like refrigerator, washing machine, microwave, air condition, these are the household appliances. And medical equipment, scanners like MRI, CT scan, or ECG device monitor blood pressure and also heartbeat. Okay, these are the medical equipments we are designing by using the embedded system. Similar way, automotives and fuel injection systems and anti-lock braking system, music and entertainment like multimedia, and controls for the air condition. Okay, these are the many real-time applications in our automotive as well. And industrial applications, assembly lines, system for feedback, systems for data collection. Okay, these are the mainly industrial applications. Next, aerospace, system for navigation guidance like GPS and all. Okay, communication routers and satellite phones. Okay, mainly if I want to design any specific embedded system, we need hardware and also software. Okay, we need to use the microcontroller. It should not be any microprocessor. We need to use the microcontroller based embedded system. About on numbering and coding systems. Okay, here we'll see the difference between the decimal system and binary system. Human beings use base 10 decimal arithmetic. There are 10 distinct symbols: 0 to 9, 10 to 19, 20 to 29. This is the way we are representing our decimal system. Computer use base 2 binary system. There are only zeros and ones. These two binary digits are commonly referred to as bits. Okay, here we'll take one example, one decimal number. That decimal number we will convert to the binary. Okay, if I want to convert decimal to binary, we need to follow these many steps. Divide the decimal number by 2 repeatedly. Keep track of all the reminders. Here, continue this process until coefficient becomes 0. Okay, write the reminders in a reverse order to obtain the final binary number. Okay, here I have taken one example: binary decimal 25, base 10 means decimal. Okay, I am just converting to the binary. 25 is my numerator. I am just dividing with 2 in my first step. I got the coefficient 12, remainder is 1. Next I am taking this coefficient as my remainder, that I am dividing with 2. I got the coefficient 6 and remainder is 0. Next I am taking this coefficient as my remainder and dividing with 2. I got the coefficient is 3 and remainder is 0. Next step, this coefficient I'm taking it as remainder. I'm dividing with 2. I got coefficient 1, remainder 1. Finally, this coefficient 1 divided by 2, 0. I got the coefficient and remainder is 1. Okay, I got the all the reminders. Then we need to represent in a reverse order: 1 1 0 0 1. Okay, similar way I represented here: 1 1 0 0 1. Okay, this is the decimal system with 10. This is equivalent to binary: 1 1 0 0 1. Okay, this is the way we need to convert any decimal number to the binary. Okay, next we'll take another example. We'll take same binary number 11001. Same binary number I'm taking here, and that binary number will convert to the decimal. Okay, know the weight of each bit in a binary number and add them together to get the decimal equivalent. Okay, here just I have taken one example: 11001. Same binary number I am taking, 11001.
Okay, this binary number I want to convert to the decimal. First we need to represent our weights. From LSB to MSB we need to represent the weights: 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4. Okay, similar way, this is my digits: 11001, this is my 11001, this is my binary. Okay, here 2 power 0 means 1 multiply 1, I got 1. 2 power 1, 2 multiply 0, I got 0. 2 power 2, 4 multiply 0, I got 0. 2 power 3, 8 multiply 1, I got 8. 2 power 4, 16 multiply 1, I got 16. Just I am adding all the numbers here. I got 25 decimal. This is a binary, equivalent to decimal is 25. Similar way here I just converted decimal to binary. Similar way I just converted to binary to decimal, I got the same. Okay, use the concept of weight to convert a decimal number to binary directly. Okay, this is the weight. Here I'm just giving 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 5 means 32. Next 2 power 0, 2 power 1, 2 power 2. 2 power 0 means 1, 2 power 1 means 2, 2 power 2 means 4. This is my 32 already covered here. I have only 7 left. That's why I'm adding last 3 digits, 4 plus 6 and 7. That's why I just represented the same way: 1 0 0 1 1 1. Okay, similar way I just represented with 39 using the binary. Okay, this 39 equivalent decimal we converted to the binary using the weights. Okay, next we'll see the hexadecimal system. As of now, we discussed binary and decimal. Now we'll discuss more on hexadecimal. Here, the hexadecimal base is 16. Okay, used as a convenient representation of the binary numbers. It is much easier to represent a strings of zeros and ones, such as hexadecimal equivalent to 896H. Okay, we need to take the four digits from the left side to right side. Okay, first 4 digits I'm taking from the left side. 0110 means 6. 0110 means 6. This is my 6. And the next 4 digits, 1001 means 9. 1001 means 9. And the last 4 digits, 10008. This is a way we can represent bunch of zeros or ones. We can represent using the hexadecimal. By each and every 4 digits we can take, and we can represent equivalent hex. This is a way we can represent easily. Okay, this is my decimal number system: 0 to 9, 10 to 19, and 20 to 29. This is the way we can represent our decimal system. And binary system, we can convert by using the weights, or by using the division we can convert to the binary: 000, 0001, 0011. This is a way we can represent. Okay, if you see LSB, all are 01010101. The next LSB, 2 zeros 2 ones. The next LSB, 4 zeros 4 ones. And the next LSB, 8081. This is a way we can represent all the binary system easily: 0101, next 2 zeros 2 ones, next 4 zeros 4 1, next 8 zeros 8 ones. This is a way we can represent our binary system easily. Okay, next hex format: 0 to F, 0 to 9 digits, and after 9 A to F, again 10 to 1F, 20 to 2F. This is the way we can represent our hexadecimal system. Okay, then we'll see for the next slides. Okay, we'll take one example, one a binary system. That binary system will convert to hex. To represent a binary system as it is equivalent to hexadecimal number, start from a right and group 4 bits at a time. Replace 4 bits binary number. It's equivalent to hex. Okay, here I have one binary system: 100510101. Okay, here we need to take 4 from the left side onwards. Okay, 0101, just I have taken the 4 digits. Next 4 digits, 1111. Next last 4 digits, 1001. Okay, here 0101 means 5. Okay, if you want you can just refer from here. 0101 means 5. Okay, this is a 5. And all ones means F. All ones means F. Okay, and 1001 means 9. Okay, similar way you can refer here. 1001 means 9. Okay, this is a way we can just group 4 digits, and we can just represent with equivalent to hex. And this way we can convert from binary to hex. Next, to convert hex to binary. Okay, here I am just converting to hex to binary. Each hex digit replace with 4 bits binary equivalent. Okay, here 29B, this is my hexadecimal system that I want to convert to the binary. to 9B. I just separated all the digits. Each digit I am representing with the binary. What is my B? 1011. What is my B equivalent? 1011 binary. Okay, similar way 9 means 1009. This is my 9, I just represented 9. 1009. And what is my 20010? Okay, this is the easiest way we can just convert our hex to binary. Okay, easily just we can convert. Okay, we'll see the next example. Okay, we'll take another decimal number to hex. Okay, we'll take one example, one decimal number system we'll convert to the hex. Okay, first if I want to convert decimal to hex, first we need to convert to the decimal. After the decimal to hex, very easy. Okay, here similar way, first decimal to binary, that binary to will convert to hex, very easiest way. Convert the binary first, then convert to hex. Whatever the decimal system, first we need to convert to binary. From binary to hex is very easy. Convert directly from decimal to hex, and repeated division, and keep track of reminders. Okay, here we'll take one decimal system and we'll see how we'll convert. Okay, here 45 is my decimal system. Just I am representing my by binary system here using the weights. 2 power 0 is 1, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5 means 32. That's why I have represented 1 here. Okay, 32 is already covered here. How many left? Only 14 left. Okay, 8 plus 4, 12 already covered, and one more left here, 13. Okay, already 44 were covered, and the last digit is 1. Okay, this is equivalent to binary. Using the weight, just we converted 101101. Okay, here I just converted the binary. This binary we can convert to hex easily. Just we need to group four digits from the left side. Okay, 1101 means this is my D. 1101, here you can refer. 1101 means D. Okay, D I represented these four digits. I just represented with D. The first two bits I will represent with 0010. Why? Because I don't have any other bits, right? The first two digits I will represent 0010 means 2. Okay, similar way 0010 means 2. Okay, this is a way simply we can convert binary to hex, very easiest way. Okay, similar way we'll take another decimal system, then we will convert to hex. Okay, here 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5, 2 power 6, 2 power 7, 2 power 8, 2 power 9 means 512. Okay, here 512 already covered. If I just mention 1 to this weight, already 512 is covered, and remaining I need to cover 512 minus 629. Remaining digits I need to cover 64, 32, and 16. Okay, here only 5 are left. I just given the weights to here. Okay, just I converted by using this 629. If I just add this one, this one, this one, this one, this one, and this one, then I will get 629. Okay, by using the weights we converted this 629 decimal to binary. Now from binary to hex is very easiest way. Okay, here from the last four digits we need to take 0101 means 5, and after that 0111 means 7, and first two digits will take 0010 means 2. Okay, from hex to from the binary to hex we can just convert. We'll take the 4 bits, then we'll write the equivalent hex. Okay, this is a way simply we can convert. Okay, we'll take another example. We'll take one hexadecimal number that will convert to decimal. Okay, convert from hex to binary, then to decimal. Okay, similar way, if I want to convert hex to decimal, first hex to binary we will convert. From binary to hex we can binary to decimal we will convert easiest way by using weights. Okay, here this is my hexadecimal number 6b2. Okay, what is my 20010? This is my binary system. I just represented equivalent to binary 0010. Similar way, B means 1011. You can refer from here. B means similar way, you can refer from there. Okay, similar way, I just represented 1011 is my B. Last 6 means 0110. This is my 6. Okay, just I just converted each and every digit. I'm just represented with binary. I got the binary number. Okay, now we'll just given the weight 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5, 2 power 6, 2 power 7, 2 power 8, 2 power 9, 2 power 10 means 10 to 4. Okay, here I have 2 power 10 multiply 1 means 10 to 4. 512 multiply 1, 512. 256 multiply 0. Okay, this is 0. Okay, 128 I just replaced here, and 64 also 0. 32 multiply 1 32, 16 multiply 1 16, 8 and 4 are 0, 2 power 2 into 1 means 2. Okay, if I just add, I got the equivalent. 17 14 is my equivalent decimal. This is the way. If I want to convert hex to decimal, first we need to convert to the binary, and after that decimal. Okay, this is the way we want to discuss more on the numbering and coding with respect to our embedded system. Thank you, friends. Today we are mainly discussing about a digital primer. We will discuss few digital basics with respect to our embedded system. Okay, here first one is a binary logic. Two voltage levels can be represented as two digits 0 and 1. Here logic 0 we have one voltage level, and logic 1 we have another voltage level. Signals in digital electronics have two distinct voltage levels with built-in tolerances for variations in the voltage. For example, 0 volt to 1 volt we are considering it as logic 0. 3 volts to 5 volt we are considering it as logic 1. A valid digital signal should be within either of the two shaded areas. For example, if I want to consider a valid logic, the voltage level should be within this shaded range, otherwise it will be invalid logic. Okay, next we'll discuss on the logic gates. First one is the AND gate. This is my boolean expression, output equal to a dot b. Okay, this is my AND gate symbol. Okay, here I have two inputs, 2 power 2, I have four combinations, 0 0 0 1 1 0 1 1. This is my output. If all inputs are 1, then only my output is 1, otherwise my output is 0. If any input is 0, my output always 0. This is my AND gate truth table. Similarly, we will discuss OR gate. This is my boolean expression, output equal to a plus b. This is my OR symbol. Okay, here again I have two inputs, 2 power 2, we have four combinations, 0 0 0 1 1 0 1 1. Okay, here if any input is 1, my output is 1. If all inputs are 0, then only my output is 0. This is my OR gate. Okay, next we'll discuss on the tri-state buffer. Okay, here we have one data input, one enable, one output. This is the inversion output. Okay, here I have enable pin. If my enable pin is 0, my output always high. Okay, if you see output, if any in any case of input, my output always high. Okay, next we'll see if my enable is 1, my input will be inverted to the output. See here the enable is 1, my input is 0, my output is 1. Similarly, my enable is 1, my input is 1, my output is 0, inverted output. See, whenever the enable pin is activated, then only my input will be inverted to the output. This is my tri-state buffer. Okay, next we'll discuss on the inverter. This is my output x equal to a bar. A is my input, my output is a bar. Here I have only one combination, 0 and 1. 2 power 1 means 2. Here we have only 0 and 1. 0 means my output is 1, 1 means 0. Okay, it will be inverted output. Okay, XR, this is my boolean expression, x equal to a exclusive b. This is my boolean expression. This is my exclusive r. Okay, this is my symbol of my exclusive r. Again I have two inputs, 2 power 2, we have four combinations, 0 0 0 1 1 0 1 1. Here mainly this XR we are using for the parity checking. Okay, here if it is having odd number of ones, then my output is 1. Even number of ones, my output is 0. Okay, this is a way for parity checking we are using this mainly XOR gate. Okay, next here we'll discuss more on the NAND gate. Already we know the AND gate. A dot B is my AND gate. To the bar is my NAND gate. Okay, this is my AND gate. I just added my bubble, inverted output is my NAND gate. Okay, here if all inputs are 1, my output is 0. If any input is 0, my output is 1. Okay, this is my NAND gate truth table. Okay, next NOR gate. This is the inversion of the OR gate. A plus B is my OR gate boolean expression. Just I am giving the complement. This is my OR gate. I am just adding my bubble. This is my NOR gate. Okay, again 0 0 0 1 1 0 1 1. Because of these two inputs, 2 power 2, we have four combinations. Okay, if all inputs are 0, my output is 1. If any input is 1, my output is 0. This is the inverted output. If you see here, AND gate is 0001, here NAND gate is 1110, inverted output just. Okay, here OR gate 0111, here 1000. This is the inverted output, just simple. Okay, next we'll discuss on the off adder and full adder. Okay, here by using basic gates we are designing the off adder and full adder. If I want to add two digits, then we are using this off adder. For example, if I want to design one exclusive OR by using one AND gate, two AND gates, one OR gate, we are designing one exclusive OR, and one AND gate just I replaced here. Okay, this is the same logic designs. I'm using the one XR and one AND gate. S equal to X exclusive B exclusive Y, X exclusive Y. This is my exclusive R. This is my carry is my output X and Y. Okay, similar way we'll understand here. For example, let us assume X and Y. I am just mentioned it as A and B. Okay, here my just replacement X I represented with A and Y I represented with B. Okay, here 0 0, here I have again two inputs. I have four combinations 0 0 0 1 1 0 1 1. Okay, here I am doing the sum. Okay, here I will get the sum 0 plus 0 0, 0 plus 1 1, and 1 plus 0 1, and here 1 plus 1 means 1 0 1 0 0 is sum, 1 is carry. Okay, this is a similar way I represented output. Okay, here I have two inputs, I have two outputs here. By using off adder we can add only the two inputs. Okay, for example, why the full adder is required? If I want to add a carry, then full adder is required. Here I cannot add one more input. Here we have only two inputs and two outputs. In case of full adder, we are using two off adders. We are designing one full adder. Okay, here one exclusive, one AND is my one of the off adder. This is another off adder. Just I am using one of the or gate. Okay, this way I am designing my full adder. Okay, full adder, it will take the three inputs and two outputs. One is sum and other is carry. Okay, here X, Y, I'm just replacing with A, B, and Z I'm replacing with C and Y, because this I can use for the carry. Okay, so that I can add three inputs here. Okay, 0 0 0, I have three inputs. 2 power 3 means 8 combination. Here 0 1 0 1 0 1, this way we can represent easily. Two zeros, two ones, two zeros, two ones, four zeros, four ones. This is the way we can represent our binary just representation. Okay, if I want to add the all the digits 0 0 plus 0 plus 0, I will get the 0 sum and 0 carry. Okay, similarly 0 plus 0 plus 1 1. Here sum is 1, carry is 0. Similarly, I have 1, 0 plus 1 plus 0. I have sum is 1, carry is 0. Here 0 plus 1 plus 1. Here we have two ones means my output is 1 0. 0 is sum, carry is 1. Similarly, I have only 1 in this row. 1 plus 0 plus 0. I have only one sum, carry is 0. Here I have two ones means 1 0 output. 0 is sum, carry is 1. Okay, next I have again two ones. My output is 1 0. 0 is my sum, carry is 1. I have three ones. Three ones means 1 plus 1 plus 1. I have 1 1. 1 1 my output, addition output. That's why carry is 1, sum is 1. This is a way I got two outputs using the three inputs. Okay, if I want to design a one 4-bit adder, so that I can use four full adders. Okay, here it is taking the carry from the previous. Initially carry is 0 and two inputs. These are three inputs and two outputs. Again three inputs, two outputs. Three inputs, two outputs. Okay, again three inputs, two outputs. Okay, by using full adder we are adding only two bits here. Okay, two bits, one carry. Okay, similar way here I am designing the 4-bit adder. Okay, here from the carry is my another input. Okay, here just I am using the full adder, four full adders. I am designing 4-bit adder, so that here I can add four 4-bit adders here: a0, a1, a2, a3, and b0, b1, b2, b3. Okay, this is a 4-bit adder. By using four full adders I am designing the one 4-bit adder. Okay, here we'll discuss more on the address decoder. Decoder can be widely used for address decoding in the computer design. Okay, here I have the address decoder for the 9 1001. This is my 9. I am passing to the input 00. This is my middle two zeros. It will be complemented to 1 1. Okay, AND gate to the all the inputs to the AND gate will be all are ones. My output is 1. Okay, here the output will be 1 if only the input 1001. Why? Because these two zeros will be inverted to the 1. Four ones I am passing to the AND gate, my output is 1. Okay, similar way I am passing to the Y. This is my LSB is my 1. Okay, 1 0 1 0 I am passing to here. 0 it will be complemented to 1. Again 0 will be complemented to 1. 4 1 4 ones I am passing to this AND gate. Again my output will be 1. Okay, here is LSB is top. Why? Because this is my LSB 1 0 1 0. Okay, similar way I represented here. What is my input will be all ones. 1 0 means it will be complemented to 1. Again 1 0, 0 will be complemented to 1. All four ones I am giving to the AND gate, my output is 1. By using this address decoding, we can just find out whether logic 1 or logic 0. Okay, next we'll discuss on the flip flop. Okay, if I want to store one bit of data, we need this digital gate, one of the flip flop, to store our data. For example, if my clock is 0, I'm not giving any clock, there is no change in our data. For example, if I am giving to the clock 0, my next state, I'm just giving the clock, my next state is 0. Okay, similar way, I'm just giving my data is 1, my next state is always 1. Why? Because here it is able to store one bit. By using the flip flop, we are able to store one bit. This is a logic gate, it will store one bit in the next state. For example, if I give the clock, whatever the previous stored bit, it will get the output in the current state. Okay, this is the way we are using the flip flops, we are designing our memories. For example, if I want to design 1 MB of memory, we need to these many flip flops we need to use and design our memories. Okay, next we'll discuss units of the data size. For example, in case of bit, either 0 or 1, we are calling it as bit. Byte means 8 bits, either zeros or ones. We need to consider 8 bits, we are calling it as 1 byte. Nibble means only 4 bits. Word means 2 bytes or 16 bit. Okay, this is my word. We need to remember byte means 8 bits, nibble means 4 bits, and word means 16 bits. And here I want to represent the memories like 2 power 10 means 1 KB, 2 power 10 bytes means 1 KB, 2 power 20 bytes means 1 MB, and 2 power 30 bytes means 1 GB, and 2 power 40 means 1 TB. Okay, based on the bytes we are representing our memories. Okay, this is the way we need to represent our memories. Okay, mainly we need to remember what is the units and also this memory alignment. What is my 1 MB means? 1 MB means 2 power 20, 1 GB means 2 power 30, and 1 TB means 2 power 40 bytes. These many bytes we are considering and we are representing with this kilo, mega, and giga and terabytes. Today we are mainly discussing about on inside the computer. First one is the important terminology. The unit of data size bit, a binary digit that can have the value 0 or 1. Byte 8 bits. Nibble half a byte or 4 bits. Word 2 bytes or 16 bits. The terms used to describe amount of memory in IBM PCs and compatibles. Kilobyte capital K 2 power 10 bytes. Megabyte capital M 2 power 20 bytes. Gigabyte capital G 2 power 30 bytes. Terabyte capital T 2 power 40 bytes. Mainly, we need to remember these terminologies in case of any computer. The CPU is connected to memory and I/O through strips of wire called a bus. Here, CPU or processor is connected to memories, RAM or ROM, and also I/O device, printer, disk, monitor, keyboard. These are the I/O devices are connected through a bus. Okay, here carries information from place to place. We are using address bus, data bus, and control bus. We'll discuss one by one here. Address bus is a unidirectional. If you see the arrow, it is showing only the one direction. If you want to identify any hardware device or a particular memory location, we are using this address bus mainly. Okay, here for example, if I have the only the address bus, I have only the 8-bit addressing, so that my addressing range 8 zeros to 8 ones, so that my 8 zeros my binary I am representing with x here 0x00, 8 ones I represented with hex here 0xff. This is my addressing range. 2 power 8 means 256. This my locations are 256. This is a way we can identify how many locations between this range. Okay, 256 locations, and each location I am storing 1 byte in our CPU. That's why 256 bytes. For example, if we have our 8-bit addressing, we can store up to 256 bytes. For example, let us take another example. We have 16-bit addressing. We have 16-bit address bus. We can access up to 16 zeros I represented with X format 0x 4 zeros. 16 ones I represented with X format 0xff. This is my addressing range for the 16 bit. 2 power 16, this is my memory I can access by using this address. 2 power 16 means 64 kilobytes. Here, as we discussed initially, 2 power 10 means 1 KB, and 2 power 11 means 2 KB, 2 power 12 means 4 KB, 2 power 13 means 8 KB, 2 power 14 means 16 KB, 2 power 15 means 32 KB, 2 power 16 means 64 KB. Here 2 power address lines equal to that much memory we can access. 2 power 15, these my 15 address lines we can access up to 32 kilobytes. Here based on our address lines we can access that much memory. For example, if we have 30 address lines we can access up to 1 GB. Okay, mainly by the use of address bus we can access, we can identify the particular hardware or a particular memory locations. And the data bus is a bidirectional one. Okay, if I want to read the data from the memory or write the data to the memory, we are using this data bus. Data bus is a bidirectional. If you see the RAM, it is a read or write access memory. Okay, it is both read or write, that's why I'm giving the both the directions. ROM, it is only the read only memory, so that I'm giving only one direction. Printer, it is the output device, I'm giving the out arrow. And disk is a read or write, I can read the data from disk and also write the data to the disk, I'm giving the both the directions. Monitor is the output device, I'm giving the out arrow. Keyboard is the input device, I'm giving the input arrow. And this is my data bus. Okay, here the mainly our processing speed we are mentioning using the data bus. For example, here we have the 8-bit data bus. Our CPU is 8-bit CPU. For example, 16-bit data bus, my CPU is 16-bit. For example, 32-bit data bus, I have 32-bit CPU. Okay, mainly our processing speed mainly based on our data bus. Okay, here the mainly here data bus, for example, this is a RAM, random access memory. It is a temporary memory. Whenever the power is off, completely this memory will be erased. Read only memory or program memory. Okay, whenever the power is off, still our data is retained. Okay, this is a printer, these are the IO devices. Okay, mainly data bus used to read or write the data from the memories. Okay, control bus, if I want to specify whether I want to read or write the data from the memory, we need this control signal. Okay, for example, let us take, I have one memory location, let us take 0x01. For example, this memory location data I want to read, so that the first I need to locate the address with 01. By using the address bus I want to identify the location with 0x01. Okay, I'm able to identify the address by using the address bus. So that after that I want to read the data or write the data by using the control. For example, I want to read the data from this location, so that the control I can give the indication to read. By using data bus I can read the data from this memory. Okay, similar way I want to write the data to the same location. By using address bus I can identify the location. I'm using the control bus to give the read signal. Okay, give the write signal. Right now I'm writing the data to the memory, so that I'm giving the write signal to the this control bus. By using data bus I can write the data. Okay, these are mainly we are using these three buses. If I want to read the data or write the data to the particular location, we need these three buses. Okay, mainly this is our mainly CPU inside our computer. Okay, next our inside the CPU we have our ALU. This is one of the logical circuitry. If you want to perform arithmetic and logical operations, we need this ALU, arithmetic logical circuitry. Okay, it will perform arithmetic and logical operations. Arithmetic means addition, subtraction, multiplication and division, and logical operations means undo or not. Okay, if you want to perform these operations we need a few registers. Okay, we are using these registers to perform the operations. And here program counter, if I want to fetch any address, for example next instruction to be executed, if I want to find out the address to the next instruction to be executed, we are using the program counter. Okay, it will always increment +1. For example, if it is 8-bit controller, my program counter increment by 1. If it is my 16-bit controller, my if my processor is 16-bit, my program counter increment by 2. If my 32-bit, it will increment by 4. Why? Because each memory locations we are storing it only 1 bit. Okay, that's why here program counter always fetches the next instruction to be executed. Okay, this is a program counter, use of the program counter. Next one, instruction register, instruction decoder, timing and controller. Okay, these are the mainly used to decode the instruction. For example, we have the some assembly instructions. If you want to decode and give to the piece of code to the ALU, we are using this instruction decoders. Okay, mainly if you want to decode any instructions, we are using these registers. And mainly this is a use of the instruction decoders. Okay, it is a mainly it is also one of the logic circuitry. It is used to decode the instructions. Okay, mainly these are the registers to perform the ALU operations. We are using these registers. Program counter to fetch the next instruction to be executed. Okay, this is the inside the CPU we want to. Today we are mainly discussing about on microcontroller versus microprocessor. Okay, which one we need to choose to design an any embedded application. Okay, to design any embedded application, we need the CPU, RAM, ROM memories, I/O ports, timers, and also serial communication port. Okay, if I want to perform any arithmetic and logical operation, then we need CPU. If I want to store any temporary data, then we need this random access memory. If I want to store our application program, then we need this read-only memory. Okay, if I want to communicate with the switch or sensor or any other I/O devices, then we need this I/O ports. Then if I want to perform any timing or counting applications, then we need these timers. If I want to communicate with any other devices, then we need this serial communication port. So that if you want to design any embedded application, we need this all the devices. Okay, for example, if I choose microprocessor as a base for our any application designing, then we need to connect all other devices externally through the data bus or address bus or control bus. Okay, in case of microprocessor, all the devices are available in a single chip. That's why we are calling it as system on chip. Okay, here the CPU or processor, here RAM or ROM memories, I/O ports, timers, serial communication ports, all are available in a single chip. Okay, based on these many criterias, we are going to the microcontroller. Okay, here the space is very less compared to our microprocessor with other devices, and here the complexity. Here all the devices are available in a single chip. Here we need to connect all other devices externally through the buses. Okay, here the very much complexity. Okay, next here the power consumption is very less. Why? Because it has only the one chip. Here we need to feed the power supply to the all the devices, so that it will consume the very much power supply than our microcontroller, and it is very less cost compared to our microprocessor with other devices, and it is a single application, so that the single application we are flashing to this read only memory, so that we are designing one dedicated application by using this microcontroller. Okay, in case of microprocessor, we are using to perform a multiple tasks. Okay, we are loading multiple tasks to the RAM memory, and based on our RTOS scheduling, we are performing one by one task by using our CPU. Okay, this is mainly for multitasking. We are using this general purpose microprocessor. In case of single applications, then we are using the microcontroller. Okay, mainly based on these many criterias, we are going to the microcontroller instead of microprocessor.
Today we are mainly discussing about an criteria for choosing a microcontroller. What and all criteria we need to follow to select a particular controller. We'll discuss more on this point today. Okay, first point, 8-bit microcontrollers, Motorola 6811, Intel's 8051, Gelox Z8, microchips PIC. There are also 16-bit and 32-bit microcontrollers made by various chip makers. Here the first point, based on our application requirement, we need to select either 8-bit microcontroller or 16-bit microcontroller or 32-bit microcontroller. This is the first criteria. For example, if my application requirement is very small, like smoke detector, so that I can use the 8-bit microcontroller. For example, if my application requirement is very big, like washing machine or fridge, so that I can select the 16-bit or 32-bit microcontroller. Okay, this is the first criteria. Okay, the next one, meeting a computing needs of your task at hand efficiently and cost effectively. Okay, we need to achieve our target efficiently and also cost effectively. Based on that, we need to select our microcontroller. First one is the speed. Speed should be effectively, we need to select based on our requirement. And the packaging, either dual inline package or quad package, we need to select the different types of package based on the space constraint. We need to select the package. The next one is the power consumption. For example, if you take the 8051 microcontroller, the power consumption will be 5 volts. If I take the ARM7 or some other microcontroller, the power consumption will be 3.3 volts. Okay, based on our power consumption also, we need to select our microcontroller. Why? Because the backup of the microcontroller will be more if the power consumption is very less. Okay, the amount of RAM and ROM memory on the chip. Okay, based on our RAM and ROM memories, also we can select the microcontroller. Based on our if the program memory is more than 4 KB, then we need to go for other microcontroller. Why? Because our 8051 has only the 4 KB of memory of ROM, read-only memory. That's why if the RAM has only 128 bytes, If it is more than 128 bytes, then we need to go for the other microcontroller. Based on our memories also, we need to go for another microcontrollers. The number of IO pins and timers on a chip. Okay, based on if the IO pins are not sufficient, if I use the 8051 microcontroller, my IO pins are only within 32 IO pins. For example, if these 32 pins are not sufficient, then we need to go for other microcontroller. For example, here the 8051, if I take, I have only the two timers. If these two timers are not sufficient for your application requirement, then we need to go for another microcontroller. Next here, how easy to upgrade higher performance and low power consumption versions. Okay, easy to upgrade to higher versions also should be compatible, and also cost per unit also very less. Okay, these are all criteria we need to follow in case of selecting any microcontroller. Okay, the next one, availability of software development tools such as compilers, assemblers, debuggers. For example, if I select any microcontroller, I should have all the possibilities. I should have a compiler, should have a assemblers, I should have a debugger. Okay, whenever we are selecting any microcontroller, we should have all the compatible tools should be available. Okay, wide availability of resources of microcontroller. The 8051 family has largest number of diversity, multiple source suppliers. Okay, 8051 first developed by Intel in 1981. Okay, and after that the remaining manufacturers also allowed by Intel, so that the only one criteria mentioned by Intel, it should be compatible with 8051. The all the variants of different manufacturers should be compatible with 8051 Intel microcontroller. Okay, that's why the remaining manufacturers also developed their own 8051 microcontroller, but it should compatible with 8051. Okay, this is a mainly family of the 8051. That's why we are mainly discussing about on 8051 further sessions.
Discussing about on features of 8051 microcontroller. It is 8-bit microcontroller. Why we are calling it as 8-bit microcontroller? It will perform the arithmetic and logical operations with 8-bit. That's why we are calling it as 8-bit microcontroller. It has on-chip 4 kilobytes of read-only memory or program memory. It is mainly used for our application program storing. It has 128 bytes of on-chip RAM, random access memory or data memory, mainly used to store our temporary data. 16 memory locations of data memory or bit or byte addressable. Okay, out of this 128 bytes, 16 bytes memory locations are bit or byte accessible. Okay, we can access bitwise as well as bytewise also by using this feature. The data and program memory can extend up to 64 kilobytes. Okay, we can connect external memory, either program memory or data memory. The RAM or ROM we can connect externally up to 64 kilobytes of memory to our microcontroller. Okay, it has four parallel IO ports: port 0, port 1, port 2, port 3. Each port is 8-bit directional IO port. Okay, it can we can use input or output. Each port is bit or byte addressable. We can access each pin wise as well as complete port wise. Okay, this is also one of the feature. It has 16-bit multi-mode programmable timer or counter. Okay, here we have two 16-bit timers that we can use for the mainly timing or counting applications. It has multi-mode high-speed programmable full duplex serial port. It has only the one serial port. Mainly it is used for our serial communication between the devices. It has 5 hardware interrupts, 3 internal interrupts, nothing but 3 software interrupt and 2 external interrupts. Okay, timer 0, timer 1, TI or RI, transmit interrupt or receive interrupt. Okay, these three are internal interrupts or software interrupts. Interrupt 0 and interrupt 1 are external interrupts, hardware interrupts. Okay, these are mainly 5 interrupts. This is also one of the feature. If I want to do any service upon a interrupt, then we can use these 5 interrupts. It has on-chip power saving circuit operated in two modes. Okay, it is also one of the circuitries available, so we can switch between the two modes, ideal mode or power down mode. Okay, these two are power saving modes. If I want to reduce the power consumption from 5 volts to less than 5 volts, so that we can switch to either of these two modes. Okay, here we will see the just relationship between the 8051, 8052, 8031. Okay, as we discussed already with 8051, it is 4 KB of our program memory and 128 bytes of random access memory or data memory, two timers and four IO ports, and each port having 8 pins. That's why we have 32 pins and one serial port and 5 interrupts. And already we discussed regarding the 8051. With respect to 8052, only the memory change here 4 KB to 8 KB, we have it is extended to double. And also here 128 bytes of random access memory, here 256 bytes of random access memory. Here two timers, here one more timer is additional. This is also one of the feature. And here one more additional, here two interrupts are added here in case of 8052. Here we have one extra timer, we have one more option with extra interrupt, timer 2 interrupt, and also one external interrupt. That's why here interrupt 2. Okay, here in case of 8031 or 8051, here we have three software interrupts and two hardware interrupts. In case of 8052, we have the four software interrupts, three hardware interrupts. Totally seven interrupts in case of our 8052. Okay, this is the main difference between 8051 and 52. In case of 80, difference between the 8031 and 51, only the this is a programless controller. Okay, only this is only the change. Okay, this is a it is a zero ROM memory. Okay, it has only the zero ROM memory. If I want to program our to this microcontroller, we need to connect external memory up to 64 kilobytes of memory we can connect externally. If I want to connect external memory, we need two IO ports, we need 16 IO pins to connect our external memory. Okay, that's why mainly we can go for 8051 or 52 to get more IO ports.
Discussing about on pin diagram of 8051 microcontroller. Okay, first if I see 8051 microcontroller, I can see only the two sides having the pin. That's why we are calling it as 8051 is a dual inline package. And how to denote all the pins we'll discuss now. First we need to identify the notch. From the notch, the left side is my first pin. From that 1 to 20 is my left side, 21 to 40 is my right side. Okay, this is the way we need to represent our pin numbers. Okay, next one we need to draw one S here. Okay, this is my port 0, this is my port 1, port 2, port 3. This is the way we need to identify the ports locations. Okay, next one, here each port having 8 pins, totally 32 pins are covered. Next we'll discuss how to denote the remaining 8 pins. Okay, here 20 is my ground and 40 is my VCC. Okay, again two pins are over, only I have 6 pins left. Okay, the right side EA bar, ALE and PSEN bar. Okay, in between this port 0 and port 1 we need to mention here EA bar, ALE, PSEN bar. This is for the external memory accessing. Okay, next one is in between port 1 and port 3 we need to represent the reset. Okay, finally crystal 1, crystal 2, if I want to connect any external crystal oscillator, so that I can use this 18 and 19th pin. Okay, totally this remaining 8 pins, 2 plus 3, here 4, 5, 6, 7, 8. Okay, 8 remaining. Okay, this is the way we need to represent our pin diagram. Okay, next one we'll discuss each and every pin functionality. Okay, first one is a port 1. Okay, port 1 is only we are having the input and output functionality. Either we can connect a switch or LED or LCD. For that purpose, we can use this port 1. Okay, there is no special functionalities, just it is a input and output functionalities. Okay, next one is our reset. Okay, if I want to start from the execution. Okay, for example, if my microcontroller is at the execution at the 1000 memory location, I want to reset back to 0, so that I can use this reset pin. Okay, next one is port 3. Initially port 3 we can use input and output functionality, and also we have some special functionalities also. For example, in my application use case, we have the transmission and reception also, so that I can use this TXD pin and RXD pin. These two we can use. If I want to transmit the data serially, so that I can use this TXD pin. If I want to receive the data from external device, so that I can use the RXD pin. For example, if there is no serial communication, these two pins we can use for the input and output use case. Okay, next two pins are interrupt 0 and interrupt 1.
port 3.2 and 3.3 are interrupt 0 and interrupt 1. For example, if I want to do any service upon a external interrupt, so that I can use these two pins. Okay, on any clock or clock change or any edge triggered, so that we need to do any external service, so that I can use this interrupt 0 and interrupt 1. Okay, next one is timer 0 and timer 1. This port 3.4 and 3.5, timer 0 and timer 1. Okay, we have two timers in our 8051 microcontroller. If I want to use this for the counting application, I can use this T0 and T1. In case of timer 0 for counting application, we need to use this 3.4 timer 0. In case of timer 1 counting application, so we need to use this 3.5 T1 pin. Okay, this is mainly for the counting applications. We need to use these two pins. Okay, next one, read bar and write bar. Okay, mainly if I want to access any random access memory or data memory, we need to use read and write. Okay, otherwise there is no use case of the read and write. For in case of program memory or read only memory, this read or write pins are not required. Okay, only to access any external memory we are using these two pins. Otherwise, input and output only we can connect switch or LED. Okay, next two pins are as we discussed, we need to connect external crystal oscillator to give the specified external clock frequency. If I want to operate this microcontroller, we need external clock frequency. Okay, next one is ground, and 40 is VCC. We need to give the 5 volts power supply to this dual inline package. Okay, next one, port 0 to port 0.7, port 0.0 to port 0.7, AD0 to AD7. We have address and data lines. Okay, for example, if I want to demultiplex this address and data lines, I can use the ALE. Okay, for example, I don't have any external memory use case, so that this port I can use for the input and output use case. Okay, here the mainly pull-up registers are not connected in the this port 0 initially. That's why we need to connect externally to use this port 0. Okay, initially this all three ports having the internal pull-ups, and this port we don't have any internal pull-up. Then we need to connect external pull-up resistor to use this port. Okay, we will discuss why we need this pull-up resistor in the next slides. Okay, here we want to discuss initially we can use this port input and output, and if I want to just connect any external memory, so that I can use these 8 pins for the address and data functionalities. For example, here main use case, if I want to read the data from memory or write the data memory, write the data to the memory, mainly we need first we need to identify the address. That's why I will send the address first, and after that I can read or write the data by using these pins only. Okay, that's why here address and data lines are multiplexed here, so that I can use the both the use cases. First I will send the address, I can use A0 to A15, and after that D0 to D7 I can use the data read or write operations. Okay, mainly that is the use of this AD0 and AD0 to AD7. Okay, next, EA bar, external access. Okay, for example, here I just connected to the ground mains. Okay, I'm just accessing the external memory. Okay, if I'm not connecting any external memory, this will be VCC. Okay, this is the active low. Whenever it is ground, then my pin will be activated, then I am able to access the external memory. EA bar is active low. If I am just supplying the ground, it is active. That means I am just accessing the external memory. Okay, next here ALE, address latch enable. As we discussed here, if I want to demultiplex this AD0 to AD7, I am using this ALE. Here see, ALE is connected to the this G pin of our 74LS373. This is our latch. Okay, this address latch enable. Here I am just giving the pin. Okay, here I can demultiplex address and data line separately by using this ALE. First I can mention the ALE is 0, so that I can access the address lines. Next, ALE 1 means I can just decode the only the data lines. Okay, this is the way we can use the demultiplexing of this address and data lines. We are using this ALE. Okay, next one is program store enable. This is mainly for the read-only memory. Okay, this PSEN bar mainly used for the read-only memory. This read and write bars are used mainly for the random access memory. Okay, read and write bar. Here only the PSEN bar we are using for the external program memory. It will be connected to OE pin of our ROM memory. If I want to just mention that I am using the external memory, this pin will be used. Okay, ALE we discussed, EA bar we discussed. Okay, next is the last port 2. Okay, initially we can use the input and output applications. For example, if I am just connecting any external memory, so that I can use for the addressing A0 to A15. Okay, here we have 16-bit addressing and 8-bit data. Mainly our 8051 controller has 16-bit addressing and 8-bit data. That means externally we can access up to 64 kilobytes. 2 power 16 means 64 kilobytes of memory we can access, either ROM or RAM memories. For example, in our controller have 128 bytes of RAM and 64 4 kilobytes of ROM. Okay, we have only limited memory in our 8051 microcontroller. If I want to access any external memory like 64 kilobytes of RAM or ROM, so that I can use these two ports and also these two pins. Totally this 8, 16, 17, 18, 19, 20, 21 pins we need to use if I want to connect any RAM or ROM memories. Finally, this many pins we need to use. For example, if I want to use any read-only memory, only PSEN, ALE, and these two ports and EA bar. Only these three pins, 16 pins are required. 16 plus 3, 19 pins are required. If I want to access a random access memory or data memory, so that we need to use 2, 3, 4 plus 16. Totally 20 pins are required. Okay, these are mainly difference between the RAM or ROM accessing. Okay, mainly if I want to access memory, then we need to use this completely right side plus these two. Okay, remaining all other pins we are using for other purpose like transmission or reception, interrupts, counting applications, and here for the external clock frequency is the ground or VCC and reset. Okay, these are our mainly pin diagram we need to remember, and always we need to know the each and every pin functionalities. Okay, next we'll discuss the reset pin. As we discussed here, we need some external circuitry to do a power on reset and also manual reset. Okay, we will design one circuitry here. Just I designed with resistor and capacitor. Just I am giving the 5 volts to this circuitry. Just I am just turning on my power supply. Then here I will get the 5 volts here to here. Okay, initially my capacitor charge is 0. That's why I will get the 5 volts at the resistor. That's why this whenever the active high, microcontroller will be reset. Okay, it will be at least 5 machine cycles. That means our microcontroller will be reset upon a power supply. Okay, after that, after some time my capacitor will be charged to max 5 volts. Okay, here my 5 volts are at the capacitor. Okay, after that my resistor having the 0 volts. After that there is no reset. Once the power is on, my microcontroller will be reset due to the resistor voltage is very high. It is equal to 5 volts. That's why my microcontroller will be reset. After that capacitor keep on increasing, my resistor voltage will be decreasing. Okay, finally it will be falls to 0. After that there is no reset. Okay, initially my reset pin will be high, and after few milliseconds, my microseconds, my capacitor will be charged. My across the resistor voltage will be dropped to 0. Then there is no further resets. That's why this circuit we are using for the power on reset. Okay, if I want to use the manual reset, so that I need to connect external one push button switch. Whenever I want to do a reset, for example, whenever my program counter is 1000 H. Okay, my program execution at the 1000 H, I want to get back to the 0, so that I can give the manual reset. Okay, this is this two for the power on reset, resistor capacitor. If I want to do any manual reset, so that I can use this push button switch. Whenever we want, we can just press this push button switch. These are mainly use of this power on reset circuit, and also this is the only the external switch for the manual reset. Okay, whenever the reset is happened, my program counter reset to 0, and also accumulator, B register, PSW all are reset to 0, and stack pointer will be always located with 07H, and DPTR also 0, and all ports will be loaded with FF. Okay, initially this we need to remember. All ports will be mentioned with FF means 8 ones. 8 ones means all 8 pins will be writing to 1. Okay, if I am writing to 1, always my 5 volts will be connected to 5 volts. Okay, all ports initially upon a reset, my initially what is my port conditions, all are FF means If I just connect the LED, that will be turned on. Okay, that we'll discuss in the practical sessions. Okay, right now just we need to understand all ports will be FF, means all port pins. FF means 8 ones, 1 1 1 1 1 1 1 1 1. Okay, totally 8 ones means, okay, each pin having the VCC 5 volts. One means logic, one means 5 volts. That means each pin having the 5 volts. That's why here all 32 pins we are having the logic FF. Okay, here initially all the LEDs will be turned on. If I just connect the LED, that will be turned on. Okay, initial all the ports with FF. Okay, here the just we need to remember stack pointer and all ports will be other values, and the remaining will be all the register will be reset to 0. Only stack pointer with 07, all ports with FF. This is our initial upon a reset. Okay, next one we'll discuss more on the machine cycle. Okay, here this is our clock frequency. Let us assume I am just giving the 12 megahertz. Okay, here this 12 megahertz, this one high to low, I am just mentioning it as P1 and P2. Next high to low, 2 high to low, I am just considering it as state 1. Okay, 12 clock cycles, I am just mentioning it as 6 states. Okay, to every 2 clock cycles, I am mentioning it as state 1. Okay, finally 6 states I am mentioning with the one machine cycle. Okay, if I want to calculate the one machine cycle timing with 12 megahertz, we'll calculate here. Time period of one clock cycle equal to 1 divided by frequency, 1 divided by 12 megahertz, 1 divided by 12 microseconds. Okay, here one t state equal to 2 clock cycles. Okay, this is a one clock cycle, one high to low, one more high to low, one more clock cycles. That's why 2 clock cycles. That's why I'm just multiplying with 2 if I want to get the t state. Okay, here S1 state if I want to get, that's why I'm just multiplying with 2 with 1 divided by 12, so that I will get 1 divided by 6 microseconds. Okay, this is my now I need to calculate one machine cycle with 60 states. Okay, that's why I'm multiplying with 6. If I want to calculate the machine cycle, that's why I'm just multiplying with 6. Okay, finally 6 multiply 1 divided by 6, I will get the 1 microseconds. Okay, if I am giving the 12 megahertz, my machine cycle period is 1 microseconds. Okay, similar way we'll calculate with other examples. 11.0592, if I am giving the external frequency of 11.0592. Okay, then how to calculate the machine cycle easily, then we'll discuss here. Okay, the frequency divided by 12, this is my first frequency, 11.0592 megahertz divided by 12, I will get the 921.6 kilohertz. Okay, here the machine cycle equal to 1 divided by frequency, then I will get 1.085 microsecond. This is the way we need to calculate the timing of the machine cycle. Okay, similar way for other frequency divided by 12 equal to 1.3333 megahertz. Okay, similar way machine cycle equal to 1 divided by frequency, 0.75 microseconds. Okay, if you have any micro frequency, so that we can calculate machine cycle easily by using these formulas. Okay, here mainly this 18th and 19th pin. Okay, already we discussed with the reset pin. This 18th and 19th pin we need to connect external crystal oscillator. Okay, here I'm just giving the mainly we will use our microcontroller 11.0592 megahertz. Why? Because if I want to mainly work on the serial communication, if I want to match with the PC baud rate 9600, okay, we are achieving with this 11.0592 megahertz. That's why we are using mainly on our 8051 microcontroller. We are always feeding with 11.0592. Okay, this much of frequency we are operating with our 805 microcontroller. This we need to remember always, 11.0592. Okay, this mainly we'll discuss in the serial communication in further sessions. Okay, here the port logic we'll discuss. For example, each port having this much logic circuitry inside. For example, if I want to write one to the particular port pin, we'll discuss what is our output functionality. For example, here we'll discuss mainly on writing. Okay, reading, just we'll forget this read latch and read pin. Okay, this will forget now. Tri-state buffers are not required in case of writing. Okay, here I'm writing one to the pin from the internal bus from the microcontroller. I'm just writing to the one here. For example, let us assume port 1.0, I'm just writing one to the from the CPU. Okay, here I'm writing one to here. I will get the latch output. Okay, here write to latch, I'm just giving the, let us assume I'm giving one here, so that my I will get the one output from as it is, whatever I'm giving the input, that I will get the output here. Q bar is that complement. 1 means 0. Here 0 means this switch will be open. Okay, here pull up, as we discussed in the initial pin diagram, this port 0 we don't have any pull up. Okay, this pull up resistor we need to connect externally, otherwise it will be open drain. Okay, that's why this port 0, this resistor we need to connect externally. If I want to use the port 0, we need to connect this external pull up resistor, otherwise this should not be used. Okay, next here I got the 0 volts, that means switch is open. I will get the VCC 5 volts to the output pin. Okay, here that means if I just connected the LED, then my due to the 5 volt my LED will be turned on. See, if I am just writing to the 1, I will get the output voltage with 5 volts. Okay, similar we will discuss writing 0. Okay, here I am just writing to 0, I am just giving the large right large to 1. Okay, here I will get the, as it is 0, 0 complement is 1, 1 I am giving to here. Okay, it will be connected to the ground. Now the switch is on, it will be connected to the ground. I will get the output is ground. Ground means 0 volts. Okay, here the 0 volts means LED turn off. Okay, the pin output will be 0. Okay, here if I am giving the, from the microcontroller, if I am giving the logic 1 to here, my output voltage is VCC. If I am just giving the output pin voltage to 0, my output is 0 volts. Okay, based on our logics, this pin will work upon the logic. Okay, here just if I am just writing the logic 1, I will get the VCC at the output pin. Similarly, if I am just writing to 0, I will get the output voltage is 0 volts. Okay, this is connected to ground due to this logic circuitry. Okay, we need to understand in the next programming, if I'm just writing to the particular pin to the 0, I will get the 0 volts to the that particular pin. If I'm just writing to the 1, I will get the VCC. Okay, the next one, reading high at the input pin. For example, for the reading purpose, we can use this tri-state buffers. TB1 and TB2 are tri-state buffers. We are not discussing this writing applications. This is the mainly we are using for the reading applications mainly. For example, this tri-state buffer here, similar way I'm just writing to the 1 to this pin. Okay, I will get the 1 output. Here latch I'm just always giving 1, so that this 1 complement is 0. My switch is open. Okay, here always 1. Okay, this whenever I am just giving the high to the pin, whatever the high voltage will be received to the tri-state buffer. Here I am just read pin, I am mentioning it as 1. This is our enable pin of our tri-state buffer. For example, whatever the input value, if I want to get to the output, this enable pin should be high. Here I am read latch is 0. Here I am just not discussing more on the here. Why? Because this enable pin is 0 means this won't be a feedback to the input. Okay, there is no connection. This is open circuit. 0 means enable pin is 0, there is no input to the output. Okay, here the read pin is 1 means whatever the input voltage will be feedback to the output. Okay, here similar way I'm just mentioning it as read pin is 1 means whatever the input voltage will be coming to the CPU. Okay, this is a way we can read the data from the external device. Okay, similarly we'll discuss how to write. Okay, similar way I'm just writing to the, from the bus I'm writing to the 1 value, I will get the 1. Okay, 1 component is 0, my switch is here 0 means open. Okay, next here whatever the input voltage will be coming to here, anyway the read pin is 1. Here whatever I am just giving the low active low here, I will get the low to here. Okay, just I am giving the read pin is 1 means whatever the low voltage will be feedback to the input. Okay, whatever the as it is, whatever the 0 volts will be coming to inside, then that will be given to the CPU. Okay, this is the way we can use for the reading operations. In case of writing also we can use mainly for the reading and writing operations, so that we can use our port pins. Okay, that's all friends, thank you.
Discussing about an architecture of 805 on microcontroller. Here the architecture means internal building blocks of our 805 on microcontroller that we'll discuss main on today. First one is arithmetic and logic unit. It is also one of the logical circuitry. It will perform the arithmetic and logical operations. Arithmetic operations are addition, subtraction, multiplication, division, and logical operations are and or not. Okay, here the mainly A and B register we are using to perform these arithmetic and logical operations. And A register we are calling it as accumulator also. Why? Because it will act as source as well as destination. For example, if I am trying to add the content of A and B, and also final result also we are storing it to the A. That's why we are calling it as accumulator.
Okay, next one is program status word or process status word. Okay, it will store the status of the ALU. For example, whether if it is after the ALU operations, if the carry affected, that carry we are storing it here. Okay, here the parity. Okay, next one is if it is overflow flag, we are going to store it here. Okay, here the RS0, RS1 we are using to select the particular register bank here. We have the 4 register bank. If it is 00, we are selecting register bank 0. And if it is 01, register selection 1. If it is 10, register bank 2. And if it is 11, we are selecting register bank 3. In our RAM memory, we have the 4 register banks. Out of that 4 register bank, we are selecting only the one. Why? Because each register bank contain R0 to R7. This register bank also contain R0 to R7, R0 to R7, R0 to R7. That's why we need to select any register bank by using this PSW register. Okay, initially my PSW register will be reset to 0. Initially we are going to select register bank 0. Okay, next here parity will discuss one by one flags, will discuss more here. Parity flag, for example, if my accumulator contains, after the addition operation, my accumulator contains odd number of ones, we are going to add one more one here. Okay, the always we are making the even parity. For example, odd number of ones, we are making the parity bit is 1. For example, we have even number of ones in our accumulator in the final result, then we are making it to 0. This is a way parity work. Okay, next is the overflow flag. If the carry from the 6th bit to 7th bit, we have the D0 to D7, right? From the 6th bit to 7th bit, for example, if I am adding the content of A and B, if the carries occurred from the 6th bit to 7th bit or 7th bit to 8th bit, then this overflow flag will be set to 1, otherwise it will be 0. Okay, these two flags we are using for the register selection. And here this is the future flag. Okay, now currently we are not using this. Here the auxiliary carry, for example, carry from the bit 3 to bit 4. For example, if I am adding the two register content, if the carries occurred from the bit 3 to bit 4, then this auxiliary carry will be set to 1. Carry, if the, for example, from the 7th bit, if I am adding content of A and B, from 7th bit to 8th bit, if I got any carry, then I am storing it here. Okay, carry will be stored here mainly. Okay, these are mainly program status word and process status word. Okay, next we'll discuss 8-bit data and address bus. Okay, here we have 8-bit data and address bus. It is connected to RAM and also to the all the ports. For example, addressing of the port also 8-bit, and also RAM addressing also within the 8-bit. Okay, if you see here, 2 power 7, only 128 bytes of RAM we have, only 8 address lines are enough. That's why we have 8 address lines and 8 data lines here. In case of RAM and also port, if I want to read the data from the port, we need 8-bit data bus. If I want to read the data from this RAM memory or write the data to the RAM memory, then we need this 8-bit data bus. Okay, this address bus to identify the, whether I want to identify the port address or if I want to identify the particular RAM address, then we need this 8-bit address bus. Okay, this is the 8-bit address bus to access all the ports. And here the next we have read-only memory. We have 4 kilobytes of read-only memory. Okay, here we are using the 16-bit addressing. We have the 8051, we have 16-bit addressing and 8-bit data bus. Okay, by using this 16-bit address, it is connected to port 0 and port 2. See here 80 to 87. Externally, we have this pins. We have 80 to 87 means 8 address lines and 8 data lines. Here A8 to A15, totally 16 address lines and 8 data lines. If I want to access any external memory up to 64 kilobytes, then we can use this complete 16-bit addressing. For example, locally, if I want to access only the read-only memory, only 12 address lines are enough. If you see here, 2 power 10 is 1 kilobyte, 2 power 11 is 2 kilobytes, 2 power 12 is 4 kilobyte. Only 12 address lines are enough to access this complete internal 4 kilobytes of read-only memory. Okay, next we'll discuss on mainly program counter. Okay, it will store the next instruction to be executed. It will store the address of the next instruction to be executed. For example, right now my ALU at the 1000H location. If I want to execute the next instruction, 1001 address will be there in this program counter. Always it will fetches the next instruction to be executed by our ALU. And here the data pointer register. It is a 16-bit register. It is used to point the data from the externally. For example, if I want to read the data from the external memory or write the data to the external memory, Then we are using this data pointer register. Here it is a 16-bit register. We are dividing into the DPL and DPH. Here the two 8-bit registers forming it as data pointer register. Okay, it is mainly used to read the data from the external memory or write the data to the external memory. Mainly we are using this DPTR. Otherwise, not required. Okay, next we have, this is a RAM. We are dividing into the this format, four register banks, and next one is bit or byte addressable memory, and last one is a general purpose. Okay, we'll discuss mainly in the next slide how the memory organization, and these are the special function registers also we'll discuss in the next slides. Okay, here the totally 32 pins, total remaining 8 pins. Already we discussed this in the previous pin diagram. Okay, the next we'll go for the next slide. Here we have 128 bytes of RAM memory. Here whatever the RAM memory, just I divided this way, right? Similar way we can see it here. We have four register banks. By using this PSW register, we can select any one of the register bank. Initially, I am going to select the register bank 0. Okay, here why we are using this register banks. For example, if I want to access this memory, we can try to access using the register is very fastest accessing. That's why this is a very useful memory. If I want to access the data from this 00 location, I can use directly register 0. From the register 0 I can access directly. Here each register bank contain R0 to R7, R0 to R7, R0 to R7, R0 to R7. See here I can access the this data from this completely address, from the address as well as the register. Okay, register is the very fastest than the address. That's why this mainly we are using this memory directly we are accessing through the registers. Okay, here each register bank contain R0 to R7, R0 to R7. Okay, by using this PSW register we are selecting particular register bank. Okay, here 20 to 2F we have the bit or byte addressing. For example, here I can access bitwise as well as complete bytewise. For example, set bit of 00H means this bit will be set to 1. For example, here if I want to move 20H comma hash 01 means one, that also by using byte address also I am going to set this flag. Okay, that's why here we can use the bit addressing or byte addressing. It is very useful so that I can directly specify this particular bit I can set by using the bit addressing. Okay, and also we can try to use the byte addressing to modify complete byte. Okay, these are useful of the bit and byte addressing. And the last one only the byte addressing, that 30 to 7F. Okay, here the 128 bytes. Why? Because 2 power 7 means 128 bytes. Here 7 zeros to 7 ones means in hex format 7F. This is the way we represented our RAM memory. Okay, next we'll see the here the special function registers, right? That we'll discuss main on the next slides and current slide also. Here port 0, this is a stack pointer. We'll discuss one by one all the registers. Okay, here the port 0. Port 0 means only for the read and write. If I want to set any particular LED or reset to LED, then we are using this port 0. Port 0 address is 80, address is 80 byte address, and also we can access bitwise also. Here port 0 is bit or byte addressable. Okay, these are bit or byte addressable. Okay, we'll discuss one by one. Here the stack pointer. Okay, here we'll discuss mainly stack pointer. Here already register bank 0, this R0 to R7, 00 to 07 is register bank 0, and stack pointer is placed at 07. It is always initially pointing at this 07. For example, if I push something directly, it will store in the 08th location. Okay, register bank 1 2 3 we are not going to use the initial time. Okay, initially we are going to use the register bank 0. This register bank 1 2 3 we can use for the stack operations. For example, this memory is not sufficient for me, so that my stack pointer I can move to the another place like 30, so that this general purpose I can use for the stack pointer. Okay, initially my stack pointer is pointing at this 07H. For example, if I want to push some data, okay, when we are using the stack pointer, that we'll discuss here. For example, my processor execution is here. My program counter next instruction will be stored in the program counter. Okay, this is our program counter. Next instruction to be executed, that address will be stored here. Okay, whatever the address in the PC, the next address I am going to store it here. For example, I have 1000H here. 00 I am storing in the 08th location, and 10 I am storing into the 09 location. Okay, why we are storing it? For example, I have the main program execution. Okay, whenever here I got the interrupt, whatever the next location I am storing into the stack pointer, and I am going to the interrupt, I am going to serve the interrupt. Whenever I am coming back to the main program, then I need to take back from the stack pointer. Okay, this program counter, okay, mainly we are using the program counter to always fetches the next instruction to be executed. Okay, whatever the next instruction I am storing into the stack pointer, I am going to the interrupt, I am going to serve the interrupt, and if I want to come back, I need to retry from the stack pointer. Okay, that is the mainly use of the stack pointer. We are storing the callbacks. Okay, mainly if I want to come back to the previous address, whatever the previous address I am storing into the stack pointer, whenever I am coming back to the main program, then I am going to retry from the stack pointer to this program counter. Okay, we are always storing the address by using the stack pointer whenever I want to come back to the normal program execution, so that I can retry from the stack. Okay, mainly we are using the push and pop operation, we are trying to access the stack pointer. Okay, here the last in last out, mainly that is a mainly use of the stack pointer. Next one is already dptr we discussed, data pointer register. Here we'll discuss more. Here we have 16-bit register, we are dividing into the dpl and dph. For example, if I want to the following instruction to write 50h into the external ram location 1000h. For example, I have connected one external ram memory. Okay, in 1000h location I want to write some data, 55 data. So I'm writing some code here. Okay, move a comma b, move is my mnemonic, here a is my operand. Okay, comma 55h I am moving to a register, and here I am going to identify that external memory address. Here I'm initially I'm assigning this address to here, move dptr comma hash 1000h. Okay, I'm trying to assign the address to here, move x at the rate, I'm pointing the 1000h location, and I am moving the content of a to the that particular 1000h locations. Okay, mainly we are using this dptr if I want to move the data from internal controller to the external memory, so that we are using the data pointer, and also from external to internal we need to use this dptr. Mainly use of the dptr, we can read the data from the external memory. Okay, that is the mainly use of these two registers, dpl and dph. Next, pcon. Pcon is a byte addressable. If you see here, pcon is a byte addressable. Okay, here we'll discuss mainly in pcon here. Okay, we'll discuss more mainly in the next slide. Okay, just we'll discuss what are all the bit and byte addressable. Okay, this is a port 0 bit and byte addressable. If you see bit level also 80, also I can access this bit address, set bit of 80h, so that I can directly set this particular bit, as well as byte also we can access directly 80. Move 80h comma, for example, if I want to write 20 value to this port, so that I can write by using the bit address or byte address, we can access this port 0. Stack pointer we have byte addressing, and also here dpl and dph also byte addressing. This is a power control. Pcon is my power control. Here right now we are discussing this special function registers. Just we'll just discuss the outlines. The next slide we'll discuss briefly. Okay, here's stack pointer, dpl, dph, and already we discussed this. Pcon, for example, power control. For example, I want to move my microcontroller to the ideal mode or power down mode. And also we have special feature, if I want to double the baud rate for the communication, that also we are using this pcon register. Okay, that we'll discuss in the next slide further. Okay, tcon, timer control register. If I want to start the timer, if I want to check the whether my timer is overflow or not. And also for the external interrupts, we want to operate the edge triggering or the external, we have two interrupts, right? Interrupt 0 and interrupt 1. Whether that two interrupt, I need to serve the interrupt based on the level triggering or edge triggering, that we are going to select using this register. Okay, next one is t mode register, mode selection. Okay, we have too many modes in this four modes. Okay, by if I want to select the particular mode, we can use this t mode registers. And also we have special feature, if I want to operate these timers in that counting applications or timing application, that also we are going to select using this t mode registers. Here TL0, TH0, this is my timer 0, TL1 and TH1 timer 1. Okay, each timer is 16 bit, that's why TL0 and TH0, this is my timer 0, and TL1 TH1, this is my timer 1. Totally 16 bit timers we have. Okay, two 16 bit timers. Port 1 we can access bit as byte addressing also. Tcon also we can access bit or byte addressing. Scon also we can access bit or byte addressing. Okay, serial control. For example, if I want to select the particular modes of the serial communication transmission so that I can use the serial control. For example, I want to check whether the transmission interrupt and also receiver interrupt, that also we are going to use this SCON register. Okay, SBUF, mainly if I want to transmit the data and receive the data serially, we are using this serial buffer. For example, if I want to transmit the data so that I want to just copy to this SBUF, then it will take care of the transmission from our microcontroller to the external device. Similar way, we need to receive through this SBUF. If I want to receive the data from externally, from the external via serial communication, so that I can use this SBUF. Okay, here the port 2 also we can access bit or byte addressable, and here interrupt enable register. For example, if I want to enable particular interrupt, we have 5 interrupts, right? If I want to enable particular interrupt, we can use this interrupt enable register. Here port 3 we can access bit as well as byte access, and also here IP interrupt priority. For example, if I want to change the initial priority so that I can use the interrupt priority register. Okay, here the PSW already we discussed, A and B register. These are all are 21 special function registers. Okay, we'll discuss mainly briefly here. Okay, first we'll discuss two timers we have, timer 0 and timer 1, TL0, TH0, TL1, TH1. Okay, this we are calling it as timer 1. This is a timer 0. Okay, for example, these timers we can use a timer or counters also. Okay, by using this T mode register we are mentioning, this is the lower 4 bits are timer 0 and higher 4 bits are timer 1 control. Okay, for example, mode 0, mode 1, if I want to select particular mode, we are using this particular modes here. In the like timers we will discuss more on the modes here. Just we'll discuss here just M0, M1 we are going to select the particular mode. Here mainly we'll discuss C by T bar. Here mainly whether I want to use the counter or timer. Initially C by T bar means initially my flag is 0. That's why initially this timer 0 and timer 1 we are using it as timers. For example, if I want to use my timer 0 for the counting, I need to write this bit to 1. Okay, here gate always will be 0 for the software control. If I want to control hardware, then we need this gate should be 1. Okay, always this will be 0, and if I want to operate timer 0 as counter, then I need to set this bit to 1, otherwise 0. Okay, similar way, if I want to select the particular mode to operate this timer 1, so that I can use mode 0 and mode 1. And C by T bar, for example, if I want to use timer 1 for the counting, so that I can write 1 to this bit, so that it will operate with the counting applications. For example, initially it will be 0, my register content. Always these two timers will be act as timers only. Okay, gate will be 0 for the software control. Okay, this is our T mode register. Okay, here next one is Tcon, timer control. Okay, here the TR0 means here the if I want to start our timer 0, then we are using this flag. If I want to check whether my timer is overflow or not, that time I'm using this TF0. Okay, here the next one, timer run 1. For example, if I want to start my timer 1, so that I'm using this flag. If I want to check my timer is overflowed or not, that time I will check this flag. Okay, by using this flag I will start the timer. Here by using this flag I will check whether my timer is overflow or not. That's why these two for the timer 0, these two for the timer 1. Okay, next here the I want to operate my interrupt 0 and interrupt 1 flags. These two flags are interrupt 0. For example, my external interrupt I need to serve based on the level triggering, so that I can set this one. For example, my interrupt 0 I want to serve based on the edge triggering, so that I want to set this one. For example, my interrupt 1 I want to serve my interrupt based on the level triggering, I need to set this one. If I want to serve my interrupt based on the edge triggering for the interrupt 1, so that I can set this flag. Okay, this is the use of the Tcon register. Use of the T mode is whether I want to operate the timer which mode, and also whether counter or timing applications. Okay, next we'll discuss on SCON, serial control. Okay, serial control register SM0, SM1 mainly we can operate four modes of the serial communication. Okay, that's why we are using this SM0, SM1, and SM2 mainly it is a future use for the multi-processing we will use. And receive enable, if I want to receive our microcontroller via serial communication, this bit should be 1. And TB8 and RB8, transmit bit 8 and transmit bit 8. Okay, receive bit 8. Okay, mainly if I want to transmit 8-bit, usually our serial communication is 8-bit transmission. If I want to use the 9-bit transmission, so that I can use these extra bits for the extra bit transmission. Okay, here the TI transmission interrupt and receiver interrupt. For example, once my this S buffer is my mainly this register we are using to transmit the data from the microcontroller, and also we are using for the receive the data from the other microcontrollers. Okay, this is the mainly we are using the sbuf. For example, if I want to transmit, I need to place the data to this sbuf 8-bit data. I want to place to this register, and I will check whether my this whatever the placed data is transmitted or not by using this flag. Okay, whenever the successfully transmitted by my microcontroller, my flag will be set to 1. Okay, then I will transmit another byte. Once the interrupt is triggered, then I will transmit another byte. Based on this is one of the future transmit interrupt. Okay, once after successful transmission is completed, this flag will be set to 1. For example, this once the complete reception is done from the external devices, I am able to receive the data serially, via serial communication. My data is successfully received to sbuf, so that the receiver interrupt will be 1. Okay, this mainly will discuss on the in the serial communication. Just we want to understand, once the reception is successful, then this bit will be set. Once the transmission is successful, then this bit will be set. Okay, here the S mod, mainly this peak on register we are using to and also double the baud rate. If you see the baud rate formula, equal to 2 power S mod divided by 32 is my serial communication division. This is my timer division. This is my oscillator divided by 12 multiplied 255 for the auto reload mode. Okay, here the mainly to understand S mode, by using this bit we can double the baud rate. In case of serial communication, we can, if we want to double the baud rate, so that I can just set this bit to 1. Okay, here the general flag 0 and general flag 1. This is for the mainly feature purpose. Here the ideal mode and power down mode. For example, if I want to change my control mode to ideal, so that I can set this flag. If I want to switch my microcontroller to power down mode, so that I can set this flag. Okay, mainly these two for the power saving modes. Okay, here the mainly for the serial communication we are using mainly scon and sbuf. For the timing application, we are using the timer 0 and timer 1. Either we can use the timer or counter, and tmod and tcon. These are mainly for the timing timers. Okay, already we discussed the port for the read or write accessing these ports. If I want to connect the led or switch, so that we can use these ports. Okay, this is a timing, this is a serial communication, this is a power. Pcon is my power control. This is a scon and sbuf we are using for the only for the serial communication. Next, last two registers are interrupt priority and interrupt enable. Okay, we have five interrupts: int 0, timer 0, and interrupt 1, timer 1. And here the ti or ri, only we have one serial communication interrupt, either ti or ri. At the time only one interrupt will be triggered. Okay, here interrupt enable register. Okay, for example, if I want to enable all the interrupts, then I need to set all the lower 4 bits to 1, and also here should be 1. Okay, for example, if I want to enable only the external interrupt 1, so that I want to set the interrupt 1 and enable bit also 1, then only I am able to enable the particular interrupt. Okay, this enable should be 1. For example, I set all the interrupts 111, but this enable bit I set to 0, then that means interrupts are not enabled. Okay, this is the complete. If I want to enable the that particular interrupt, this should be 1, and also that particular interrupt should be 1. This is the interrupt 0, timer 0, interrupt 1, timer 1, serial communication interrupt. Okay, these are the five interrupts serially. And here if you see, here we have the internal. Initially we have initial priority: interrupt 0, timer 0, interrupt 1, timer 1, tir ri. Okay, this is the initial priority. If I want to change the initial priority, so that I can use the interrupt priority register. Here the interrupt 0, timer 0, interrupt 1, timer 1, serial communication. Here the timer 2 interrupt. In case of 8052, this timer 2 interrupt will be used. Okay, right now this is not used. Okay, in our 8051 this is not used. Only the interrupt 0, timer 0, interrupt 1, timer 1, and also this is the last one, serial communication. For example, this is my initial priority. For example, I want to this timer 0 I want to make the higher priority, so that this bit I can set to 1, this timer 0. Okay, if I want to change the initial priority, so that I can use this register. But in case of interrupt enable register, If I want to enable the interrupt 0, then this bit should be 1, and also EA should be 1. Then only I am able to enable the particular interrupt in my particular feature. Okay, I think this you will understood better. I think if you have any question, you can post into the systems.
Today we are mainly discussing about an introduction to 8051 assembly language. If I want to write this 8051 assembly language, first we need to know the architecture of 8051 microcontroller, and also we need to know some English keywords like mnemonics. Once we know the mnemonics and architecture of 8051, then we are able to write this 8051 assembly language very easily. Today we are going to learn step by step today about the assembly language. First one is 8051 instruction set. The 8051 instruction set can be divided into 5 subgroups. First one is data transfer. Here mainly if I want to move the data from one place to another place so that these many mnemonics can be used. Okay, next one is arithmetic, addition, subtraction, multiplication, division. For example, if I want to perform any arithmetic operations so that I can use these many mnemonics. Okay, next one is logic, and or XOR, not, and rotate operations. If I want to perform any logical operation so that I can use these many mnemonics. Okay, next one is boolean variable manipulations. Okay, here the mainly if I want to manipulate any particular register in a particular bit so that I can use these many mnemonics, or we can directly we can manipulate in a bit addressable memory so that I can use these many mnemonics. Okay, next one is program branching. Here the mainly conditional and unconditional jump instructions. For example, if I want to move our microcontroller control from one place to another place so that I can use this branching mnemonics. Okay, if I want to write any assembly language, first we need to know these mnemonics. Okay, first one is data transfer. Okay, we will discuss one by one mnemonic now. First one is move. For example, let us take one example, move a comma b. Okay, here the whatever the b content we are moving to a. Here the this mainly this mnemonic we are using to transfer the data from one register to another register or one memory location to another memory locations. Mainly we are using this mnemonic for the data transfer. Okay, next one here move c. For example, here move c is my code. If I want to move the data from code memory to my accumulator so that I can use this move C. Next one is move X. For example, if I want to move the data from external memory to the accumulator or some other register so that I can use this move X through the DPTR. Okay, next one is push or pop. Okay, mainly for the stack operations. If I want to push some data to the stack memory so that I can use this instruction. If I want to pop or retrieve the data from the stack so that I can use this pop instruction. Next XCH. Okay, here the mainly exchange. Okay, if I want to exchange the content between the two registers so that I can use this XCH. Okay, next XCHD. For example, if I want to exchange the content of only lower 4 bits between the registers so that I can use this XCHD. Only the lower 4 bits can be exchanged between the registers. This is the mainly use of the mnemonic. Next one is arithmetic. Okay, here add. If I want to add the two registers content so that I can use this ADD. Next, ADDC means add with carry. If I want to add the content of two registers plus a carry so that I can use this ADDC. Next, sub B. Okay, here mainly for the subtraction we can use this one. If I want to subtract from the one register to another register so that I can use this one. Next, increment with some register. For example, if I want to increment the content of register by 1 means so that I can use this one. Okay, for example, if I want to decrement by 1 so that I can use this mnemonic. Okay, next mul. Let us take example mul AB. Okay, in case of multiplication we can use this mnemonic. Okay, here the mainly if I want to multiply 8 bits then I will get the result of 16 bits. Okay, first lower 8 bits I can move to the A register, and higher 8 bits I can move to the B register. These are mainly the multiplication operation. Okay, next one is div AB. For example, in case of division, whatever after the division my result or coefficient I am storing to the A register, and whatever the remainder I am storing to the B register. This is the operations of the division. Okay, next one decimal adjust accumulator. For example, if I want to after the addition or subtraction If I want to adjust my result so that I can use this DAA. Okay, mainly if I want to follow my BCD code, binary coded decimal. For example, let us assume after the addition or subtraction, my result is 2A. Okay, for example, here decimal adjust always it will follows the binary coded decimal format. Okay, my 2A is not a binary coded decimal. Why? Because the second digit is A means greater than 9. Okay, if the every digit it will check. If it is greater than 9, it will add plus 6. Then it will make always a BCD format, binary coded decimal. Always each and every digit should be 0 to 9. Okay, that way it will represent our accumulator. Okay, mainly we'll use of the decimal adjust. Okay, next we'll discuss more on the logical. If I want to perform logical AND so that I can use ANL between the two registers. Next, OR logic, ORL is my OR logic. If I want to perform OR operation between the registers so that I can use this one. Next, XRL, if I want to perform XOR operation between the registers so that I can use this one. Next, clear, if I want to clear the register content completely with 0 so that I can use this clear. Next, complement, here this CPL is my complement. If I want to just complement from the 0 to 1, if I want to change the bit status so that I can use this one. Zeros ones will be converted and ones will be zeros. Mainly it will complement the whatever the register content. Okay, next one is rotate left. Here the mainly rotate left means each and every bit will be shifted to the left. Okay, next here this D7 will be coming to the D0. This is the way mainly rotate left. Next to rotate left with carry. Let us assume here my carry is there. This carry will be moved to D0, D0, D1, D2, D3. This is the way complete shifting. Final D7 will be coming to the carry. This is a rotate left. Next to rotate right. Next, rotate right means here this D0 will be moved to D7. Next, D7 to D6. This is the rotate right. Next, rotate right with carry. Here, let us assume here we have one more carry. This D0 will be moved to the carry. This carry will be moved to D7. Again, D7 will be D6. This is the mainly rotate right with carry. Next is the swap. For example, if I want to do a swap between the lower nibble to higher nibble, this lower 4 bits will be moved to the higher 4 bits. Higher 4 bits will be moved to the lower 4 bits. This is a mainly swap operation will work. Okay, next we'll mainly discuss on the boolean. If I want to perform any particular bit manipulation so that I can use this many boolean mnemonics. Next, clear. If I want to clear the particular bit so that I can use this instruction. Next, set bit. If I want to particularly, I want to set this particular bit so that I can use this one. Next, move. Here the mainly this move is the mainly for the byte operation. This is the mainly for the bit operations. If I want to move the content from one bit location to another bit locations, so that I can use this mnemonic. Okay, here the JC means jump if carry. Okay, if the carry is set to one, then we are moving to another locations. Then otherwise we'll going to execute the next instruction. Next here the JNC, jump if no carry. For example, if the carry is not set, then we are going to another locations. If the carry is set, then we are going to execute the next locations. Here the JB means jump if the bit is set. Okay, for example, if my bit is set, then I'm going to another locations. For example, if my bit is not set, we are going to the next locations. Here JNB means jump if bit not set. Okay, here bit not set means, for example, if my register bit is not set, then we are going to another locations. Otherwise will be the next instruction to be executed. Okay, next here JBC. Here the will check whether the relative location, bit location, and also our register bit locations. If both locations are set to one, then only we are moving to the other locations. Otherwise, will be the next instruction to be executed. Okay, here the ANL. If I want to do the AND operations between the two register bit contents, so that I can use this one. Okay, next one RL. If I want to apply the R operations between the two register bit content so that I can use this one. Here the complement to the particular bit locations if I want to do the complement so that I can use this one. Okay, these are the mainly for the Boolean operations. Mainly if I want to manipulate the particular bit memory locations or the particular register bit location so that I can use these many mnemonics. Okay, next one finally the branch instructions. Here the long jump. If I want to move my microcontroller control from one place to another place, so that mainly we can use these many branching instructions. This is a L jump, means long jump. We can completely move the complete 64 kilobytes of memory. We can try to move from another place to another place by using this complete L jump. Here the absolute jump means within 2 KB we are able to move my microcontroller control to one place to another place within 2 KB. Here short jump means within 128 bytes of memory, so that we are able to move the my microcontroller control from one place to another place. For example, if my microcontroller control, if I want to move from one place to another place within 128 bytes, I can use this one. Within 2 KB, I can use this one. Within complete program memory or data memory, complete 64 kilobytes of memory, if I want to move my microcontroller control from one place to another place, so that I can use this one. Next here, jump if 0. Here I will check the register content. If the register content is 0, then I will going to other place. Otherwise, next instruction. Jump if not 0. Here I will check my register content is not 0. Then only I am going to execute the other locations, otherwise the next instruction. Here compare jump if not equal. Okay, here we'll check the two register content. Two register contents are not equal, we are going to move to the another locations, otherwise the next instruction. Here decrement jump if not 0. Okay, here I will just decrement the register content. After the decrement, we'll check whether the register content is 0 or not. If it is 0, not 0 only, we are going to move to the another location. If it is 0, next locations. Okay, here the no operations. Here the L call also, we are going to move our microcontroller control from one place to another place. We can use this long call to complete 64 kilobytes of memory we can move. Here a call means absolute call. Mainly within this 2 KB, if I want to move my microcontroller control from one place to another place, so that I can use this one. Next here RET means return. Written from the one of the function, so that I can use this one. Here RETA means written from interrupt, so that I can use this one. Next one is jump. Okay, finally, if I want to jump from one place to another place, I can use this one. Okay, mainly these are the branching instructions. These are the Boolean instructions, logical instructions, arithmetic, and data transfer. Mainly, if you know these many mnemonics, so that we can write our program very easily. And also, if you know the each and every functionality of this mnemonic, so that we can write our programming very easily. Okay, next we'll discuss more on here how we are going to write our assembly language. First is the label. For example, here we are using long call. Here I am mentioning some label, so that we are going to move to that particular label. Okay, here we need to write our mnemonic as we discussed so far, right? These mnemonics we are writing in the second location. And after the destination and source. Okay, always destination is the first place, and the source is next place. Finally, we are writing the comments. This is the way we are writing each and every instruction in our assembly language. Okay, here already we discussed these three are optional. This should be mandatory. This we need to write RET is my mnemonic. Okay, this should be mandatory. The label, destination, and source is optional. Okay, next we'll discuss the addressing modes, the way of specifying our operands by using the operations, so that I can use this addressing modes. Here, first one is immediate addressing mode, register addressing mode, direct addressing mode, register indirect, indexed addressing mode. Okay, we will discuss these five addressing modes one by one now. Okay, first one is immediate addressing mode, means whatever the we are using mainly hash. Hash means immediate data. Hash 10 means this is my immediate data. I am going to move to my A register content directly. Okay, next one is R0. I am moving hash 0A. Okay, here is source. Here is my destination always. Okay, if you see here the mnemonic and destination and source, this is my source. Okay, here move a comma hash 10 means direct immediate data I am moving to the A register directly. Next move R0 comma hash 0AH. Immediately this 0A I am moving to the R0 register. Okay, this is a hex format. H means hexadecimal value. If I am not mentioning anything, it will be decimal. Okay, here if you see the difference, okay, default will be the decimal 255. I am assigning to the R0. This is my decimal if I am not mentioning anything. For example, if my any digit is greater than 9, so that I am going to treat it as hexadecimal. For example, if 0FFH means this is my hexadecimal, I am moving to the R0 directly. Okay, next last one is binary. If I want to move my binary data to the R0 so that I can write this way. Okay, any data we can move to our any register content. This is immediately so that I can use the immediate addressing mode. Okay, here the next one is register addressing mode. If I want to move the one register content to another register content so that I can use the register addressing mode. Here the directly we are mentioning the register contents. Okay, directly one register to another registers if I want to copy the data so that I can use this addressing mode. Here the mainly we are using the A register R0 to R7 and DPTR. Okay, mainly we are using these many registers for our operations mainly. Okay, here this instruction should not be used. Move R0 comma R0. Okay, memory to memory we cannot move. Okay, if I want to move from R0 R1 to R0, first this R1 content I need to move to the A register. From A register I need to move to the R0 register. This is the way we need to write our program language. But here R1 to R0 we cannot move. This will get the assembly error. Okay, here mainly this is a mainly register addressing mode. If I want to move from one register to another register, this addressing mode we need to follow. Okay, next one is direct addressing mode. Here this is my 20H is my address. That is the address content I am moving to the accumulator. Here mainly whatever the here we have the internal data memory, RAM memory, we have 128 bytes, 0 to 127 locations we have, 0 to 7F in the hex format. Okay, this is a complete address range we can try to specify, and that register content we can directly move to the particular register. From the memory location to memory locations also we can follow this direct addressing mode. And also this also comes under to the direct addressing. Whatever the A register content I am also moving to the port 1. We this is also we have the addressing, right? E0 and port 1 means 90. Whatever the data we can move between the locations. Okay, here 20 means this is my address location. This address location content I am moving to the A register. This is a 40H, this address location content, and I'm moving to the 30H locations. Whatever the content of 40H locations, I'm moving to the 30H. Okay, this is a mainly if I want to work on the mainly direct addressing so that I can use this one. Mainly direct addressing is the we need to mention our address source, and the destination can be a register or the address. Okay, these are mainly for the direct addressing mode. Okay, next indirect addressing mode we'll discuss here. First, if I want to load my 20H is my address I am loading to the R0. Okay, here at the rate R0, this address indirectly I am specifying 20H location. I have to move this 50H data to the 20H address location. This is the mainly indirect addressing mode. Okay, mainly we are using at the rate operator here. Okay, R0 is my I'm just assigning hash with immediate data. Okay, immediate 20H I'm assigning it here. I'm mentioning it as at the rate R0 means here the mainly indirect this will treat as address. This 20H address content will be moved to the this 50H. 50H is moved to the this 20H address indirectly. I'm using the indirect addressing mode. And this way also we can use move a comma at the rate R0. Okay, here the R0 indirect addressing mode 20H whatever the data content will be moved to the A. This is the indirect way we are specifying. Mainly in indirect addressing mode, mainly R0, R1 and DPTR. Mainly these three registers will be used for internal data accessing so that we can use indirect mentioning so that I can use this R0 and R1. For example, for the external memory access, we can use this DPTR. If I want to point the external data memory so that I can use this DPTR. If I want to read from the external memory or write to the external memory, mainly this DPTR will be used mainly in the indirect addressing mode. Similar way, this R0, R1, internal we have some data memory. If I want to read the content indirectly from the particular memory location so that I can use this R0 and R1. Okay, last one is indexed addressing mode. Okay, here the mainly we are adding the two address contents. DPTR has some address content plus I am adding my offset to the this DPTR. For example, let us assume this is my 1000 locations. If I want to access 1001 location, so that my offset is 1. Let us assume this 1001 location I am pointing indirectly in the code memory. Move C is my code memory. whatever the code memory whatever I am pointing, that content will be moved to the accumulator. This is a mainly indexed addressing mode. If I want to access particular code memory location, that I want to move to the accumulator so that I can use this index addressing mode. Mainly here the dptr or program counter can be used. Okay, thank you friends, thank you for watching assembly language programming. Okay, first one about the move instruction. Move destination comma source. Source always right side and destination always left side. The instruction tells the CPU to move. In reality, copy the source operand to the destination operand. Okay, here the move a comma hash 55h. It is a immediate value that I am copying to the A register. Move R0 comma A. The content of A is 55h. I am just copying to the R0 register. Next, move R1 comma A. Content of A 55h. I am copying to the R1 register. Move R2 comma A hash 55h. The it contains 55h. The whatever the content of A 55h, I'm moving to the R2 register. Next, move R3 comma hash 95h. This 95h immediate data I'm moving to the R3 register. Next, move A comma R3. This R3 contains 95h that I am just copying to the A register. This is the mainly we need to understand about the move instruction. Next, continuation to the move instruction. Notes on programming. The value preceded with hash can be loaded directly to the register A, B, or 0 to R7. For example, here move A comma hash 23 means this is the immediate value that I am just copying to the A register. Next, move R5 comma 0F9H. For example, if it is a letter, we should always add 0 in front, otherwise we'll get the compilation error. Okay, for example, to indicate to the assembler it is a not a letter, to indicate it is a hex value, that's why we need to add 0, otherwise we'll get the compilation error. If the value 0 to F, moving to the 8-bit register, the rest of bits assumed all are zeros. For example, here I am moving move a comma hash 5. Okay, here the higher nibble, uh, okay, sorry, here the lower nibble I am just copying 0101, but the higher nibble I am just replacing with zeros. The result will be A05. Okay, here in the binary I am representing four zeros. This is my higher nibble, always zeros. Why? Because initially our accumulator will be reset to 0, all are zeros. Here I am just loading with 5 means only lower nibble will be copied from this 5 content 0101, but the higher nibble will be always zeros. Moving a value that too large into a register will cause an error. For example, here move a comma has 7f2h. Okay, it is a more than ff. That's why here we'll get the compilation error. Okay, which should load up to 002 ffh. Okay, within this 255 we have to load to the 8-bit register. Okay, next we'll understand about the add-in section. Okay, for example, here move a comma source. Source can be a immediate data or a register, but the destination always a register. For example, here I am using add r4 comma a or add r2 comma hash 12h. These are the invalid. Okay, always destination should be always register, always a register, but the source can be a immediate data or a register. Okay, we'll discuss here more on addition. Move a comma hash 25h, move r2 comma 34h. Here I am just copying the 25 to a register and 34 to r2 register. Here I am just using the add instruction, add a comma r2. Here the always the source can be a register or a immediate data. Okay, here the R2 content is 34H and A content is 25H. Here I am going to add these two contents, and finally result will be saved to the A register. If you see this equation, A equal to A plus R2, what is the content of A is 25 plus 34. The final result will be stored to A register. This is the add instruction we need to understand more. And here move A comma 25H and add A comma has 34H. Here it will add the 25 plus 34H. Finally, the result will be stored to A register. Okay, here the mainly we need to understand the destination register always accumulator. The source can be a immediate data or any other register. Okay, next we'll understand structure of assembly language. Here the structure of assembly language, we need to write our assembly language this format. First one is the label. Okay, here if you see
label here colon sjump here. If I want to jump sjump here to here, so that we can use this label. Next one is the mnemonic. Okay, here move, add, these are the mnemonics. Next, operands. It can be source or destinations are the operands. Next, finally the comment. Okay, this is the way we need to write our each and every instruction in our assembly. Okay, first one we'll understand the each and every instruction here. org0h means, okay, here in our program memory 00h I am planning to store the this complete program from the 00h. That's why I'm just giving the origin 0h means I am trying to store my program from the 0h location onwards. Move R5 comma hash 25h, move R7 comma hash 34h, move a comma hash 0. Next, here I am just adding the content of a plus R5. Okay, 25 here I have accumulator has 0 plus 25 I am adding. Final result will be saved, stored to accumulator. Okay, here the 25 value. Okay, add next 25 a comma R7 has 34. I'm just adding the 25 plus 34. I will get the final result here. And add a comma hash 12h. This 25 plus 34 plus 12h. The final result will be saved to a register. Okay, just this is the some instructions I wrote. Okay, here asm to here. Okay, just I am jumping to here. This is a finally end instruction. Okay, for example, from here to here only we have the code memory, and after that here this is my end of my program. Here origin and end are the directive to the assembler to indicate whether is the program starting and ending. This I am just indicating to the assembler. This is the starting point, this is the ending point. Okay, these are the mnemonics. It will produces the opcode that will discuss on the more about the opcodes next slides. Okay, here these are the directives as we discussed, origin and end. Okay, this is the label. If I want to jump from one location to another locations, we can use these labels. Okay, these are the comment hash comma hash. Here I'm just representing with colon. Okay, colon, after that we are writing, these are the comments. Okay, this is the way we need to write our any assembly language, first with origin and end. In between that we can write all our programming. Okay, here this is the structure of, this is the steps to create a program. For example, if I want to flash a code to the ROM memory, so that we need to follow these many steps. Okay, here editor program. For example, if I am just written this program, this can be saved as .asm. Okay, that .asm I am giving to the assembler. Assembler, it will generate two files, .list files and object files as well. Okay, here the list files, it will show the any errors or something, it will show in the list file. For example, if I got any error, then I will go back to the editor and I will change the again code, then I will give to the assembler. Okay, there is no errors, then the object file will be generated. Okay, this object files I am giving to the linker. Okay, we may get some other object files also, like math.h, will get the some other object files. Okay, here I am just linking all the object files and I am getting the absolute file from the linker. Okay, it will just arrange our all object files in a one structured way, then finally we'll get the absolute file. Okay, this absolute file I need to convert to the hex. Here I am using the oh converter. Okay, absolute to hex converter. Okay, that this hex value we are, this hex code we are storing to the finally to our program memory, ROM memory. Okay, then we'll understand more in the next instruction. Here the list file. Okay, list files mainly. Okay, list which is the optional, is very useful to the programmer. It lists all the opcodes and addresses as well as the errors that assembler detected. Okay, for example, if I am writing the incorrect instruction at the, for example, line 5. Okay, in the list file it will show, okay, you have the error at the line number 5. Okay, the mainly use of the list file, it will show the errors, and also in case of debugging also it will mainly helpful this mainly list file. Okay, here the mainly whatever the code we written here, right, the similar code it will store in the list file as like here. Okay, in the list file it will show the address. First column is the address, the next column is the opcodes, the next one is our program. Okay, here is the origin 00h, this is my program ROM memory. 00h means my program storing, I am starting from 0, just I am directed to my assembler, I am trying to store my code from the 00h. Next, move R5 comma hash 25H. Okay, it is converting to the opcodes. Assembler, it will convert the whatever the assembly instruction to the opcode. This is a 7D is my move R5 means 7D. It will convert to the opcode to 7D. This 25 is my second byte. 25 will be loaded to this R7. Okay, R5. Okay, see here, four zeros means four zeros. Okay, 70 I am storing into the first locations, and the second location I am storing this 25 value. Why? Because in each memory location we can store only the 8 bit in each location. That way this 70 will be the first location, and 01 is the second location. Okay, next after that, this 25 is stored in the second location. Then third location 02 means third location. Here I am storing this 7F. Move R7 nothing but 7F is my opcode. This 35 value I am storing in the next instruction. 03 also over. Next 04 means I am storing 7400. Next 2D, 2F, 2412 and 80EF. FE. Okay, here I am just storing the what is the content of the opcodes here to the directly to the program memory. Okay, first we are writing to the writing assembly language. From this assembly language, it will be converted to the opcodes. Once there is no errors, then we will get the opcodes. These opcodes will be stored to our final to our program memory. Okay, this is the mainly we need to understand about the list file. Okay, it will mainly useful for the list file. It will show the errors and we'll try to modify those errors, and whenever there is no errors, then it will produce the object files. Okay, it will the linker stage, it will command all the object files, then finally we'll get the object files. This object file we are going to convert to the hex file. This hex code will be flashed to our program memory. Okay, this instruction will be executed by one by the CPU. Okay, next we'll understand about the directives. First one is the defined byte. Okay, if I want to define any particular byte, it might be a decimal or binary or hex. We can use this DB. Okay, define a byte. Okay, it can be defined a byte. We can use to store the strings of the digits or strings of the letters. Also, we can store by using this defined byte. Okay, mainly to understand, this is the directives for the assembler. Okay, we can define any byte by using this defined byte. Okay, next we'll understand more about the origin and end. Okay, this origin already we discussed. If I want to tell to the compiler, tell to the assembler, I want to store the code from the 0, so that I can use give the origin 0h. For example, if I want to store my code from the 06 location, so that I can give 6h. Okay, here the mainly, if I want to give the particular location to store our program, so that I can use this directive. Next, end. If I want to show to our assembler my program is ending here, so it will understand the assembler, it will understand, okay, program is ended here by using this directive. Okay, mainly use of this origin and direct end we are using to start the program and end the program of the assembly language. Okay, next we'll understand equate. For example, we have the so many count I have used in my program. For example, I want to replace in count with the my 25 value. For example, throughout the program, so that I can use this equation. Okay, count equate 25. Here this 25 I am just storing to the count register. For example, here as count I have used in my complete program 10 times. Okay, this 10 times, if I am just changing the value to the 10, this 10 times will be replaced throughout the program. That is the mainly use of this directive equate. Okay, next we'll understand, already we discussed in the architecture about the PSW. Just we'll discuss just outlines here. This is a parity flag. For example, after the addition, after the ALU operations, if my accumulator result is number of ones is odd, then we are going to add one more one here. For example, if the number of ones are even, then our parity is 0. Here the overflow flag. Here the mainly, if the carry from the 6th bit to 7th bit, then this overflow flag will be set to 1. Here the register selection 0 and register selection 1, mainly to select particular register bank in our RAM memory, we are using these two flags. This is mainly for the future flag. This is the auxiliary carry. If the carry from the D3 to D4, then this bit will be set. Carry. If the carry from the 7th bit to the this carry will be stored. If the more than 8 bit, if we got the carry, this 7 bit will be we are storing it. For example, what and all the instruction, these many flags get affected. For example, in case of addition, carry, overflow flag, auxiliary carry will be affected. And they add with carry also, these three flags are affected. Sub with borrow also, three flags are affected. In case of multiplication and division, only overflow flag might be affected. Next, decimal adjust instruction, only the carry may affect. Okay, here the set bit carry. Okay, here I'm just setting my carry to 1. Clear bit carry, I'm just clearing my carry to 0. And here the complement, if it is 0, I'm just complementing to 1. If it is 1, I'm complementing it 0. In case of and logic or or logic, we are using this carry also. It may affect carry also. Directly in the final equation, here CJNE, compare jump if not equal, maybe it may affect the carry mainly. Okay, the carry in most of instruction may carry may affect. In case of multiplication and division, only the overflow flag, mainly this arithmetic operations, only this overflow flag might affected. In addition and subtraction, this auxiliary carry will be affected. Okay, this is a mainly, these are the flags may get affected whenever these instructions are executing. Okay, okay, we'll understand, we'll take one example and we'll understand what all the flags are affected. Okay, here move a comma 38h, this immediate data I'm moving to the a register. Next, add this 38h plus 2fh, then finally that result will be stored to a register. This is a understand, we need to understand our instructions. Here just I am adding 38h plus 2fh. Finally, I got the 67h. Okay, these are the hexadecimal. Just I am representing to the binary here. Okay, 38 means 0011. This is my every digit I am representing with the 4 bits. And 8 means 1000. And 2 means 0010. And F means all ones. Okay, here I am just adding 0 plus 1, 1. 0 plus 1, 1. 0 plus 1, 1. 1 plus 1, 1, 0. Okay, here I got the carry from the bit 3 to bit 4. Then auxiliary carry will be set to 1. Okay, here I got the 1. Next, 1 plus 1, 1, 0. Okay, here 1 plus 1 plus and also carry plus 1. Okay, here 3 ones means 1, 1. Here I got the 1 and also here 1. Okay, the finally here 0 plus, here I got the carry from here, I got 1. Okay, here 1, finally 1. Okay, next finally 0, 0, 0. Okay, if I just done the addition, only the auxiliary carry affected and there is no carry affected here. Okay, here the finally parity will check. Here if you see the in accumulator register, it has only the 5 ones. It means if I want to make the even parity, then I need to add to the parity flag to the 1. Okay, only the auxiliary carry parity were affected, carry is 0 in this case. Okay, if I add this 38h and 2fh. Okay, we'll take another example, we'll see what and all the flags might affected. Okay, here I'm just move a comma 9ch, I'm moving 9ch to the a and add 9ch plus and 64h, I'm just adding, I will get the 100 hex value. Okay, if I am just adding just representing here, 9 means 1001 and C means 1100 and here 6 means 0110 and 4 means 0100. Okay, just I represent in binary 0 plus 0 0, 0 plus 0 0, 1 plus 1 1 0. Here again I will get 1 0. Here I got the auxiliary carry also 1. Okay, here 1 plus 1 1. Again I got the carry here and remind here is the result is 0. And again 1 plus 1 1 0. Again 1 plus 1 1 0. 1 plus 1 1 0. Okay, finally I got the carry as well as auxiliary carry, both are affected. Here number of ones are 0, that's why parity also 0. Okay, for example, if the number of ones are odd, then parity will be 1. Okay, next we'll understand the last example. Here move a comma 80h, add a comma 93h. Here just I'm adding the similar way, 0 plus 1 1, 0 plus 1, 0 plus 0 0, 1 plus 0 1, 0 plus 1 1, 0 plus 0 0, 0 plus 0 0, 1 plus 1 1 0. Okay, here only the carry was affected, there is no auxiliary carry, there is no parity. Here if you see the number of ones are even, 4 ones. Okay, that's why parity is 0, there is no auxiliary carry, there is no carry from the bit 3 to bit 4, that's why auxiliary carry is 0. Finally I got 1 plus 1 1 0. Okay, this carry will be stored in the carry flag in our PSW. Okay, if you take the any two edition, then we used to have the similar way and we'll check what and all the flags are affected. Okay, next we'll understand the our RAM memory. Okay, RAM has 00 to 7F. We have 128 bytes of RAM memory, and here the 00 to 1F. 00 to 1F is my register bank memory. Okay, each register bank contain R0 to R7. Okay, for example, if I want to select for example register bank 2, so that I need to set the register bank 2 means RS 1 bit I need to set to 1. This RS 0 bit initial will be all are zeros. That's why this RS 0 RS 1 all are zeros. Initially I am going to select register bank 0. If I want to select particular register bank, we need to set or reset the this RS0 RS1 flags in our PSW. Okay, for example, initially we are going to select the register bank 0. For example, if I want to select the register bank 1, we need to set the RS1 flag in our PSW, so that I can move to here, so that I can use these many registers. For example, initially we will use this R0 to R7. For example, if I want to use this R0 to R7, so that I need to move to the bank 1. For example, I want to use this R0 to R7, we need to use this bank 2. Okay, similar way we have 20 to 2F, we have bit or byte addressable. We can access bit level as well as byte level. Okay, here 30 to 7F is a scratch pad. Okay, and we have one more feature here, register bank 1. It has stack pointer also. For example, if I'm using this register bank 1 for my general purpose, so that this stack pointer I can move to the some other locations. Okay, we'll understand one by one with example in my next slides. Okay, here I'm just directly I'm writing the programming move R0 comma 99H. For example, initially I'm not moving to the any of the register bank. Initially my register bank 0 directly. Here I'm just writing this program R0 comma 99H means directly this register will be accessed. Okay, I am directly moving to the R0 to with 99H and R1 with 85H. This R1 with 95H. Why? Because initially I am in register bank 0. And similar way, I'm just writing 00 means this is the address. I'm just moving to the 99 and move 01 comma hash 85. These are the both are equal. If I'm accessing with the 00H location means this is R0 only, nothing but, and 01 location means R2 only. Okay, this and this are both are same. Here I am accessing through the register whatever the memory 00 memory. Here if you see 00 to 07, this is my first memory first register bank addressing. Next 08 to F my second bank addressing. 10 to 1F my second bank addressing. 18 to 1F is my third bank addressing. For example, if I want to access the R3 register directly 03 comma 20H, directly I can move this particular location with the address. Okay, this is the address. I am accessing the data. I am just copying the data through the address. This is the through the register. Okay, next one, last example here, set bit of PSW zero point 0.4. Here point 0, point 1, point 2, point 3, point 4. Here I am setting this flag to 1. 1 0 means here the register bank 2. We need to refer here. Okay, if I want to go to the register bank 2, okay, here I am going to the register bank 2 here. Okay, if I am want to use these registers, so that I can shift to here. Okay, here we need to understand here move R0 comma 99H. Here I am just moving content to R0 with 99H. Directly we are accessing this one. Why? Because right now we are in register bank 2. I am using currently this register. Okay, that way we need to understand. Here move R1 comma 85H. Now this R1 will be used. Okay, here we can switch to that respective bank, and we can use those registers. For example, if I want to use these registers, so that I can switch to this branch, switch to this bank, and we can use these many registers. Okay, next we'll understand push and pop operations here. Okay, here I am just moving the R6 with 25 and R1 with 12H and R4 with 0F3H. For example, if it is a letter, we need to add with 0. Okay, just I wrote this instructions. Just I am pushing one by one register to the stack memory. Okay, initially our stack pointer start with 07. If I am just pushing R6 to the stack pointer, then 25 will be saved to the first locations. Okay, my stack pointer incremented by 1, and after that we are storing the value. Okay, next after that, see here next I'm just pushing the R1 content, the 12H to here. Again increment by 1 I am storing, and again increment by 1 I am storing the F3. Okay, here mainly in case of pushing the some content to the stack, always it will increment by one, and after that copy the content to the stack pointer. These are mainly we need to understand our stack pushing operations. Next we'll discuss on the pop operations. We have already filled our stack pointer. Here initially my stack pointer with 07, from the 08 it was filled completely up to 0b. For example, I want to retry from the stack, I can use the pop 3. I'm retrying content from here, so that I can decrement the stack pointer and we can retry from that. Okay, here I retrieved this data and it will be decremented by 1. Again I retrieved the second byte, then again it will be decremented by 1. Again I'm just retrying the third content, a third byte, it will be decremented by 1. Okay, in case of swapping operations, the stack point will be decremented by 1. Here if you see 0b, 0a, 09, 08. In case of pushing, my stack pointer will be incremented by 1. Okay, based on our controllers, for example, if it is 16-bit controllers, it might be increase the 2 bytes, stack pointer incremented by 2 bytes. But in case of 8-bit controller, only incremented by 1 or decremented by 1 by using this push and pop operations. For example, the last one we'll discuss here, if I am using this register bank 1 for the stack, for example, for the general purpose one. For example, this register bank 1, we have the two functionalities. I can use the stack pointer purpose, or I can use for the general purpose this register bank 1. For example, if I want to use this register bank 1 for the general purpose, this stack pointer I can move to the top. Okay, similar way we'll do the same. Here I am just moving the stack pointer to 5fh. Here 30 means 5f means at least here. Okay, I am just moving the stack pointer to here, so that this register bank 1 I can use for the this general purpose. This complete this R0 to R7 I can use for the general purpose. Okay, here set bit of PSW 0.3, 0, 1, 2, 3. Here I am setting this PSW 0.3 means RS1 is 1. That's why I am selecting the register bank 1. Okay, here I got selected the register bank 1. My stack pointer I have moved to the top. Okay, after that I am just using the R2, I am loading with 25, R1 I am loading with 12h, R4 I am loading with F3h. Okay, right now my stack pointer is 5f. If I am pushing some content to the stack pointer, it will be incremented by 1. Okay, pushing means increment, popping means will be decremented by 1. Here I incremented to 60, I am storing the first content 25. Again incremented to 61, storing the second content 12, and incremented to 1 and storing the third content. Okay, these are mainly for the push operations. For example, if we have the conflicts between the stack versus bank 1, so that I can move the stack pointer to above, so that I can use for the general purpose that memory. Okay, this register bank I can use for the general purpose, the stack pointer I can move to the some other location. And today we are mainly discussing about on jump, loop and call instructions. Okay, these are the branching instructions. If you want to move our microcontroller control from one place to another place, mainly these branching instructions can be used. Today we are going to discuss about these instructions one by one today. Okay, first one is the looping. Repeating a sequence of instructions a certain number of times is called a loop. For example, this looping concept is not available. This sequence of instructions we need to write multiple times. Due to this, our code memory may exceed. Why? Because we have within 4 kilobytes of memory in our 8051 microcontroller. It may exceed if this looping concept is not available. Okay, that's why we should understand about this looping concept. We can reduce the code memory as much as possible. Okay, looping action is performed by this instruction djnz register comma label. Okay, here decrement jump if not 0. First we are decrementing the content of the register by 1. After that decremented, we are just checking if it is 0 or not. If not 0, we are just moving to this label referred by the address. Okay, first one is we need to decrement the register value. If not 0, jumps to the target address mentioned by this label. Okay, prior to start of the loop, the register loaded with the counter for the number of repetitions. Okay, before starting any loop, we need to mention the one of the counter that should be loaded with some value. And counter can be R0 to R7, can be used for the counting applications. This program adds the value 3 to the accumulator 10 times. For example, this is my statement 10 times. For example, if this looping concept is not available, I need to write this instruction 10 times, add a comma 03. Okay, instead of writing this 10 times, I am just using the looping concept here. Move a comma has 0, 0 value I am just copying to the accumulator. Move r2 comma has 10, just I am copying this 10 value to the r2. Next, add a comma 03. Initially my accumulator contains 0 plus 03. Finally my accumulator value is 03 after this instruction. Next, djnz decrement jump if not 0. The R2 value is 10 initially, just I am decrementing by 1 to 9. Okay, 9 is not 0, I am just moving to this label, to this target address. Okay, I am executing add a comma 03. What is the content of a accumulator is 03, just adding again 03. Now I will get the result is 03. Again I am just executing this command decrement jump if not 0. Now the content is 9, I am decrementing to 8. 8 is not a 0, again I'm just moving to this location. Okay, this loop will continue until 10 times. After the 10 times I am just checking decrement jump if not 0, this register value is 0. Then I will go to the next instruction, move a r5 comma a. Okay, a contains complete result 30 value, that 30 value I'm just moving to the r5. This is the mainly use of this looping concept. Okay, if the looping concept is not available, we need to write the very much 10 times these instructions for 10 times. Okay, here mainly here I'm using the counter with 10. Okay, here this is a r2 raised is a 8-bit register. We can repeat the loop until 255 times. If I want to repeat more than 256 times, we can write the nested loops. Okay, here if I want to repeat the actions more than 50 to 56 times, then I can use this nested loop. Okay, we will write a one program and we will use the nested loop. How we will write the nested loop? Write a program to load accumulator with 55 and complement the accumulator 700 times. See here the it is telling about this statement more than 256 times. That's why we need to write the nested loop. Move a comma has 55h. This is the first statement. It should load with accumulator with 55. Move r3 comma has 10. Okay, just I am moving the r3 with 10. This is my outer loop. My inner loop move r2 comma 70. Okay, this is my 70. I am just loading with the inner loop. Okay, next complement of A. Just I am complementing what is the content of A with accumulator. Okay, just 55. I am just complementing. Just I will get AA. Okay, zeros will be 1 and ones will be zeros. Okay, decrement jump if not 0. This R2 content I am decrementing by 1. See, 70 decrementing by 1, 69. 69 is not 0. I am jumping to here. Okay, this loop will be continued 70 times. After the 70 times I am going to here decrement jump if not 0 or 3. Okay, this 10 value I am decrementing by 1, 9. 9 is not 0, I am just moving to here. Again I am loading with R2 with 70. Okay, again this loop will continue 70 times. Okay, 70 times multiple 70 times, this R3 is 70 times, that finally 700 times we are repeating with a complement. Okay, these are mainly nested loop. Okay, next we'll discuss about the conditional jumps. Okay, jump if a certain condition is met. Okay, mainly conditional jumps are all are the same way. Okay, if the particular condition is met, then we are going to the that respect to label. Otherwise, next instruction. Move a comma r0. Here the jump if 0 label. Here we need to mention the label. Okay, move a comma r0. Okay, I don't know about the initial r0 content, just I am copying to the accumulator. Just here I am checking jump if 0. Okay, if the accumulator is 0 or not, I am just checking. If it is 0, I will just move to this label. If not, I will go to the next locations. Okay, next move a comma r1. I don't know about the initial content of r1, just I am moving to the accumulator. Here just I am checking whether my accumulator content is 0 or not. Jump if 0. If my accumulator content is 0, nothing but r1 also 0. Okay, if the r1 is 0, just I am moving to this location. If not, next locations. These are mainly use of this jump if 0. Next we'll write one program with jump if not 0. Okay, determine if r5 contains the value 0. If so, put the 55. Okay, here first we need to check if the r5 content is 0. If it is 0, just we need to put the 55 to this r5. Okay, this is the mainly statement. Move a comma r5. I don't know about the content of r5, just I'm moving to the accumulator. Okay, here jump if not 0. Okay, not 0, I'm moving to here. If it is 0, next instruction. Okay, move. Okay, here if it is next, if accumulator content is 0, nothing but if r5 is 0. Okay, just I'm moving to here, I'm just loading with 55. Okay, this is the mainly use of jump if no 0. Okay, these are the conditional statements. Okay, next we'll discuss another conditional statement, jump if no carry. Okay, here the carry carry is not 0, we need to jump to the respective label. If the carry is 1, then to the next instruction. Okay, if the carry is 0, if no carry means if the carry is 0, we need to move to the that respective label. If not, next instruction. Okay, we will write one program using this JNC. Okay, find sum of the values 79H, F5H and E2H. Put the sum in register R0 and carry will put into the R5. Okay, move a comma has 0, just 0 value. I am just clearing the accumulator. Move R5 comma a, and R5 also I am just copying the same content with 0, and add a comma 79. This is the first byte I am adding to the accumulator. Then initially my carry is 0, that's why I am directly jumping to this label. Okay, JNC, jump if no carry. Okay, my carry is 0, right? I will directly jump to here. Next, add a comma F5. Okay, here already A contains 79 plus F5. Now here I got the carry is 1 and result is 6E. This 6E I am storing to the accumulator. Then carry, I got the carry, right? Jump if no carry. No, I got the carry. I will go to the next instruction. I won't jump to this location. Now I got the carry. I am going to the next instruction. I am incrementing the R5 content. Now the R5 value is 1 now. Okay, now here my R5 value is 1. Yes. Okay, next add a comma E0. Okay, now I got the 6E here. After finally I am adding this final byte to the E2. Okay, finally I got the result is 50, carry is 1. Okay, here is jump if no carry. Okay, I got the carry here also. That's why I am going to the next instruction. I am incrementing by 1. Okay, R2 again I am incrementing by 1. Finally my result is R2, R5 is 02. Next move R0 comma A. Okay, here the A result it contains 50. 50 is my just I am moving to the R0. Okay, finally my R0 contains 50 and two carries. R5 is 0, 2. Okay, here I got the one carry and here I got the another carry. Finally R5 is two ones, and here the R0 it contains the final result 50. Okay, this is the mainly use of the conditional statements, and we'll discuss all the condition statement here. Jump if 0, for example, if the accumulator content is 0, just we are moving to the that respective label. If not, next location. Jump if no 0, if the accumulator is not 0, we are moving to the respective location, otherwise next instruction. Decrement jump if not 0. Okay, here I am just decrementing the content of register. If not 0, moving to the another location, otherwise next location. Okay, compare jump if not equal. Here I am just comparing these two byte and accumulator. If not equal, just I am moving to the that respective label. If not, next instruction. Compare jump if not equal register with immediate data. Just I am comparing with the register with immediate data. If both are not equal, just I am moving to the respective location. If not, next location. Jump if carry, if I got the carry, then I am moving to the that respective label. If not, next instruction. Jump if no carry, if the carry is 0, I'm just moving to the that respective label. If not, next instruction. Jump if bit, if the bit is 1, then we are moving to the respective label. If not, next instruction. Jump if no bit, if the bit is not set, then we are going to the that respective location, otherwise next instruction. Okay, mainly all the condition state jumps are short jumps. Okay, the address of the target must be within this minus 128 to plus 127 bytes of the content of program counter. Okay, the program counter may shift within this 128 bytes of plus or minus to the program counter. For example, my location is at 10th location. Okay, I can maybe shift to the previous to the 0 or plus to 127. Okay, within this 256 bytes only we can able to shift our program counter. Maybe plus 127 or minus 128 bytes only we can shift our program counter using this short jumps. Okay, all are short jumps. Okay, we can discuss about short jumps and long jumps here. Okay, here the long jump is the, these two are unconditional. Okay, here these are the conditional jumps. Whenever this condition is met, we are going to move to the that respective location. But here without any condition, just we are just moving to the that particular label. Okay, L jump means just will jump without any conditional, and the short jump also unconditional statement. Okay, these two are unconditional statement. Okay, this is a 3 byte instruction. First byte I am storing the opcode, and the second 2 byte and third byte, and the second byte and third byte I'm storing 16-bit address. Okay, we can using this long jump, I can move our microcontroller from complete program memory within 64 kilobytes of memory. We can move by using this long jump. Okay, short jump means we can move up to, okay, here all conditional jumps are also short jump, and the s jump also short jump. Okay, s jump also within the short jump we can, this is also 2 bytes. First byte we are storing the opcode, and second byte we are storing the relative target address where we want to move, just we are storing the second byte. Here for the long jump, second and third byte we are storing the address is a 16-bit. We can move wherever we want using this long jump. Short jump we can move within this 128 bytes of plus or minus. Okay. Next one we'll discuss to calculate the target address of the short jump. SJump, JNC, JZ. These are the conditional statements, and also unconditional sjump also comes to these short jumps. Okay, all are short jumps only. Next, the second byte added to the program counter, the instruction immediately below the jump. Okay, for example, wherever we want to move our program counter, whenever the condition met or the short jump, then finally we are storing the second byte to the address. Okay, if the target address is more than minus 128 to plus 127 bytes from the address, the below short jump instruction. Okay, mainly for example, if the address target address is more than minus 128 to plus 128 bytes of program counter, may assembler may give the error. Why? Because these instructions should use within this minus 128 to plus 127 bytes of memory. Okay, for example, if it is exceeding that, we should not use these short jumps. We need to use this long jump. Okay, mainly. Okay, these are mainly use of this long jumps and short jumps. Okay, then we'll take one example how we'll calculate the address and how we are putting into the opcode. Okay, this is my code. Jump if 0. Okay, if my accumulator content is 0, I'm just moving to this location. Okay, here assembler it will calculate the relative address and it will put to the second byte of opcode. Okay, as we discussed here, okay, short jump is the 2 byte. First byte is the we are storing the opcode, second byte is the relative address. Long jump also, first byte we are storing the opcode, second and third byte we are storing the relative address. This is the 16-bit address, this is the 8-bit address only. We can jump up to within this 128 bytes of memory. Okay, here all the sjumps and all the conditional statements are short jumps only. We can just move up to within this 128 bytes of memory. For example, here JZ, I'm just moving to this relative location whenever this condition is met. For example, JZ is my opcode is 60, and 03 is my relative location wherever I want to shift. Okay, here assembler it will calculate 1 2 3. Okay, three times it will add to the accumulate program counter whenever this condition is met. Then I need to move our microcontroller control to here 3 bytes front. Okay, here whenever I am executing this instruction, my program counter will be located here. I am just incrementing with 3 1 2 3. Okay, whenever this condition is met, okay, my program counter is here, I am just moving to here. Okay, similar way we'll discuss about the another instruction also. Jump if no carry to the over. Okay, to here I need to move. Okay, similar way it will calculate how many bytes and it will just add to the second byte. Okay, 5. Okay, currently my program counter is here. Currently I am executing this instruction. My program counter is here. I just want to move the 5 locations. Okay, whenever this condition is met, I want to move to the 5 location. 1 2 3 4 5. Okay, whenever this condition is met, our controller directly here it will assembler it will store the address here. Whenever this condition is met, it will go to this relative address. Okay, by using these short jumps within this 128 bytes only, we can shift either positive or negative. Okay, we'll see about the negative addressing. Jump if no carry again. Okay, here I am just moving to here to here to the negative addressing. Okay, addressing will start from the ff fe fd. Okay, I need to just minus with 13 locations, then finally I will get the f2. Okay, these are mainly negative addressing and positive addressing. Okay, here as we mentioned here, right, minus plus 127 to minus 128. Okay, here minus 128 to plus 127 bytes only we are able to shift. Okay, this is a negative addressing. From ff2 we need to come back. This it will treat as a negative addressing. If it is positive, then the msb bit won't set to 1. Okay, this is the mainly difference of the positive and negative addressing for the short jumps. Okay, these are all are the short jumps. S jump, all the conditional jumps are short jumps. Okay, for the long jump, we can jump to any relative location by using this 16-bit address. First bit is opcode. Okay, next we'll discuss about the L call and A call. Okay, mainly for the subroutines we can use this one. Subroutine means subprogram. Whenever we want to call from the main program to subprogram, mainly this long call and A call can be used. Call instruction is used to call the subroutines. Subroutines are often used to perform a task that need to perform frequently. Okay, for example, I want to write any delay function. Okay, I want to call whenever I need to I need require any delay. I can call to that program. Okay, this makes a program more structured in addition to save memory space. Okay, mainly we can use this L call and A call whenever we want to call the subroutine. Okay, 3 bytes instruction. Okay, 3 bytes means first byte I am storing the opcode, and second byte and third byte is a 16-bit address. Okay, we can jump to any location in our complete 64 kilobytes of memory. For example, A call can be used within this 2 kilobytes range only. We can use this absolute call. Okay, for example, within 2 KB my subprogram is available, I can use this A call. For example, more than 2 KB my subprogram is allocated more than the 2 KB, I can use long call. Okay, next we'll discuss in the next slide how the operations. For example, this long call or A call. For example, long call we can use whenever my subprogram is located more than 2 KB, I can use long call. Let us assume this is the long call, whatever we are discussing about. Okay, long call delay. Okay, delay is my subprogram. I am just calling to here with long call. This is my function subprogram. Delay is my subprogram. Okay, here it is located with 300H. Right now, my execution at the, let us assume 0, 1, 2, 3. Let us assume location 3. Okay, just I want to move to the 300H so that I can use the long call. If it is more than 2 KB, I can use the long call. Okay, just I am moving to here. Whenever I am moving to the subprogram, I have to store my the next instruction address to the stack memory. Okay, mainly use of the stack. We have the stack memory pointing at 07. Okay, that we will discuss in the next slide. Just mainly here we will understand whenever my microcontroller control from here to here, my program counter holding the address here. Okay, this address I will copy to the stack pointer, then I will move to our program counter to this address. I will execute this complete instructions. Then whenever this ret is called return, okay, I will retrieve the address from the stack memory to again program counter back. Again I will start executing from here. Okay, just understand how the flow is. Just whenever this lcall is called, whatever the program counter address we are storing to the stack pointer. Okay, and I will go to the new address with the program counter. I will execute this complete instruction. Whenever the ret is called, we need to retrieve from the stack memory whatever the address we saved, right? Again I will retrieve from this stack pointer. Again I will execute from here. These are mainly if you want to execute any subprogram. Okay, we'll understand how we were generating delay here. Okay, here delay, whenever I'll call delay I have called here, my PC counter will come to here directly. Move R5 comma has 55H. Okay, this I'm just treating it as counter with I'm just loading the max value of 255. Okay, DJNZ I'm decrementing with 1, 255 I'm decrementing by 1, 254. And if it is not 0, I'm just going to this again here. Okay, this loop will be continued 255 times. Okay, here again I will decrement. If not 0, I will go to here. Decrement again, not 0, I will go to here. Okay, this statement will execute until 255 times. After that I will go to the return. Return means I will retrieve the address from the stack pointer to program counter back. Again program counter start executing from here. Okay, this is the mainly sequence of the subroutines. Okay, here we'll see how we are storing the whenever the lcall is called, lcall delay. Okay, the next instruction address we need to save to the stack pointer. Okay, this is my next instruction address. This is my subprogram I need to move. Whatever the next instruction always pointing my program counter. Okay, this address I am just copying to the stack pointer. Okay, always stack pointer will starting with 07. Whenever the first byte is pushed, then it will be targeted to 08 address. Okay, here 0007, just 07 I am moving to the first byte and 00 next byte. Okay, whenever this ret is called, again we will retry from this program counter from the stack pointer to again program counter back. Again we'll start executing from here. Okay, this is the mainly use of the stack pointer. Okay, next, if we have so many subroutines also, we are going to store to the stack pointer. Again, we are retrying from that. We can execute many subroutines as usually. Okay, here a call, absolute call. Only the difference whenever this long call can be used within this 64 kilobytes of memory. If you want to move our microcontroller, we can use this long call. A call within this 2 KB of memory. Okay, next, here a call, I'm just using absolute call. Instead of that, yeah, anyone we can use. Here just move. Here I'm just writing one of the program. Here move a comma 55. Move port 1 comma a. Whatever the content of a, I'm moving to the port 1. A call delay. Okay, just I'm calling to the same delay function as we discussed previous. And I'm just complementing a 55. I'm just complementing with a. And short jump, here I'm just using the short jumps is the just it is a unconditional jump within 128 bytes of memory we can shift. Okay, this program, this complement, this sjump, always this is infinity program we are executing. Sjump here means infinity times we are executing this statements in infinity times. Mainly this is the mainly use of this one. For example, if we want to execute our program infinity times, see here indefinitely. Keeping this loop in indefinitely means infinity loops. I'm executing this back to back. Whenever my execution here, again I'm going back to here, again here. This is a continuation. If you want to execute, I can use this short gems mainly. Okay, here how to calculate the delays in our 8051 we'll discuss from here. Okay, for example, CPU executing an instruction takes certain number of clock cycles. Yes, it's correct. For example, each instructions it will take one machine cycle. One machine cycles contain 12 clock cycles. The length of machine cycle depends on the frequency of the crystal oscillator connected to the 8051. Okay, here mainly this machine cycle period mainly depends on the 8051 external microcontroller frequency. In original 8051, one machine cycle lasts 12 oscillations periods. Okay, that's why here we'll calculate period. Okay, find the period of the machine cycle. For example, I am giving the 11.0592 megahertz to the our 8051 microcontroller. Then we'll calculate the machine cycle period. 11.0592 megahertz divided by 12. I will get the 921.6 kilohertz. Okay, machine cycle period is 1 divided by frequency. This is my machine cycle period, 1.085 microseconds. Okay, if I want to execute any instructions, it will take one machine cycle, nothing but 1.085 microseconds. Okay, this is every instruction it is taking this much time whenever my frequency is 11.0592. Okay, basically in our 8051 microcontroller, always we are connecting this frequency. We should remember this timing for each and every instruction execution. It will take 1.085 microseconds. Okay, similarly, we'll calculate the time period. For example, for the first instruction, move R3, comma 55. Okay, it is taking one machine cycle. That's why 1 multiply 1.085 microseconds. Finally, it will take this much time to execute this instruction. Similar way, for the second instruction also, it is taking the same timing. And the third, fourth, fifth also, it is taking the two machine cycles, 2.17 microseconds. 2 multiply 1.085 microsecond, then 2.17 finally. Okay, similarly for the last instruction mul ab, it is taking 4 machine cycles. 4 multiply 1.085 microsecond, 4.34 microseconds. If I want to execute this multiplication operation, it will take 4.34 microseconds. This is a mainly how to calculate the mainly timing of the each and every instruction. Okay, here find the size of the delay in following program if the crystal frequency is 11.059. Okay, for example, I am just giving this external frequency, then we need to calculate how much delay is taken to execute this delay function. Here see, whenever move a comma has 55 55, I'm just moving to the accumulator. Move port 1 comma a, just I'm content of a, I'm just moving to the port 1. A call delay. Okay, just I am moving to this sub function. Move R3 comma 200. Let us take, it is taking one machine cycle. And decrement jump if not 0 R3. Okay, this is 200. I am just decrementing by 199. And if it is not 0, I am just moving to here. Okay, this loop will continue until 200 times. And every machine cycle is 2. Okay, every instruction time is 2. 2 into 200 totally. This is the second instruction. For the first instruction is the 1. Okay, plus 1. and the last instruction is 2 machine cycle it is taking plus 1. Okay, finally these many instructions we have multiply 1.085 microseconds. Okay, finally 436.255 microseconds it is taking if I want to execute this delay function. Okay, these are mainly if I want to increase further I can use the nested loops or some other loops. So, okay, we'll discuss in the next slide. Okay, this is the for the normal loop we can execute up to we can just repeat our execution up to 436.255 megahertz. Okay, here microseconds. Okay, next here by using no operations also we can increase the our microcontroller delay. Here I am just writing my delay program using the no operation delay. This is my subfunction subroutine move r3 comma 250. Here no operation, no operation, no operation it is taking one machine cycle. For the no operations it will take four machine cycles. And dj and z I am just decrementing by 1 250 249, and if it is not 0 I'm jumping to here. Okay, this instruction will execute until 250 times. Okay, 250 here 1 1 1 1 4 ones plus 2. Okay, this is the plus 2. Okay, this it will execute 250 times, 250 times. That's why I'm just multiplying with 250 times, and I got the 1627 microseconds. And adding two instructions outside loop we have. Okay, here I'm just adding this one and this one. Finally for the delay the first instruction it is taking one machine cycle, and last one two. Finally I am adding this result to with the three machine cycle. 3 multiply 1.085. Finally 1630 755 microseconds. Okay, similarly we can calculate the delays when we have the these many instructions. We can calculate the exact delay by using these calculations. Okay, next is a large delay using a nested loop. For example, if I want to increase further delay more than this, let us take more than 1630 microseconds. If I want more than this, so that I can use this nested loops. Okay, as we discussed in the initial case, nested loop and normal loop. In case of nested loop we can repeat our loop in the outer loop and inner loop way. Okay, delay move r2 comma has 200. I'm just moving to here. Move r3 comma 250. Okay, here for the first, this is the outer loop, this is the inner loop. Okay, here no operation, no operation, it will take one machine cycle. This also one. And dj and z just I am decrementing 250 with 249, and it is not 0 I'm jumping to here. Okay, this loop will continue 250 times, and after that decrement jump if not 0 r3. Okay, here r2, here 200 will be reduced by 1, and here the finally reduced to 200 reduced to 199, and again I am shifting to here and just repeating. I am just reinitializing r3 with 250 times. Here 250 multiply into 200 finally. Okay, this much delay we can reproduce. Okay, here the loop we are calculating, we have the 4 into 250 times. Okay, here 1 2 3 4. Okay, inner loop just I am calculating here to here. 4 multiplied 250 times I am repeating. I got this 1085 microseconds. Okay, here 1085 microseconds I am just repeating how many times? 200 times. Okay, 200 into 1085 microseconds, and finally I will get 217000 microseconds. Okay, then first instruction and last instruction also we need to add. Move r3 comma 250. Okay, here the 250, and dj and z r2 comma again at the start and end of the again loop. Okay, here three machine cycle. Okay, 1 plus 1 3, 1 plus 3 machine cycle into 200 times. Okay, this is the last cycle written, right? Okay, this is the 200 times. Finally 651 we need to add to the previous one. 217000 plus 651 equal to 217651 microseconds. Okay, finally if you use this nested loop we can increase our delay as much as possible. Okay, by using two counters we can increase by using a nested loop we can increase as much as possible. We can create the delay by using these instructions in our 8051. We are mainly discussing about on Proteus 8 Professional and also Keil Microvision, and how to use these tools we are going to discuss step by step today. First, we need to open this Proteus 8 Professional, and this is a hardware simulation tool. If you want to verify the your hardware behavior in real time, we can use this Proteus design. Okay, first after opening this Proteus 8 Professional, we need to click on this IS. Okay, if you want to design any hardware, so that we can use this design. Okay, here if you want to take any chip from the library, so that you have to go to the place component. I need one of the component from the library. Okay, here you can search whatever tool you want. Just you can just search and take that component. Okay, here I need 8051 microcontroller. Just I am clicking OK, then place it here. Okay, I got the 805 microcontroller to here. Okay, initially as we discussed in pin diagram, initially all ports are logic high. That means each port pin having the initially 5 volts. For example, if I connect any LED, it will turn on. Again, I am going to the same from library. I am importing LED. Okay, we'll take any of the LED, animated LED will take. Okay, just I'm importing to the microcontroller. Okay, this anode and cathode. This is a common cathode, means the cathode should be ground. I need terminal and ground. Okay, here I am just connecting my LED to the ground cathode, and the anode I am connecting to the port 2.0. Okay, for example, here I have interfaced my LED. Just I am running without my any program. Here I have not selected any program. Here this is my 8051 controller. Here you can select program file. File means executable. Whatever we are storing our program to ROM memory, right? That program we can select from here, executable. And here I am operating my 805 microcontroller with 12 megahertz. Here if you want, change the clock frequency to the 11.0592, so that we can change it here. Okay, currently I have not flashed any program. Just I am checking the initial after the power on. I am just checking the initial behavior. Just I am turning on the. I am just running the my Proteus 8 Professional. Okay, initially this port 0 we don't have any pull-up resistor. We cannot connect to the any of the LED or LCD. Okay, if you want to use this port, we need to connect one external pull-up resistor to the VCC. After that, we can use this port 0. This port 1 2 3 we can use for the initially for the already we have internal pull up, directly we can use for LED or LCD interfacing. Okay, just initially I have connected my LED, it was glown. For example, if I stop, see my LED is off. Again, if I just turn on my Proteus, my LED is on. Okay, initially if I understand in my pin diagram, initially I explained. Okay, initially my port logic is logic 1 means 5 volts. 5 volts I am giving to the LED. This is on. For example, I want to turn off the LED. with port 2.0, I want to send logic 0 to the port 2.0, then I need to write some program, then only I can able to turn off the led. For example, if I am just running this one, initially this led is turned on. For example, if I want to turn off this led, we need to write some specific program. Then we need Keil microvision IDE. Okay, first go to the Google and just search the Keil download C51. We need one of the IDE, integrated development environment. Go to this Keil product downloads. Okay, after entering here, we need to just click on C51. Okay, this is my IDE. If you want to develop any programming, we can just use this C51 software. Okay, here you can just provide your details, first name and last name, email ID, and company like personal and job title. Also, you can just mention personal, and here country you need to select, and phone number. And here you can just give the device name C51 we are currently working on. Just you can give that and submit. And after submitting, then you will get the executable from the directly from the Keil. Okay, for example, I already given the just already my sign up details, so that you will see this kind of executable. Okay, once you have the executable, just click on this, then it will get downloaded. After downloading to your PC, just copy to the D drive. Okay, I have already downloaded and copied to the D drive, and we'll see how we are going to install now. And here the softwares. Here I have downloaded the C51V, the same one. Okay, 960A. Okay, same thing I have downloaded from that. And here just double click on this tool, this exe. Just press S, and after that we need to press next, and we need to agree all the terms. Okay, next we are going to the next. Okay, here you can give your name, first name and last name. And here we need to give our company name. Here I can just mention it as just personal. And here we need to give our mail ID. Okay, after that just we need to press the next. Okay, wait for the installation. Okay, after the complete install, then we are able to open the IDE, integrated development environment. We can write the code and also generate the executable from this IDE, and that executable we are going to flash in this Proteus. We are going to simulate in a real-time manner by using this Proteus. Okay, here also we can just debug step by step as well. Yeah, we'll discuss step by step now. Okay, just we can see in the desktop the our Keil Microvision 5 will be available. Okay, right now I can open this and I can start working using this Microvision 5. Okay, this is a Microvision 5. This is also one of the IDE. We can write our program, and also we can generate the program file from this IDE, and also we can debug step by step. For example, here initially they have given one of the program. Just I want to write my specific program. For example, I want to turn off this LED. Initially I'm just turning just I'm running this Proteus 8. Initially my LED is on. For example, I want to turn off this LED. I need to write some specific program, so that I am just removing all other contents. Okay, these contents are not required for me, and also these timers and all not required. Maybe later on we can discuss deeply. Okay, just I am initializing with port 2. Okay, right now I am working on with port 2. Okay, here just I am writing with the all the logic with 0 0. Okay, initially my port 2 having the FF. For example, here I have saved my program. Yes, this is for the compile. Okay, if you have any compilation error, it will show. For example, here I am just written a wrong syntax, so it will show in which line you have the kind of error. Okay, this is a very useful. Just you can compile also. Okay, after writing your program, you can compile whether if there are any errors. Then we are going to identify using this first step. Okay, this is a translate. It will convert our .c to the directly to the executable. Okay, here the next step, if I want to generate any executable, the second step we can use. Okay, for example, if I want to generate executable from this code, so we need to do some special settings. Okay, here you can change the crystal oscillator frequency to the 11.0592. Okay, usually we are using 11.0592 to generate the particular baud rate to our controller. Okay, just always we are using this crystal oscillator frequency. Okay, in case of debugging, this might be used. Okay, mainly. And here in output, okay, here you can select the folder. For example, my program I'm storing it here currently. Okay, for example, if you want to store to desktop, here also you can also move to the cursor to the desktop. For example, I am trying to move my control to the desktop, so that here you can create your executable folders. There you can store our executables. Okay, just I am creating a new folder like exe. Okay, executable I am just trying to store it here. That's why I'm selecting it here. Okay, here my program will be stored here. Okay, initially I am not selecting this one, creating executable. Okay, just I am doing the second step. Okay, for example, if I am going to my folder, what I have created executable folder, so I does not see any .exe file here. Okay, for example, if I want to generate .executable file, so go to the output, create ex file. Okay, this we need to select, otherwise our hex file won't be generated in the out folder. Okay, that's why here we need to click on and just press OK. Then if you press the second option, then we will get the executable. This is our program file. This we can flash to our ROM memory. Okay, this will be executed our microcontroller by step using the our 805 microcontroller. Okay, and also already we discussed about this IDE. We can also debug step by step. Okay, here I am just going to the debug option. Okay, the running code will be within this 2 KB of memory. Okay, this IDE is allowing up to 2 KB. That is a warning. Okay, here you can take the peripheral. Right now I am working with the port 2. Okay, first we'll understand the .c programming. This is embedded C. Okay, import a register 52.h. For example, if I want to use this port 2 in my program, this header file should be included. Okay, next void main, and this is our main program. This is my open and close braces. Here while one means always my while one is true. I'm going inside. Port 2 I'm assigning with 00. Why? Because here I want to turn off the this complete port, so that I am writing with 00. Initially all port logics are logic 1, just I am writing with the logic zeros to the complete port. Okay, if I am just I have enabled my debug option, here we can go step by step. Okay, here I can execute the step by step my program. Here see, here my complete port was clear to 0. Okay, initially, for example, again I have stopped. Okay, again I have executed. I am going to a debug session again. Okay, the running code should be okay. This ID is allowing our code limit up to only 2 KB. If you want to flash up to 4 kilobytes of memory, then we need to upgrade that Keil officially. Okay, here I went to the debug option. Initially my port logics are all are high. If you see, all the ticks means all are high. For example, if I want to turn off this logics to 0, so that I am writing to port 2 with 00, just I am going to the next step. See here, all the port 2 bits are cleared. It is 0. I am initializing with port 2. Here this 0x0 is written to the port 2. That means directly this all the port pins are cleared to 0. Okay, if you see assembly program, see here, I am just clearing the accumulator. That accumulator cleared one I am just passing to the port 2. Okay, here the similar way, just I am clearing the accumulator, the 0 value I am passing to the port 2. And here the sm, just I am executing multiple times. Here the while one means nothing but sm, short jump. Okay, after the executing this instruction, again I will go back to the while one. Okay, this will be repeated my execution. Okay, these are only two instruction was generated from this .c file. This is my assembly. Finally, from this assembly, we are generating the dot executable. Okay, first dot c will be converted to dot assembly. From the assembly, we'll get the finally executable. Okay, hex code. Okay, that hex code, if you see now, it should be generated output. Why? Because here we have already selected our option to generate the executable. Okay, I have created executable from this program. Okay, if I flash this program to our this Proteus 8, my LED should be off. Just I am selecting my program. Here program file we can select from here. Okay, just double click and go to the desktop. I have exe folder. Okay, that my hello.x I am just selecting, and I am just running my microcontroller. Okay, if you see here, blue means turned off. Okay, initially if I am not flashing any program, my LED is turned off. Okay, here I wrote some piece of code to turn off my port 2. That's why I'm just writing with 00. See, if the blue dot means all are logic 0. Okay, I'm just sending the logic 0 means 0 volts to the LED. This is off. Okay, that's all, friend. I think we have discussed about the what is the use of the Proteus 8 and also Keil Microvision. This is the ID. We can write the specific program, and after the writing our specific program, once we are able to generate the executable. That executable we can flash it here, and we can check the behavior in real time manner by using this Proteus 8. Okay, these are mainly useful of this microvision is mainly to generate the executable and also write the code and also debug step by step.
Discussing about on 8051 IO port programming in assembly language. Okay, it is also one of the feature in 8051 microcontroller, and it is a 40 pin dual inline package. That means it is having the two sides having the pin 1 to 20, 21 to 40, and here the port 0, 1, 2, 3 in S format, and each porting having the 8 pins, totally 32 IO pins we can use for the input and output use case. For example, we can connect LED or switch to the this 32 IO pins. For example, here the port 1 we are having the only the input and output use case, but in case of port 0, 2, 3 we are having the input and output as well as some special functionality as well. For example, if I want to connect any external memory like RAM or ROM, this port 0, port 2 can be used. For example, we don't have any external memory to be interfaced, so that I can use these two ports also input and output use case. For example, here port 3 we are having the multi-functionalities as well as input and output use case. For example, we don't have any serial communication. For example, we have the TXD means if I want to transmit the data serially, I can use this pin. For example, we don't have any transmission use case, so that I can use this port 3.1 also for the input and output use case. Similar way RxD. For example, we don't have any reception application use case, so that I can use this port 3.0 also input and output use case. Next, interrupt 0 and interrupt 1. For example, if I want to serve any service upon any external interrupt, so that I can use these two pins. For example, if this use case is not there, so that I can use these two pins also for input and output use case. Next, here T0 and T1 for the counting applications we can use these two pins. For example, we don't have any counting use case, so that I can use these two pins also input and output use case. Next, read and write. If I want to connect any external memory to indicate whether I want to read the data or write the data, so that these two control pins can be used. Otherwise, we can use input and output use case. Okay, these are mainly use of the 832 IO pins. For example, initially, for example, this 32 IO pins we can use for the input and output use case. We can connect LED or switch to any of the pin. We can write the program as well. Okay, today we are mainly discussing about on the IO port programming. We won't discuss these special functionalities today. Okay, then we will discuss more on today about the port programming, and we need to understand about the port 0 one more use case. Here we don't have any internal pull-up resistors, but in case of port 1, 2, 3 we have internal pull-up resistors. But if you want to use this port 0, we need to connect external pull-up resistor. Okay, we'll see here. Okay, for example, each port pin having this configuration MOSFET. For example, here I'm just giving the logic one. Here VCC and ground will be connected. Okay, that's why we are calling it as open drain. Okay, it can be used for input and output use case. This port 0 also. Each pin must be connected externally to 10k ohm resistor. For example, if you want to use this port 0, for each and every port pin, we need to connect one external resistor to the VCC to the pin. Okay, similar way we need to connect all the port pins. If you want to use the complete all the port pins, we need to connect to the all the resistors, and this we can connect to the LED or switch to the externally. Okay, this is the way we need to configure for the port 0. But in case of 1, 2, 3 we are having internal pull-ups. This 1, 2, 3 we are having internal pull-ups. This we don't have any internal pull-up. We need to connect externally if you want to use. Okay, next we'll discuss, we'll write one program in our Keil software, and we will see whether this output is working as expected in our Proteus. Okay, this is the following code will continuously send port
send out to port 0 the alternatively value 00 and FFH. Okay, we need to write one program continuously. I need to send 00H and FFH to the port 0 continuously. That means I need to write the some while program. Okay, that means completely some infinity loop I need to write here. See, sgem back, I will come to here. Once my program is executed again, if my control is here, sgem again I will come back to here. This is my continuously, I am just satisfying this statement. And here the alternatively I need to send 00H and FFH with some delay. Okay, similarly we wrote the program. Here we'll understand more. Move a comma 00H. I'm just loading the accumulator with 00. Move port 0 comma a. What are the content of a having the 00H? I'm just copying to the port 0. This is my first statement is completed. I just return port 0 with 00H, and I am just waiting for some delay. If I want to observe whether this port 0 is written or not, just I am giving some delay. Okay, here a called delay. This is the other function I am calling it. I am just storing my other program in the origin 300H. Okay, this program I am storing from the 00H. From the start onwards, I am storing this program origin 0H. I am storing from the start. Okay, whatever next I am writing the program, it will be stored in the from 00H from the program memory, and this subprogram I'm storing from the 300H. Okay, this 300H I am storing this complete this function. Okay, here I am just calling the a call, means within 2 KB we can call this function. Okay, I'm just using the a call delay. Here I'm come to here and move R5 comma FFH. Just I am loading R5 with FFH, and here I have loaded with FFH means 255. And again here I am just looping the thing 255 times. DJNZ means decrement jump if not 0. R5 having the 255 value, I'm just decrementing by 1, 254. It is not a 0. This time jumping it here, and this loop will continue until 255 times. Okay, after this I'm just come back to the main program. Just I should write this return. Otherwise my controller will be stay here only. Okay, if I want to come back to the main program, I should always write the return command. Okay, after the completion of this function I will come to here again, and I am just writing the accumulator with ff. I am just copying the accumulator to the port 0. Okay, here I am just writing ff to the port 0. First I wrote 00 to the port 0 and I am waiting some delay, and after that I am writing to the port 0 ff. Again I am waiting for some delay, and from here sgem to the back. Okay, just we understood. First from the I'm just writing to the port 0, I'm waiting some delay, and again I'm writing to the port ff and I'm waiting for some delay. For example, here I'm writing 00 to the port 0 means all the port pins I'm writing with 00. For example, 00 means 8 port pins having the logic zeros. That means if I connect the LEDs, all the LEDs off. For example, if I am just writing ff to the port 0, then all the port pins will be turned on. All the logics I am sending logic 1, all the port pins, all the 8 port pins I am sending logic 1. If I connect the LED will turn on. Okay, we'll write the program in our Keil software, the same program, just I am copying this one. Okay, we'll try to create one program, one project in the Microvision 5. Okay, here initially it will be blank. Okay, if I want to write any program, first we need to create our target in our Microvision tool. Okay, just I am going to the project, new Microvision project, just I am clicking that, and here I will go to the desktop. I will create new folder, and if you want to create a new project, we need to go this similar way. Okay, here my project, just I am writing my project name. Okay, and I need to go inside and save my project name. Okay, this is my first project. We can write anything. First, my first project. Okay, here I have saved my Microvision format. Okay, next after that we need to select our target, whether I need to write we have so many target hardwares, so that I can take the Intel one. Okay, just search the Intel. Okay, just in the Intel we have 8031, we have 3251 we need. Okay, right now I'm just writing the program to the 8051 microcontroller. That's why I took this one. If you see the features, MCS NMOS single chip 8-bit microcontroller with 32 IO lanes, as we discussed in the port introduction. We have the port pin, 4 IO ports, and each port having the 8 pins, totally 32 IO pins, and two timers. Two timers are counters, we can use these two timers, and 5 interrupts and 4 kilobytes of ROM memory. Okay, we have ROM memory of 4 kilobytes and 128 bytes of RAM. Okay, whatever the features are matching to our 8051 microcontroller, that's why I can just take this one, just okay click, and whatever the startup will be added to our target. Okay, next I want to write my assembly program. Okay, today we are mainly discussing about the assembly program. Just I'm just copying this complete assembly program and just copying to here. Okay, just if you want to copy, first I need to add new item to the group. Okay, I need to create one assembly program, right? That's why I'm creating my, this is my assembly. Just I am writing my code, just my file name, and it is my format is assembly, and just I am doing add. Okay, just I have created my assembly dot a51 means assembly 51. Okay, just I am writing my same code here, and my subprogram also I will write to the similar way. Okay, end should be always at the end, that's why I'm just writing from here. Okay, as we understood, see, here to here is my subprogram. From here I am storing my origin is 0h. From here to here I am storing the my program 0h onwards, and from the 300h onwards I am storing my subprogram. Whenever the a call delay is called, and will come to here my microcontroller, I will execute this one. After the completion of this function, I will come back to again to the main program. Okay, similar way we will run our code. Just build, if you want to build, if you want to check any errors, this is the first step. Okay, for example, if I am just writing some wrong here, if I am just compiling here, see, it is the line to having some error. Okay, it is showing by using the dot list file, we are trying to find out the issues. Okay, here just I have compiled, there is no errors. And here this is for the executable generation. If you want to store our executable in a out folder, so that we need to press this one, create X. Otherwise it will just to generate internally, and it will try to debug. If you want to generate any out folder, we need to just select this one, and it will generate the executable in a out folder. For example, if I just see in my desktop objects, okay, here you see the executable. Okay, corresponding this program, we have generated our executable. Okay, we'll understand how the program is executing. We can also, we have the debugging option. Okay, by the use of this tool, we have edited our program, and also we have compiled, and also we generated the executable, and finally we can also debug the same code here. Okay, and here we are getting one of the pop-up. Okay, we'll just go back again, just I'm going to the debug again. Okay, here evaluation mode running with code size limit 2 KB. Okay, our program memory having up to 4 KB, but our compiler it is showing us that you should write the code within this 2 KB. Okay, for example, if you are writing the code more than 2 KB, then we need to take the another IDE. Okay, right now just for us it's 2 KB is enough. I'm just going to the execution. Okay, if you want to execute your code step by step, you can use these options. Okay, for example, I have written the code for the port 0. I can go to the peripherals. I can take the port 0 here. Okay, I want to check whether the real time I'm just writing the port 0 with 00 or FF or not. I need to check in the debug mode. Okay, here also we can simulate, and step by step if you want to simulate, just I am going the step by step here. Okay, here I just written port 0. Here already this instruction was executed. I just written 00 to the port, means all the port pins having the logic 0. That means all the LEDs will off. If I connect the hardware all the LEDs to the port 0, all LEDs will be off. For example, if I am just going further, okay, next step I'm going to here, see here, a called delay. I come to the 300 location, my stack pointer is increased. That means I stored my program to the stack pointer, and I came to here, and I'm executing this one. Here my alpha is 0. Right now I'm loading with FF. If I just execute the next step, see I have loaded R5 with FF. Next step, I will just increment by 1 FE. It is not 0. Again, I will jump to here. Okay, this loop will continue until 255 times. Okay, just if I execute this one like this, F7, F6, this will decrement to up to 0. Once it is 0, it will exit and it will return to the again main program. Okay, if you want to execute furthermore fast, I can just press this one. If you want furthermore fast, I can press this one. See, I completely executed 255 times. I come back to here and I will write ff to the port now. Okay, here I wrote ff to the port. Okay, just again I'm just calling the delay. I will wait 255 times. See here again I have loaded with R5 with ff. I am just waiting for 255 times. Okay, if you want to do further more fast, I can press this one. Again I am just sm back. I will come to here. I will write to the 00. Just I am pressing here. See again I return to 00. Okay, this process will be continued until infinity times. Okay, here this code I need to write, I need to send 00 and ff continuously. Okay, as per the code we have executed, and also it's working fine, so that I can flash, I can design our hardware now. Okay, here by using Proteus, otherwise I need to design, I need to just buy the hardware, I need to flash and check. Okay, by the use of this Proteus 8, we can design our hardware and we can simulate whether in a real-time manner we can connect the LED, and also we can see whether the LED is turned on or off. Okay, here I need 8051 microcontroller from the library. Just right click, place, components, and from library. Just I am taking the 80C51. Okay, I want to flash my code to this microcontroller chip. That's why I'm taking this one. And if you want to use this port 0, we need to connect external resistor again to the place component. I need resistor. Okay, usually we need to connect 10k resistor. For our case, we'll be connecting only 100 ohms. Why? Because this here the voltage drop is very less compared to our in our real-time hardware. But in case of real-time, when you are buying any hardware resistor, we should connect the 10k resistor. But here I am using only the 100 ohms. Okay, why? Because we will get the highest voltage to our resistor to our LED. Just I am connecting LED now. Okay, I will just take the resistor. Okay, here this resistor I am okay. I don't want resistor. I need LED. Okay, from LED. Okay, I need some animated LED so that we'll see the real-time behavior. So that I am just taking the LED and just I'm connecting anode to the pin and cathode to the ground. Okay, here I have designed my hardware, but only one pin I have designed. Okay, similar way we can design for the remaining seven pins also we can design the same hardware. Okay, here we need power supply. I need some DC power supply, 5 volts. I'm just giving 5 volts to here. Just double click here. You can give how much supply you want. Just right now I have given that 5 volts. Okay, just initially I have not programmed this. I have the executable. This I have not flashed initially. I have not flashed my program. Just I am running with initial configuration. This port pin is on. Okay, initially if I just given the 5 volts power supply to the microcontroller, all the initial port pins having the logic one, that means LED on. For example, if I connect this one to, okay, same similar way, if I want to connect to the 8051 to our port 2.0, but there is no need of this external pull-up resistor. In case of port 2, 3 and 1, we no need of this pull-up resistor, but in case of our port 0 we need external pull-up resistor. This is only the difference. Okay, initially all the four IO ports, initially logic 1, all the four LEDs will all the four IO ports initially, all the if you connect any LED to the any pin of the microcontroller, it will be turned on. Why? Because logic 1. Okay, this is due to the logic 1 means 5 volts. I'm just sending the 5 volts to the each and every pin so that LED is on initially. For example, if I want to write this program, just I want to flash my executable. Okay, corresponding this executable I am flashing it now. What is my behavior? This port 0 I need to write with 00, and after that after some delay I need to write with FF. Okay, similar way, if I'm just pressing OK, here just we need to flash our executable in the desktop. We have our my project objects, the same executable I'm flashing it here, and I can just play now. Okay, see here, LED off on, off on, off on. Okay, if you right now I'm sending completely complete port 0, I'm just sending with 00, right? If you connect the LED to here also, it will just turn on. Okay, why? Because I am writing FF means all ones, all zeros, all ones I am writing. If you design any hardware, you need to design same hardware to the complete 8 pins, so that 8 LEDs will on. Okay, similar way, if I want to change the program to port 2, so you can change to the port 2. Just I am changing these two lines of code, just I am saving, again build, generate executable, and I got the executable, and same executable I have selected here. Okay, here right now I have written the program for the port 2, but port 0 as usual. Okay, initially on. Okay, just we need to connect array of LEDs now. Here we have one more hardware that is very useful one. Okay, here LEDs, here we can take the multiple LEDs, so we can just design our hardware efficiently. Okay, here we have gray. Yeah, here we can connect so many LEDs to our port, so I can use this one. This time moving to the right side. Okay, here I can connect 10 LEDs. We have 10 LEDs. This 10 LEDs we can use. Okay, just I am connecting all the 8 LEDs. Why? Because here we written the program for the port 2. That's why I just connecting to the port 2. Okay, this is my all anodes. The left side is anodes and the right side is cathode. This is the mainly hardware use case. Okay, just I have connected 8 LEDs, and the right side we should connect to the ground, all the 8 pins, otherwise it won't turn on. Okay, these 8 pins we need to connect to the ground. Okay, just click here, just go through that, and it will just click on this, it will just create the ground. It will just create our efficient way. Just if you start working on this, it's very useful, and also you can just flash and verify your real-time behavior. See here, I'm just writing with 00 means all the 8 port pins having logic 0, that means all LED is off. If I'm just writing FF to the port, completely all LED is on. For example, we can pause also and verify whether the all LED is on or off. Similar way, you can just pause whenever you want. Okay, see, whenever turn off, I just stopped. Okay, here based on our 12 megahertz we are executing now. If you want to reduce, even you can also reduce. For example, if I am just executing with 1 megabytes on it will be very slow. See, here our microcontroller speed, I am operating with 1 megahertz. See, it's sending zeros and ones very slowly. Okay, usually we should operate our microcontroller frequency 11.0592 in our in mainly in real time in our serial communication we are using that, but normally you can operate with 12. Okay, initially all ports having the logic 1, but in case of port 0, if you want to use, you should connect the external resistor, but all other ports you can use. Okay, but here we wrote the program to turn on or off LEDs, 8 LEDs. We wrote the program, and also we verified the in real time manner, verified the behavior. And similar way, we have another use case also. This IO port programming, we can access bitwise and also bytewise. We can access complete port, or we can also access particular pin. We should not touch the other pins also. We have the bit accessible registers also we have. That's why here I'm writing the program for the only one pin. Okay, sometimes we need to access only one or two bits of a port. Why? Because if I want to connect one switch to the microcontroller, so that I need to access only one pin, one bit. Okay, that's why we can write the bit operations also. We need to remember. Okay, here we have the set bit. For example, if I want to set a particular bit, I can use this set bit instruction. Clear bit. If I want to clear the particular port register bit, so that I can use this one. Complement. If I want to toggle the port status. Initially, my logic is 1. if I want to toggle to 0, so that I can use this one, complement. Here this is mainly for the jump instruction, jump bit. For example, if the bit is set, I need to jump to this respective target. For example, JNB, if the bit is not set, then I need to go to the that respective target. Okay, we'll implement one program for the jump if bit or jump if not bit. And right now we'll implement the for the complement or set or clear bit, we'll implement one program. Okay, here for the complement, I'm just implementing one small program. Here back to back for the short jump, always I need to execute this program. Complement port 1.2, initially my port 1.2 having the logic 1. Why? Because all the IO ports having the initially logic 1, and here I'm just complementing logic 1 to logic 0. Okay, it will be complemented means logic 1 to logic 0 I'm writing to the port 1.2, and here I'm just giving the delay. And similar way we can execute a small delay or max delay, you can just write to the program. Okay, here I am just calling the 8 delay, and here sjump to the back. Currently my port 1.0 having the logic 0, and here I am just complementing again logic 1. Okay, this is a program to just complement the port 1.0. Just I am writing okay, as of now we just access the complete port. Right now we are writing the program for the only to access particular bit. Okay, here I wrote only two statements of program, and here I need to add the my delay program also. We need return also, written from the program. And finally I'm just ending. Okay, if I am not mentioning any origin to the our microcontroller, here you can just mention 0h. Okay, if you're not mentioning also, it will automatically take default 0. Why? Because our program counter always holding with 00h, that's why will be always 00. Okay, here I have just compiled, I am just complementing this one, and I am go back to here. We have the delay. Where is the delay function? I'm just calling 8 delay. Okay, it's went to some other place. 1 minute. This 8 delay, just copied the thing. Okay, 8 delay was here. Okay, okay, this we need. Okay, here I'm just this is my comment complement 1.2. Okay, this is my delay program. Okay, whenever okay, we'll execute and we'll understand better way. Okay, just I have compiled, I got the executable also, we can just debug also. Okay, initially our right now we are mainly executing on port 1.2, that's why I will close the port 0, then I will take port 1. Right now I'm executing for the port 1.2, that's why I can take the port 1 here. Okay, 1.0, 1.1, 1.2. Okay, here I am just accessing this bit. Okay, first I am having the 1. If I just execute this instruction, I am just complementing this 1 to 0. Okay, if you just go to the step, see, I just complemented this 1 to 0. Okay, now I got the logic 0 I have written, and I am waiting for some delay. Okay, if I am just going to the step, okay, I will go to the delay, and I am just writing the R5 with FF. Okay, here the stack pointer also incremented, that means already our whatever the address or the next address is already stored into the PC or stored into the stack pointer. Whenever the return is called, we are retrying back to the our again program counter, again we will execute from the here. Okay, here we came to delay, and here we are executing until 255 times. Here ff it will decrement until 0 to 55 times. After the completion of that, and again we'll come back to the complement. Okay, if you want to execute faster way, again I just executed short jump. Then again I come back to here, I just set to 1, again delay. Okay, if I just execute this one, see, always infinite times continuously. SGM I have the short jump, again I am just go back to here, the infinite continuously I am just complementing the port 1.2. This is my output behavior with some delay. Okay, this is a program we written, and also we simulated, and it's working fine, so that we can design our hardware and also we can flash. Okay, right now I need to connect the LED to the port 1.2. Okay, here this port 0 anyway we are not using it. I will just disconnect. Now I need to connect this anode to the port 1.2. Right now I am just operating 1.2. If you see the code, right, I'm just written for the 1.2. That's why I have connected the LED to the 1.2. Just I'm replaying. Why? Because already my executable is already selected. No need to select again and again. Why? Because this already executable is always generating in the same place from the key, and the same executable is already selected here. Okay, no need to select multiple times. Already it was selected. Just we need to just stop and play. Whatever the changed program will be reflected here. See here, the LED is turn on off toggling. Only this bit I am operating, but if you see the other bits are as it is in a initial format. Okay, if you see here, port 1.0 I have connected to the other LED. Okay, it will just turn on always. Okay, see here, it's always turned on. I have connected to this LED. This LED is on. Okay, this is the way we need to just work on. If you want to work on particular bit also, we can work. Why? Because we have the bit instructions as well as byte instructions also. This is my byte instruction. Move port 0 comma a, completely port I am accessing. Completely port bits are affected. But in case of bit accessing, only particular bit will be accessed. Okay, this is also similar program, just I written with the set bit and clear bit. See here, set bit, I'm just setting the port 1.2, and I'm just waiting for some delay and just clearing. Okay, instead of the complement we can use the set and clear. Okay, same program, if you just flash this one also, we'll get the same output. Okay, similar way I will just flash and I will show you. Okay, just I have written the same program here, just set clear with some delay, and that's it. With some delay. Okay, just I'm executing the same and we'll get the same output. Okay, see here, port 1.2 will be always toggled. For the remaining bits always, if I'm just connecting 1.10 to the LED, it's always turned on. Okay, then we'll understand the next programs as well. Okay, jump if bit, for example, we'll do one real time use case. For example, whenever the switch is pressed, we need to turn on the LED. Okay, here I am switch is connected to the 1.7. Write a program to check the status of the switch and perform the following. If switch is pressed, turn on the LED, and if switch is not pressed, turn off the LED. In our home use case, if I just press the switch, I want to design with our microcontroller so that I can write this program. A simple program we can write whenever the switch is pressed. Okay, here I just taken the 1.2 here. Just okay, here I just took the 1.2 pin for the switch. Okay, JNB jump if not bit set. For example, if this logic is 0, I'm just going to this over and I am just clearing the port 2.0. Okay, here I need to connect the LED. For example, if my jump is set, for example, this bit is set, I will set the port 2.0. Okay, just we'll flash this code and we'll verify the in real time manner. Just I'm just pasted this code, and similar way I have executed. Okay, in this program we need to connect switch to the 1.2 and LED to the 2.0. Okay, here LED to 2.0. Here 2.0 means only the first one is required, and I will just disconnect all other things. Why? Because we'll get confused. Okay, just I have removed all other pins, and here we need 1.2, we need to connect the switch. Okay, here I will take the switch from the library again. From library, I need switch in a real-time manner. I need the switch, and I have just connected to 1.2, 1 point, not 1.0, 1.2, and the left side we need to connect to the ground. Okay, this is the way I have designed my hardware as per my program. Okay, if I just press the switch, I need to turn on the LED. Just see. Okay, it's now it's working reverse order. If I just press the key, it's turn off. It's working near reverse order. Okay, I will just change my program to the just jump if bit to the place. Okay, if the switch is pressed, I need to turn on the LED. If not, just turn off. See here, if the switch is open, my LED is off. If I just press the switch, my LED is on. Okay, now we'll understand the in a real-time manner. Jump if bit. Okay, this port 1.0 is bit is set. If it is bit is 1, then I will go to over and I will clear the bit. and here if the bit is not set, I will come to here, I will set the port 2.0. Here we are clearing the 2.0, here we are setting the 2.0. Assume here, okay, whenever this is executed, always we are going to the back to the again from the start. Okay, this is a simple program. Here if you see here in a real-time manner, jump if bit, for example, if I'm just pressing this one, it is connecting to the ground, I will get logic 0. For example, if it is open, right, I will get the logic 1. Now we'll understand. Now see here, jump if bit, now the bit is set, I need to clear that one. See here, now this bit is set, this 1.2, the red means it is set, blue means it is 0, it is cleared. Okay, now the bit is set. See here, now JB 1.0 bit is set. Now I am going to here, I am just clearing 2.0. Okay, this 2.0 is cleared. See, okay, I have executed, I have just satisfied this statement. If I just open the switch, if I close the switch, it is our logic will be 0. I will come to the this case. Okay, I will just set the port 2.0. Okay, this is a simple way we can understand the program and we can design. Okay, here we have written the same program. If I just press the switch, I need to turn on. Okay, here also we are accessing the bitwise, we are using the jump bit or jump no bit. Okay, these two instructions, the bit instruction we have used and we have implemented one of the use case. If the switch is pressed, we need to turn on the LED. If switch is not pressed, we need to turn off the LED. Okay, mainly we need to mainly use of this Keil macrovision. We need to write the code and also we need to generate the executable from this, and also we can simulate the in a real-time manner. Here also we can just check the real-time manner. Here we need to take the 1 point and port 2 also. Here I will here initially it was set, I will just go to the step. Okay, it's cleared. See, it's cleared. Okay, for example, this 1 point what is the thing, 1.2, right? 1.0, 1.1.2. Okay, here just I have cleared that one, just I am going further. See, it's set to 1. Okay, this is the way we need to simulate in our Keil also. For example, in Keil also we can debug, but if you want to graphically view our output, we can use this Proteus. Okay, in case of Keil also we can see in case of debugging we can also observe few things, but better to simulate in our real-time hardware. Okay, these are mainly discussing about on 8051 programming in C. So far we have programmed using the assembly. Today we are going to program using the C language. Okay, first one is why we program 8051 in C. Compiler produces a X file that is downloaded to the ROM of microcontroller. Okay, here the compiler we have to write the program and also generate the executable. That executable we are flashing to the ROM of our microcontroller. Okay, the size of the hex file is mainly conserved. Microcontrollers have a limited on-chip ROM. Okay, in our 8051 controller, it has only 4 kilobytes of read-only memory. Okay, we can program up to 4 KB, and also we can extend up to 64 KB using the external ports, port 0 and port 2 we can use and extend the memory up to 64 kilobytes of program memory. Okay, this is our limitation in our 8051 microcontroller. Okay, if I program using in C language programming is less time consuming but larger X file size. This is a mainly we are going to the C programming instead of assembly. Okay, it is less time consuming. Maybe it may produce the larger X file. Okay, this may be the one of the use case. And the reasons for writing programming in C, it is easier and less time consuming to write in C than assembly. This is a mainly point we are going to the C. C is easier to modify and update. Okay, it is easier to modify whenever we find any errors or something. We used to modify easily and also update accordingly. And you can use code available in function libraries. Okay, we can also use the code available in a function like math.h if I want to include and do some calculation, so that I can directly use the C libraries also we can use in our embedded C. And C code is portable to other microcontroller with little of modification. For example, I written one of the application programming that I want to port to the another pick controller. For example, I have written the programming in 8051. For example, due to our memory constraint or something, I want to port to another microcontroller, so that I can just with the little modification, so that I can just port it to the another microcontroller. This is the mainly use of our embedded C programming instead of the assembly. Okay, this is the reasons we are going for the embedded C programming. Okay, we will discuss mainly data types today about the embedded C programming. Okay, this already we are aware of unsigned char, unsigned int, signed int. These are the same as it is in our C language programming. Okay, these three are different: S bit, bit, SFR. These three data types are completely different. Okay, we are going to discuss one by one today. Okay, first one is unsigned char, means it is 8 bit 0 to 255. This is the range of my unsigned char. Okay, if you want to take any variable within the range of 0 to 255, so that I can define with the unsigned char. For example, if I want to take my negative range also, minus 128 to plus 127, so that I can take the signed char. Okay, signed is optional. If I am not mentioning it also, just I am defining with the char of variable, directly it will be treated as signed char. Okay, this is the range minus 128 to plus 127. And next, unsigned int, it is 16 bit 0 to 65,535. This is the range of our unsigned int. For example, if you want to take create any variable with the range of 0 to 65,535, so that I can use this one. Signed int means if you need any negative range, minus 32,768 to plus 32,767, so that I can use this data type. Okay, next one is S bit, is the special function register bit addressable only. For example, we have special function registers. If I want to access only specific bit, so that I can use this data type. Next, bit. For example, we have our bit addressable memory from 20 to 2F in our RAM memory. If you want to define any one bit from the bit addressable, so that I can use this data type. Next, last one is SFR. If you want to access complete SFR register through this data type, so that I can use this one. For example, if I want to access any particular SFR register through address, so that I can use this SFR data type. Okay, we'll discuss one by one in deeply with example. First one is unsigned character. My unsigned range 0 to 255. Okay, write an 8051 C program to send the value 0 to FF to the port 1. Okay, this is a program just writing to simple program. Okay, if I want to write this program and if I want to just see the output, so that I can use the Keil IDE. Okay, we can just debug and also see the output. I am just planning to create a new project. Okay, just I will create a new project here in my desktop. Okay, here go to the project, new microvision project we need, and I will create a new folder in the desktop. Within that I will save my program. Otherwise so many files will be generated from the compiler and it will get confused. Okay, here I am my project. This is my folder name. Okay, I'm just going to the inside my project folder. This is my microvision project. Okay, this is my microvision project. Just I'm saving to the same folder. Here I need to select Intel. Okay, here I'm just selecting my Intel 8051 microcontroller. Here we can just check the our features. It is matching to our 8051 microcontroller. 4 kilobytes of ROM, 128 bytes of RAM. Okay, just I'm taking that controller. I want to write the C programming instead of, as of now we written in assembly. Just now I will take the new .c file, add new item to the group 1. Okay, just I want to write, as of now we written using the assembly. Right now I am going for the C. Okay, here is my C file. Okay, just C program file. Just I written my file name. This is the type is .c. Just I am adding to the my project. It was created like my C program .c. Okay, my extension is .c. For example, if I am writing any .c program, first it will be converted to the assembly using the compiler, and after the assembly it will be converted to the object file. That object file will be converted to the finally hex file. Okay, finally that executable we are flashing to our 8051 microcontroller. Okay, this is a simple program I'm writing here in the C programming, just void main. This is my start of the programming, open and close. This is a unsigned char. My unsigned range is 0 to 255. Just one for loop I am just writing it here. This is a first statement is initialization semicolon, and the next one is condition z less than 255. This is my condition semicolon. This is my increment or decrement, always we used to write. This is the initialization, condition, and the increment. This is a mainly for loop. Okay, for example, we have only one statement, there is no need of open and close braces, just simply I can write. For example, if you have many statements, so that I can just write with the open and close braces. Right now the open and close braces are not required, since we have only one statement within the for loop. Okay, for example, I have saved in my program in .c. Just I have executed. See, I got the port 1 is undefined. I have not defined anywhere this port 1, so that I can use the one of the register, one of the hash include we need to do, one of the library I need to include here, otherwise we'll get the compilation error. Okay, here already we have register 51.h. They have already created one of the header file for the embedded C use case. That's why I have just included here. Just again I am compiling. See, this port 2 is already defined in this register 51.h. Okay, that's why if I just open this one, see, port 1 already here it's defined. See here. That's why here all the registers are defined here. That's why I'm just including this register 51.h. Okay, I just included so that my compilation error is gone. Okay, just I want to send, what is my program, write an embedded C program to send values 00 to ff to the port 1. Okay, here I'm just writing the decimal values, it will be converted to the hex, that hex values will be returned to the port 1. Okay, just we'll debug step by step now. Just I'm going to the debug. Okay, here only we'll see the output of my program. Here I'm just going to the port 1. Okay, here I am just modifying the port 1, that's why I took the port 1. The remaining ports will be, there is no effect on the remaining ports. Just I'm executing step by step. Okay, first I am writing 0 to the port. Okay, 1 minute, something was problem. Okay, unsigned char z. Okay, we have executed, right? Unsigned char for z equal to 0, z less than 255, z plus plus. Just I'm assigning z value to here. Should be fine, right? Okay, let me debug. It's going to the, yeah, see, it's working now. Okay, here I'm just written the first 0, and it will be incremented 1 now. 1 is less than 255, just I'm writing 1 to the port. See, 0 1. Next 0 2, 0 3, 0 4, 0 5, 0 6, 0 7, 0 8, 0 9, and a. Okay, here always it will be written to the hex format. Just here I am writing the value 10 to the port, it will be converted to the hex value, that hex value is written to the port. Okay, similar way until 255 we are going to write the values. See here, 10 to 1f, next 20 to 2f, 30 to 2f, until ff it will reach. Okay, this is the way we need to send our program. Okay, here this is a simple program. We return our data from 00 to 255 using the unsigned char. Okay, this is unsigned char range 0 to ff. That's why I took the data type is unsigned char. Okay, next we'll take the another example. I want to write an embedded C program to send hex values for a ASCII characters. For example, I have the ASCII character 0 to 9 that I want to send as a X format to the microcontroller into the port 1. Okay, just I am writing to the just same program. I'm just copying and putting to the my compiler. Okay, this register 51.h should be required. Why? Because here I am using the port 1. Okay, here we'll discuss mainly here. Here there is no compile. I just generated the executable. Okay, before debugging, I will explain the code here. Unsigned char my number array. Okay, this is my array group of characters. If you want to store, I can just define with the open and close braces. Here double quotes, I am just giving the number of ASCII characters here. Okay, here from these characters I am going to take one by one character, and that character I am going to send to our port 1. Okay, here unsigned char z. Why? Because for the index accessing I need one more variable. Okay, I want to access the particular index, that index I am going to that index value I am going to write to the port 1. Okay, for z equal to 0, this is my z equal to 0. 0 is less than 10. Okay, that's why I'm going to the inside. Okay, here this is my only one statement. There is no need of open and close braces. Just I'm going to the inside. Port 1, my name of array 0 of 0. Okay, here my number of 0. Okay, index 0 I'm accessing. 0 will be written to the port 1. Next I'm going to the increment the value to 1. 1 is less than 10. My name index 2, index 1 I am accessing. Okay, here index 1 I am accessing, and that what is the content of index 1? One value I am writing to the port 1. Similar way, increment index 2, index 3, index 4, similar way until index 9. Index 0 to index 9, totally 10 indexes we are just writing to the port. Okay, here we'll just see the output whether we are writing properly. Here see, I just written the value 0, but I see 30. Okay, this is not the correct one. Okay, here I'm just the ASCII digits up to only one nibble only. See here, if I'm just converting this 0 to the hex value, I will get 4 zeros only. Okay, lower I'm able to see 4 zeros, but higher I'm just seeing some I think this garbage value. That's why I want to do some operation here. I will do some undo operation. I will always mask with 0 the higher nibbles. Okay, just I will do and 0x 0f. Okay, here I am just taking the only the lower nibble. The higher nibble I am always keeping the 0. Why? Because I am just getting the always garbage value. That way I am just initializing with always 0, and I am doing the undo operation with the 0. I will get higher nibble always 0, but lower nibble whatever the value from the ASCII, that I am just going to convert and put it to the port. Just I have executed. Now we'll see, it should be written only 0 at the first time. Okay, see 0, there is no garbage data now. Why? Because I am just clearing the higher 4 bits here, and lower 4 bits I am just taking from here, all the ASCII characters. Okay, just I am executing one by one now. See, now it is 1. It is as per my program, it is executing now. I does not see any junk data here. Okay, just 0 1 I wrote. Next 0 2 means 0 0 1 0. 0 0 1 0 means 0 2. Next 0 3 0 4. 4 means 1 0 1 double 0. 5 means 0 1 0 1. If you just click on the next one, 5 0 1 0 1. 6 means 0 double 1 0. 0 double 1 0. Only lower nibble. Higher nibble always I am just doing the undo operation with 0. It will be always 0. Okay, here I wrote the 6. Next 7 8. 8 means 1 triple 0. 9. That's it. Okay, we end our program. Okay, this is the way we can access one of the array, and we used to access one index at once, and we are writing to the port 1. Okay, this is a very simple way we wrote the program using the unsigned character. Okay, this is a range up to 0 to 255 range only. If you want to use the any variable within this range, so that I can define the variable using the unsigned. Next is the signed char. Okay, here minus 128 to plus 127. Okay, if you want to write some negative values to the port, so that I can use the signed character. Okay, here if I am not defining any signed before the character keyword, so that it will treat as signed. Okay, this is the optional one. Okay, just I can write the same program. Just here write an 8051C program to send the values of minus 4 to plus 4 to the port 1. Okay, just I want to write the negative values as well as positive values to the port 1. Okay, this is a simple program. I'm just copying to here. Okay, I will explain the similar way. Here it will treat as signed char. My array, this is my array. Okay, here I'm just initializing my array with the different elements here, minus 1 comma minus 2. Here minus 1, here the plus 1, sorry, and minus 1, and plus 2 minus 2 plus 3 minus 3 plus 4 minus 4. Here I am just writing the minus 1 to minus 4 and plus 4. Here I am just writing the minus 4 to plus 4 values to the port 1. Okay, here that's why I take the one of the array, and I am just initializing the all the elements here. And if I want to access the particular index, I need another variable unsigned char of z. Here my for loop, I'm just repeating my for loop until 8. Why? Because we have only 8 indexes. Z equal to 0, Z less than 8 means 0 to 7 my loop will be continued up to 8, and here the Z plus plus. Okay, similar way we'll debug the output. Okay, there is no errors, then I will just debug. Okay, now the negative values means here we will just give the overview. Normally our controller will, it will store 0 to ff, my controller 8-bit range. For example, minus 1 means ff, here minus 1 means ff, and here the minus 2 means, next before the value means f e, next minus 3 means fc, fd, fd, next minus 4 means fc, F, C, D, E, F. Okay, this is a way the negative values will be represented. Normally, our range is 0 to FF. Minus 1 means the last one. Last one means FF. Minus 2 means FE, the before one. And minus 3 means FD. Minus 4 means FC. Okay, similarly, we'll check the output. First, I am writing the value to the port plus 1. Just I am writing the value to the port 1. Here my value is 0, 1. Okay, next one is minus 1 means FF. See, minus 1 means ff. Okay, next value means I'm just writing to the 2 value 2. Okay, next minus 2 means fe. Okay, just I written the minus negative value fe, and the next one is 3, 3 value written to the port, and the minus 3 means fd, and the next plus 4, and minus 4 means fc. Okay, this is a way we are storing the negative values as well as positive values using the character. Okay, this is a way we need to remember. We can also use the negative numbers also, we can store to the port using the signed character. This is a negative range. If you want to use the any variable with the negative range, so that I can use the signed char. Okay, next we'll discuss on the unsigned int. Okay, here write an 8051 C program to toggle the port 1 50,000 times. Okay, here I am just writing the same program. Okay, 50,000 times I have to toggle my port. Why? Because this the 50,000 times means I should use the unsigned int. Why? Because I don't have any other variable with the range of 50,000. Okay, that's why I'm using the unsigned int here. Unsigned int with z. Just I am repeating my for loop. This is my initialization. If you have many statement, it should be open and close braces. If you want to write your for loop only for the one statement, there is no need of open and close braces. Okay, here I am just compiling the program. Okay, there is no error, there is no errors here. I'm just generated the executable. I'm just going to debug session. Okay, first here z equal to 0, it will be initialized with 0, and 0 is less than 50,000. I'm going to execute the loop, and after that I will increment the value 1 less than 50,000. Again I will execute 2 less than 50,000. Again I will execute until 50,000 times. I will execute this for loop. Okay, see here 0 0 ff. I'm just toggling my port complete bits 0 zeros and 1 ff, 0 0 ff, 0 0 ff. This is the way I'm repeating my code until 50,000 times. Okay, I'm just toggling my port 1 until 50,000 times. This is a simple program using unsigned. Okay, here the we can also use the signed. Signed means I'm not just mentioning the any value, just I can write some negative value here minus 10. Okay, I want to repeat until 0, minus 10, minus 9, minus 8 until 0. I just want to repeat my loop only the 10 times. I want to toggle so that I can use the signed int. If you want to just uh, repeat my loop until from minus 32,000 to 0, also we can write the program. Here I can just mention the 32,000 instead of the 10. Okay, here I can just minus 32,000. If you want, just I can use the signed int. Okay, if I'm not mentioning this signed also, it's fine. This is the optional one. Okay, just I want to mention and show to you in the negative indexing. Just build, execute. Okay, here this for loop I need to execute only 10 times, then I need to come out of this loop. Just I am executing 1 2 3 4 5 6 7 8 9 10 times. Okay, just I have executed from this loop. Okay, here after the 10 times I executed from the loop. Okay, this is a mainly if you want to use the negative indexing up to minus 32,000 to plus 32,767, so that I can use the signed int. Okay, if you want to use the positive indexing up to 65,535, so that I can use the unsigned int. This is a mainly based on our variable our use case. Based on our range, I can take the particular data type. Okay, next we'll discuss on the mainly our embedded C data type. These are mainly important data types. Okay, next S bit. Okay, already we discussed about this one. S bit means special function bit addressable. Okay, for example, we have so many special function registers: port 0, stack pointer, DPL, DPH, and pcon register, tcon, port 1, port 2, port 3. All are the special function registers. If you want to access only particular bit in a port, so that I can use this S bit data type. Okay, here write an 8051C program to toggle the D0 bit of port 1. Okay, I want to toggle only D0 bit of port 1. Okay, here only this 90 bit I want to access. I want to toggle only this bit. I should not touch any other bits in the port 1. Okay, that's why I'm using the S bit here. Okay, this we will discuss in the Keil here. Okay, I'm just writing the same program here. Okay, here my S bit, my bit. Okay, here this is alias name. We can write anything here. My name, like my name also you can just write. Okay, here I'm just mentioning with my bit. Here port 1 cap of 0. This means 1.0 I'm accessing. And here the main program. This is my 50,000 times I need to toggle my port 1.0. That's why I just taken the unsigned int z. This z for loop I am just repeating 50,000 times. First 0, 0 is less than 50,000 times. I will execute once and increment 1, and 1 less than 50,000 again I will execute. Okay, just similar I just compiled and will debug the same. Whether I am just toggling the port 1.0 or not, we'll see here. Okay, here I'm just enable the debugger. See here only 1.0 I'm toggling. Okay, for example, if I want to toggle only 2.0, so that I can just change the, instead of 1.0 I just mentioned 2.0. Just similar way I will just debug and enable the debug. Just compiled and also have executed and also done the debug option. Okay, here if I just do this one, see here port 1 is no effect. Why? Because I am just to access the port 2 instead of port 1. Here the port 1 2.0 will be affected. See here. Okay, here based on our programming we can access the any particular bit and we can toggle that particular bit in any of the SFR register. Okay, any register we can access like accumulator or B register. Okay, any register we can access and we can modify the values. Okay, in a particular bit level, so that I can use the SFR bit, S bit. Okay, here you can see the all the SFR registers here. Here the S bit also, see here I'm just defining using this one S bit WR 6. Similar way here the port 0 should be there. See here 80. Okay, here we have only the SFRs only. Yeah. Okay, here I just come to know how to define my particular bit in a SFR register using the S bit. Okay, similar way we have executed. If you want to access the 1.0, we can access here. Just I can change it here. Okay, similar way bit. Okay, for example, if you want to use any bit in a bit addressable memory, so that I can use this data type, bit data type. Okay, here I can just define my variable name. Okay, this bit I can store only one bit here. This is a simple program. This is a S bit. If I want to access, see here, write an 8051C program to get the status of bit 1.0 and save it and send to the 2.7. Just whatever I am doing, just I am taking the data from the one of the port 1.0. I am copying it to the memory. From the memory I am just copying it to the another bit. Okay, here I need two bits. That's why I am just using the two S bits. In the two special function registers I am accessing 1.0 and 2.7. That's why I will use S bit here. And the other one I want to save the one memory bit. That's why I will use the bit data type. Okay, this is the same thing I am just copying to the our Keil programming. Keil compiler. Just I am copying and doing the paste. Okay, here I am just saving and just storing the data here. Okay, let us see here. We'll complement the data, otherwise we cannot see whether it we are copying and we are doing the complement or not. Okay, first let us execute the same program. We does not see any change. Why? Because initially our port values are 1 1. Okay, after that I will show you the difference. Okay, here I took the port 1 and 2.7. See here 1.0 means this one, 2.7 means this one. Okay, this is a LSB and this is a MSB bit. Okay, here I am just storing, I am just copying the data to in bit my port 1.0 to the memory. saved memory I am just copying to the out bit to the here. Okay, just I am executing. We does not see any change. Why? Because here also bit 1, here also bit 1. Okay, I will just toggle the memory bit. Okay, after just copying to here, I am just toggling the bit to the 0 to 1. Okay, here I got initially bit 1 in the port 1.0, that will be toggled. The toggle will be copied to the out bit. This 2.7 will be toggled. Okay, here if it is 1, it will be 0. Okay, here just I'm see here the this is complemented. For example, if I'm just modifying 1.0 here, just I will execute now. Okay, see here, if it is 0, my it is 1, it is complemented. See here, if the 1.0 is 0, and I'm just complementing and copying to the 2.0. Here it is complemented. 0 means 1, 1 means 0. If I'm just giving the 1 to here, it will be 0. After execution, it will be 0. Okay, this is a way we can just store our bit using the bit data type, and the S bit data type only to access a particular SFR register in a particular bit, so that I can use this S bit. Okay, so far we discussed S bit and also bit data type. Final one we are just discussing about SFR. Okay, special function register. For example, if I want to access any particular special function register through the address, so that I can use this one. Write an M8051C program to toggle the all bits of port to 50,000 times. Okay, just I am writing the same program and just copying and pasting to the Keil programming. Okay, just I am go back to the normal editing program. Just I have copied. Okay, see here, just we'll discuss on the how to define. Okay, this is a SFR. Here we can define whatever name we want. Okay, this is any name we can put, and here I am just giving the address of the port 2. Okay, here if you see here, port 2 address is A0. Okay, similarly we can see here port 2 address is A0. Okay, this is my byte addressable. Okay, okay, here just similar way I'm just executing. Okay, here SFR port 2, I am just giving the address through the address I am accessing, so that this register 51 dot is not required. Why? Because I am not using this capital P1, capital P2, capital P3, capital P4. Okay, if you want to use this capital P1, P2, P3, P4 and P0, sorry, okay, P0 to P3. Okay, this is my 0, 1, 2, 3. Okay, if you want to use this ports, so that I should include this register 51.h. For example, directly I'm accessing through the SFR to the address, so that the hash include register 51.h not required. Okay, just I am compiling. See here, it is showing the error at the unsigned unsigned int. Okay, I need integer. Why? Because I need to store until to 50,000, right, until that, so that I can use unsigned int jet. Okay, just I return. I see there is no errors. Okay, here I have not included any hash include register 51.h. Okay, why? Because here I am just accessing the register through the address. That's why I'm there is no errors in the compilation. Okay, just I'm just going to the execution now. Okay, here I'm just doing the compilation. See here, I'm just toggling the port to using the SFR address, using the SFR data type. Many 50,000 times I'm just compiling. I'm just toggling my port data. Okay, similar way, if I want to access the port one, so that here the naming can be anything. Just have changed the to the port one now. Now you will see the port 1 will get affected now. Okay, why? Because the address I have changed to port 1. See here, 90 means port 1. Okay, A0 means port 2. Okay, here you can just change the address here whenever we want to change the port of the hardware. For example, if I want to toggle the bits in port 1, so that I can change the address here, no need to change the program. Okay, here whenever the change, so that I can change it here. Okay, I think okay, the last thing, for example, if you want to define any particular, if you want to access a particular SFR bit, so that I can use the S bit data type. These are all the small letters we need to write. S bit or bit, SFR, these are the all the small letters. This is a all are small letters, we need to write the keywords. Okay, and my name, here you can give the any name. Here port 1 cap of 0. If you want to access the port 1.0, so that we need to write this way. Okay, this is the syntax of the S bit. Okay, here we can give the any name and a bit memory bit. Okay, here just you can define with the any variable name using the bit data type. Next, SF for my name. Here you can give the any name. Based on the address, we are going to access the particular register. For example, if I just mention the A0, directly our port 2 will be selected. See here, A0 port 2, 90 means port 1. Okay, this is a similar way we can access using the address. Here hash include register 51.h not required. For example, here if you want to access the port 1, for example, I have not defined any hash include register 51.h, we'll get the errors. Okay, that's all friends. Thank you for watching my session. Yeah, thank
8051 IO port programming in embedded C. Okay, today we will take the few problem statements and we will try to implement the program, and also we'll see the real-time behavior in a Proteus. Mainly we used to write the programming in Keil software. Just I am just copying my problem statement, and just I will open my Keil Microvision 5 software. If I want to write my program so that I can use this, already I have the project open. I have initially project set up with the .c so that I can write my program. Okay, here this is my problem statement. I am writing in a multiple comment lines. Okay, this is my multiple comment. For example, multiple lines. If you want to comment, so that I can use this slash star star slash. Okay, this is the way I can just write the multiple comments. Okay, here for example, first we'll just read the statement. Write an 80C program to toggle the bits of port 1 continuously forever with some delay. Okay, here I need to toggle the port 1 continuously forever with some delay. This is my statement. Okay, first for example, I want to use the port 1 in my program. That's why I will include one of the header file. This is our embedded C header file. Hash include register 51.h. Okay, register 51.h. Okay, this is a main header file. All the registers are defined here. See here, port 1, port 2. Directly I can use the whatever the port 1 directly address are defined here. Okay, directly I can use that, and here I am just starting my program. Void main. This is my start of execution. In each and every program, my execution start from this main. Okay, just this is my open and close. Okay, here first statement I will complete. Toggle bits of port 1. Okay, for example, port 1 I am just writing with 0x00. That means 8 zeros I am sending to the port. Each port we have 8 pins, and I am just writing 8 zero logics to the port 1 completely. That completely, if I connect any LED, all LEDs are off. All LEDs or off. Why? Because here I'm just writing logic 0 to the each and every pin. That means 0 volts, nothing but the LEDs are off. Okay, next statement, port 1 equal to 0x equal to 0x ff. Okay, this is a hexa value I'm just writing. I'm just mentioning the binary value here. All f's means here the 8 ones. Ff means 8 ones. Each nibble I'm just representing in hex format. F means 4 ones. Again, F means 4 ones. That means here I'm just writing each and every pin to the logic one. I'm just writing to the port 1. That means all LEDs are on. Why? Because here logic 1 means 5 volts. If I just give the 5 volts to the LED, that will on. That means if I connect the 8 LEDs are on. Okay, here I written the embedded C program for the toggling of bits of port 1. Right now I need to implement this continuously forever. Okay, if I want to continuously forever means infinite loop. Okay, here in embedded C we can implement the infinite loops two ways. One is a for loop. One is a for loop. This is my for loop without nothing. Okay, here there is no initialization, there is no conditional statement, there is no increment or decrement. This I will consider as one of the infinite loop. And similar way, and other one, this while of one is another infinite loop. Okay, here see, there is no nothing, and it will go to the further, and there is no condition, there is no increment, just it will just loop forever. Okay, these two are infinite loop. We can use any of the loop. For example, I want to toggle my ports infinite times so that I can use this while. Okay, just I am writing this while here. See, this is my while open and while close. Okay, this is my main open, main close. Okay, here I am just toggling my port continuously forever. Okay, until here I just implemented my code, and I need to generate some delay here. Okay, we can generate the delays two ways. Okay, one is my using for loop, we can generate the delay, and the second one using timers. Using timers also we can generate the delays. Using 8051 timers, we have two timers, right? Using that also we can generate the delays. Right now we can use the for loop. Okay, we can generate the delays two ways. Here I am just using my for loop. If I want to use any variable, so that I am just defining my variable here. Okay, here I can just write my for loop for I equal to 0, I is less than 50,000. Okay, my I range between 0 to 65, 535. This is my unsigned range, so that I can use until 50,000. Okay, here I can use just I plus plus. Okay, here normally for loop we have the open and close braces. Instead of open and close braces, I am just ending with my semicolon. This is also fine. Okay, just this is a replacement. Open and close braces, I'm just replacing with semicolon. Okay, it will also just repeat the loop until 50,000 times. Okay, similar way I'm just giving the delay. With some delay, I'm just toggling my pins. Okay, here I'm just writing all the logic 0, all LEDs are off, and this much delay, my all LEDs are off. Next I'm changing my, I'm just writing to the port FF means all LEDs are on this much time. Okay, this is my delay. Okay, this is also delay. Okay, this is a delay statement, and this is also delay statement. Okay, here just we are generating some delay. Why? Because here for I equal to 0, 0 less than 50,000. Okay, it's true. Okay, here I will stay here only, and plus plus I plus plus means 1. 1 is less than 50,000. Again increment, 2 is less than 50,000. Until 50,000 times I will stay here only. That means I am just generating some delay. Okay, here we implemented this complete use case. Okay, these are my, I can just comment. Otherwise, we'll get the compilation errors. Just I'm using the multiple lines of comment use case. Okay, here I just commented all the lines. Now we can execute our program and we'll see the output of my program. Okay, here if you want to generate executable, we need to see whether this create X file is selected or not. Otherwise, we won't generate any executable. Okay, just this is the first step, and there is no errors and nothing, and just I will generate the executable. Okay, next here similar way, here also we can check the output. Go to the debug option, and here I am just to toggling my port 1 forever. Here just run. See here port 1 is toggling very fast way. Here just all LEDs are off and some delay, and all LEDs are on. This is the way we have just written the program, and it is working as expected. And in practical way, we'll see whether all LEDs are on or off. In a practical way, we can just observe from here. Okay, here I need 80C51 first. 8051 microcontroller. Okay, I will interface LEDs to the port 1. Okay, here port 1 is my left side, so that I can just take my group of LEDs. Okay, I will take from the library again. Okay, LED, here we have so many LEDs also. See here, I can take this group of arrays. Otherwise, I have to take each and every LED and I need to connect. It will be very complex. So that 1.0 I am connecting to the. This is the left side. All are anodes. The right side are the cathode. So I am just configuring it with the common cathode configuration. Just I am connecting each and every pin to the this 8 LEDs one after another. Okay, here 1.0 I am connecting to the first LED. Similar way, I am just expanding my connections. Okay, here 8 LEDs we need to connect to the left side. Okay, here this is my multiple LEDs we here in this hardware. Just I am connecting each and every pin to the left side, and similar way to the right side to the ground. Okay, this we need to consider it as one LED. Okay, here just I am connecting to my left side. I am just connecting to the ground, and we'll see the real-time hardware behavior now. Okay, here I have designed my hardware. Usually, we used to connect one more resistor to the series, and we are connecting to the LED in a real-time hardware. Right now, in simulation hardware, just we can connect directly to the anode. This is fine. Okay, just without programming, I'm just running my controller, just my turning on with my initial frequency and also initial power supply, so that initially all port pins are turned on. That means logic one. Initially, if you connect to the port 2 and port 3, also it will be initially if you connect any LED, all are on. All are initially logic 1 state, 5 volts. For example, port 1, if you want to use, you have to connect external one LED to the VCC. Then only I can use one resistor to the VCC. Then only I can use this port 0. Okay, if you want to use this port 0 for the input and output, you have to connect one external pull-up resistor to the VCC. Then only we can use this complete port 0. For other ports, we have already internal pull-ups so that I can directly use the input or output use case. Okay, here I am just port 1 I am using. There is no need to connect the external pull-up resistor. It has already internal pull-ups. Okay, here I will select the program now. Whatever we have generated now, right? I have stored my executable in a desktop. I will go to my project objects. Okay, here it is generating my executable at 8:33 means just now. Okay, just now we generated the executable that I have selected. Just I am running my code. See, all are off and some delay. See here, our execution always start from the main. Okay, first whenever I am just starting, my all the port pins are logic 0. Just see. Okay, why? Because here always execution from the main. See, initially all are off, delay, and all on, again some delay. Okay, here in a practical way we have seen our output. This is my solution for the first problem. This is a simple solution for the first problem. Just I will copy and I will put it into the PPT solution. This PPT I will attach in the end of the maybe complete 8051 assessments. Okay, here I written my solution. Okay, next one similar way, and I need to generate some exact 250 milliseconds delay. Right now we have generated with some delay. Right now my problem statement was changed. Okay, here my I'm just changing my problem statement. Here just we'll read the problem statement now. Here, write an 8051 C program to toggle the bits of port 1 continuously with a 250 milliseconds. Okay, previously we toggled with some delay. Right now we need to write with the 250 milliseconds delay. Okay, here I will write one more program. Just I will delete my this for loop. Okay, otherwise this for loop I can use the other way. Okay, just I'm copying this one. I'm just removing the all the for loops. Okay, here I'm just toggling the port 1 forever, but right now we need to write the some delay program now so that I can generate exact 250 milliseconds. Okay, I can just implement 1 milliseconds delay program. Okay, this is my milliseconds delay program so that I can just call with 250 milliseconds. Okay, this is my 250. I'm just calling. Similar way, I can just call another 250 after the turn on. Okay, this is a normal way. Here I need to implement my subprogram. Just I am just calling from the main. Okay, here definition I will write here void milliseconds delay. Here I am just taking my argument, right? This is my argument I am passing. Here I need to accept that argument unsigned int. Here I can just take the value any variable. Just I am taking the k value. Okay, already we have used the for loop, right? One of the for loop. Here I can use a nested for loop so that I can generate the multiple whatever the required delay. 250 milliseconds means it is huge delay. I can use the just nested for loop unsigned int I comma j. Okay, this already we written the for the I loop already for I equal to 0, I is less than 1275. Okay, usually we are writing 1275. Why? Because I think this already calculated with near to 1 millisecond. That's why I'm just writing this for loop. This is a 1 millisecond. Okay, this is a loop for the 1 millisecond, which is generated by our 8051 microcontroller with 1275. If I'm just repeating this for loop 1275 times, then I'm generating 1 millisecond delay. So I need to generate 250 times. I need to just repeat this loop. That's why I'm just writing one more for loop. Okay, this is my sum delay. Initially, I think we discussed it. Similar way I wrote, but instead of 50,000, I'm just writing 1275. With this, I'm generating 1 milliseconds. So right now, I can just repeat this loop 250 times so that I can generate the 250 milliseconds delay. Just I am writing one more for loop. Here I will take the argument. I am just taking the j value, j equal to 0, j less than k. Okay, k argument I am just taking here, right? The same I am just compare. I need to just repeat this for loop until k times. That's why I am just incrementing j plus plus now. Okay, here the simple program. Here this is I am just not mentioning any open and close braces or semicolon, so it will execute only this complete statement. Otherwise you can just mention open or close to this statement. If we have only one single statement, we can remove the open and close braces. Okay, here just I j equal to 0, 0 is less than 250. Here I am just calling with argument 250. J less than 250, I will execute this complete statement. It will take the 1 millisecond. After that I will increment this one. 1 less than 250, again I will execute this for loop. Again second 1 millisecond generated. Similar way, if I am just calling with 250, 250 milliseconds are generated. If I just call with 2500, this much delay I can generate using this for loop. Okay, how much delay we want, we can just generate using this statement. See here, I just written my subprogram after my main program. See, if I just compile, we will get the compilation error. See here, delay function is not recognized by the compiler. That's why before the main, we need to always declare the program, and after the main, we can define our program. Define means we can write our program. Declare means okay, here I am just using this program later on. Okay, that's why I'm just defining here, declaring here, and I'm just defining my program. Otherwise just we can move complete program to the before the main. This is also fine. Okay, just I will show you the same way. See here, there is no compilation error. The other way, you can just move the complete subprogram to the before the main. There is no need of declaration here. Directly I can just define the program. The similar way I'm just compiling. See, there is no errors. Okay, here usually this is a better way. We can just define. We can just declare, and after that we can define our program. This is the easiest way, and we will follow the same structure. Okay, just I'm just generating the executable. Right now I'm just similar. Previously we have generated with some delay. Right now with 250 milliseconds. Now already I have my executable same. Okay, it was generated now recently. If you see the timing, 8:43. Okay, and right now only I have just generated. Okay, just similar same executable I'm selecting. See here, 250 milliseconds means it's more than the with some delay. Okay, similar way I'm just waiting off 250 milliseconds, on 250 milliseconds. Okay, off initially. If I just run the simulation, that's initially off with 250 milliseconds. If you see the program, right, execution, always execution from the main. While of one means always true. I will execute this piece of code multiple times with forever. Okay, continuously. Okay, this is my statement I have fulfilled. Port 1 I am just writing with 00. Okay, all the LEDs are off and with 250 milliseconds delay. And similar way, port 1 FF, again 250 milliseconds delay. Again I will go to here, while of 1 true. Again I will execute this loop forever. If you see here, on off multiple times. Okay, here if you want to give further more delay, just you can give the 25,000 also you can give. Why? Because it is unsigned int. You can give up to 65,000 milliseconds also you can generate using this for loop. Okay, if I see here, right, it will just take 2500 milliseconds, it will wait with the logic 0. Similar way, after the logic 1, again it will wait to 2500 milliseconds. Okay, this is a way we can just generate how much delay we want. Just we will execute this for loop many times. Due to this, we are waiting our microcontroller here. Due to that, we are generating some delay. Okay, this is my solution for the second problem statement. Just I can just copy and paste to the our ppt. Okay, this is my second problem statements and the solution. Okay, this is my sub program. I will just mention to the right side. Okay, this is a delay program and just we have generated, and we'll take the another problem and we will try to implement in a embedded C way. Okay, here mainly we will understand, right, and 8051 C program to toggle only bit port 2.4 continuously without disturbing rest of pins of bits of port 2. Okay, right now here only we need to toggle the only port 2.4, but the rest of bits of port 2 should be there is no nothing to be done. Okay, right now I need to toggle only 2.4, the rest of pins as it is in a initial format. Okay, right now I can just right now there is no use of this complete program. Just I can delay program. Yeah, we can use the delay program. Okay, why? Because here I'm just continuously toggling, right? I can use the same delay program. Okay, just I can redefine my port. Okay, here I need to define as bit special functional bit. Okay, this is my special function. For example, if I want to access this special function registers, right? This all are special function registers. For example, this port 1 also special function register. If I want to access port 1.0, so that I can use this completely. If I want to access port 2.4 means one of the special function register, I want to access any particular bit, so that I can use this data type. My pin. Okay, here I am just defining my any of the name here. So here I need to mention port 2 cap of 4. Okay, here I am accessing only one pin. This is my pin. I am just writing 0. Okay, I am without disturbing any other pins of port 2. I am just toggling my only pin 2.4. Okay, similar way here I am just turned off my LED. I am just sent logic 0 to the port 2.4 and here logic 1 to the port 2.4. Okay, here logic 1. Here logic 1 to port 2.4. Okay, here logic 0 to the port 2.4. This means LED off. Here LED off. If I just connect the LED with logic 0 means 0 volts, the LED off and it will wait for 250 milliseconds. Again, I will just turn on the LED and wait for 250 milliseconds. Okay, here I am without disturbing any other pins of port 2. I am just toggling my port 2.4 with some delay. Okay, this is my program I have executed, and similar way we will connect to the port 2. Okay, here I need to connect to the port 2. The hardware design I need to change. Just I will delete all the lines, or we'll take the one more hardware so that that will be very easy. And just I will import already we took the LED array, right? Just I can connect to the port 2 now. Okay, here without disturbing 2.4 I need to toggle only 2.4 without disturbing other pins of port 2. I need to just toggle the port 2.4. Just I am connecting all pins to the LEDs. Okay, just this wire should be connected one to one, otherwise we will get confusion. Okay, here the left side I have connected to the anodes, and the right side I will connect to the ground. Okay, the left side I have connected to the microcontroller, and right side completely to the ground. This is a common cathode configuration. Similar way how we connected with port 1, and similar way I am connecting with port 2. Okay, here I have just designed my hardware. Okay, here just whatever the executable was selected as it is. See here Port 2.4 is toggling. This is a one. This is a 2.4. See here, my 2.4. It is only the toggling, but rest of pins are as it is. Means initial state only. Initial state means all are logic one. Only I am just toggling this one. That's why I have used this S bit, special function bit. If you want to access the any one pin in a particular register, particular bit in a register, so that I can use this S bit. Okay, similar way we know already how to write the delay, and the similar way I have written the program, previous program. Okay, this we have implemented as per our requirement, so that I can just copy it to the solution. Okay, this is my complete program. I'm just copying and pasting to my PPT. Okay, here we implemented as per the thing. Okay, here just I am sub program just mentioning it here. It will be very clear. Okay. Next program will take from the PPT and will try to solve this as well. Okay, just I am copying my problem statement to here. Okay, this is also very nice program. Write an 8051C program to monitor bit of 1.5 pin. If it is low, turn on the LED, otherwise turn off the LED. Okay, here I don't want to delay any program here. Delay program is not required, so that I am just removing off. Okay, here I need two S bits. Okay, we'll discuss one by one. Here I have while loop. Why? Because I need to execute each and every program infinite times. I am just keeping my while loop, and also main program. This register 51.h also required if I want to define any S bits also. It's required. Okay, here I will take the LED to 2.0. LED LED connect LED to 2.0. Connect LED to 2.0. Okay, just I'm connecting LED to 2.0, port 2.0, and here 1.5 I'm connecting to the switch. Okay, here I'm just monitoring. Okay, here if it is low, here my microcontroller, it will just monitor 1.5 pin. If it is low, I will turn on the LED. If it is high, otherwise if it is high, just I need to turn off the LED. Okay, similar way we'll implement. We need two pins to we need to define. Okay, in special function register, this is a port one is a special function register. Port two also special function register. I want to access only 1.5 here in port one and 2.0 in port two. Okay, that's why I will define two pins here as bit. This is my switch. I will mention switch is 1 point equal to port. This is always we should write the capital P, 1 cap of 5. Okay, this is my 5. This is my pin 1. I'm just mentioning it as switch. Why? Because I'm just monitoring this 1.5. That's why I will mention it as switch. I will connect one of the hardware, switch hardware to the this pin 1.5 pin, and the LED I will connect to the port 2.0, 2 cap of 0. Okay, this is the way I have defined my two pins here, switch and LED. Okay, here this switch is my one of the my capital case, right? That's why I can just already this is my one of the keyword in our C. That's why I will just mention SW switch. Okay, switch case we have right in our C programming. That's why it is taking like in a blue format. That's why we should write in a different keyword. This is like always we need to take the we should not use the special keywords in our C language. Okay, here I will just monitor the key. Here if I will use a if loop, if I want to check the any if I want to monitor any pin, right, I can use the switch. I can use the if loop. Okay, if case. Okay, here I'm just checking the switch double equal to 0. Okay, if it is low, just I'm checking if it is low, I'm just using the if loop. If my switch logic is 1.5, logic is 0, what I need to do, I need to turn on the LED. I will turn on the LED means logic 1 means turn on the LED. Turn on LED. Okay, here I am just turning on the LED. This my comment means double slash. Okay, here similar way I can write. Otherwise, just I will use the else loop. If and else, I am just using the if and else case. Simple way. Okay, here the in the else loop I just turn off the LED. Otherwise means I am just using the else in our C programming. Okay, this I have implemented. I will just will execute. Let's see if you have any issues. Okay, here I have used the capital SW, right? Similar way, I will just replace. Right now, we'll execute. Okay, there is no errors and will generate the executable. Okay, right now my program is changed. Now I have to design my hardware as per our my program. So a switch I need to connect to the 1.5. Okay, here I have connected LED. That's why I will just remove this wire and I will connect switch to this one. Okay, just again I will go to the library. From library I will import switch. Okay, in this switch I can just directly take and I will connect to the 1.5. Okay, this 1.5 I have connected and I'm just the left side I'm just connecting to the ground. Why? Because here the initially our port pin logic is 1. 1 means here I'm just checking when it is 0. Here I will go to the compilation. Okay, here in my compiler. Okay, here switch double equal to 0. Okay, initially my port pin is logic 1. Okay, initially logic 1. If I am just pressing my hardware, this my if I am pressing my switch, my port pin, whatever the voltage logic 5 volts to the ground, I am just connecting to the ground. Okay, I will get the logic 0. Okay, okay, whenever the logic 0, I need to turn on the LED. That means if I just press the switch, I need to it will go to the 1.5 has logic 0. If I press the switch, it will go to the 0 volts, logic 1 to logic 0 volts. Okay, finally my switch is at 1.5. My pin just always my microcontroller it will monitor the pin. Whenever this logic 0, I'm just turning on the LED at 2.0, and if it is logic 1, just I'm turning off the LED. Okay, similarly we have implemented and we have flashed the executable. Now we'll execute in a real-time manner. Just I'm playing this thing. See here, if the switch is open, my LED is off. If I switch is pressed, my LED is on. Okay, see here, but the remaining things I am not touching anything. See here, only this pin I am connecting to the switch, and the remaining LEDs as it is. I'm not disturbing any of the pins. Only 1.5 and 2.0 only I am using. 1.5 I am using for the switch, and 2.0 I am using for the LED. Okay, similarly, for example, if I am just pressing the switch, it is on. For example, I want to implement in a reverse logic way so that I can just change my program. For example, if my switch is 0, I'm just mentioning it as LED 0 and here the LED 1. Just I'm changing the logic reverse way, and similar way I have executed. If I want to reflect that change, again stop and start. Okay, here this switch is open, my LED is on, switch is pressed, LED is off. This is a reverse way we have implemented. Okay, here just what is my problem statement? Here we need to just monitor the 1.5 pin. If it is low, I need to turn on the LED, otherwise turn off the LED. Okay, similar way we have implemented, and this is my solution. I can just copy and paste to my problem statement. Okay, okay, this also we have implemented so far. Yeah, we implemented 1, 2, 3, 4. The last problem, I think it is also very interesting. And here I'm just copying my problem statement here and just we'll discuss about the problem statement first, and after that we'll write the program. Okay, here a door sensor is connected to port 1.1 pin. Okay, similar way I need to use the S bit, and buzzer is connected to 1.7 so that I can define with the two S bits. Write an 80C program to monitor the door sensor. Okay, similar way how we monitor the switch, right? Similar way I need to monitor the door sensor when it is opens. For example, when it is 0, similar way when it is opens means 0 will consider as logic 0. When it is closed we can consider it as logic 1. Okay, here sound the buzzer. Okay, whenever it is opened, sound the buzzer. You can sound the buzzer by sending the square wave of the few hundreds of hertz. Okay, it is also very easy program. Just we will define the program in a first we'll define the pins. Okay, first one is door sensor. Just I will just rename my program. SBit door sensor I have connected to the 1.1 port 1.1. Next, similar way, the second one is buzzer. Okay, here buzzer similar as same thing I can just take. This is a buzzer. Okay, same name I'm just taking 1.7. Okay, this is 1.7. I can just connect the buzzer. Okay, here 1.1, 1.7 I have defined, and in my while of one program means this while of one should be required. Why? Because I need to just monitor this door sensor when it is open. Okay, similar way I will just consider as 0 means it is open. Okay, let us consider 0 is open. We can design any of the logic, just I will considering it as 0 is open. Okay, here I will write my buzzer thing here. I have to generate some delay, right? Okay, here I need delay program as well. I will just take the delay program from here. Okay, already we written the delay program. Just I will take the same. Why? Because I need to generate few mega hedges, right? Few hundreds of hedges. That's why I'm just taking the delay program with 250 will take. And this is my definition. This is my declaration. Okay, after the main I can just mention my declaration with semicolon. Okay, here after writing this delay I can just call this delay. Okay, this if loop I am just extending until here. This is my milliseconds delay 250. Just I will just mention 250 milliseconds a similar way, and I will mention here again 250. Okay, here I will just mention it as buzzer. I'm just sending my some frequency to the buzzer. Why? Because see here, buzzer 0 means I'm sending logic 0 to the buzzer. That means my waveform is 0. Okay, logic 0. Okay, here I will show you in a real-time manner in a Proteus. Just here I'm just sending the logic 0. Here I'm just sending the logic 1. Okay, here logic 0 I'm maintaining this much delay with 250 milliseconds, and logic 1 again 250 milliseconds. Okay, here whenever the door is open, let us assume it is logic 0 will consider as door is open, and logic 1 here if you want we can just change the logic as well. Based on our hardware we need to design our code as well. Okay, here the door is open, then I am just sending my frequency to this buzzer. Okay, for example this much time my buzzer will on with the logic 0 again off. Okay, this is the way we are generating some square wave to the this buzzer. Okay, similar way here I'm just checking whether my door is open or not. If it is open I'm just giving the some frequency to the buzzer. Okay, mainly we need to understand by using our programming we can generate frequency also. Just I am just compiling my program. Okay, there is no errors, just I generated my output. Okay, here we have written our code. Now we need to design our hardware as per the code. Okay, here 1.1 I need to connect the door. 1.1 I need to connect the door. Here I will just remove all the connections. 1.7 is it? 1 minute. This is a 1.1 is door. Okay, let us consider this my switch is door 1.1, right? 1.1 I have connected my switch, and 1.7 is buzzer. Okay, here I will take the oscilloscope. We'll see the frequency, and later on, if you want, we can just connect the buzzer as well. Here I'm just taking the oscilloscope. Here, virtual instrument oscilloscope. Okay, here I am just connecting what is my 1.7 to the buzzer. Okay, here buzzer I'm generating some frequency here. I want to monitor that frequency. Okay, as the same program I have selected. Okay, whenever this is open means logic 0 means I need to press the switch. Whenever the logic 0 means I need to press the switch. Otherwise, I will just return a reverse order so that switch open means door open. We'll consider that way. Okay, if it is logic 1, the switch is open, right? That's why I'm just changing my program. Okay, here if it is open, I'm generating my frequency. See here, I can just change. Okay, here I will reduce the frequency. See here in channel 1, I am just generating some frequency here on or off. Okay, I will reduce the delay here so that we'll just mention in a clear way. We'll just right now my square wave is, yeah, it's very faster way. That's why I'm just reducing my frequency to the very faster way with 25. Previously it was very big waveform. Right now I'm just reducing to 25 milliseconds, so that right now we'll see the difference. See here, my waveform is generating like this. See here, on off on off on off on off. Some frequency I'm generating whenever this is open. If it is closed, I'm not generating any frequency. It is initial condition on. Okay, if it is open only, I'm just generating the frequency. If it is closed, I'm not generating any frequency to the buzzer. Okay, here we can connect buzzer as well. Buzzer also. Let me check whether we have the buzzer in my library, in our library. Okay, here I'm just typing my buzzer. Okay, here we have the buzzer also, DC. Okay, here I will take this one. Okay, let us see. Okay, the left side one I will just connect to the ground. See here, I'm just sending logic 0 1. Red means 1 0. Okay, this is a way we can generate our yeah, square wave from the our microcontroller as well. How much frequency we want we can generate, and also we can monitor the whether the door or not, based on the logic 0 and logic 1. Yeah, similar way, whether the switch or door or anything is same. Okay, here this is a way we need to write our programs, and we can implement whatever the program easily in our embedded C. Okay, here I am just write my solution here. This is the last problem, and that is also we have implemented. Okay, this delay program I will just mention to the right side. Okay, that's all friend today. That's all friends today. Okay, I think we have implemented, I think, 5 programs on this port programming. Thank you friends. Thank you for
Today we are mainly discussing about an universal power supply for embedded system. Mainly we need 5 volts DC and 12 volts DC. If I want to operate my microcontroller, we need 5 volts DC. If I want to operate DC motors or some other devices, we need mainly 12 volts DC power supply. Okay, that's why in our home appliances we have 230 volts AC power supply. That's why we need one device to convert AC to DC. Okay, here I am using conversion, AC to DC conversion. Mainly this 230 volts I am giving to the transformer input. This transformer I am just using the step down transformer. It will just convert the 230 volt to, it will just step down the voltage to 230 volts to 12 volts AC. Okay, just I am using the 12 volts AC transformer. This 12 volts AC means always we will get the positive and negative spikes. Okay, like this the sine waveform. Okay, positive and negative spikes. Okay, this positive and negative spikes 12 volts I am giving to the bridge rectifier. Okay, this is a rectifier. We have 3 rectifiers in our electronics: half wave rectifier, full wave rectifier, and bridge rectifier. Bridge rectifier is giving the highest efficiency. That's why I am using the bridge rectifier in our power supply designing. Okay, here this due to this by use of this rectifier, always we used to convert to the always positive spikes. This negative spikes will be inverted to the positive spikes. Always I used to get the output of the bridge rectifier is always positive spikes. Okay, after just giving the after I'm just using the capacitor filter here, just it will filter and it will completely give the DC voltage. Okay, next I'm using the final one, Zener diode as a regulator. This is a filter, and the next one is a regulator. Okay, here I will just get the constant voltage. I will use the Zener diode. Okay, this is a mainly we need to use the circuitry to convert AC to DC. Okay, here I can use the 12 volts regulator so that I will get the 12 volts constant output DC voltage. Here I can use the 5 volts regulator so that I will get the 5 volts DC power supply. Okay, this is a circuitry we need to design in our Proteus, and we'll see the output of the our circuitry. Okay, here I have the Proteus already open. Just I will take the first power supply we need, right? Just I will take from the library. Okay, here we have V sine, one of the sine source, sine waveform. Okay, here I can give how much voltage we want to fit. I can give that much voltage from here. Just we need to double click on this, and here we need to mention the amplitude is 230 volts, and the frequency always in our home appliances 50 Hz. That's why I'm giving these two values here. And after that we need to import the transformer. Okay, now I need transformer. Here I need some simple transformer so that I can take the simple transformer here. Okay, this is enough. Okay, just I'm connecting 230 volt source to the input of the transformer as we discussed initially in introduction. Just I'm giving to this one, and here the main parameters we need to adjust: primary inductance and secondary inductance also one. Then we'll get the same voltage. That's why here I will give 5.12 millihenries. Okay, for example, if you give 5 millihenries, then you will get the 13 volts or something. Okay, if I want to get the constant 12 volts, so that 12 volts AC, near to 12 volts AC, so that I can give this inductance. Only this parameter we need to remember. Okay, just I have given that, and we can measure the voltage by using virtual instruments. We have right now I have the AC source only. Just I am step down into the 12 volts. The output of the transformer I will get AC voltage only. That's why I am just taking the AC voltmeter, so that I can measure how much AC voltage I am getting from this transformer. Just to validate, I am using this voltage regulate voltage. Okay, here I can just start my simulation so that I can observe how much voltage I am getting. See here, 11.6 near to 12 volts AC I am getting output of the transformer. Okay, just I validated. Okay, this is my sufficient AC voltage, so that I can take the bridge rectifier now. Okay, go to from libraries. I can take the bridge rectifier. It's already available in our simulation, so that I can just take the bridge rectifier. This I have to connect to the first end, and this is I need to connect to here. These two I need to connect to the capacitor. Okay, next I will take the capacitor one filter. After the bridge rectifier, I need to take the capacitor. Okay, here I am just taking the capacitor. I think here it should be like 22,000 microfarads. 2200 microfarad is enough. If I want to get the constant output of 12 volts, we need efficient filter here. I need to get the exact DC voltage. Okay, just I am connecting to here, and we need ground also. Okay, here I am just taking the terminal ground. Okay, ground should be connected. Here I am just connecting to the ground, and I have the complete circuitry, so that the finally I can take the regulator now. Okay, after that we will measure the load here. RL means load. Okay, I designed the transformer, and after that bridge rectifier, and after that capacitor. Now finally Zener diode place I am using the regulators. Here already we have ICs. We have two regulators that we can use directly from the library. Okay, here I have 7805 is the 5 volts regulator, and 7812 is the 12 volts regulator, so that I can just use those two regulator. 7812, just we need to type and just import. Okay, here I have two regulators, so that I can design efficiently. Just I am connecting capacitor output to the regulator as we seen in the diagram, similar way. Just this is a voltage in, this is a voltage output. Just I am connecting to the ground, this one. Okay, next finally I can just take the, right now I got the DC voltage. After the capacitor we will get the DC voltage. Here I am just regulating the constant 5 volts. That's why I'm using this constant 12 volts. 7812, it will give the constant 12 volts. I'm using the regulator. The output always should be constant 12 volts. I can take the DC voltmeter. Previously we took the AC here, AC voltmeter. Here I am just taking the DC voltmeter, so that I can measure whether I am getting the 12 volts exactly or not. Just I will play now. Okay, here see I got the constant 12 volts DC. Okay, similar way I will design parallelly also. We can design similar way. I'm just connecting here, and this will be going to the ground as it is. Okay,
Next here, similar way I will take another voltmeter and I will measure the both the voltages now. Okay, here a DC voltmeter I need, just I will connect to here. Similar way, just I will connect to the ground. Okay, now my circuitry is done. Just I will play. See here, 5 volts I got from the 7805 and 7812 I got the 12 volts. Okay, mainly this way we are designing our AC to DC. Okay, this voltage I will connect to the mainly to the our microcontroller. This voltage I am just mainly I am just connecting to the any relays or a DC motor so that I can use this 12 volts power supply. Okay, that's all, friend. I think today, I think only we need to design the power supply and efficient way. And okay, here you can just adjust. Here, this is our main circuitry. Okay, here 230 volts. I am just converting to the 5 volts DC and 12 volts DC. This is the mainly circuitry. And this mobiles also we can use this our mobile pin. We can just connect here, and we can use for the charging. This is a way we can design in our home appliances also. Just a similar way we can design and we can use to connect to our mobiles also. And okay, here that's all, friends. I think for
Discussing about an initial circuitry of 8051 microcontroller. For example, if I want to program to our 8051 microcontroller, and what and all the initial circuitries are required to program to our microcontroller, that we are going to discuss mainly on today. First one is the AC to DC conversion circuitry. Okay, it will just convert the AC voltage to DC voltage. For example, if I want to operate my microcontroller with 5 volts, then we need 5 volts DC power supply. And also if I want to operate any DC motors or a relays, then we need 12 volts DC power supply. Okay, this is already we discussed in the previous session. Today we are mainly discuss about on the power on plus manual reset circuitry, and other circuitry is the oscillator circuitry. Okay, today we are mainly discuss about on only these two circuitry. Okay, here this combination of this resistor and capacitor mainly it is performing this power on reset. Whenever I am just switching on to the power supply to this microcontroller, initially I will get the 5 volts across the resistor. Why? Because this capacitor is not charged initially. Then I will get the 5 volts across the resistor. Due to the 5 volts across the reset pin, I am going to reset my microcontroller from the start. Okay, for example, after that it will keep on charging my capacitor, and the voltage across the resistor keeps on decreasing to 0 volts. Okay, after whenever it is reaches to 0 volts, my there is no reset to the microcontroller. Okay, by the use of this resistor and capacitor, I'm just doing the power on reset. Whenever I'm just supplying 5 volts to this resistor and capacitor, initially one time our microcontroller will be restarted, and after that there is no restart to this reset pin. And if I want to reset after the initialization, then I need to connect one external push button switch. This is the switch if I want to do manual reset, so that I am just directly feeding 5 volts to this reset circuitry. Due to that, I am just doing the manual reset. This is a combination of power on plus manual reset. And the other one, oscillator circuitry. For example, if I want to operate my microcontroller with specified frequency, so that I can connect externally. This is my external crystal oscillator frequency. Okay, and two capacitors we need to connect here. Why? Because if I want to remove the just noise in my oscillations, so that I can use this crystal oscillator plus two capacitors. Okay, this is a mainly 33 picofarads we need to use. Here 10 microfarads, 8.2 kilo ohms. Okay, these are the mainly components we are using. And here 11.0592 we are mainly operating this 805 microcontroller. Why? Because if I want to operate with 9600 baud rate in case of serial communication, mainly we need to feed the external frequency of 11.0592. Okay, these are the three circuitry plus 805 microcontroller, and this circuitry we need to design in a real-time manner, and after that we can program to our microcontroller after the power on. Okay, here and here this circuitry already we designed, this AC to DC conversion circuitry already we designed. Today we are mainly designing this reset circuitry. One, we need capacitor, the first one. Just I am importing the capacitor here, and after that I need resistor also. Just go to the browse option, and I need resistor also. Just I am importing the resistor as well, and here I will just rotate clockwise so that it will be easy to connect between the components. Okay, here I am just connecting to this, and we need push button switch as well. Okay, I need push button switch as well. Just I am typing this push button in the browser so that I am able to find, and also I am able to import. So I am just doing the anti-clockwise direction. So as per our circuitry, I am just connecting to here. Okay, this is my initial power on plus manual reset. Okay, for example, here I already designed my 5 volts power supply. This is my output of the 5 volts power supply. I'm just connecting to the 5 volts of the power supply, and this one I'm just connecting to the ground. Okay, now we will validate whether initially whenever my power on to the this reset circuitry, I will get the 5 volts to this capacitor, and gradually it will reach to 0, and whenever I am just pressing this push button, then I will get the 5 volts across this resistor. Okay, for example, similar way I will take the voltmeter. Okay, here we have the virtual instrument DC voltmeter I am taking. I will just connect across this resistor. Okay, this is the second element. I'm just connecting to the ground. Okay, here I'm just checking. See here, after the just I'm just playing. See, initially if it is power on, from the 5 volts it is dropping to 0. Okay, whenever this capacitor is charged fully, then it is dropping to 0 volts. Okay, similarly here we need to use 10 microfarads usually. Okay, and here always we need to use 8.2 kilohertz. Okay, and kilo ohms. Okay, these are two components we need to design, and here we can just measure. For example, after see here it is gradually dropping to 0 volts. Okay, I will just restart again. See, from the 5 volts it is gradually dropping to 0. That means on the just I am just giving the just turning on the power supply means it will restart once, and after that there is no restart to the microcontroller. Okay, this we need to connect to the our 805 microcontroller. This validation is over. Just this pin I can just connect to the 8051 ninth pin of the 805 microcontroller. And if I want to do manual reset, so that I can just feed the 5 volts power supply to the microcontroller. But this is a circuitry we need to design a real-time hardware. But in case of Proteus, the logic was different. For example, if I am just connecting 805 microcontroller. Okay, for example, this reset circuitry I am just connecting to the microcontroller. Okay, here I will just do one sample program here. Okay, this is a program. Just I am initially my port 1 with the logic ones means initially if I connect any LED to the port 1, all are on. Okay, after this delay I am going to turn off by my complete port. Here I am just sending 4 zeros to the complete port. That means all the LEDs will be off. Initially all LEDs on. Why? Because initial status of the port all are 1. Okay, here I am just giving the logic zeros after some delay. Okay, this is a simple program I am writing here so that I can flash. I can just validate whether my reset circuit is working or not. For example, if my reset circuit is working, if I just press on restart, then my execution should start from here. My port 1 should restart with all ones. Okay, for example, I am just flashing the same code here. Just I am browsing the same code whatever we just flashed. I have the project in the desktop. Just I'm selecting my executable. This is my 344. Just I'm selecting the same executable. I'm just I will connect one LED to the port 1. Okay, initially here I have the LED. Just I will connect to the anode. The cathode I will just connect to the ground. Okay, here I have the ground. Just I will connect to here. Okay, I have connected to the ground. Then just I am playing the thing. See here, initially on. Okay, after some time I'm just turning off the LEDs, all the port 1 LEDs. Okay, here if you see after some time, see all are blue means all are zeros. I'm sending all are zeros means off. Okay, if I press the reset circuitry, it should start from again from 0. All the port pins should be initialized with ones. Initially my LED should on, but it is not restarting. Why? Because in case of this Proteus, the logic is reverse. Whenever the logic 0, whenever the 0 volts only, my microcontroller will restart. But in case of our real-time hardware, Whenever the logic 1 5 volts means it will restart. If I'm just giving the 5 volts to this reset circuitry, my microcontroller will restart in case of real-time hardware. If you buy any 805 microcontroller, we should feed the logic 1 to the reset pin, then only my microcontroller will restart. But in this case I need to reverse my complete voltage here. Okay, here that's why I'm just here I'm just connecting, instead of the 5 volts I'm just connecting to the ground. This I'm connecting to the ground, and the other end I am connecting to the VCC. Just I am just reversing my my RC, one of the RC circuitry I'm just reversed. Instead of initially we used to connect VCC to the capacitor, and right now I'm connecting VCC to the resistor. Just I am doing the reverse logic here. I'm just inversing the, instead of the 5 volts I am connecting to the ground, and if it is ground I am connecting to the 5 volts. This is the way I just reversed. Now we'll see whether my microcontroller is restarted or not. See, initially after the power on, my LED is on. After some time, my LEDs will off. This is my program. Okay, here my program is executing. After some time, my LED is off. If I just press this switch, my execution again should start from initial. See, I'm just pressing this LED, just push button switch. My execution is started from initially. Again, turn on. After some delay, again turned off. Okay, this is the reset circuitry. It is working in the Proteus, but in case of normally in our hardware we should design this way. Okay, the VCC we should connect to the capacitor, and the ground we need to connect to the resistor, and the parallelly whatever the capacitor, parallelly we need to connect the one of the push button switch. From here we need to connect to the reset circuitry. This is a normally in our real-time hardware we are designing this way, but the Proteus whatever the logics are different. That's why I'm operating with the inverse way here. Okay, and if I want to design this crystal oscillator also, we can design here. Okay, similar way we need to browse the crystal oscillator from the library. Okay, we need to stop before if you want to browse any components. Similar way I'm browsing from the here, and I can type just crystal. Just I'm quartz crystal we have, just I can put here, I can just rotate and these two pins I have to connect to the 18th and 19th pin of the our microcontroller. And if I want to operate with specified frequency, so that I can give here for example 1 megahertz, usually we used to provide 11.0592 megahertz. Okay, just I have given that much of frequency, so that I can connect two more capacitors. I have already capacitors already brushed, so that I am just re-importing. Okay, similar way I need one more capacitor. Okay, similar way we can just design these two similar way. You can just connect to the crystal oscillator. The left side we need to connect to the ground. Here this one I already connected to the ground. Okay, similar way I just connected to the these two capacitors I connected to the ground. Okay, similar way I just designed. Okay, here if you see here two capacitors we need to connect the other end to the ground, and the right side I need to connect to the crystal oscillator. For example, if I want to reduce the noise, these two capacitors will be help out. Okay, here I have designed with 11.590. This is the external circuitry we need to design in case of external crystal oscillator if I want to connect. For example, if I want to do a hard reset on power on reset, whenever we need manual reset, so that we need these three components, and we need this power supply also we need to design. For example, if I want to operate my microcontroller, we need 5 volts. This output voltage that I can give to the VCC to the our 805 microcontroller, and ground to the this ground of the microcontroller. Okay, this is the way we need to design the basic circuitry for our 8051 microcontroller, so that I can flash whatever the program we want. But this circuitry is mandatory if I want to program in our real-time hardware. If you want to buy any microcontroller, if you want to turn on, and if you want to program your 805 microcontroller, then you need to design this completely this circuitry, this circuitries machine should. Then after that we can just interface to the our microcontroller, and after that if you want to connect any LED or LCD, then we can connect to our IO ports.
Today we are mainly discussing about an LED interfacing with 805 microcontroller. How we are going to interface one LED to our 805 microcontroller, that we are going to discuss mainly on today. And this is the LED, And how to identify the LED pins? Here we have the two pins, and one is the anode and another is the cathode. Which is the pin having the highest length, that we need to consider it as anode. The other one is cathode, and this is a symbol of LED. And here the anode, cathode, this anode is positive, cathode is negative. And whenever we have this emptying lines, then we need to consider it as it is a LED symbol. And here the LED operating voltage is almost 2 to 3 volts. That's why always we need to connect one series resistor to operate within the 2 to 3 volts. Why? Because here I am just giving the logic 0 or logic 1 to the LED. Logic 0 means 0 volts, logic 1 means 5 volts. Whenever I am giving 5 volts to the LED, it might break down. Okay, that's why we need to connect always series resistor. Okay, here almost the 2 volts might drop here. The remaining 3 volts will be goes to this LED. Okay, that's why always we used to connect one series resistor. And here we'll see two type of LED interfacing techniques. One is common cathode and another is common anode. In case of common cathode, cathode should be grounded. This is a cathode, should be grounded, and anode should be connected to the 8051 microcontroller. Here, in case of common anode, anode should be connected to the 5 volts, and cathode should be connected to the 8051 pin microcontroller pin. Okay, this is a mainly interfacing to the our 8051 microcontroller. Here, this common cathode configuration, whenever the logic 1, then only my LED will turn on. Okay, here the whenever the logic 0, then only my LED will turn on. This is the mainly difference between the these two types of interfacing. Okay, here we will also design our circuitry, and also we'll see practically how we are going to uh, blow our LED. Okay, here I have the already existing project. I will open the existing project. Okay, we have already designed our project. Just I will go to the open project. No, I have not saved any program. Yeah, here. Go to the project. Here I have my initial 8051 circuitry. Here I have designed my power supply circuitry, reset circuitry, and the crystal oscillator circuitry. Okay, right now we are designing one LED interfacing circuit. Okay, here I am going to the library. I am searching LED here. Okay, here we can take any of the animated LED. Okay, next I will take the resistor also. I need to connect resistor in series with the LED. Okay, I'm just taking a resistor with 2.2 kilo ohms. Here, this resistor we can connect always series. It can be before or after mainly. Okay. Okay, the other end I will connect to the ground. Okay, here we'll go to the terminal, and here ground is there. Okay, just I will connect this one. Okay, always my resistor value should be 2.2 kilo ohms. Okay, whenever we are connecting any LED, and here we need to change some options. Here it should be digital. Why? Because we are applying digital logics, that's why this is digital. Okay, right now I'm interfacing to 3.0 pin number. Okay, initially all port pins logic 1. Okay, here initially port 0 we don't have internal pull-ups, we need to connect external pull-up to use this port 0. But in case of port 1, 2, 3, we have already internal pull-ups, and initially we have all our logic 1. Okay, here already I have programmed previously, that's why I will remove the programming. Initially all the port pins are logic 1 means 5 volts, and each port pin we have 5 volts. For example, I am just feeding the 5 volts to the LED, this will on. Okay, this is a common cathode. Whenever the logic 1, my LED is on. This is a common anode. Whenever the logic 0 only, my LED on. This is a mainly difference. Okay, I am just connected with the common cathode I grounded. This is I am just connecting series with the resistor. Let's see whether it should turn on. Why? Because it is initially my logic 1, I am feeding to the LED, this should on. Okay, see here the LED is on whenever the my logic 1, initially my port logic is 1, my LED is on. For example, if I want to turn off this common cathode LED, then we need to do some programming here. Okay, I will do one programming. Initially my port pin is on, and here after some delay I am using the for loop for the delay. Here unsigned. Initially my port pins are all are logic 1. Okay, here unsigned int I for I equal to 0, I is less than 65,000, I plus plus. Okay, here 0 is less than 65,000, again increment, again 1 is less than 65,000. Until 65,000 I will wait my always my microcontroller wait here until 65,000. Similar way one more for loop, again I will wait 65,000 times here. Finally I am making port 3 completely 0x00. That means all the port pins I am sending the logic zeros. My LED off, all the LEDs will off. If I connect 8 LEDs to the port 3, all the 8 LEDs will turn off. Okay, here the mainly I just written the simple program. This I am going to select. Okay, initially my LED is on, see here initially on. Okay, right now I am going to program. After some delay I want to turn off my LED. That program I written with the common cathode. Let's see how the common cathode LED work. Okay, initially is turn on, see here initially will turn on, and whenever I am sending logic 0, then only my LED will off. See, after some time my LED will turn off. Okay, this is my common cathode configuration. Common anode is different, this will be reversed. Okay, again I will remove my flash program. Okay, initially we'll see, initially it should be, see here similar way I have connected both to the in series, and here there is no need of ground. This should be connected to the VCC. Okay, VCC I have already designed my power supply, I am connecting to the VCC. This cathode 1 minute, sorry, this anode should be connected to the VCC. Common anode configuration. Right now we are doing the second interfacing. Already we did the first interfacing. The second interfacing, anode should be connected to the 5 volts DC power supply. Yeah, anode I connected. Cathode should be connected to the pin of the microcontroller. This is a common cathode configuration. This is a common anode configuration, sorry. Okay, this is a common anode configuration. Anode should be connected to the VCC and cathode should be connected to the microcontroller pin number. Okay, next here I am just playing initial without any program. If you see here, I does not flash any of the program. Initially here I am supplying 5 volts. The anode also I am giving the 5 volts to the DC power supply. Okay, both the sides I am giving 5 volts now. Initially my port pin having the logic 1 5 volts. The cathode I am giving the 5 volts, and also anode also 5 volts. Initially it will be turned off, common anode configuration. Why? Because if, here I am just giving the logic 1 logic 1. Both the sides if I give the logic ones, then initially my LED is off. Okay, just I am playing this one, initially is off. Okay, next one, if I want to turn on the LED, I need to do some program. Okay, initially I am giving the logic 1. After that logic 0, after some time my LED is on. Okay, same program I am flashing it. Okay, here the reverse logic. Okay, here just I am flashing the same executable. Initially it will off. After some time it will turn on. Why? Because whenever I am sending the logic 0, my LED is on. Okay, after some time my LED will on. Okay, these are mainly they are operating in a reverse order. For example, whenever I am giving the logic 1, this common cathode will LED turn on. Whenever I am giving logic 0, this common anode LED will turn on. Here mainly we can change the program. For example, whenever I want to turn on or turn off, if I want to do in a reverse order, so that I can modify the hardware instead of modifying the software. Okay, these are mainly we can use any of the method. We can try to interface to our microcontroller, and we can use any of the method for our interfacing. Okay, thank you friends.
Mainly discussing about on how to interface 7 segment to the 805 microcontroller. This is our initial circuitry, this is our power supply circuitry, this is our reset circuitry, this is our crystal oscillator circuitry. Right now I'm importing 7 segment from the library. Here just we can type 7 segment, so we'll get so many ICs as well as the graphical displays. Right now I am importing this common cathode configuration. Okay, for example, in case of common cathode,
all the anodes we should connect to the microcontroller. The cathode should be connected to the ground. And here each pin, this pin is connected to the segment 1, this pin is connected to the segment 2, this pin connected to the segment 3. Similar way for the all the segments. Whenever this logic 1, this particular segment will turn on. Whenever the logic 0, this particular segment will turn off. Logic 1 means 5 volts, logic 0 means 0 volts. Okay, this is a mainly we have to treat as each and every segment we will consider it as one LED. Okay, whenever this logic 1, this particular segment will turn on. Here this is a group of 7 LEDs, we will call it as 7 segment. And here if you want to display 0 to 9, and if you want to display any ASCII digits, right, so that we can use this 7 segment mainly. And here we have two configuration: common anode 7 segment, common cathode 7 segment. This is a mainly every segment will turn on whenever this logic 1. In case of common anode, every segment will turn on whenever the logic 0. Why? Because this anode should be connected to the VCC. Whenever this logic 0 volts, then only my particular segment will turn on. Okay, these are only difference between the common anode and common cathode. These are mainly familiar with our programming. That's why I'm taking this one, common cathode. Okay, whenever this logic 1, I'm going to turn on this particular segment. That's why I'm just interfacing with the 805 microcontroller with our common cathode. Cathode should be connected to the ground. Okay, this is our we need to take the terminal. That terminal we need to connect to the ground. Okay, I have connected to the ground. These anodes I need to connect to the port pins. Okay, here initially our port pin with logic 1. Why? Because initially if I turn on power supply to the 805 microcontroller, all the port pins initially with logic 1, that means 5 volts. Each port pins giving the 5 volts power supply. Due to that, my complete 8 digit will turn on. If I just turn on my 805 microcontroller without any program, so that all the port pins, red means logic 1. Okay, here if you want to use port 0, we need to connect external pull-up resistor, then only we can use port 0. But in case of port 1, 2, 3, we have already internal pull-ups, so that directly I can interface with any of the device. Okay, here I have interface 7 segment. Initially this 7 segments I am sending with logic 1, so that this I am displaying logic 8. For example, here I am not connected any of the pin, so that this 0 I will display. See here, this is a segment 1, segment 2, segment 3, segment 4, segment 5, segment 6, segment 7. This is a normally the always clockwise direction. All the segments are notated. Okay, here this is the display I have interfaced with 805 microcontroller. Right now we'll program how to display 0 to 9 digits on this 7 segment. I am just written some small program. Hash include register 51.h. For example, here I want to use port 2, so that I have included this hash include register 51.h. And here this is a starting of our program, void main void. This is a open braces, start of the program. Here unsigned int I. For example, if I want to observe each and every digit, so that I am giving the some delay between the each and every data writing. For example, here I am writing 0 digit to the 7 segment, so that if I want to send 0, this last segment I need to send with logic 0. This last segment I need to send with logic 0 means I have not connected, so here I displayed 0. Okay, similar way I have written my particular code here. Here I am sending all ones. Okay, here from the LSB all are ones, this MSB both are 0 0. Okay, here this MSB, these two pins I am sending logic zeros, and the remaining pins I am sending logic 1. That means until here will turn on, from here to here until here it will turn on. Due to that, we are displaying logic 0, 0 ASCII value to the 7 segment. For example, if I want to display 1, so that I need to just this is a LSB bit 0 1 1, all are 0. Similar way I am just written some binary value here 0 1 1. I'm just turning on this segment and this segment. This is a 0 1 1, all are 0 remaining. That's why I have just written this 0 1 1 0.
So that 6 I am writing to the port 2. Finally I will display 1 to the this particular 7 segment. For example, if I want to display 2, see here I need to turn on this segment, this, after that this segment, this segment, this segment. Only I need to turn off this and this, so that I am writing this hex value. See here, 1 1, this and I have turned on, and this I am not turning on, 0. Okay, lower these two LSBs are I turned on, this one, and this one I have made it as 0. This means this segment will turn off, this and this turn on, again this I need to turn on. Okay, after that I will come to here, this I need to turn on, this I need to turn on, again this I need to turn off. Okay, that's why here I written 0. Okay, this segment and this segment I will turn off, so that I will display 2 on to this 7 segment. Okay, similar way I have written 0 to 9. For example, if I want to display 0, so that I will send logic 0 to this segment, so that I can display 0. For example, if I want to display 1 to the 7 segment, only this segment I will send with logic 1. The remaining segments I will send with logic 0. Okay, this is a way we need to write the particular logics to the particular segment, so that we will turn on or turn off. Okay, based on that we will display 0 to 9 digits onto this 7 segment. And here I written the logics, and after that I have given some delay here. For I equal to 0, I is less than 40,000 I plus plus. Okay, for example, due to this for loop we are waiting so much time here, 40,000 times within this for loop. I equal to 0, 0 is less than 40,000, and 0 plus means 1. 1 is less than 40,000. This loop will continue until 40,000. Due to that we are waiting so much time here. Okay, I am just writing port 2 with 3F, so that I am displaying 0. I am waiting some time, and after that I am displaying 1. I am waiting for some time, and after that I am displaying 2. I am waiting for some time. After that I am displaying 3. I am waiting for some time. Okay, this is the way we wrote the program until 0 to 9. I am displaying, and after the 0 9 and I am just stopping my program. 0 to 9, finally I will stop my program. This is my program we wrote in our Keil. Okay, similar way I can generate the executable. Okay, here there is no errors, it will generate the executable. That executable will flash it here. Right now we can display 0 to 9 and we'll stop the program. Okay, here if you see the 9 5, okay, just now I have generated the executable, so that I have just imported that one. So I am displaying 0 first, and after that 1. Next 2 means this segment should be turned on, only this and this I need to turn off. Okay, that's why I have displayed 2. 3 means only this and this segment I need to turn off. 4 means only these 3 segments I need to turn off. I need to send logic 0, remaining logic 1. Similar way 5 also, only this and this segment I need to send logic 0, remaining 1. For 6 these are 0 and remaining logic 1s. 7 these are 0, all are 1s, these 3 are 1s. And similar way 8 means all are 1s, we need to send all are 1s. 9 means only this and this I need to send logic 0, remaining all 1s. Okay, this is a similar way we displayed 0 to 9. For example, if I want to display 7, only these 3 segments should turn on. 7F means all are 1 means 8 I am displaying here. See, all the 7 pins I have interfaced. This is a 2.0, we need to consider as 2.0, 2.1, 2.2, 2.3, 2.4, 2.5, 2.6. 2.0 to 2.6 I am sending with logic 0, logic 1s. That means 8 I am displaying. This is the mainly we need to write. The right one we need to consider as port 2.0. This is a 2.7. And similar way, if I want to display particular segment, for example, if I want to turn on only this segment, so that I can just write 0 1, all are 0. That means 2 I can write to this port, so that I can just turn on only this segment. For example, if I want to turn on only this segment, this is a 1 I need to write, and remaining all are 0. 0 6 zeros 7 zeros 1 1 means 0 1 hex format. That hex value we need to write to the port 2. Okay, mainly first we need to represent with the binary format. For example, let us display only I want to just turn on only this first 2 digits. Okay, just how I am going to write, let's see. Okay, just I am removing everything, complete code. First I want to turn on only first two digits. Okay, let us assume for example this digit, this I want to turn on. This is a zero digit, I need to turn on. This is a 1 2 3, third digit I need to turn on, 0 third. Okay, similar way I can represent here. Okay, here this is our simple program. Here I have let us assume we have 8 digits finally, but I have connected only 7 digits. Okay, I want to turn on this digit, this I want to turn on only these 3 digits. Let's see how we can turn on. Okay, first one I need to turn on, this is my logic one, and the second is not required, and third also not required, fourth is required. Okay, that's why I'm just turning on here, and fifth is not required, sixth is not required, seven is not required. Okay, just simply I wrote this. I have just converted, I need to convert to the hex format now. Okay, here 1001 means 9. Here 100 means 4. This is a 4 9, so that I can display. Here I can turn on this segment, this segment I will turn on, this segment also I will turn on. Okay, let's reproduce the executable, so that just I can replay. Why? Because I have already selected the same executable, so that I can just replay. See, only these three segments I turn on. Okay, based on our requirement, if I want to turn on only this particular segment, so that I can just write that particular logic one to the particular segment, so that I can turn on easily. This is the mainly we need to prepare our program. Okay, similarly, if I want to turn on, for example, one I have turned on only these two, I can turn on these two also. Okay, similar way we need to write this x value. Okay, similar way I can just write this one 1 1, remaining 0. Okay, last these two digits I am writing with. Okay, similar way I wrote like this 3 0. This I just converted, 4 zeros means 0, and 0011 means 3. Okay, here I am sending all are 0. This is 0 0 0 0 4 zeros, and after that these two are 1 1 1 I am sending, last one is 0. Okay, so that initially we displayed 1 like this 1 1. I can also display only these two segments also. Okay, similar way I wrote the program. I want to display 1 here. Previously we displayed 1 here, and right now I am going to display 1 here. Okay, similar way I have converted, I display like this. See, if I want to just turn on the particular segment, so that I can just send the particular logic one to the particular segment, so that I can just turn on that particular segment. These are mainly we are going to interface this 7 segment. A similar way, if you add 3 digits, so that if you want to design our clock also, digital clock also, we can design by using this 7 segment. So many digits we can connect parallelly, and also we have so many graphical displays, so that I can just I can just display 0 to 9 to the particular digit, and 1 to 20 to the another digit. Okay, similarly we can design so many digits parallelly, and we can interface all the 7 segments to the microcontroller, and we can design some digital clock also we can design by using this 7 segment. Okay, thank you friends, thank you for watching.
DC motor interfacing with 805 microcontroller. Mainly this DC motor we are not directly interfacing with this 805 microcontroller. Why? Because this DC motor mainly operating with 12 volts, and also if I connect this DC motor directly to the microcontroller, we may get back EMF from this DC motor. Due to that, our microcontroller may damage. Okay, that's why we are not directly interfacing this DC motor with the 805 microcontroller. We need some intermediate some circuitry to interface this DC motor with our 8051 microcontroller. Okay, mainly we'll discuss on the H bridge. Okay, H bridge, we are using 4 transistors and one motor. This is one of the circuitry. Okay, mainly from the microcontroller, we used to operate this mainly these transistors. For example, if I am giving the from the microcontroller logic 1, logic 0. Logic 1 means this transistor will turn on. Logic 0 means this transistor will turn on. Okay, this is the transistor is connected in the reverse way, so that if I give the 1 0, this and this transistor will turn on. This positive 12 volts, I am giving the positive 12 volts to the positive sign of the motor. Due to that, our motor will always rotate clockwise direction. Okay, similar way, for example, if I give the 0 1 from the microcontroller, this transistor and this transistor will turn on. Due to that, this positive 12 volts I am giving to the negative sign of the DC motor. Due to that, our DC motor will rotate always anti-clockwise direction. Okay, for example, if I give the both are logic 0 from the microcontroller or both are from the logic 1, due to that, my DC motor will be always open circuit. For example, this transistor will turn on, this transistor will be open. If I give the 1 1, this will on, this will open circuit. Okay, there is no closed circuit to the ground. Okay, due to that, this motor rotation always stops. Okay, mainly, for example, if I want to rotate clockwise direction, then we need 1 0, we need to feed from the microcontroller. For example, if I want to do anti-clockwise direction, then we need to give from the microcontroller 0 1. For example, if I want to stop this DC motor 1 1 or 0 0, I need to feed from the microcontroller. These are mainly we need to operate DC motor efficiently in all the direction by using the microcontroller. Only this H bridge is required to operate one DC motor. Okay, for example, we have L293D. It contains two H bridges. Okay, they have designed one IC. It contains two H bridges so that I can operate two motors efficiently in any direction. Okay, here we need to remember all the pins. What is the use of the each and every pin? This is a 16th pin is VSS means 5 volts. Okay, if I want to operate this IC, then we need to give this 5 volts power supply, and VS means this is a power supply for the motor, whatever we discussed here, right? This one we need to give the 12 volts. Okay, here we need to give 12 volts to this eighth pin, so that it will give the power supply to the both the DC motors. Okay, next one, input 1 and input 2 are the to operate. For example, for the motor 1 for the clockwise direction or anti-clockwise direction or stop, we need these two inputs, input 1 and input 2. Output 1, output 2, I need to connect to the first DC motor. Okay, next here, enable pin should be connected to the VCC 5 volts. Okay, otherwise this motor will always stops. Okay, to enable our motor for the rotation, this should be connected to VCC 5 volts. Okay, similar way, this ninth pin also should be connected to VCC to operate motor 2. Okay, we have input 3 and input 4 also we need to connect to the microcontroller to operate DC motor 2. Okay, this motor 2 I am going to connect output 3 and output 4, and mainly by using this input 3 and input 4, I am effectively operating the motor 2. Okay, this 4 5 12 13 I need to connect to the ground. This is a mainly we need to mainly know about this L293D IC. Okay, we have the Proteus. We will design this two DC motor circuitry and also will operate in the both the directions. Okay, for example, here I am taking the L293D IC. We have in our Proteus we have L293D IC, so that I am taking from the library. Okay, if I zoom it here, for example, here as we discussed, 16th pin is VCC means 5 volts. Okay, here we have the generators, go to the DC. Okay, here I can give 5 volts. The other one I need to give the 12 volts. The right one is 12 volts. This is a motor power supply. Okay, here I need to give the 12 volts. Here I need to give the 5 volts. Okay, similar way I am just giving the 5 volts VCC to here. Okay, next here enable 1 and enable 2 I should connect to the VCC. Okay, here enable 1 and enable 2 I should connect to the VCC. Okay, this is the mainly we need to connect. If I want to operate this motor 1 or motor 2, then we need to connect this enable 1 enable to the VCC 5 volts. Okay, this VSS means 5 volts, VS means 12 volts. Okay, next I need to connect on DC two DC motors from the output. Okay, I can type just DC motor. Okay, here I can take the simple DC motor so that I can interface both. If I just click the one more time, I will get one more DC motor. Okay, similar way I'm just connecting to here. Okay, these outputs I need to connect to the motors. Next I need to take the ground. Okay, ground I am taking and I am just connecting to the ground, both the ground pins. Okay, here we have the two inputs, input and input 2 for the motor 1 and input 3 and input 4 for the motor 2. For example, if I want to operate this motor 1 clockwise direction, okay, initially I am just turning on my power supply. Initially both are stop. Okay, here I have not given any of the logics. Okay, logic 1 means 5 volts. For example, I want to operate the motor 1 is clockwise direction. This is input 1 I am connecting to the VCC means 5 volts. VSS means 5 volts. That means logic 1 I am giving to the input 1 and input 2 I am connecting to the ground. Okay, due to this my motor 1 will rotate clockwise direction. If you click on this one, motor 1 will rotate clockwise direction and motor 2 I have not connected to anything, that's why it is still in stop. Okay, similar way I want to rotate motor 2 also. This I need to connect to the VCC. Okay, this is a VCC is going to the VCC means 5 volts. This is a VSS means 5 volts and the input 4 I am connecting to the again ground. Okay, similar way I have connected like input 1 and input 2 so that both motor will rotate clockwise direction. For example, if I want to rotate both the motors anti-clockwise direction so that I can give these two motor pins to the one is to the ground and another is to the VCC in reverse order. Okay, here I want to rotate this motor one anti-clockwise direction. The first input I can give to the ground and the second one I need to give to the 5 volts VCC. Okay, this motor one will rotate anti-clockwise direction. Okay, here 10 means clockwise direction, 01 means anti-clockwise direction. Okay, next stop means 11 or 00. For example, if I am going to connect this one also to the ground, then you will get zeros only. See here, this input 1, input 2, I am just connecting to the ground means stop. If I am going to connect to the VCC also, it will stop. Okay, similar way I'm just connecting to the VCC both the input 1 and input 2. This case also it will stop. Okay, mainly as we understood in the H bridge, if it is 10 clockwise direction, 01 anti-clockwise direction, this is a current flow in 01. Okay, next if I give the 11 means this on, this will off. Due to that open circuit to the motor, there is no rotation. Okay, the similar case here, if the both are 00 means both are 11 means here I connected to the 11 or 00, the motors always stop. Okay, similar way I can design these two motors from the programming. For example, if I want to rotate this both the motors clockwise direction, due to that our robot will always goes to the forward direction. For example, the front wheel is free wheel, this motor is clockwise direction, the second motor also clockwise direction, always my robot will move forward direction. For example, this is also anti-clockwise direction and the second motor also anti-clockwise direction. Due to that our robot will move to the backward direction. Okay, front is the free wheel. Okay, due to this my robot will move to the backward direction. And similar way if I want to rotate for example, if I want to turn right side, okay, this is the clockwise direction. For example, left side. Okay, this is a clockwise direction. This is the anti-clockwise direction. My robot will rotate left side. Why? Because this is a clockwise. This is a anti-clockwise. Okay, again this is a clockwise. This is a anti-clockwise. My robot will rotate right side. Okay, by the use of these two motors, we can treat it as robot. Okay, for example, I want to I want to write one embedded C program. Okay, here we'll discuss about the some little bit small embedded C program. Okay, here hash include raised to 51.h. For example, here I am using port 2. That's why I am included this raised to 51.h. Okay, here while of 1 means always. This is a void main. This is the start of my program. Here while of 1 always I am executing this piece of code. While of 1 means it is an infinite loop. it will execute this piece of code infinite times. Next here, unsigned int of I. Okay, here I'm taking one of the variable to create the delay. Here port 2 equal to 0x05. Okay, here I am just writing this is a 2.0 pin, 2.1, 2.2, 2.3 pin. Okay, these four pins will connect to the microcontroller. Right now I will take the 80C51 microcontroller, 80C51 microcontroller. Okay, this I will import and I will connect to the 2.0. I will connect to the input 1, 2.1 I will connect to the input 2, 2.2 I will connect to the input 3, 2.4 I will connect to the input 4. Okay, here initially, for example, my microcontroller always giving the logic ones. For example, initially there is no program to the microcontroller. Initially, all port pins are logic 1, but in case of port 0, we don't have external pull-ups. Due to that, we should not use the port 0, but port 1, port 2, port 3, we have internal pull-ups, so that it will give the initially logic 1 to the each and every pin. Logic 1 means 5 volts. Okay, due to that, I am giving 1 means both the motor will stop. Okay, initially if I just turn on, both the motors are in stop state. For example, I want to rotate both the motors in a clockwise direction, so that I need to give the from the microcontroller logic 1, logic 0. Okay, similar way I wrote the similar program 1 0, this is for the motor 1, and one more 1 0 for the motor 2. Okay, similar way I'm just giving the 1 0 and 1 0. Okay, this is a LSB 2.0. I am giving, see here, this is a 2.0 pin. Okay, this is a 2.0 pin. I am giving the logic 1, and 2.1 pin I am giving logic 0. This is a 1 0 means the motor 1 clockwise direction, and next motor also, next input also I am giving 1 0, again here 1 0. Okay, the second motor also clockwise direction. Okay, this binary I need to convert to the hex value. That hex value I need to write to the port 2, so that I am going to rotate these two motors in a clockwise direction. Due to that, my robot will move front direction. Okay, here this is a value I am writing to the port 2. Due to this, my robot will move front. Okay, both the motors are clockwise direction. Due to that, my robot will move to the front direction. Okay, here I am giving some delay. For I equal to 0, I is less than 40,000, I plus plus. Okay, first initial I equal to 0, 0 is less than 40,000, 0 plus plus means 1, 1 is less than 40,000. This loop will rotate until 40,000. Due to that, I am generating some delay using the for loop. Okay, next one I'm going to write 0 0 means, as we discussed in the initial H bridge, 0 0 or 1 1 always motor stops. Okay, but here both the motors are stopped. My robot, we need to treat as robot stop. Okay, again I am just giving the some delay. First initially both the motors are clockwise direction. After that I am just stopping my both the motors. Next again both the motors, now I am giving the anti-clockwise directions. Okay, anti-clockwise direction means 0 1 0 1, again 0 1 0 1. Okay, 2.0 is 0 0 1, again 0 1. This is the 2.0, this is a 2.1 pin, 2.2 pin, 2.3 pin. Here I am giving 0 1 0 1 in this case, so that 1010 means I am just converting to the hex value that I am writing to the port 2. Okay, here 1010 means A, 4 zeros means 40. Similar way, I just converted to the hex format. That hex value I am writing to the port 2. Okay, again I am giving some delay. Next here again I am stopping the both the motors. Due to that, our robot will stop. Okay, now I am going to rotate. One is the clockwise direction. The motor one is clockwise direction, and the motor 2 is anti-clockwise direction. Due to that, my robot will move to the left side. Okay, one wheel is clockwise and another is anti-clockwise. Due to that, my robot will move to the left side. Okay, next I am giving some delay, and again I am stopping some delay. Okay, both the motors I am stopping some delay, and after that I am just giving the one is the anti-clockwise direction and another is the clockwise direction. Due to that, our robot will rotate right direction. Okay, after that again I am giving some delay, and here I am just stopping the both the motors with with some delay. Okay, this is the mainly program I wrote. Okay, this program we are going to flash it now. Okay, here I does not have any error, so that I can just I got the executable from the Keil that I am flashing it here. Okay, right now we'll observe whether as per the program my motors are rotating or not. That will just understand one by one. First, it is a both are clockwise direction and it should stop. Both are clockwise direction and it should stop for some time. See, it stopped. Again, anti-clockwise direction, both are, it will stop sometime. Next one is the clockwise direction and another is the anti-clockwise direction. Due to that, my robot will move left side, again stop, again right side. One is the clockwise and another is the anti-clockwise. This is the right side. We are moving the left side. Okay, these are mainly both are clockwise, stop. Both are anti-clockwise, stop. One is clock, another is anti-clockwise, again stop. And other is clock and another is anti-clock, again stop. This is as per the program we are rotating our motors. Okay, if you want, we can give further more delay. Maximum we can give 65, 535. Here I am just giving the 65,000. We will observe a little bit better way. Just I am giving a little more delay so that we can just observe it's in a better way. Here I am just increasing the delay to 65,000. Previously I have given 40,000 only, just I increased to 65,000 so that we can clearly observe what is the robot forward direction. Again I am stopping, again started. Okay, that program will be reflected. See, here both the motors are clockwise direction and here both the motors are stopped. Okay, both are next both are anti-clockwise, again it will stop. Here this means robot is backward direction. Next is the left hand, after some time stopped. One is the clockwise direction and another is the anti-clockwise direction, robot left. Okay, and again I stopped the both the motors. Next, robot right. Okay, one is the clockwise direction, another is the anti-clockwise direction. Finally I will stop. Okay, this program will execute until infinite times. Okay, this while one is a infinite times, this will repeat forever. This is a mainly we need to mainly work with the DC motors. Mainly we need L293D IC to operate two DC motors. Mainly if I want to operate one DC motor also, we need this L293D IC. Okay, this is a mainly intermediate IC between the 8051 microcontroller with the DC motor. Okay, mainly this 16 pin is a 5 volts. This 8 pin is a 12 volts power supply to the motors. Okay, this input 1, input 2, we can try to operate this motor 1 effectively, either in case of clockwise direction or anti-clockwise or stop. Okay, 1 0 means clockwise, 0 1 means anti-clockwise. Okay, similar way the second motor also 1 1 or 0 0, both are stop. Okay, this enable pin should be connected to VCC. This input 1, input 2, we need to connect to the microcontroller. Similar way, input 3 and input 4, we need to connect to the microcontroller. All the ground should be connected to the ground. Okay, this is a mainly L293D IC. We are going to interface two motors effectively, and mainly in our robotic cases, we used to have this L293D IC. Okay, thanks about on 230 volts bulb interfacing with 8051 microcontroller. Okay, this is our home appliances bulb. Okay, it is operating with 230 volts AC power supply. And how we are going to turn on or turn off this bulb by using this 8051 microcontroller, that we are going to discuss mainly on today. And here 12 volts DC relay control from the 8051 microcontroller. Mainly we are controlling this relay, and due to that we are going to turn on or turn on off the this particular 230 volts bulb by using this mainly relay. And relay has 5 pins. This is a normally closed pin, normally open pin, and this is a common pin. This is the middle one is a common. These two ends we have the inside we have the coil. Okay, this is the mainly relay. We have the 5 pins, and here we can see these 5 pins here. This is a coil 1, coil 2, 2 pins, and this is a normally open, this is a normally closed, this is a common pin. And this is the way we need to connect our power supply to the bulb. Okay, see here initially I am going to connect to the normally closed. See, whenever this switch is switched from the normally closed to normally open, then only I am going to turn on the lamp. And otherwise, for example, initially there is no power supply across this bulb. Initially it is open circuit. Whenever the relay is turned on, then only I am going to
give the 230 volts to this bulb. Okay, here we have the some relay circuitry and how we are going to operate from the microcontroller, that we will discuss now. Okay, here from the microcontroller I'm giving the logic 1 means 5 volts to this transistor. Due to that it will turn on. Whenever it is turned on, I am giving the 12 volts to this coil. Okay, due to that it will generate some magnetic field. Due to that it will attract the contact from the normally closed to normally open. Okay, this contact will switch from the normally closed to normally open. Due to that our I'm going to give the 230 volts to this bulb, it will turn on. Okay, whenever I'm going to send the logic 0, that means 0 volts to this transistor, this will open circuit. Okay, there is no 12 volts across this relay. Okay, it will be there is no magnetic field across this coil, and due to that it will be this contact will switch from the normally open to normally close. Okay, again it will go back to the initial position, and there won't be any 230 volts to this bulb. Due to that it will turn off. Mainly whenever this logic 1, my bulb will turn on. Whenever the logic 0, this bulb will turn off. And this is the mainly use of this diode. Whenever this back EMF it is going to give to the ground, this is the mainly use of this diode. Okay, mainly whenever this logic 1 I'm going to turn on, and whenever the logic 0 I'm going to turn off the bulb. This is the mainly operating of this circuitry. And similar way we will design our circuitry in our Proteus. I will take the relay from the library first component, relay. And the same relay we have the two this is a coil 1 and coil 2, and normally closed, normally open, and this is a common pin. Okay, here in our Proteus we have the 230 bulb, 230 volts bulb we don't have. We have only 12 volts DC power supply bulb. Okay, just I can type the bulb, so that we'll get the 12 volts DC bulb. Okay, here we have the 12 volts DC bulb. Okay, instead of the 230 volts I am just giving the 12 volts here. In our normal in our real time hardware you can give the 230 volts here. Just I am giving the 12 volts here, but we should give the 230 volts in our real time hardware. If you buy any relay circuitry, here we should give the 230 volts, but right now I am giving the 12 volts DC power supply. Here we need to give the 12 volts AC power supply, but in case of Proteus I am showing with the example of 12 volts DC power supply. We should give real time in a 230 volts AC here. Just I am giving the 12 volts DC for our testing purpose. Okay, here I am just connecting to the ground, the other end. See, whenever this relay is operated, I'm going to give the 12 volts to this 12 volts lamp. Then only it will turn on. Whenever this switch is moved from the normally closed to normally open, my bulb will turn on. Okay, how we are going to operate this relay? And now we are going to design our circuitry, complete circuitry. We have NPN transistor, and also we need one diode. We have one NPN transistor. This I am going to connect to this coil one end, and other end I am going to connect to the ground, and the other end I need to connect to the resistor. From that we need to connect to the microcontroller. Okay, this is a resistor I am going to connect to the transistor. From here I can connect to the microcontroller. Okay, here I need only 1K as we discussed in initial PPT. Here we have 1K and one diode, and also we need one diode, and after that we need 12 volts DC power supply. Okay, here we can just type the 4007 is my one of the diode, so that I can take this one. Okay, here I can just do anti-clockwise direction. This I can connect to the coil for the grounding of the back EMF. And here I have already 12 volts, I can connect here. Usually here the 12 volts DC relay, that's why I'm giving the 12 volts DC here. Already we have 12 volts DC. Okay, right now I am operating this bulb with 12 volts DC. In our real time, if you buy any hardware, we need to give 230 volts here. These are 12 volts DC as usual. Okay, and here I am going to connect to our microcontroller. Finally I need to take 80C51 microcontroller. Okay, this I am going to interface to this particular pin of the microcontroller. Okay, here initially my port pin with the logic 1. Okay, in logic 1 means 5 volts. Initially all the port pins having the logic 1. Why? Because we have the internal pull-ups to the port 1, 2, 3, but we don't have internal pull-ups to the port 0. If I want to use the port 0 in each and every pin, we need to connect external pull-up, and after that we need to use that particular pins. Okay, right now we have the internal pull-ups, it will give the initially with logic 1, that means 5 volts to this transistor. Due to that it will switch from the normally closed to normally open. Due to that my bulb should on. Okay, initially without any program I am going to run my microcontroller. Okay, initially it should turn on. See here, my switch is moved from the normally closed to normally open. Due to that, my bulb will turn on. Okay, this is a normally when by using the microcontroller, we are going to turn on the 230 volts bulb. But here I am just giving the 12 volts DC. But instead of this one, we should give the 230 volts AC in our real-time hardware. Here we don't have 230 volts bulb. That's why I have given this example. And similar way we'll write one simple program. Okay, how we operated one of the LED, right, in the previous sessions. I'm going to operate this bulb by using this switch. Whenever the switch is pressed, I'm going to turn on the this bulb. Okay, here whenever this switch is pressed, I'm going to turn on the this bulb. I'm going to write a simple program. Okay, so that whenever this switch is pressed, I'm going to turn on this bulb. Okay, here I'm going to write one simple program. Here we have mainly we are using only two pins from the microcontroller. That's why here this port 2 is one special function register and port 3 also one of the special function register. Within the special function register I'm going to access only one pin. That's why I'm using this data type as bit. Here switch I am going to connect to the 3.0 equal to port 3 cap of 0. Okay, here 3 cap of 0 I'm going to connect the switch, and similar way as bit relay. Relay I'm going to connect port 2 cap of 0. Okay, 2.0 I'm just connected the relay and the port 3.0 switch. Okay, whenever the always my execution start from the main, while of 1 means always it will execute infinite times. Okay, if switch is pressed, whenever for example if I just press the switch, I will get the logic 0 to the this particular pin. Okay, similar way I'm just writing the program. Whenever this is logic 0, switch is logic 0, I'm just checking whether this port 3.0 is 0 or not. Okay, if it is 0, I'm going to turn on the relay. Okay, relay equal to 1, and we need semicolon here. And the else part, what I am doing for the else, if the switch is not pressed, I am going to the else part. Okay, here I am going to turn off the relay. Okay, here whenever the relay is off, whenever I'm just sending the relay to the 0, my bulb will turn off. Okay, this is a comment I can write, bulb off. Here the bulb is on. Okay, here this is a simple program we wrote, and we are going to generate the executables now. Okay, there is no errors. It the executable was generated at 9:13. Okay, here just similar way I can double click. I can select my program which we generated now. Okay, that I am going to select my program here. 9:13 is the correct time the executable was generated. Okay, here whenever my switch is pressed, okay, initially I am just going to open my switch. It should turn off the this bulb. Okay, whenever my switch is pressed, I'm going to send logic 1 across this transistor. Right now blue means logic 0 I'm sending. Right now we are in else condition. Okay, right now the switch is not pressed, I will go to the else condition. I'm sending logic 0 to the transistor. Okay, whenever the switch is pressed, I'm going to send logic 1 to this transistor. Okay, similar, whenever switch is pressed, I'm going to send logic 1 to this one. The 12 volts goes to this relay, and finally it will switch from normally closed to normally open. Okay, due to that my this 12 volts pass to this bulb and it will turn on. Okay, normally we should connect 230 volts here. Just for example I have connected like this, and this is a mainly circuitry we have designed. For example, if you want to operate in a reverse order, so that I can change the logics here. For example, whenever the switch is pressed, I want to turn off the bulb. Okay, so if I want to operate in a reverse order, so that we can do this as well. For example, whenever the switch is pressed, I am going to turn off the bulb. Okay, this is a reverse order. Okay, similar way I am just going to flash the same executable. Whenever the switch is pressed, I am going to turn off. Open, I need to turn on. This is a reverse way I need to operate. See here, whenever it is open, my bulb is on. Whenever it is closed, my bulb is off. Okay, this is if I want to operate in a reverse order, so that we can operate. And also we can also change the relay connection from the this normally power supply connection from the normally open to normally closed also we can change. We can also operate in a reverse order by using the hardware. Okay, either we can change the hardware configuration or the software configuration. Anyway, we need to finally achieve the based on our requirement, whether I need to based on whenever the switch is pressed I want to turn on, or whenever the switch is open I want to turn on, based on our requirement. Okay, thank you friends, thank
We are mainly discussing about an LCD interfacing with 8051 microcontroller. Mainly we are using 16 into 2 LCD. How we are going to interface with the 8051 microcontroller, how we are going to program using this 16 into 2 LCD, and also how to write the data to the LCD, and also how to write the command to the LCD, that we are going to discuss mainly on today. And here we have the 16 into 2 LCD, that means 16 columns and 2 rows. Mainly we are going to display each row 16 characters, totally 32 characters we can display. For example, if I want to display more than 32 characters, we need to clear the complete data, and we can display other information. Okay, mainly by the use of commands, we can control the LCD. By the use of the alphanumerical data, we are going to display on to this LCD. Okay, here we'll discuss each and every pin one by one. Here we have the 16 pins of this LCD. First one is the ground. We need to connect this pin to the ground. The second one is VCC, 5 volts DC supply we need to give to the this LCD. To mainly working of this LCD we need plus 5 volts DC. Okay, next one V is the contrast. Okay, we are going to connect one external potentiometer to adjust the resistance of this voltage across this VE pin. Directly we are going to change the contrast of the LCD. Okay, here we are connecting one external potentiometer to the VCC. We are adjusting the resistance. Due to that, we are changing the voltage across this VE pin. Directly we are adjusting the this contrast across this LCD. Okay, next pin is the RS. Okay, here it will differentiate whether I am going to write the uh, data or command to the LCD. Mainly this RS pin will decide. For example, RS is 1 means we are going to write the data. If RS equal to 0 means we are going to write the command to the LCD. Okay, RS it is only the differentiating between the data and command. Okay, next one is read or write. Okay, read or write bar mainly. Okay, if I connect to the ground, always I am going to write the data to the LCD, either command or the data. That's why here this pin always I am connecting to the ground. There is no need to connect to the microcontroller. Mainly this RS pin, enable pin, we need to connect to the microcontroller, and 8 data pins. Okay, here the enable pin, whenever the high to low transition, then only I am going to write to the LCD. Okay, I will tell you the one use case how we are going to write the data first. Okay, first if I want to write to the data first I will make the this RS pin to logic 1 means 5 volts, and read write anyway connect to the ground. Next I will place the data across this 8 bits. Okay, db1 db0 to db7 I am going to place the one ASCII character here. Okay, after that I will write the enable pin 1 to 0 transition. Whenever the logic 1 to 0 transition, I am going to write the whatever the placed data to the LCD. Okay, similar way if I want to write the command to the LCD, first I need to make the RS to 0. Anyway, read write is connected to the ground, and command also I am going to write. Next, I will place the command across this 8-bit data lines, parallel data lines, and after that I will give the high to low transition across this enable. Whatever the placed command will be written to the LCD. This is the mainly how we are going to write the data or to the command to the LCD mainly. Okay, next here LED plus and LED minus. Here we have the backlight across this LCD. Okay, if I want to glow the backlight, mainly this we need to give the 5 volts DC power supply. This one we need to connect to the ground. Okay, this is the mainly working of the all the pins of LCD 16 into 2 LCD. Okay, here we will learn more about the commands of the LCD 16 into 2. Okay, for example, here the 0x01 means we can clear the display. As we discussed initially, for example, more than 32 characters if I want to display, I need to clear the complete LCD, so that we need to pass this command to the LCD so that I can clear all the data within this LCD. Okay, next one, 0x02 return to home. If I want to move the cursor to the home, so that I can use this 0x02. Next, 0x06 means for entry mode. For example, if I want to enter any data, so that I can use this 0x06. Okay, next one, 0x80 for cursor to beginning of the first line. Okay, here the 80 C0 are the important. These are the addresses. Okay, mainly. Okay, 0x C0 means force cursor to the beginning of the second line. Okay, here the 80 is the first location and the C0 is the second location. For example, if I want to display the data from the 85 onwards, so that from the sixth column onwards, so that I can give the 85. Similarly, if I want to display the second row from the C5 onwards, I can give the C5 address. Here the 80 means beginning of the first line. Okay, C0 means beginning of the second line. For example, if I give the CF means last, I'm going to give the address to the last location. Okay, here if I give the command 85 means I'm going to give the address of this location. After that, if I am going to write the data to the LCD, that I am going to display from here onwards. Okay, here these two we need to remember always. 80C0, these are the mainly address of the LCD. This complete 16 columns we need to represent with C0 and 80. And here 0x80 display of cursor off. Okay, here if I give this 0x08, I am going to display off the complete LCD. Next, 0x0e display on cursor on. Here cursor also will on. Okay, additionally, okay, 0x0c display on cursor off. 0x0f display on cursor blinking. Okay, it will blink the cursor additionally. And 0x10 means shift the cursor position to the left, and 0x14 shift the cursor position to the right. Next, 0x38 and 0x28, these two are mainly important. And 0x38, two lines 5 into 7 matrix 8-bit mode. For example, if I want to operate 8 data lines, so that I can use the 0x38 command, so that I can use the 8-bit operating mode. For example, if I am writing the command 0x28, two lines 5 into 7 matrix 4-bit mode. Okay, only I am going to use the higher this data lines, and remaining data lines are not used. Only I need to connect these 4 bits to the microcontroller and RS and enable. These 6 pins are enough in case of 4-bit mode. In case of 8-bit mode, we need to connect all the 8 data lines plus RS plus enable pin. These many pins we need to connect to the microcontroller in case of 8-bit. Okay, mainly today we are going to discuss mainly 0x38, mainly 8-bit mode we are going to use, and how to write the command, and also how to write the data that we are going to discuss in coding, one step by step. And here we'll discuss how to initialize the LCD, what and all the initial commands are required. Okay, 0x38 means already we discussed. If I want to operate my LCD with 8-bit mode, I need to write this command to the LCD 16 into 2. Okay, next one, if I want to display on and cursor off, so that I need to write 0x0c. Okay, for example, if I want to write any data to the LCD, if I we need to turn on the LCD. Okay, we need to display on the LCD, then only I can able to write. Okay, this is the mainly importance of the 0x0c. 0x01 means I can just clear the complete already displayed data, I can clear with 0x01. 0x80 means this is the first beginning of the first row. Okay, address of the first row. For example, if I give the 81, that I am going to display from here onwards, I am specifying the address of the LCD. Okay, here these four commands are required to initialize our LCD. From here onwards, I can use the 0x01 for the clear. If I want to display new data, for example, for the first row I can use this one, for the second row I can use this one. Okay, mainly these commands are enough to use of this complete this 16 into 2 LCD. And right now here this is the initial circuitry of 8051 microcontroller. This is a power supply circuitry, and this is a reset circuitry. This is the crystal oscillator circuitry. Right now I am going to import LCD to this complete circuitry. Just I am going to type the LCD here. I will get the 16 into 2 alphanumerical LCD. Okay, mainly we can display all the alphanumerical characters, all the ASCII characters we can display in this LCD. Okay, here I am going to interface this complete 16 into 2 LCD to here. Okay, here this 3.0 I will connect to the D0, 3.1 I will connect to the D1, next to 3.2 I will connect to the D2. Okay, here these 8 pins I am using for the LCD data. We have the 8-bit mode I am using. That's why I am connecting 8 lines of the microcontrollers. Okay, here if I want to write any data or command, mainly we need to place the data across this port that will be returned to the LCD mainly. Okay, this is a mainly use of. This is a VSS as we discussed. This is a ground pin. Okay, here I have already the ground I have connected. This is the VDD, means 5 volts DC power supply. That's why we already designed the power supply circuit. Here 7805 it will give the 5 volts DC power supply. Okay, here the contrast initially, if I am not giving the any potentiometer to the VCC, initially here the Proteus always it will provide the initial contrast. Okay, that we are going to use here, not connected. And here the RS pin I am connecting to the 2.0, and the enable pin I am connecting to the 2.1. Okay, here 2.0 and 2.1, this is a RS pin, enable pin. Mainly these 8 pins and 2 pins. In case of 8-bit mode, these 10 pins are enough. This read write bar I will connect to the ground. Okay, here already I have connected to the ground this one. That's why I will connect to here. Read write bar I am connecting to the ground, means always I am writing the data to the LCD, data or command to the LCD. That's why this read and write bar I connected to the ground. Always I am writing. This RS pin, if I okay will write the program, how I am going to write the data or how I am going to write the command to the LCD, that will write in a program. Okay, mainly we need some delay. For example, okay, first we need some delay in this program. That's why I will write some delay function here. Delay unsigned int. I will tell you what is the use of the delay also here in this case. Here I am using the declaration of the function. Here I am defining my program with some delay. Here I will write some unsigned unsigned int j. Okay, here I will write some for loop. By using the for loop, we are generating few delay. J equal to 0, j is less than, here I, j plus plus, j plus plus, here I am giving the semicolon. Okay, here if I pass some delay from the main function, okay, this function will be executing. Here I am using some argument. Okay, here I can pass the 100, so that this for loop will repeat until 100 loop, so that I am waiting some 100 microseconds here. Due to that, we are generating some 100 microseconds delay. Okay, here I written the delay program. Why? What is the use of this delay program? Mainly, if I want to write the this enable pin high to low transition, we need, right? For example, we need some high to low transition with some delay. That's why we need to give some pulse, high to low pulse. That's why I'm giving this delay, mainly use of this delay function. Next, I will write LCD command. How we are going to write LCD, one command to the LCD, that we are going to write now. LCD underscore CMD. Okay, this is my LCD command function. Here I need to pass the command as the argument unsigned int. Here I can take the character also fine within the 0 to FF, so that I can give the unsigned char of A as the argument I am giving. Okay, here I am passing the one of the argument in this API function. Okay, here I am going to write the definition of the function here. Okay, here first point we need to define all the pins. Okay, here mainly we are using 8 pins, complete this port 3 and 2.0 and 2.1. 2.0 is RS, register selection bit RS equal to port 2 cap of 0, and S bit. Okay, if I want to define any special function register within a, if I want to access only particular pin, so that I can use the S bit data type. Enable pin I have connected to the port 2 cap of 1. Okay, this is the two pins we are using, and the complete port 3 we are using it. I can use the SFR data type for the complete data uh, port 3. Here I can mention the L data, LCD data equal to 0x B0 is the address of the port 3. Okay, here L data nothing but port 3. Okay, here if I want to write command to the LCD, first this RS pin I need to make it as 0. Okay, that means whatever the data I am writing, that will treat as command. Okay, next one I need to place the data, L data equal to A. Okay, whatever we are passing the argument, that I am placing complete at the port 3, and that data if I want to write to the LCD, that enable pin should be 1 to 0 transition. Okay, here enable I am just making to 0 with some delay. Okay, here mainly we are using some delay here. Okay, why? Because I'm giving the some high to low pulse. That's why for the high logic high, we need some delay. That's why I'm just giving the some 5 delay 5. This 5 milliseconds, 5 microseconds I'm giving delay for high to low transition. Okay, this is a mainly function for the command writing. Okay, similar way I'm going to write the program for the data writing. Okay, only the difference, this RS1 I need to make it as 1. This I will treat as data. Okay, what I am going to write this function, this is the data. Okay, this is the argument, I can change it as B. Okay, this function I will define here. Okay, we need always definition and also declaration. Here I am giving the declaration here. Okay, I have declared and also defined the LCD data function. Okay, next function is the LCD init function. Okay, as we discussed initially, if I want to initialize the LCD, we need these many commands we need to pass to the this LCD. Okay, here I am going to write LCD init program. Okay, void LCD. Okay, this is a void function, init function. Okay, here I am going to write the void as well. There is no need of argument. Okay, here I am going to write my the same definition here. Void LCD underscore command LCD init. Okay, init function I am writing. This is the definition I am writing here. Okay, here I will pass anyway I have the command LCD command of 0x38. For example, if I want to use the this 8-bit mode, so that I can just pass the 0x38. If I want to use the 4-bit mode, only 0x28 we need to pass. Next, LCD command. Next, what is the command here? 0x0c means display on. If I want to turn on the LCD display, then only I can display something onto the LCD, otherwise we cannot display. I need to turn on the display. Next one is the LCD command 01. This is a 01 means I want to clear the previous already displayed data. Okay, next one is the 80 is the first line, the first line address. Okay, if I just see the 80, force cursor to the beginning of the first line. Okay, it will go to the beginning of the first line. Okay, next I am going to write one more function, so that I will display the complete string. Okay, for example, I am going to write and I will explain clearly. Okay, void LCD. Okay, some string program I am going to write. Here I will take the argument as pointer unsigned. Here I will take the character star str. Okay, here I'm just giving the pointer as the argument. Okay, here I'm going to write the definition at the end. Okay, here this is the definition of my program. Okay, here mainly here I am checking whether it is my character is null or not. until null character I am going to repeat this loop. That's why I am going to write the loop here. And here I am going to just pass the each and every character to the LCD data. Okay, anyway I have the data here. This is the data. If I want to pass the each and every character to this LCD, okay, this is the LCD data. Here I can pass each and every character to the LCD so that I can write star string plus plus. Okay, this is the mainly semicolon. Okay, if you want to write the open and close braces, even we can also write the open and close braces. Anyway, we have the only single statement. Okay, here I will explain the statements one by one. First, always execution will start from the LCD init. Okay, here I am going to just initialize my LCD. Before I want to display any data onto the LCD, first we need to initialize. Okay, first always execution starts from A. I am just calling the LCD init function. I will come to here. I am just passing the LCD command. Here LCD command is the function. Here I will write LCD command. This is also LCD command, LCD data. Okay, here some mistakes are there. Here similar way I will write LCD command, LCD command. Here also LCD command. Just I am just changing the name. LCD command, LCD data. Okay, here it's fine. Okay, here I am just passing the LCD command of 0x38. That means it will treat as it is 8-bit mode. And after that I am passing the LCD command of 0x0c. I am just passing to here, but as the argument. First we'll discuss from here onwards. Just I am passing LCD command of 0x38. I am just passing here this 38, 0x38. Just I am making a rx equal to 0. That means the LCD will treat as whatever I am passing the data as this command. And that 38 I am placing at the port 3. And after that I am just giving the enable pin, this port 2.1 pin I am giving high to low transition. This 2.1 pin I am giving the high to low transition. That means we are going to write the whatever the command to that LCD. This 38 I am going to write to the LCD. Similar way 0x03 also I am going to write to the LCD. 0x01 also I am going to write to the LCD. 0x80 also I am going to write to the LCD. Next, I already defined the first line, beginning of the first line, so that I can display the data here. LCD str. Directly I am just passing the string here. Okay, here I will give some three spaces. Welcome to. Okay, here in each row we can display up to 16 characters. For example, here 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. Okay, totally 16 characters. This means first row I am displaying this welcome to. Here I am giving the 0x80 welcome to I am displaying. Okay, here I am just passing the complete string to the LCD string function. Okay, here complete string I am taking it here. Here while of, here I'm just checking the null. Okay, usually in our C language at the end they are going to pad the null here. Okay, null character. Okay, at the end they are padding the null. Okay, until null I'm going to repeat this while loop. Okay, first I'm going to pass the space. Okay, this all the space I will pass, and after that W character. Okay, while of W is not a null. Okay, I'm going to pass to the this LCD data. This W character I'm passing it here. Okay, this rs1 whatever this w is the data, and whatever the w character I'm placing at the port 3, then I'm just giving the enable 120. This w will be written to the this LCD that we are going to display w onto the LCD. Okay, similar way the next character I'm going to increment the pointer here. Okay, next w, next one is e is not a null. Again I am passing it here, and similar way I am going to write the e to the LCD, and similar way each and every character I am passing to the LCD data. Okay, that's why this function it will pass each and every character to this LCD data, and it will display one by one character. Finally will display all the characters across this LCD. Okay, next if I want to display second row, I need to give the this second command. 0xc0 is the second line. For example, if I want to write the data onto the second row, so that I can give the C0 address. Okay, I will write the another string here. Okay, similar way I will write welcome to project, welcome to my project. I will write the second row like this, and each row we are displaying totally 16 characters. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. Okay, totally 16 characters I am displaying in second row. Also we need semicolon each and every statement. Okay, right now we'll compile and we'll see whether we are displaying this complete welcome to project onto the screen or not. This while of one means always I'm stopping my program after displaying this content. I'm just stopping my program. Okay, here I'm just building. Okay, here I am getting some one of the compilation error. We'll see. Okay, here argument I'm using b, that's why here I need to change it as b. Okay, and similar way here I does not have any errors. I will just compile. I will get the executable. Okay, that executable I am going to flash it now. Here we seen already all the interfaces here. Okay, here 2.0 RS pin and 2.1 is enable pin, remaining data pins. Okay, here I am going to write select the same program. Here if you see 8 o'clock 26 is the same executable what we generated now, that I am selecting now. I'm going to run the program. Okay, whether we'll see whether we are displaying this welcome to project or not. See here welcome to project. Okay, here first what we did, initially we initialized the LCD. After that we specified 0x80, the first row. I'm just displaying welcome to. If you see welcome to the second row, my project, C0 means second row. For example, if I want to display from C5 onwards, for example I am going to write some ABC here, ABCD. Okay, let's see. If I want to display this ABC from the C4, I'm just giving the C4 address. Okay, just I stopped my execution and also again started. See here, I'm going to display from here. Some of the data was missed. Okay, due to this address, we have the only the 16 locations. If you see here, 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16, totally we are going to display until here. Okay, here from C4 onwards I am displaying. This is a C4, C5, C6, C7, C8, C9, CA, CB, CC, CD, CE, CF. Okay, we are going to display until J. See here similar way. Why? Because here I am just displaying from here onwards, C4 onwards. Okay, here I can give the whatever the address we want to display, from that onwards we can display. But usually I am just giving the this C0 means from the second row beginning of the second row. Okay, this is the address we can specify. For example, if I want to clear the data, I'm going to display another text, so that we can display another text as well. I'm going to clear the complete data, and after that if I am just displaying the data, other data. Okay, here I need to give the 80 again. Why? Because the second data I'm going to display here. Here we'll display our channel content here, YT training. Here I will just write the institute. Why? Because in single row we can write up to only 16 characters. Okay, here I'm just going to write the YT training institute. Okay, here what I'm just doing, first I'm going to display welcome to on the first row. Why? Because already I have given this 80 address. I'm going to display welcome to. After that second row I'm displaying my project, and after that I'm just clearing the display. Here I will give some delay here, otherwise we cannot observe whether it is displayed or cleared. Okay, here I will give the delay function here. Okay, this much delay I'm going to display these many characters, welcome to project. And here I'm giving some 65,000 for loop. Here I'm just calling the delay. Here we have the delay function. I'm just passing as a 65,000. Here I'm just accepting that 65,000 here, j equal to 0, j is less than 0 is less than 65,000. And here always semicolon. I will be waiting here only until the this condition is false. Okay, again 1 plus 65,000, 2 plus 65,000, until 65,000 I am waiting here. Until this much time I'm going to display welcome to my project, and after that I'm going to clear the LCD. Okay, this clearing we should do after the delay. And after that the second row 80 YT training I am displaying, and the C0 second row I am displaying institute. Okay, I'm just saved my program, I just generated my executable. Here we'll see some delay. Okay, here some delay, we just return incorrectly. Similar I will just execute. Yeah, we got the executable. And that executable, if I want to just replace, just I need to stop the execution. Anyway the executable is same. Okay, that's why I just replay. The all the changes should be reflected here. See, welcome to my project, and after that YT training institute. Okay, similar way it will display. See, again I stopped again and started welcome to my project YT training institute. Okay, this is the way we are going to display our onto the LCD efficiently and effectively. Okay, first here always execution start from the main. We are going to initialize the LCD. We need to pass these many commands. 0x38 means I am going to operate the LCD with 8-bit mode, and 0x0c means here completely 0x03 means display on and cursor off. And the second one is clear. If I want to clear the LCD, I need to pass the 0x01. If I want to display at the first row of the beginning of the first line, so that I can pass the 80, and the initialization is done. Okay, and after that LCD string I am passing welcome to. Okay, each and every character I am passing from here to here LCD data. Okay, this will pass the data to the LCD. Initially I will display W, and after that ELCOME, one by one it will display. Why? Because our microcontroller execution within the microseconds, that's why we will display as soon as faster. Okay, here I'm just displaying all the welcome to my project, and after that I'm giving the C0 address. My project I'm displaying a similar way. I'm just passing the each and every character to the LCD data that I am going to display onto the LCD. And after that this much delay I'm waiting, and after that I'm just giving the 0x01 means I will clear the complete data. Okay, for example, if I am not clearing that data, for example the first row and second row I am just passing. For example, second row only I am displaying the data. Okay, let's see whether this data will be retained. For example, the first row welcome to my project, the second row is my project, and after some delay, right, the project we will replace with institute. The welcome will be retained. If I am not clearing the LCD previous data, the old data will be retained. We'll see now. Okay, here first we'll display welcome to my project. My project will be erased and it will display the institute. Okay, here here I am not clearing the data. For example, if I am clearing my old data, that welcome also will be cleared. If you just see my output again, this welcome to is there. Again, if I stop here, I enable my clear command. Now what it will display, welcome to my project it will display, and after some time it will be cleared, and only it will display institute now. Okay, this is the mainly usage of the LCD. We need to see here. I'm going to display welcome to my project, and after that I will clear complete data, and I'm going to display only institute. Here it see it's displaying first location to the first row. Okay, here the C0 we have given, and I have cleared the data. LCD command C0. Okay, here I will give the 80. I think the changes are not reflected. Okay, similar way I will just write the 80 and C0 here. Okay, we will display both the rows the same data. Okay, here welcome to my project. After that we have cleared the complete data, and again YT training institute. Okay, this is the way we need to write to the LCD. Okay, this is the mainly working of the LCD we discussed I think from the start, and how to define the pins and how to write the any functions easily from the start. Okay, today we written the program practically, and also we are going to display the data on practical way. Okay, thank you. We are mainly discussing about on keypad interfacing with 8051 microcontroller. How we are going to interface this keypad with the 8051 microcontroller, and also how we are going to detect particular key whether it is pressed or not. If it is pressed, that particular key we need to display onto the LCD. This LCD interfacing already we discussed in the previous session. today we are mainly discussing about on this keypad interfacing. Okay, here we'll discuss the basic concept, how we are going to detect the particular column, how we are going to detect the particular row. For example, initially I don't know what the key pressed or not. That's why whenever the particular key is pressed, I want to detect the particular column. Due to that, I am going to initialize the all the columns with the logic 1, all the rows with the logic 0. Okay, for example, whenever the user pressed any key, for example, let us assume this switch is pressed. Okay, due to that logic 0 across the row 2, due to the short circuit, column 2 also will become a logic 0. Okay, due to that, I am able to find the column 2 is pressed. Okay, similar way, if I want to find out the row, particular row, all the rows I am just initializing with all the ones, logic ones, and all the columns I am initializing with logic 0. See, whenever the switch is pressed, this due to the column to logic 0, whenever the short circuit, row 2 also becoming a 0. Okay, due to that I am going to find out, okay, row 2 is pressed. Okay, if you know the column, particular column, if you know the particular row, then we'll be able to identify the what exactly which switch is pressed. Okay, then due to that we are going to detect and we will display particular digit onto the LCD. Okay, this is a basic concept. Okay, for example, if I want to find out the particular column, first we need to initialize the all the columns with 1 and rows with 0. Whenever the any user press the particular switch, due to the short circuit of the this row 1 column, this row 2 across the already initially that row 2 across the logic 0, due to that short circuit, column 2 also will be becoming a logic 0. Okay, due to that we are able to identify, okay, column 2 is pressed. Okay, similar way we'll be able to identify the row 2 as well. Okay, if you understand the basic concept, then we'll be able to write the program very easy way. Okay, here I have the initial circuitry in the previous session. Here we have the LCD, already we interfaced in the previous session, and here the power supply circuitry, reset circuitry, here the crystal oscillator circuitry. Okay, here clock circuitry. Here mainly we are going to interface 4 into 3 keypad. Okay, from the library. Here we will just browse the keypad. Here we have so many keypads. We'll take the phone keypad. We have the 4 rows and 3 columns. Okay, here this I am going to interface with the 805 microcontroller. Okay, here we have the 7 rows here. Okay, 4 rows and 3 columns. Totally we have the 7 pins. Okay, here 1.0 I am going to connect to the row 1. 1.1 I am connecting to the row 2. Okay, similar way, row 3 I am going to connect to the 1.2. Similar way, row 3 I am going to row 4 I am going to connect to the 1.3. Row 4. Next, column 1 I am going to connect to the 1.4 pin. Next, to column 2 I am going to connect to the 1.5 pin. Column 3 I am going to connect to the 1.6 pin. Okay, similar way we need to define in our program as well. Here, whenever the switch is pressed, I want to display that particular digit onto the LCD. This program I am going to write now. Okay, initially this program already we written LCD interfacing. Welcome to my project YT Training Institute. This we written in the previous session. Similar program I have here, and right now we are going to extend this program with the keypad. Okay, first we need to define all the pins as bit. Here the row 1 equal to port 1 cap of 0. Okay, 1 cap of 0 I connected the row 1, and as bit similar I will expand for the row 2, row 3, row 4. Row 2, row 3, row 4. Here I will just rename with row 2, row 3, row 4. Here the 1.0, 1.1 pin I connected to the row 2, 1.2 pin I connected to the row 3, 1.3 pin I connected to the row 4. Okay, similar way, column 1, column 2, column 3 I need to define. Okay, here the column 1 I will just treat as column 1, column 2, column 3. Okay, here the column 1 is connected to 1.4, column 2 is connected to 1.5, 1.6.
Okay, similar way, how we connected in the hardware, similar way I have defined here all the pins. Okay, here the initial concept will understand. Before that, this I will clear. Okay, after the YT training institute, I will clear. I don't know when I need to press the particular switch, so that I am going to display some text here. Press any key. I will just write the press any key in the first row. 80 means first row. Press any key. Okay, here if I press any key, it will be displayed in the second row. I'm going to display all the digits in the second row. That's why I'm going to give the C0 address for the second row. Okay, from here I'm going to write the keypad programming in while of 1. That means I need to check always whether the particular column is pressed or not, or particular row is pressed or not. Always I need to check. That's why I'm going to write the program in the while of 1. Always true. I'm going to execute this piece of code always. Okay, infinite times. Okay, here initially whatever we discussed, if I want to find out the particular column, first we need to initialize all the columns with 1 and rows with 0. Okay, similar way I'm doing it here. We have the three columns, column 1, column 2, column 3. I'm going to initialize with 1. All the rows I'm initializing with 0. Row 0, row 1, row 2, row 3, and okay, here from row 1 we have we don't have row 0. Row 1, row 2, row 3, row 4 equal to 1. Okay, here we need to initialize with 0. Okay, initially we discussed in the concept, if I want to find out the particular column, we need to initialize all the columns with 1 and rows with 0. And whenever that particular switch is pressed, for example, let us assume one first row and first column, this digit 1 is pressed. Okay, first row and first column, so that I need to display here. I will check whether the first column is pressed or not. C1 double equal to 0. That means here I am just checking whether the C1 is pressed. Okay, if the C1 is pressed, I am going to get the logic 0 due to the here the column initially column 1 is 1. Whenever the switch is pressed, due to the row 1 is 0, due to that column 1 also will be 0. Okay, similar way I am going to extend for the rows. Here initially I checked whether it is C1 is pressed or not. Okay, if the C1 is pressed, I need to check the row now. Okay, for the second this one, I need to check the row whether which row is pressed, so that I need to initialize all the columns with 0, rows with 1. Okay, here similar way I will just extend a row with 1, all the row with 1, and all the columns with 0. Okay, just I extended the similar concept here, and here I will check whether the if row 1 is pressed, double equal to 0. Here I will check if the row 1 is pressed. Row 1 is pressed. Okay, what I need to display here, if the row 1 is pressed, just I will write LCD data. I am going to display the data here. If I want to display single character, so that I can pass to here. Okay, here I am going to display, see here, column 1 pressed and row 1 pressed. See here, column 1, row 1 means 1. Okay, 1 I am going to display onto the LCD. Similar way, if row 2 double equal to 0, if the row 2 is pressed, okay, here just we need to change to row 2. If the row 2 is pressed, what I am going to display onto the LCD, row 2 means 4, 1 4 7 star, this 1 4 next 7 star. Just I copied for the other rows as well. 1 4, this is a 7 star. Here I will mention row 3. If the row 3 is pressed, I am going to display 7. See here, row 3 column 1. Row 3 and column 1 is 7, and row 4 column 1 is star. Here the row 4 column 1 is, this is a column 1, row 4 is star. Okay, similar way this is for the first column. Okay, let us check whether my expectation is coming as per the, whether if I press the particular column, the first column, whether I'm going to display that particular exact digit or not. Here just I'm giving the 65,000 delay. Why? Because our program will execute within microseconds. For example, whenever the switch is pressed, I'm going to display particular content and I will wait for some delay. Okay, okay, whenever the switch, whenever the particular digit displayed onto the LCD, and I need to release that particular switch. Otherwise, it will be keep on displaying the all the content. Okay, just I'm going to run the program. Okay, here we have one warning. Warnings is fine. LCD date. Okay, here see row 3. Okay, we missed something. Okay, okay, we should not be any warnings mostly. Yeah. Okay, here let us see our output. It should be first column should work. For example, if I press 1, I need to display onto the second row, right? When we are, where we are displaying from the second row, we are displaying the all the digits. Okay, I written for the first column for the 1 digit and 4 7 star. Okay, similar way we are going to display whether the all the this data, all this column is displaying or not. Okay, I will just zoom little bit to understand better way. Here if I press any key, see here the one is displayed. Similar way 4 should be displayed here, 7 should be displayed here, star. Okay, just we written for the first column. Similar way I need to extend the code for the second column and third column. Okay, similar way I'm just going to copy and copy the 2 times. This is for the column 2, this is for the column 3. Okay, this is for the column 2, this is for the column 3. Here we need to write the else if, otherwise might be all the columns might be affected. Due to this, here I need to write the else if. See, any one column will be pressed, right, at one time. That's why I'm just writing to the this one. Okay, even internally also you can write else if, else if, else if, but here I'm just checking the column. Okay, here see any one column might be pressed at once. Okay, that's why I'm just writing this one. Okay, if else if, for example, if the column 1 is pressed, I don't enter to the column 2. Okay, similar way column 3. Okay, that's why I written this else if case. Okay, here any one column will be pressed only one. Similar way you can extend else if also here. Let's see whether we are going to display all the content or not. Okay, here 1 4 7 star. The second column, what are the digits we need to display? Here the second column 2580. Similar way we need to write second column 2580. Okay, second column here 3 6 9 hash. Okay, if you see the last column 369 hash. Okay, similar way I written the program. Okay, let's see if we are going to display all the digits onto the LCD or not in the second row. Okay, here just I am displaying welcome to my project. Next one, YT Training Institute. Press any key. Okay, here I am going to display all the digits. I written the program for all the pins, so that I am just pressing any key here. Okay, one is displayed, fine. Just once if it is displayed, we need to release. Why? Because if we are not released, we are going to display a digit again. Okay, similar I will show you the at the end. See, 2 is I displays 3 4 5 6 7 8 9 star 0 hash. For example, I just pressed always. See here, always I am going to display. Okay, why? Because always we are going to execute the key infinite times. Okay, that's why if the digit is displayed, for example, let us assume I'm going to coming from here always while of one will execute infinite times. I'm going to wait this much delay, and I'm going to check whether the column 1 is pressed or row 1 is pressed. If both are pressed, I'm going to display the one digit onto the LCD. Okay, again if the again switch is pressed, again I am going to display. Okay, this is the while of one loop. Okay, that's why we are going to display multiple times onto the LCD. Okay, this is the basic concept we need to write for the keypad. Okay, initially we need to make the all the columns with logic 1, and all the rows with 0, and we need to find out whether the user is pressed the particular switch, then automatically that particular column will be becoming a 0 due to this shortage of the row to the column. Okay, due to that we are going to identify the column. Similar way we are going to identify the row. Okay, initially I need to initialize all the rows with 1 and columns with 0. Whenever the particular switch is pressed by the any one, okay, the automatically due to the column 0, automatically row also becoming a 0 due to the short circuit. Okay, this way we are going to identify the particular column and particular row. Then due to that we are going to identify the particular switch. For example, this is a column, first column, and first row means I'm going to display 1. Okay, similarly we written the program so that it is working as per the program. Okay, this is the way we need to write any program in easy method. First we need to understand the concept, and similar way we need to write the program. This is the concept we need to follow always. Okay, thank you friends.
Mainly discussing about on sensor interfacing with 8051 microcontroller. Okay, here we cannot interface directly the sensor with the 8051 microcontroller. Why? Because we don't have any internal ADC feature within this 8051 microcontroller. That's why we are not going to interface the sensor with the 8051 microcontroller. If I want to interface the sensor with the 8051 microcontroller, we need some intermediate IC that will convert some analog to the digital. That digital output will be given to the 8051 microcontroller. Okay, mainly we'll discuss here we have so many types of sensors. Let us take the temperature sensor or humidity or smoke sensor. Okay, mainly today we'll be discussing mainly on the temperature sensor. Whenever the temperature increases, automatically that resistance across the this sensor will be decreases. Due to that, voltage across this sensor will be increases. Okay, whatever the analog voltage is increasing, due to that the digital corresponding the digital value also will be increasing. Okay, that digital value will be given to the 8051 microcontroller. Okay, today mainly we'll discuss how to interface the sensor to the 8051 microcontroller, how we can monitor the this current temperature in our home. Okay, here we have the ADC0804. This is the intermediate IC. It will convert the analog input. This is a V in plus is my analog input. That corresponding analog input it will convert to the digital value. This digital value will be given to the 8051 microcontroller. Okay, this is a successive approximation register, one of the ADC type, and it will convert the corresponding analog input to the digital. Okay, here mainly here from the microcontroller we need totally 11 pins. These are 8 pins data pins we need to connect to the 8051 microcontroller, and the 3 more pins read, write, interrupt. These 3 pins also we need to connect to the microcontroller to convert from the analog to digital. These 3 are controlling pins. That's why we need to connect these 8 pins plus 3 pins, total 11 pins we need to connect to the microcontroller. Okay, today we'll be discussing completely about this each and every pin functionality. This is a chip select. Okay, this is the always we need to connect to the ground. If I want to use this ADC0804, this pin should be we need to connect to the ground. And here the read bar. Okay, for example, if I want to read the whatever the digital data from the ADC to the microcontroller, then this pin should be active low. Okay, we need to send the logic 0 to access the data from this ADC to the microcontroller. Okay, here next one is the write bar. Okay, here this is also active low pin. Okay, whenever I want do the conversion from the analog to digital, mainly to start the conversion, mainly this writing pin is required. Okay, from the microcontroller we need to send logic 0 to start the analog to digital conversion. Okay, that's why here mainly this is the pin for the start conversion. Okay, here the clock in and clock or, mainly here we are using the RC oscillator. That's why we need to connect external resistor and capacitor to these two pins. Okay, mainly we are providing the external RC circuitry to these two pins. Okay, here the interrupt pin. Okay, whenever this conversion is done, okay, we are getting the logic 0 from this ADC output. Okay, mainly whether the conversion is over or not, by using this pin we will come to know. whether it is conversion is completed. Okay, here this is a pin mainly for the start the conversion, and once it is started after the successful conversion, it is giving the indication to the microcontroller whether it is conversion is completed or not. This is a completed pin, this is a start conversion pin, this is for the read pin. Whenever I want to read the data from the ADC to the microcontroller, this pin we can use. That's why we need to connect these 3 pins plus 8 pins, total 11 pins we need to connect to the microcontroller. Okay, next one is a VIN plus. Mainly this analog input we need to give to the sixth pin. It will convert that corresponding analog to the digital value mainly by the this ADC0804. And this is a VIN minus we can give to the ground. And this is a analog ground. This is a digital ground. For the digital pins we have the digital ground. For the analog input we need analog ground. Okay, these two and this one three we need to connect to the grounds. VIN minus, a ground and D ground, digital ground. And V reference by 2 always unconnected. Okay, for example 0 to 5 volts, if I want to use the analog input 0 to 5 volts, mainly this V reference by 2 is unconnected. Okay, no need to connect any external voltage to this one. Okay, finally the step size 5 divided by 5 volts divided by 255, the 8-bit value, 8-bit conversion value. Okay, so that I will get the each step size. Okay, this is a 255 is 8 bit, 2 power 8 is 255, 256 totally. Okay, 8 5 volts divided by 255, that is a step size of this ADC conversion type. Okay, here the clock or also we need to connect to the this RC circuitry. This is the digital data we need to connect to the microcontroller. This is the 5 volts power supply to this ADC0804. Now we understood the each and every functionality of the ADC0804, and also we know how to start the conversion and how to just monitor the conversion whether it is completed or not. And also we have the pin to read the data from this ADC 0804 to the microcontroller. Okay, we know the functionality of this IC, then we can write the program very easy way. Okay, here we have the Proteus, here we have the initial circuitry, we have the LCD circuitry, here we have the power supply circuitry, reset circuitry, crystal oscillator circuitry, and we have the initial program of the LCD program. Okay, why mainly this LCD program already we written in the previous session. If you want more details, you can go through the previous video. Okay, right now I have the LCD video, and right now I'm going to interface this LCD, this ADC0804 to the microcontroller additionally. And right now we'll see the output of the this circuitry. Okay, welcome to my project YT Training Institute. This is the LCD program which we written initially, and right now I'm going to extend my project with the additional IC ADC0804. We will connect one sensor, that ADC value we are going to display onto this LCD. Okay, that program we are going to write now. Okay, here we need ADC0804. Okay, here from the library we can just type the ADC0804. Okay, that IC we can just take to our project. Okay, here we have completely, here we have 8 data pins. Here the DB0, DB1, I am going to connect all the data pins to the port 1. Port 1 completely, the digital data will be receiving from the ADC to the microcontroller. Okay, that's why I'm connecting 8 pins to this microcontroller, and 3 more pins we are going to connect from this read write interrupt. Okay, read pin I am going to connect to the microcontroller. Okay, read pin is my, this is a pin. 2.2 is my read pin. Write pin. Write pin I am going to connect to the 2.3 pin. Next interrupt pin I am going to connect to the 2.4 pin. Interrupt pin. Two 2.4 pin I have connected. Okay, these 11 pins are enough to this interfacing with the 805 microcontroller. Then this CS pin, right? CS we have the we need to connect to the terminal ground. Okay, here I have the ground. Okay, this CS we need to connect to the ground, And here the V in minus also we should connect to the ground, and analog ground and digital ground, these two also we need to connect to the ground. Okay, next V reference by 2 is unconnected. This is a 5 volts input to the this 8-bit digital output. This step conversion size is always 8 divided by 255. This is a step conversion size. Each and every step conversion, that is a voltage 19.8 millivolts for the conversion. Okay, here I will take the one resistant capacitor to this clock in and clock out. Here I will just here I have the resistor, and also I have the capacitor. We'll take the capacitor from this, already we have imported, and that capacitor is the 150 picofarads mainly. Here 150 picofarads. Okay, this is a or we need to give to this or circuitry clock or. Here this is a clock in. Clock in is the middle of the this RC circuitry, we need to the clock in, and this is the mainly we need to connect to the ground. Okay, this is RC circuitry we need to connect, and then right now we'll interface one temperature sensor. We have the already we have this temperature sensor. Just we can type the sensor, we'll get so many, and here LM35 is our temperature sensor. I am going to connect to the V in plus. Okay, here let us take this is a normal 27 degrees temperature, and I am going to connect to the V in plus, and this we need to connect to the ground. This we need to connect to the 5 volts VCC. This is a sensor. Okay, here we can take the generators DC. Okay, this 5 volts required for the this IC working, and also this temperature sensor also we need to connect additionally 5 volts to working of this IC. Okay, working of this temperature sensor we need 5 volts. Okay, whenever this temperature increases, automatically this resistance across the this sensor always decreases. Due to that voltage across this always the sensor will be increases. Due to that digital value also will be increasing. Okay, let us see the exactly output. Now we are going to convert this analog input to the digital output using the programming, and as we discussed in the initial programming, this is for the read pin. Whenever I want to read the data from the this 8 bits to the microcontroller, then we need this read pin. For the start conversion we need write pin. We need to check whether it is conversion is completed or not, mainly this interrupt pin. Okay, we know the functionality of this okay, this IC, then we can directly interface to the microcontroller. Okay, here uh, I have already interfaced all the pins. Okay, here we'll define S bit. Okay, read pin we have connected to read pin equal to port 2 cap of 2. Okay, 2 cap of 2 I have connected to the read pin, and the 2.3 write pin, and the other one is interrupt. Okay, this is the interrupt. Interrupt is 2.4. 2.3 is write pin. Okay, next another is our port 1 is connected to the completely ADC 8-bit ports, so that I'm just defining the SFR ADC. This is my port name, and here 0x90 is my port 1 address. This is my port 1 address. Port 1 address. This is my port 3 address. I have connected LCD 8 bits data, and here the ADC data pins I have connected to the port 1. If you see here, port 1, the 8 pins I connected to the port 1, and here I have just defined my all the pins. Okay, right now we will write our program. Okay, here welcome to my project, and after some time it will clear and it will display the YT training institute. Okay, right now I'm going to interface the ADC value. Okay, here I will just clear, and after some time I will clear the about text, and the 80 I am going to display the ADC value. Okay, here I will give the ADC value. Okay, here I will just write the ADC value. Okay, just will count how many Here every line we used to display 16 characters: 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. Okay, totally we have the 16 characters. I am just displaying ADC value here. Okay, next here I am going to display my ADC value. Okay, here I am just open and close braces for, I am just writing my program here. Why? Because here this is a infinite times I need to check the temperature value, and if it is increases, always I need to display onto the LCD. Okay, that's why I am writing my while of one means infinite loop. While of one is true, I am going to execute this piece of code. Okay, here I am going to write my program. Initially here the read pin is 1. Okay, initially I am not reading my value. Okay, if you see here, whenever I want to read the data, only after the conversion, that's why I am making the read is 0, read is 1 initially. Next write is 0 to start the conversion, and here we will wait some delay here. Okay, I need to give the logic 0. Okay, for the start conversion, that's why I'm just giving the delay of some 100. Next right pin is 1. Okay, here to start the conversion, okay, right 0 means start the conversion. Just I am giving some active low signal, so that it will start the conversion. Whenever the right pin is 0, then it will start the conversion. Why? Because it is the active low pin. Okay, whenever it is logic 0, then it will start the ADC conversion. It will take the analog input and it will convert the corresponding digital value. This for the start the conversion. Next I will check whether it is conversion is completed or not. Okay, here I will check interrupt bit is 0 or not. That's why I'm just comparing with the 1. Initially let us take this is the interrupt pin is 1, 1 double equal to 1. Okay, it is true, I will always wait here. Okay, whenever this interrupt pin is 0, then I will go to the next step. That means already conversion is completed. Okay, here I will wait until the conversion finished. Until conversion finished. Okay, here this whenever the conversion is completed, I will get the logic 0 from the this pin. Okay, from the interrupt pin act to low. Okay, whenever his conversion is completed, then I will get the logic 0. Okay, that's why I am waiting until this is 0, then I am waiting here. Okay, initially 1 double equal to 1 true, I am always waiting here. Whenever it is false, I am going to the next. That means until conversion ends, until conversion finished, I am going to wait here. Okay, once it is finished, I am going to read the data. Okay, read 0. Read 0 means I am going to read the data from the ADC to the microcontroller. Here I am just giving some delay, and here I can get the my data, my ADC data. Okay, here I will this is my hex value I will get from the this completely to the this port 1 I will get the digital value. That hex value I need to convert to the ASCII to display onto this LCD. Okay, we need some API to convert. This is an analog, this is a digital data I got it from the ADC. Okay, whenever the read pin is 0, my port data nothing but my ADC converted value. Okay, that I am passing to the one of the function. It will convert hex value to the ASCII. That ASCII value we can display onto the LCD. Okay, here I am just writing the void hex to ASCII function. Okay, here I am just writing this function unsigned char value. Okay, this is a value I got from the above function. Okay, here I am just passing my ADC value. Okay, this is an interrupt pin, we need to make it as 1 for the next conversion. Okay, this is the next conversion. Again it will start the conversion. This is an infinite loop. Again we'll start the conversion and we'll wait for the, again it is 0, and at the end I am making it as 1. Okay, this is a process will be continued forever. Okay, here I want to display my data. Okay, here the 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 88, 8B. I am going to display from 8B onwards. 8B onwards, I am going to display the 8B, 8C, 8D. Okay, I'm going to display the ADC converted value. I'm going to display from here. Okay, here I'm going to display complete remaining data. Okay, this LCD converted data. Here hex to ASCII. I'm writing this program. Okay, I got the hex value. Let us take my hex value is 255. Okay, hex values. Let us take FF. Just for example, I am just passing 0xFF, and let us convert this hex to ASCII value. Okay, let us take, I got the value as 0xFF, and here I'm just writing the my function here unsigned char. I'm just taking I need to convert to the three digits D1, D2, D3. Okay, I taken these initial variables I want to use for the conversion. Okay, here I'm just writing my logic here. X equal to, I'm going to divide my value divided by, I'm just doing the 10. Okay, here I will get for example, this is a 255 value. What is my x value here? Let us take ff, means what is my decimal value is 255. Here I will get the 25. Okay, here initially nothing but 255. 255 divided by 10, I will get the 25 value to the x value. X value is my 25. I'm going to split these three digits individually like D1, D2, D3, and that decimal values I will convert to the ASCII to display onto the LCD. Okay, initially we need to convert to the decimal. Okay, each and every decimal digit we need to split these decimal digits. Okay, that's why I'm writing this program. Right now I'm just dividing the D1. Okay, next, okay, let us take the D3. Okay, I'm just exporting my D3 now. Okay, here my value reminder 10 means here I 255, my value is 255, reminder is 5. Okay, I exported last to D3. Okay, digit 3 I exported here, my value is 5. Okay, just I exported 5 here, and the next one, next D2 and D3 I will export. Okay, D3. Okay, D3, next one is D2, sorry, here the D2. Okay, here I want to get this value. I will take the x value, x reminder by x reminder 10. Okay, 25 reminder 10 means here I will get the 5 value. Okay, here second 5 I exported from here. Okay, last D1 is 2. D1 x divided by 10. Okay, I will get the 2 value 2. Okay, I just split it into the three digits. Okay, my decimal value is 255. I'm just going to divide into the D3, D2, D1. Why? Because individually I need to split, and after that I need to add 0x30, so that I'm just converting to the hex value, ASCII value. Okay, here LCD data. Okay, here first what I need to display D1. D1 I need to display onto the LCD plus 0x30. Okay, this is my decimal value. I'm just converting to my ASCII data with plus 0x30. The decimal value I'm just converting to the ASCII for our displaying. Okay, the first two value I'm displaying onto the LCD. Okay, next one I'm going to display onto the 5 value, 255 I'm going to display. This is a D2. Next one is D3. Okay, last D3 I'm displaying it here. Okay, I just split it and I'm just going to display each and every digit onto the LCD. Okay, here let us we have taken the example of FF is my 255 value. I just splitted all the digits like 255. I splitted all the three digits, and I got the individual decimal values. And if I want to display onto the LCD, we need always ASCII. Okay, that's why I'm just doing plus 0x30, and it will be converted to the ASCII. That ASCII data we are displaying onto the LCD. Okay, this is a mainly program we written, and this program will be
display, just we will flash and check whether it is working or not. Just I am flashing like this, and we will verify whether it is working or not. Okay, and here I got the compilation issue, and here this prototype is not defined. Okay, that's why here it is showing the error. Okay, that's why I'm just copy this one. I will just written my prototype here, and let us check. Okay, there is no errors now, and I have generated my executable. That executable I will flash it now. Okay, here welcome to my project YD Training Institute. ADC value is 14. See here, I just displayed my ADC value 0x. Here the if it is 25 temperature, this is my real time temperature. I got the ADC value of 14. That means always divide, if I just doing the plus 1. Okay, I got the 14. 30 means let us increase. Okay, 30 degrees Celsius temperature means I got the ADC value is 15. Okay, if I want to match to this temperature, okay, I got the ADC value. If I want to match to this temperature, I can just multiply with 2, so that this temperature and the whatever the my ADC value will be also matching. Okay, let us multiply with 2. Whatever my I got the ADC value here, I'm just multiplying with 2, so that this ADC value and our temperature always matching. If I just stop and start, that whatever the changed program will be reflected, and we'll see whether it is matching the 30. See here, whatever my temperature and also ADC value is matching, so that I can consider this is my real temperature. Okay, so that what I will change, just my text I will change to this is the temperature value, and here I will give one more space 8C I will give. It will display clearly onto the LCD. Okay, here let us see both the temperature and our the ADC value are nothing but my temperature. Okay, whatever my real temperature I am displaying onto the LCD. This is the mainly if I want to display the real temperature, so that we can write our program like this, and whatever the converted value we can display the ADC value nothing but this is my temperature, so that we can match. Here I am just using the multiplier of 2 to match the ADC value to the temperature. So we can display that real temperature onto the LCD. Okay, this is a program. If I want to monitor, we can buy the just temperature sensor, and also this ADC 0804, and also this 805 on microcontroller and LCD. Okay, whenever this temperature increases, automatically this ADC value also increases, and due to that we are going to display what are the exact temperature onto the LCD. Today we are mainly discussing about on timer or counter programming. The 8051 has two timers or counters. They can be used either as timers to generate a time delay, or as event counters to count events happening outside the microcontroller. Okay, here the port 3.0, 3.4 pin and port 3.5 pin we are using to count the external events or the external clock pulses to the microcontroller. And here the timer 0, if I want to use the counting 0, so that we need to feed the external clock pulses or the external events to the port 3.4 pin. Similar way for the timer 1, if I want to use for the counting applications, we need to feed the external clock pulses or the external events to the port 3.5 pin, so that we can use it as a counter. Okay, these are mainly working principle of the timers as well as the counters. Both timer 0 and timer 1 are the 16-bit wide, but our 8051 has an 8-bit architecture, and each 16-bit timer acts as a separate registers, lower byte and higher byte. Okay, here this timer 0 we divide into the lower byte and higher byte, TL0 and TH0. Timer 1 also we divide into the lower byte and higher byte, TL1 and TH1. We are considering it as timer 1, and this is a timer 0 16-bit wide, and timer 1 also 16-bit wide. Okay, this is a timer 0 and timer 1. Next we'll discuss mainly on the T mode register. T mode register is a 8-bit register. This is only the byte addressable, and lower nibble, lower 4 bits we are using to control the timer 0 or the counter 0. Similarly for the higher nibble, higher 4 bytes we use to mainly control of the timer one or the counter one. Okay, mainly here the gate bit always for the software control we are setting it as always 0. If in case of hardware control, then we need to set this gate bit as 1. Okay, if I want to control this timers or the counter using the external hardware, then we need to set this gate bit is to 1. And next bit is the C by T bar. Okay, if I want to use the timer 1 as a counter 1, so that this bit we need to set to 1. Similar way, if I want to use the timer 0 as a counter 0, this bit we need to set to 1. And similar way, if this bit set to 0, this timer 1 we are using it as a timer 1 only. Similar way, this bit if we are setting to 0, this timer 1 we are using it as a timer 0 only. Timer 0 we are using it as timer 0 only. Okay, for example, if this bit is 0, we are using it as timers. If this bit is 1, we are using it as a counter. Okay, next two bits are the mode selection bits. Here we have the M0 and M1 bits. Okay, these are two bits. We have the four combinations. 0 0 is the mode 0, 0 1 is the mode 1, and 1 0 is the mode 2, and 1 1 is the mode 3. Okay, here the mode 0 we are operating the both timers on the 13-bit timer mode. Okay, here we have the each timer is a 16-bit, but in case of mode 0 we are using only the 13-bit. Lower 5 bits D0 to D4, and the higher complete byte we are using totally 13 bits in the timer 0. Similar way, timer 1 also lower 5 bits we are using, and also higher complete 8 bits. Totally 13 bits we are using in case of mode 0. Okay, next one is mode 1. We are using complete 16-bit timer in case of mode 1. Okay, we are using complete timer 0. We are using complete timer 1 in case of mode 1. Okay, next one is a mode 2 8-bit auto reload mode. This is mainly we are using in our serial communication to generate a 9600 baud rate. Mainly we are using this auto reload mode. Okay, here I will explain the use case of the what is the principle of working of this auto reload mode. Mainly here TLX it will start incrementing from the 0 to max value overflow. Once it is overflowed, the content of the THX value will be copied to the TLX. This is the mainly working principle of the auto reload mode. Whenever this TL is overflowed, whatever the content of TH value will be loaded to the TL content. Okay, next one is mode 3 split timer. Okay, here in this case this timer 0 we are using it for the timer 0 as well as the timer 1. Okay, this lower 8 bit we are using for the timer 0, and this higher 8 bit we are using for the timer 1. That's why we are calling it as a split timer. Timer 0 only we are using for the timer 0 as well as timer 1. Okay, that's why we are calling it as split mode. Okay, next we'll discuss this all the modes in our programming in the next slides. Okay, next here TCON register timer control. Here the bit or byte addressable. We can access a particular bit as well as a complete byte also. That's why we are calling it as bit or byte addressable. This is the only the byte addressable. T mode is a byte addressable, and this also byte addressable. We need to access byte by byte. Only TCON is the bit or byte addressable. Okay, here lower 4 bits we are using to mainly we are using for the timer for the interrupts, and the higher 4 bits we are using to control the timers. Okay, here we are using this TR0 bit. If I want to start the timer 0 or the counter 0, or the if I want to stop the timer 0 or the counter 0, we can use this flag. For example, if I setting TR0 to 1, we can start the timer or the counter based on the mode. I can start the timer. If this bit I am setting to 0, I am just stopping the timer 0 or the counter 0. And here this is the flag to check whether our timer or the counter is overflow or not. We are going to check this flag. Okay, this flag to monitor whether our timer or the counter is overflow or not. This flag indicate us to whether the counter or timer is overflow or not for the timer 0. And similar way, if I want to start or stop the timer 1 or the counter 1, this flag we can use. Similarly, if I want to check whether the timer 1 or the counter 1 overflow or not, this flag we can use. Okay, here we have the flags to check whether it is overflowed or not. Okay, next we'll check if I want to create the 5 millisecond delay. Okay, usually first we will calculate how much delay we can generate using this 16-bit timers. Okay, mainly here in our mode 1 we can mainly use the max timer 16-bit timer. Okay, if I use the 16-bit timer, max delay we can generate 71 1.106 milliseconds. Okay, why? Because this 16-bit timer 65 536 is my range of the this 16-bit timer. Into each clock pulse it is taking 1.085 microseconds. Okay, that's why we are generating 71.106 milliseconds. Okay, by using our timer 16-bit timer, we are generating max delay of 71.106 milliseconds. For example, if I want to generate 5 milliseconds delay, okay, this is a program to generate, this is a just calculations to generate 5 milliseconds delay using the timers. Okay, here 11.0592 is the my external clock frequency, and each counting it is taking 1.085 microseconds. That's why if I want to generate 5 milliseconds delay, so that I am just here 5 milliseconds divided by 1.085 microseconds, here 4608 clock pulses. Okay, for example, if I want to generate 10 milliseconds delay, 10 milliseconds divided by 1.085 microsecond, this way only we need to divide with the always 1.085 microseconds, then we'll get how many clock pulses. Okay, this many clock pulses will generate 5 milliseconds delay. Okay, that's why we are always separating. Why? Because we have the flag to check whether the timer or counter overflow or not. Okay, that's why we are subtracting from the max value. That's why I'm loading the, for example, I'm just loading the 65 536 is the my max value. Okay, max overflow value, that's why I'm just minusing with the overflow value. 65 536 is my overflow value, minus 4608 is my clock pulses. These many clock pulses I need to generate. If this many clock pulses, so that I am generating 5 milliseconds. That's why 65 536 minus 4608 is my final count. I will get the decimal value. That decimal value if I convert, I am just getting the hex value here. E is 00h. This 00h I should load to the TL0. Because this is a lower byte, and higher byte we need to load to the TH value, TH register. Okay, this is the mainly this working. For example, if I want to generate the 10 milliseconds delay, similar way 10 milliseconds divided by 1.10 milliseconds divided by 1.085 microseconds. Just I am dividing this one. I will get the 9216 9216, and this is my decimal value into 1000. Okay, 9216 clock pulses, so that I can just give you a minus 65 536 minus 9126. Okay, I will get this value, and this value I need to convert to the hex 56, so that that hex value we can load to the th register and as well as the tl register, so that we can generate the 10 milliseconds delay. Okay, for example, if I want to generate the 5 milliseconds delay, 5 milliseconds divided by 1.085 microseconds, then I will get the 4608 clock pulses. Okay, this clock pulses we need to always minus with the 65 536. Why? Because my timer is always overflowing at this point. That's why I'm just giving the this value 65 536 minus 4608, so that I'm starting always 71 minus 5 milliseconds, so that I'm just always starting from the 64 milliseconds onwards. 64 to whenever the 71.106 reach, my timer is overflowed. At that time I can stop the timer. That's why I'm always loading this value to the timers. Okay, if I want to generate the 10 milliseconds delay, 10 milliseconds divided by 1.085 microseconds, I will get the clock pulses. And similar way we need to minus with the max value 65 536. I will get the 10 millisecond respect to decimal value also. I need to minus that value. I will get the final x value. That x value we need to load to the timers. Okay, this is the mainly calculations behind the timers. Okay, next programming of the timers or the counters. First, initialize the T mode register to select particular mode of timer or counter operations. First we need to initialize the T mode register, whether I want to use the timer or the counter or which mode of operation. So that I need to load the T mode register first. Next one, right now we have already calculated some TL value and TH value based on our timing. Okay, that values we need to load on to the this timer 0 and timer 1 registers. And after that we need to start or stop the counters by using the TR0 and TR1 flag. Okay, if I want to start the timer 0 or the counter 0, I need to use this flag. If I want to start or stop the timer 1 or the counter 1, I can use this flag. Okay, the third step also completed. Next one is the check whether uh, my timer is overflow or not, whether my counter is overflow or not, by using this TF0 and TF1. For example, if I want to check my timer 0 or the counter 0 overflow or not, I can check this flag. Similar way, if I want to check my timer 1 or the counter 1 overflow or not, so that I can check this flag. Okay, this is to check the whether my timer or the counter overflow or not. Okay, next one, if it is overflow, stop the timer or the counter. Okay, next step, we need to stop the counter by using this starter stop the counters by using TR0 flag. We can set to 0 so that I can stop the timer 0 or the counter 0. Similar way, if I want to stop the timer 1 or the counter 1, this flag I need to set to 0. Okay, here we stopped my counter or the timers. Next, for the next operation we need to clear these flags, otherwise the next operation won't be continued. We were not able to generate next further delays. That's why clear the overflow flag for the next operation. Okay, once it is overflowed, we need to clear this flag for the next operation. This is a mainly programming of the timers or the counters. These are steps. Okay, similar way, this is our clock frequency, external clock frequency 11.0592, and always the division factor is always in our hardware always doing the divide by 12. I will get the 9 to 1.6 kilohertz, and if I do the 1 by this 9 to 1.6 kilohertz, then I will get 1.085 microseconds. That's why we are dividing with the 1.085 microseconds. Okay, here and each increment it is taking 1.085 microseconds. Each timer increment it is taking 1.085 microseconds based on this clock frequency. Okay, now we'll write one program for the mod 0. Okay, we'll try to write the programming for the all the modes. Okay, I'm going to the Keil programming. Here we'll write the specific program. Okay, here I'm just loading the 0x00 value, and we'll discuss right now which mode we are in. Okay, here 0x00 means what is my binary value? Four zeros, again four zeros. Okay, this we are using for the timer 0, this we are using for the timer 1. Okay, let us consider all are 0. Okay, here the gate is 0 for the software control, it's fine. And the next one is 0 means timer 0 we are using. Okay, if this bit is 1, we should use this timer 0 as counter 0. Okay, right now it is timer 0. Here 00 means mode 0. Okay, here the lower byte it is telling timer 0 mode 0, and similar way for the higher byte also it is saying the same. Okay, 0 means always software control, gate is 0, and this C by T bar is 0 means timer 1 we are using it as timer 1 only. 00 means mode 0. Okay, here the timer 1 mode 0. Okay, this is the, if I load this T mode to 00, nothing but timer 0 mode 0 we are using, timer 1 mode 0 we are using. This is the mode of operation. Okay, this is my first step in our programming. First we need to load the T mode register. I am using the mode 0. Okay, timer 0 mode 0 I am using. Right now I will just start my timer 0 only. That's why here I selected with T mode with 00. Okay, I'm using timer 0 mode 0. I will start timer 0 only right now. Okay, next one, if I want to load some values, we can load this th0 equal to 0x00 I am loading, and similar way th tl0 this is a tl0 and th0 is a complete the timer 0. I'm just loading with 0x00 values. Okay, my timer always I'm starting from the 00. Next second step I loaded with the TL0 and TH0. The second step also over, and I am just started with my timer with the 0 value. If I want to load with the this double E double 0 also, even we can load. Okay, later on we can try to change the values. Right now I am just starting with 0 zeros only. Next I want to start my timer 0 or the counter 0. I need to set my tr0 to 1. If I want to start my tr0 to 1, okay, here I am just starting the timer 0. Okay, timer 0 start. Okay, if I want to start the timer 1, tr1 we need to set to 1. Okay, next I want to check whether my timer 0 is overflow or not. Here I am checking timer overflow 0. Here I am checking my timer 0 is overflow or not, equal to 0. Okay, whenever it is 1, my timer is overflowed. My timer 0 is overflow. Whenever this flag set to 1, my timer is overflowed. Right now is 0 double equal to 0. I am always staying here. Whenever this timer is overflow, I am going to the next step. Okay, whenever it is overflow, I need to stop this timer. Okay, the next step, we need to stop the timer whenever it is overflow. Okay, whenever it is overflow, check whether it is overflow or not. If it is overflow, stop the timers. Okay, here I am just stopping my timer and clear the overflow flag for the next operation. This timer overflow flag, okay, this flag will set by the controller to 1, and we are making to 0 for the next operation. Okay, this is a mainly programming for the timer 0 mode 0. Why? Because I am just always starting the timer 0. That's why I am speaking about the timer 0 mode 0. Right now my this is program for the timer 0 mode 0. This is a timer 0 mode 0. Why? Because I am just starting the timer 0 only. I am just starting the timer, and also I am stopping the timer whenever it is overflow. Okay, here this timer 0 stops. Okay, this is my program I written. I will just execute. Okay, let us check whether how it is operating. It is 13-bit mode. In our this timers, only lower 5 bits we are using, and higher 5 bits, higher complete 8 bits we are using. Okay, totally 13 bits timer 0 we are using it in this programming. And similarly we'll check lower only the 5 bits. Okay, this lower 5 bits we are using. In our lower only we are using 5 bits, and higher we are using complete 8 bits in case of mode 0, 8 bits. Okay, similarly we have executed. I does not get any errors, so that I got the executables. Here always we should set our frequency 11.0592 as we discussed in our initial. Okay, next I am going to the debug. We'll check whether how the timers or the counters are working. Okay, here these are the peripherals I took from the peripherals. Okay, here peripherals, go to here timer 0. Here I written the program for the timer 0. That's why I took this one. Okay, initially I am operating timer 0 with the mode 0 only. Initially, even I am not loading any of the value initially. My operating mode is mode 0 and 13-bit mode only. That's why initially it is in 13-bit mode only. And TL0 and TH0 I loaded with 0, TL0 and TH0 I loaded with 0 0. And the next value I am just starting this TR0. Okay, initially my timer is on stop. Okay, I want to start my timer using this TR0. I am just setting the flag to 1. My timer 0 will start now. Okay, now it started, and the TL0 it will start increment. This is only the 5 bit we are using. 0 0 to 1F it will increment. Whenever it is overflow, it will start increment by 1 to this value. And let us check how the timers running. Okay, here TL0 value it will increment until 1F. Okay, once it is overflow, it will increment by 1 to the th1 value. Okay, it is increment by 1. Again it will start from 0 to 1f. Again th1 1 th0 value increment by 1. Okay, this is the mainly working of the timer. Whenever this is overflow, this will increment by 1. Again it will start from 0 0 to 1f. Again increment by th0 by 1. Okay, this is the mainly working principle of the 13-bit timer. Okay, this is a 0 0 to 1f. Whenever it is overflow, this will increment by 1. This is the mainly working principle of the timer 0 mode 0. Okay, this is the mainly working principle of the timer 0. So that we can generate how much delay for each increment. We are considering it for the 1.085 microseconds. Okay, lower we have the 32 counts. Okay, every 32 counts we are incrementing th0 value by 1, and this will increment up to ff, means 256 value into 256 value. Okay, we are generating this many counts, this many timer increment until overflow. And that's why, and each increment we are considering it as 1.085 microseconds. so that we are generating this much delay 1.085 microseconds, so that we are generating 8.8 milliseconds by using the mode 0. Okay, only this much delay only we can generate by using the mode 0. Okay, if I increment until 1f, and it will start incrementing th0 value by 1. Okay, it will increment until max value until 8192 counts, and each count it is taking 1.085 microseconds, so that it's creating 8.8 milliseconds finally. Okay, by using mode 0 we are generating up to 8.8 milliseconds. Okay, this if I use this mode, I can generate only 8.8 milliseconds delay only we can generate by using these timers. Okay, similar way if I use the mode 0. Okay, right now I will I am going to write the program for the mode 1. Okay, timer 0 mode 1. Okay, I am going to write the timer 0 mode 1. Okay, here the mode 1 means 0 1. Okay, now timer 1 I am using as it is timer 0 mode 0, but I am always starting the timer 0. Mode 1 means 0 1 0 0 0 1. Okay, here 0 1 means mode 1. Okay, I am operating with the 16-bit timer. Okay, just I have changed this one. This is a binary value. I'm just converting to the hex value. Four zeros means zeros. Triple zero one means one. Okay, I just written this one. Right now I'm using both are 8 bits. Lower 8 bits I'm using and also higher 8 bits. Totally 16-bit timers I'm using in case of mode 1. Okay, this is a programming for the mode 1. Okay, next I'm going to the debug mode. Okay, here always let us check if this instruction is executed. I am going to switch to the instead of mode 0 to the mode 1. Right now I written program for the mode 1. See here mode 1 16-bit timer. Right now I'm using for the 16-bit timer. Completely this 8-bit I'm using. This 8-bit also I'm using. Okay, this will start incrementing from 00 to FF. Once it is overflowed, this will increment by 1. Again it will start from 00 to FF. Again it will increment by 1. Okay, this is the mainly timer operation. 256 into 256, totally 65 536 counts we are generating. Max we are generating this 71.16 millisecond, 106 millisecond. Okay, similarly you can calculate here. 256 is the lower. Every 256 times it will increment by 1. Okay, that's why I'm considering it as multiply 256 multiply 1.085 microseconds, so that I am generating 71.106 milliseconds by using this mode 1. Okay, here I am just start incrementing this lower value also I am using 8 bit, so that 20 to 2f, again 30 to 3f, 40 to 4f, 50 to 5f, 60 to 6f, 70 to 7f, 80 to 8f, 90 to 9f, A0 to AF, B0 to BF, and C0 to CF, and D0 to DF, E0 to EF, and F0 to FF. Okay, once it is overflowed, it will start increment by 1 TH value, and again this TL value continue incrementing until again FF. Okay, this will keep on increasing until 71 milliseconds we can generate. Okay, if I want to generate 5 millisecond, so that we need to load this EE00. For example, if I want to generate only 5 milliseconds delay, this EE and 00 we need to load to here, so that we can generate the only 5 milliseconds delay. Again I need to build. Okay, by using this program we are generating only 5 milliseconds. Why? Because we have already calculated this 5 milliseconds delay. 5 milliseconds divided by 1.0885 microseconds. Why? Because in each increment it is taking this much microseconds, and 4608 I got this many clock pulses. And in our 16-bit mode, this is my max value 65 536 minus this is my whatever I my decimal value here. Now I got the final hex value that I have loaded into the th0 I loaded with EE, and TL I loaded with 00. Okay, similar program I written here for the 5 milliseconds delay I am generating using this one. Okay, if I just start my programming step by step, see here TH0 I am loaded with EE, and TL0 I loaded with 00. Next I start my timer, and I am waiting for the overflow. From EE002 it will start incrementing up to all FF, TH0 also FF, and TL0 also FF. Then we reached 5 milliseconds delay. EE002 all Fs we reached 5 milliseconds delay. Okay, this is a mainly we are generating how much delay we want we can generate. Similarly 10 milliseconds divided by this one, I will get the decimal value. and that decimal value we need to minus from the max value, so that we are able to identify the only overflow, whether my timer or the counter is overflow or not. Okay, I executed the for the mode 1. Similar way for the mode 2, we need to check whether my TL, if it is overflow, automatically this TH value should be copied to the TL. Okay, this program will write now. Okay, this 0 to I will write now. Here 10 means mode 2. Just I converted this value to the this one. Okay, this is my mode 2 programming, timer 0 mode 2, and whatever the TH value will be copied to TL value whenever this is overflow. Okay, now we'll check the same program will check. Okay, whenever this TL is overflow, automatically this TH value will be copied to here in case of mode 2. Okay, I am just running my mode 2 only, mode 2 programming. Let us check. Okay, one by one. Okay, here I executed. See here, timer 0 or the counter 0, I am using mode 2 8-bit auto reload mode. Okay, in this case, whenever it is overflow, automatically this value will be copied to here. Okay, here I am executing one by one TL value. Okay, it is keep on increasing from the 0 to max value until FF. Whenever it is reaches FF, automatically this TH value will be copied to TL value. Okay, here 60 to 6F, 70 to 7F, 80 to 8F, 90 to 9F, and 80 to AF. Here I am just executing step by step my program, and D0 to DF, and E0 to EF, and F0 to FF. Okay, whenever it is overflow, the EE value will be copied to here, then it will start incrementing from here. Okay, right now I am just stopping my timer. Let's see whether it is reloaded or not. Okay, here see, E0, after that E1, after that it is going went to F1. Okay, why? Because it is reloaded from this TH value, and it's again it will start from E to EF and F. Okay, again we'll see, I will load another value and we'll see. Okay, here I just loaded with value 10. Okay, if I want to observe again whether it is, whether I am just starting from the 10 value or not. Okay, just I am executing once again. I went to debug mode, and again I will start. Okay, whenever the lower is exceed, my TH value will be loaded to TL value. It will start incrementing from the 10 again. Okay, is here 60 to 70 to 7F, 80 to 8F, 90 to 9F, and A0 to AF, B0 to BF, and the C0 to CF, and D0 to DF, and E0 to EF, F0 to FF. Okay, once it is overflow, this 10 value will be copied to TL. Okay, see, it started from 10 and 11, it's incremented by 1, that's why we see 11. Okay, this is the mainly working of the auto reload mode. Whenever this TL is overflowed, automatically this TH value will be copied to this one. Okay, next is the auto reload mode, also we discussed. Okay, whenever this is overflow, this will value we are copying to TL value. Okay, next one is a split timer. Okay, here in this case, okay, timer 0 mode 3 we are using for the split timer only. This is also 8-bit mode. 3 means 0011. Mode 3 means 11 we need to load. See here, 11 we need to load for the timer 0. Okay, similar way I am executing this for the mode 3 programming. Right now we are in mode 3. Okay, let's see whether we are in mode 3 or not. Let's go to the debug, and here only this is a 8-bit mode. Let's see whether only it will be used by TL0 only. In case of timer 0 mode 3, only this 8-bit will be used. Okay, here I'm just going to the debug mode. Okay, here 8-bit auto reload mode only it is saying, so it's not the correct one. Again we need to build. Okay, here we need to load 03 value. It will be going to the split mode. Okay, right now we are in the split mode. Let's see. Okay, here see, mode 3 means two 8-bit timers or counter. Okay, we are into the mode 3 now. Okay, we can execute only lower 8-bit only, it will be considered for the timer 0, and this whenever it is overflow, only this 8-bit value. Okay, in case of split mode, this lower TL0 will be used as a timer 0, and the TH0 will be used by timer 1. Okay, that also will check. Right now I am just checking the timer 0, it will be used by this TL0. Okay, I'm just start checking whenever it is FF, my this 8-bit mode is overload, this split timer. Only in case of this mode 3, only TL0 used by the timer 0, and TH0 will be used by the timer 1. That also will execute the next step. 70 to 7F, 80 to 8F, 90 to 9F, 80 to AF, B0 to BF, and C0 to CF, D0 to DF, and E0 to EF, and F0 to FF. Whenever it is overflow, we are done the program. Okay, this is a mainly split mode. It will be used by only TL0. Right now I will start the timer. Okay, right now we are in split mode. I will start the timer 1. Similar way I will check that timer 1 is overflow or not. And right now this TH0 will be used by the timer 1. Okay, let us check whether in case of split timer. Okay, here I am using in the timer 0 mode 3, but here I started the timer 1. Here I started the timer 1, and here I stopped the timer 1. Here I am checking whether my timer 1 is overflow or not. Okay, let us check. This TH0 should be used by the timer 1. Okay, I will check the timer 1 also here. We'll take the timer 1. Okay, I am just starting the timer 1 here, but always this will be used by the timer 1 in case of split mode. Let us check. Okay, see here, it will start incrementing. This th value I loaded with 10, that's why it is starting from the 10. See here, th1 value will be used by the timer 1. Here see, I started the timer 1, and it will start incrementing the value on this timer 0, this th0. Okay, here in case of split timer, this th0 will be used by the timer 1. This will be used by the timer 0 in case of split mode. That's why here I started the timer 1, and th0 it will start on incrementing. See here, th0 value incrementing, and also here the timer 0, timer 1 I'm using the mode 0. That's why it is also incrementing the this one. Okay, that's why here always we should consider in case of split mode, this will be used by the timer 1, this will be used by the timer 0. This is the mainly use of the split mode. Okay, mainly in our we understood all the modes of operation. Mode 0 only the 13-bit timer, we can generate only 8.8 milliseconds. By using the mode 1 we can generate 71.106 milliseconds. Auto reload mode only we have the 255 counts, only the lower bit will be used. Whenever this is overflow, this will be copied. This is also until 255 counts only. We can generate only this much delay, 256 into 1.085 microseconds. Only 278 microseconds only we can generate using this last two modes. Okay, in case of for the delay generation we always use this one. In case of serial communication we are using this 2-bit. Okay, right now we'll discuss on the counter programming. Okay, I will write the for the counter 0, I will write the counter 0 mode 1 programming, so that we can count up to max value. Here I want to use the counter 0. Okay, here I am just writing the counter 0 and mode 1. Okay, here I want to switch my counter 0 mode 1. Okay, I am just timer 1 I am using as it is. Timer 1 mode 0 only I will be in. Here I always I am using the counter 0. That's why I am just starting the counter 0 and always stopping the counter 0. Okay, here 0. Okay, here I want to use the counter 0 mode 1, so that I'm just writing here counter 0 mode 3 mode 1. Similarly I wrote here. Okay, if I want to use the counter 0 and mode 1, counter 0 means this bit should be 1. Okay, these 4 bits I will just rewrite. Gate always 0, and the C by T bar I'm using for the counting application. This timer 0 I'm using it as a counter 0 now. That's why I made it as 1. And after that mode 1 means this is a 0 1. Okay, mode 1 means 0 1 we need to write 0 1. Okay, here this value, the corresponding hex value we need to write it here 5. 4 zeros means 0, and the 0 1 0 1 means 5. Okay, 0 5 I wrote here. Right now I am just operating timer 0 as a counter 0 mode 1. Okay, I am always starting my count from the 0 0, TL0 and TH0 I loaded with 0. Here I am just TR0 1 I am making it as here counter 0 start. Counter 0 start. Right now I am starting the counter 0. Here I am stopping the counter 0. Here I am checking whether my counter 0 is overflow or not. Whenever it is overflow I am just stopping my counter 0, and for the next counter operations I am clearing this counter. Okay, similar way I will execute. Right now we are in counter mode. Counter 0 means I need to send the pulse to here. Counter 0 means 3.4 pin. Okay, then only my count will increment. Okay, I have executed and I will go to the debug session. Okay, I have two timers. Right now I should use this timer as a counter 0. Let us see. I will execute first step. See here, this timer or counter 0 I am using for the counter application, and mode 1. Mode 1 is 16-bit counter. Right now I am using complete this 8-bit and this 8-bit. Totally I can count up to 65 536. Okay, lower I can count up to 256. Okay, whenever it is 256, it will increment by 1. Again 00 to 256 counts. Again this will increment by 1. That's why I am incrementing with 256. Totally this many counts I can count up to by using this mode 1. Okay, counter 0 mode 1. Okay, let us see. I just started my counter. Okay, here I just started. It won't increment. Okay, if I want to increment, my external event should be set. Okay, external clock pulses I need to give to the port 3 point. Here we'll check. Okay, port 3.4 I need to give the pulses to the events. Okay, port 3.4 pin, 3.0, 3.1, 3.2, 3.3, 3.4 pin. Okay, if I give the high to low pulse, automatically this count will increase 3.0, 3.1, 3.2, 3.3, 3.4 pin. See here, whenever I am giving the low to high pulse, one time is increasing, my counter value is increased by 1. Okay, this is my, I am just counting the external events. Whenever my external events are coming from the external clock pulses I am giving to the 3.4 pin, this timer 0 or counter 0 is start incrementing. Why? Because right now in counter mode, whenever any pulse from externally, then only my timer keep on increasing. Okay, that's why here I am counting the my external events. Okay, this is my counter operation. This is my counter 0 mode 1. Similar way, if I want to operate counter 1 mode 1. Okay, let us change the counter 1 mode 1. So that same value I will write here, counter 1 mode 1. I'm just starting my counter 1. Here also I'm just checking my counter 1 is overflow or not. Just I'm stopping my counter 1 here, and for the overflow flag I'm clearing for the counter 1. This is my counter 1. Okay, let us see. This is a counter 0 mode 0. This is also counter 0 mode 1. Same. Okay, here the counter 1 mode 1. Counter 1 mode 1. Okay, here I am just writing the same value to the lower and higher, but I am just starting. See here, 5 value means I will go to the again T mode register. Here we'll check what is my current value. Okay, here I'm just using the gate is 0, and I'm using the counter 1. That's why I'm set it as 1, and 0 is my 0 1 means mode 1. Okay, counter 1 mode 1 I'm using the higher nibble, and lower nibble counter 0. Okay, here for the counter 0. Why? Because this second bit I set it as 1, so that I'm using the for the counting 0 1 means mode 1. Okay, here I just selected 5 5 means counter 0 mode 1 and counter 1 mode 1. Okay, this is the value I set, and initially I am loading my counter 1 values. TH1 and TL1 is my counter 1 values. Initially I am loading with the 0 zeros. I'm just starting my counter 1, and I'm checking whether my counter 1 is overflow or not. I'm just clearing my counter 1, and I'm just stopping my counter 1, and next one I'm just clearing my overflow flag for the next counting operations. Okay, again I just build my code, and right now we'll check this counter one and this one also counter 0. I'm using both the use cases, but I'm going to start only my counter one. Right now I written programming for the only counter one I'm starting, and I'm stopping for the counter one. See here, right now I'm operating both the mode 1 and counter 0 and timer 0. Okay, here if I just return the 0x55 value, and the timer 0 I am using it as counter 0 with the mode 1. Similar way, timer 1 I am using it as a counter 1 with the mode 1 with the 16 bit. And here I am going to the further, I am just starting the only for the counter 1. Okay, for the counter 1, what is the bit I need to give the pulses, external pulses 3.5 pin. Okay, then only this count will keep on incrementing. Okay, right now I'm in checking the overflow. Okay, right now until 4 apps I'm going to wait here. 3.0, 3.1, 3.2, 3.3, 3.4, 3.5, 3.6 pin. Okay, it is 3.5 pin only, right? Yeah, 3.5 pin. 3.0, 3.1, 3.2, 3.3, 3.4, 3.5 pin. Okay, whenever I'm giving low to high pulse, automatically this counter one, it will start incrementing. Okay, here I'm giving low to high pulse, it will start incrementing. See here, whenever I'm giving the external events, it will start incrementing. Okay, here mainly based on the T mode register, I'm selecting particular timer mode or particular mode of operation, and also whether I'm using the timer or counter by using the T mode register. Okay, based on the which timer we want to start, we need to start here whether the timer one or the counter one by using the this tr1 flag. And okay, we'll discuss here all the programming steps once again. Okay, here first whatever the program we written similar way, initialize the T mode register to select particular mode of timer or counter operation. Next we need to load some initial values. If I want to load to the timer 0 or the timer 1, we can load here. Next we can start the timer or counter by using this tr0 or tr1 flag. Next check if the timer 0 or the counter 0 is overflow or not by using these two flags, and stop the timer or counter using the tr0 and tr1 flags. And similar way the last step, and clear the overflow flag for the next operation. This is the mainly programming steps for the each and every programming for the timer or counter operations. Okay, today we discussed all the modes of operations of the timer as well as the counter. We discussed only the mode one. Okay, thank.
Discussing about a timer or counter programming continuation. We already discussed about the timer or counter programming with different mode of operation in the previous session. Today we are mainly going to discuss, we are going to take the two problem statement that we are going to solve using the embedded C programming. Write an 8051 C program to toggle only pin port 1.5 continuously every 50 millisecond. Use timer 0 mode 1 16-bit to create the delay. Okay, here first I need to select my first I need to initialize my T mode register with timer 0 mode 1. Okay, here I have my T mode register. Okay, here the timer 1 I am not using, I will just initialize with all zeros. And I am using timer 0, gate always 0 for the software control, and C by T bar is my I am just using this timer 0 as timer 0, that's why I will initialize with 0. And right now for the mode 1, my hex value, my binary value is 01, so that this are four zeros, 0001 means my T mode value is in hex format is 0x01. Okay, my T mode equal to 0x01. Okay, now I initialize my T mode value. After the next step, I need to initialize my TL0 and TH0. For the timer 0, I need to initialize these 2 bytes. Okay, right now I am going to initialize this TL0 and TH0. Okay, if I want to generate this 50 milliseconds delay, in our timers we can generate 71.106 milliseconds by using our this 16-bit timers. Okay, for example, if I want to generate this 50 milliseconds delay, always we need to divide this 50 milliseconds divided by 1.085 microseconds, then we'll get the clock pulses. Okay, similar way we can take the calculator. Okay, here we can have a calculation. This 50 milliseconds divided by 50. Okay, I will go to the program standard mode. 50 milliseconds, 50 I am just taking into 1.085 microseconds. Okay, here microseconds means I have to multiply with 1000 divided by microseconds, right? That's why I'm just multiplying. 46082 is my clock pulses, and I should minus with 65536. Why? Because my timer is always overflow at this place. Okay, whenever my timer is overflow, I have the bit to detect. Okay, here we have the TF0 and TF1, so that I am able to identify whenever the timer is overflow. That's why I am always doing the minus with the max value. Here this is my 46082 is my value. 46082, 65 536 minus 46082. Okay, here this is my maximum value in my timer 0 mode 1, and I am just subtracting my this clock pulses. Okay, I got this one 19454. This I need to convert to the hex value 19454. This is my programmer 19 decimal value 19454. Okay, my hex value is 4BFE. Okay, my hex value is 4BFE. I'm just initializing with my TL0. TL0 is my lower byte. Lower byte is FE. Here this is my lower byte, this is my higher byte. 0xFE, and TH0 is 4B. Okay, 0x4B. Okay, here I have initialized my tmod value as well as my timer 0 value, and after that I need to start my timer. Next, after that I need to check whether my timer is overflow or not. Next, if it is overflow, I need to stop my timer and clear the overflow flag for the next operation. This is the program steps. Okay, I have the value now. Just I will copy these two values, tmod value as well as my uh, timer 0 value. This is my tmod value. Okay, here I'm just going to create one more delay function. There I will write this delay program. Delay, I will write underscore 50 millisecond. Okay, my 50 milliseconds delay. Okay, here I'm just writing my function name. Here there is no arguments. Okay, here semicolon, and same function I'm writing definition here. Okay, declaration is done, and I'm just writing my definition here. And here I have to write my tmod value is 0x01 and semicolon, and after that I need to copy this TL0 and TH0 already we calculated for the 50 millisecond. This TL0 and TH0 I need to add always semicolon in our C language statement. Okay, TL0 TH0 also done, and after the initialization of the initial timer with 5 millisecond, I am just starting my timer. TR0 is timer 0 start. Timer 0 start. Okay, next I need to check whether my timer is overflow or not. It will start counting from 4B FE to next FD. No, after that FE, AFF. Next here is 4C. Next after that 00 to FF 4D. Next again 00 to FF 4E. Okay, similarly it will increment until 4Fs. Okay, at that time my timer will be overflow. TF0 double equal to 0 semicolon. Okay, if it is 0, always I'm staying it here. Whenever it is 1 means overflow, I'm going to the next step. I'm going to stop my timer. TR0 is 0 and TF0 equal to 0 for the next operation. Okay, here I'm just clearing. Here my TF flag will set to 1 whenever this timer is overflow. Okay, after that here I'm just clearing for the next operation. Okay, this is the function to create the 50 milliseconds delay. This is the function for the 50 milliseconds delay. Okay, next here whatever my program statement, I just created my 50 milliseconds delay. Now I need to define my S bit here, port 1.5. Here I'm just using my 1 bit only, that's why I will just define S bit LED. I will going to connect the LED here, port 1 cap of 5. Okay, 1.5 I'm connecting LED. Okay, here while of 1, always I need to toggle, right? That's why I'm writing while of 1 continuously with 50 milliseconds. If you just read this statement, 1.5 continuously every 50 millisecond. Okay, continuously means we need to always write the infinite loop. This is my infinite loop. Okay, next here I am just writing my LED equal to 0. This is my, I am just toggling my LED always. LED equal to 1. with 50 milliseconds, right? That's why I will write this delay 50 millisecond my program. Here this API it will wait for 50 millisecond. Similar way, the second API after the LED set to 1 also, I am just waiting 50 milliseconds. Okay, I just written my program. I will just start compile. Okay, here I got the error. Okay, see here I am just missed the semicolon. Okay, again I will save my program. Again I will compile. See, there is no errors. I will go for the hex file generation. Okay, here I got the executable. Now I am going to connect LED across this 1.5 pin. Okay, I'm going to browse this is my initial circuitry, power supply circuitry, LCD, and here this is a reset circuitry. This is my crystal oscillator circuitry. And here right now I'm going to browse the LED, animated LED from the library. Okay, here I'm just taking the any one of the LED, and I'm going to connect to the 1.5 pin, and this cathode I will connect to the ground. This is my common cathode configuration. Whenever the logic 1 it will turn on, whenever the logic 0 it will turn off. Okay, initially in my program I'm just stopping my LED and waiting for 50 milliseconds, and again I am just turning on my LED and wait for 50 milliseconds, and again while of on means true. Okay, this process will continue forever. Always my LED is just blinking. Okay, if you just see my output program, okay, it's just loading. Let's wait for the respond. Okay, here it should be this LED should be blowing always. It should toggle. Okay, it's loading. Okay, mainly here as per the program we wrote. Okay, we had selected that also. This time playing that 0. Delay LED equal to S bit LED port 1.5. Here I have connected to 1.5. It's correct. And okay, here the ground is this is not the ground. Sorry. Okay, we did a mistake in the hardware thing. Okay, here it should be connected to the ground. Then only it should start working. Okay, this is my ground pin. I'm going to connect like this. Let's see. See here it's always toggling. Okay, this is my hardware design. Okay, here we previously we had connected here. That's why we see the issue, but there is no software issue. Okay, that's why we identified. Right now, if you see, it is always toggling with 50 millisecond as we created using the timers. Okay, right now in our timers, we used to generate max delay of 71 milliseconds. For example, if I want to generate 100 millisecond, so that this API I can call one more time, so that I can generate this is the 50 millisecond, the other one is again 50 milliseconds. Similar way, I can generate 50 millisecond. This is a 100 millisecond. Similar way, if I want to use the timers, if I want to generate 200 milliseconds, so that I can just take the 4 times. Okay, this is a 50 millisecond. Using these timers, I'm creating again 50, 50, 50, totally 200 millisecond. Okay, similar way, if I just build my program with 200 millisecond, this is my program for the 200 millisecond. Just I will stop and again I will start. Okay, see here it is just blinking with the some delay. Okay, compared to previous it is just blinking slower than the previous program. Okay, this is a way we can create how much delay we want using the timers. Okay, next one is the counter programming. Next, the second statement we'll try to read. Write a C program for counter 0 mode 1 with 16. Okay, this is also 16 to count the pulses and display the state of TL0 and TH0 registers on the LCD. Okay, this is a we need the LCD program. Okay, already we wrote the LCD program in the previous sessions. Okay, I just copied here so that I will just take the same LCD program. Why? Because I want to display this counts onto the LCD. That's why I'm just taking the LCD program here. I'm just replacing here. Okay, I have the LCD program. Just I'm just initializing my LCD. I'm just displaying welcome to my project. After some time, I'm just clearing my content, this content. I'm displaying YT Training Institute, and I'm always waiting here. Okay, let us test whether the same program is, if I just flash and check, it's working or not. Right now, this is the initial state only. I'm just flashed this YT Training Institute. Okay, right now my LCD program is working. I will just delete my LED thing. Okay, right now for the counting application, this LED is not required. Okay, here one thing we need to understand. Here I just connected to the port 3. Okay, my LCD is connected to the port 3, but in our counting application I should use this T0 pin. Okay, I want to give the external clock pulses to this T0, so that I can just use my timer 0 as the counter 0. Okay, that's why this LCD, this data pins I need to shift to here, so that I can use this 3.4 for the counting applications. Okay, here I am just reconnecting my LED to the complete data pins to the port 1 instead of port 3. Why? Because this port 3, this 3.4 pin I should use for the counting 0 to feed the external clock pulses. Okay, that's why I'm just deleting all the this data pins. I'm going to connect to here. Okay, from here I will just connect to the D0, next to D1, next to D2. Likewise, we should connect the 8 pins to here. Okay, 1.4 we should connect to the 1 minute. Okay. Similar way, we can just connect to the D4 and D5, D6, D7. Similar way, we can just connect all the pins, all the data pins to the all the data pins to the LCD. Okay, here the one more last pin. Okay, here I have connected all the 8 data pins to the LCD, and the this 3.4 pin, so that I can use for the counting applications. Okay, similar way I have to change my program to this 8090 is my port 1. Okay, previously it is B0 is port 3. Just now I changed my LCD data pins to the port 1. Let us check after changing the hardware and also program. I should display the same content onto the LCD. This welcome to my project and YT Training Institute, and okay, that's it. Okay, here I my LCD is started working, and right now I want to count the external pulses, and that external pulses I want to display onto the LCD. Okay, this is my program. Okay, here I have the LCD program. Here I will just let us write the while of condition. Why? Because I should always monitor the external clock pulses. If any external clock pulses received, so that I should increment, and I should always display onto the LCD. That's why I'm writing inside the loop. Okay, here again I will wait for some more time. Okay, again in 80 I am going to display this TL0. I'm going to display the TL0 content. Okay, this 80 I am going to display this TL0 content. TL0. This is my lower byte I am displaying. Similar way for the counting application, this TL0, TH0 act as a counting 0, and TL0 and TH1, TH0 will be act as a counter 0 right now. Okay, this is the TH0 equal to. Okay, right now I am just displaying the content TH0 and TL0. Okay, here I am going to display my content from here. Okay, here I will write LCD command of. Okay, here I will write my program tmod equal to 0x05. Here I just initialized with 05 means this is a counter 0 mode 1. If I go to this tmod register, okay, I want to use timer 0 as a counter 0, so that gate always 0, and this is a counter I am using timer 0 as a counter 0, so that I can just set this bit to 1, and mode 1 means 0 1. 0 1 0 1 means 5, and the lower nibble I am not using at all, so that I will just initialize with 0. 0 5. Okay, here the counter 0 mode 1, nothing but counter 0 mode 1. Okay, here and the programming concept is same. In case of timers or counters, the programming concepts are the same. Here I should initialize this TL0 TH0. Initially there is no clock pulses, so that I will just initialize with TL0 is 0, and for the counter 0, this two I am using for the counter 0 equal to 0x00. Okay, here I just initialized my timer with 00. This is my counting pulses, nothing but 0. This TL0 TH0 is the counting pulses. Okay, here I am using this timer 0 as a counter 0. Okay, whenever the any external pulses, so that then only this TL0 and TH0 will be incrementing. Okay, TR0 equal to 1. Here I just started my counter. Started counting, counting the external pulses. Okay, here I just started, and here I need to write some do while loop. Okay, do while loop. Why? Because I should display always to the LCD. Here I'm just writing do while loop. Okay, until it is overflow TF0, until this 16-bit counter is overflow, I need to just monitor TF0. Here I'm just checking whether my counter is overflow or not. Counter is overflow or not. Okay, if it is not overflow, I will always execute here. I'm just going to write this display program here. Here 0x80 is this one, 81, 82, 83, 84, 85 I will give. Okay, 85. Okay, similar 85 I'm just displaying my TL0 content. Okay, here if I want to display this onto the LCD, LCD always is the ASCII format. Okay, this registers contains the hex values, so that already we discussed in the ADC program. We just converted the hex value to the ASCII, and already I have the this program. Okay, this program is required to display onto the LCD. Whatever the hex value, if I want to display onto the LCD, this program is required. So that I'm just adding my this program after the main function. Okay, here I am just defining my declaring my program here. Okay, I declared my program, and yeah, okay, I declared my program. Here I should use those this additional API here, ASCII. Here I am just calling my TL0. Okay, TL0 I am displaying from this 85 onwards. TL0. Okay, here if there any external pulses, it will start incrementing this TL0, so that whatever the hex value I am going to display onto the LCD by using the this program hex to ASCII. This hex value I am just converting to the ASCII digits. That ASCII digits I am going to display onto the LCD. Okay, similar way for the C5 I will write the same way. The second row I am displaying this TH0. TH0 I am displaying onto the second row. Here if you see this TH0 I am displaying onto the second row. This is my second row address C0, C1, C2, C3, C4, C5. Okay, from here onwards I am just displaying. Let us check whether we are always counting and displaying onto the LCD or not. Let's see. Okay, right now I will just stop, and again I will start. Welcome YT Training Institute. Here I am just displaying with 0. Why? Because I don't have any external pulses as of now, so that it is displaying with 0. Okay, here I will just connect for the switch first time. Okay, later on we'll connect some external clock pulses also. Okay, I will just connect one switch, and from the switch I will try to give the pulses. I will explain clearly here. Okay, here I am just connecting one switch here, and the other node I should connect to the ground. Okay, here I connected to the ground. Okay, here whenever I just press the switch, this initial logic across this pin is logic 1, means 5 volts. Whenever I press this one, logic 0, okay, it will connect to the ground. Logic 0, 1 to 0, nothing but I'm just generating one clock pulses when I press this switch. Okay, here when I am going to press this switch, it should be blue, means ground. Okay, initially 1, and whenever I press this switch, I am going to increment this count across TL0. TL0 always increment from 0 to 255. Again, this is overflow, and this th value increment by 1. Again this will start from 0 to 255. Again I am going to increment value by 1. Okay, this is my counting application. Okay, similar way I'm just generating some clock pulses across the 3.4 pin so that it will start counting the actional pulses. See here, I'm just giving the actional pulses to here, and it is just started counting the actional events. And the similar way I can just provide the actional clock frequency so that it will count very faster way. Okay, here instead of this switch I will connect the some actional clock pulses so that here generators I can go. Here digital pulse, digital clock we have. Okay, here I will just connect to 3.4 pin. Here I will just give the some one hedge means it's very slow. Okay, let us see how it's counting. Okay, it's a one hertz frequency I'm giving to this one. I am always giving the clock pulses. See here, 1 hertz means it is very slowly it is incrementing. If I give the some 10 hertz or 100 hertz, it is very fast. Okay, I will give some 100 hertz so that it will start incrementing very faster. The clock pulse is the frequency is very much high. See here, 00 to 255 means FF. Once it is reached FF, it will increment by 1 by TH1. Okay, this is a normally the timer operations only. Just now the instead of the timer, it is always depend on the external clock pulses due to our T mode register we initialized with counter 0 and mode 1. That's why it is always 00 to 255 means FF 0 to FF. Once it is overflow and automatically this one value increment by TH1 value. TH0 will be incremented by 1. Okay, this will continue until 65 536 clock pulses. Okay, similar way I can give the max value also. Okay, here I will give the 1000 hedge. It's very faster way it will increment all the counting pulses. Okay, here similar way I can just given the 1000 hedges so that it will just count very faster way, and we are going to complete until 255, and this 255 and this 255 we are able to complete 65 536 pulses we are able to count in this mode. Okay, that's all friend today. Okay, I think we discussed about the two statements clearly, and also we written the program very effective way. Here the write and C program counter 0 mode 1 we just selected. Here similar way here until here the previous program only LCD program until YT training institute. Here I just displayed LCD command of 0x00 means I cleared the previous content. I'm going to display TL0 onto the this one in the first row TL0. If you see this LCD TL0 and TH0 second row. Okay, similar way I just displayed here, and from here onwards I am just displaying this TL0 content and TH0 content. Here 85 means I am going to display this TL0 from here. Similar way C5 means I am going to display this TH0 value from here. Okay, here I just used my T mode. I just initialized with counter 0 mode 1. Okay, next here TL0 initially my counting. If I just start my microcontroller, initially my counts are 0. Okay, if I am not giving any external clock pulses, initially my counts are 0. Okay, see here initially I initialized with 0 0. If I initialized with 10 10, so that the 10 value will be displayed onto the LCD. Here I started my counter, and here I am just checking until overflow I will be in this do while loop only. Okay, this will be incremented whenever any external clock pulses. This TL value and TH value be incremented by the microcontroller, and automatically just I am displaying this content onto the LCD always. Okay, from 85 address onwards I am just displaying these three digits, and similar way the C5 onwards these three digits I am displaying onto the LCD. This is the TH0. Okay, here I am just checking whether it is overflow or not. Okay, if it is overflow we need to stop our counter. Okay, here my I just stopped my counter TF0. I should clear the overflow flag for the next operation. Okay, this is a just program for the timer counter 0 for the mode 1. Okay, that's all friends.
Today we are mainly discussing about on serial communication. It is also one of the feature in our 805 microcontroller. And today we are mainly going to discuss what and all the important registers in our 805 microcontroller. By using these registers, how we are going to transmit the data from the microcontroller, how we are going to receive the data to the microcontroller serially, that we are going to discuss mainly on today. Computer transfer data in two ways, serial transfer and another is a parallel transfer. In case of parallel transfer, often 8 or more data lines are used to transfer the data to a device that is only a few feet away. Okay, mainly if I want to transmit 8 bit of data at a time, then we need 8 data lines. If I want to transmit 16 bit at a time, then we need 16 bit data lines. For example, if I want to transmit a data over long distance using this parallel communication, the cost is very more. That's why we are going for the serial communication. To transfer data to a device located in many meters away, the serial method is used. The data is sent one bit at a time. Okay, in case of serial communication, we have only one data line, and by using this data line, we are transmitting bit by bit at a time from the sender to receiver. And here mainly today we are interested to discuss mainly on serial transfer. And the serial data communication uses two methods: synchronous method transfer a block of data at a time, and asynchronous method transfer a single byte at a time. Okay, here we'll discuss mainly difference between the synchronous and asynchronous. Okay, mainly synchronous method. Okay, mainly the serial communication we are going to achieve using the both the methods. We can transmit using the synchronous method and also asynchronous method. Okay, synchronous method means this both sender and receiver both should be synchronized with the clock, then only I am able to send block of data at a time. Okay, here the clock is used to synchronize between the sender and receiver, then only I can send this block of data. And in case of asynchronous method, and here we need start and stop bit in between a byte of data. Okay, here in case of asynchronous method, we are not using any of the clock. We need start bit and stop bit to identify the start of the communication and end of the communication. And here this is the mainly difference between the synchronous and asynchronous communication. Here we are transmitting byte at a time, and here we are transmitting block of data at a time. This is the mainly difference between the synchronous and asynchronous, and we are mainly interested about the asynchronous communication today. Why? Because our 8051 follows the asynchronous communication. It is possible to write the software to use either of these method, but the program can be a tedious and long. And there are special IC chips made by many manufacturers for the serial communication. Few ICs are made with UART and few ICs are made with USART. In our 8051 IC made with this UART, Universal Asynchronous Receiver and Transmitter, and we are using asynchronous type of transmission. We are transmitting byte at a time with the start and stop bit. But few of the ICs having this USART, we are using the clock to synchronize between the this sender and receiver. Then only we are sending this block of data in our USART, Universal Synchronous and Asynchronous Receiver and Transmitter Communication. Okay, but we are mainly interested on this UART. Why? Because our 8051 follows this UART communication. That's why we are mainly interested on this UART. Okay, here we'll discuss the types of transmission. We have the simplex, off duplex, and full duplex. This is simplex, only one direction, one way of communication. For example, keyboard to the PC, it is a simplex communication, only one direction. There is no PC to the keyboard. Okay, this is a simplex communication. The other method is off duplex and full duplex are the both way we can communicate. But here in case of off duplex, only one at a time. I can send or receive only once at a time, one at a time. But in case of full duplex, we can send or receive both at once. These are mainly difference between the off duplex and full duplex. This is about the type of transmission in our communication. And we'll discuss about a protocol. What is the protocol? A protocol is a set of rules agreed by the both sender and receiver. How the data is packed between the sender and receiver, how many bits consist to a character, and when the data begins and end. Okay, this is all the terms telling about the protocol. And asynchronous serial data communication is widely used character oriented transmission. As we discussed here, asynchronous communication is a byte oriented, nothing but we are calling it as character oriented. Each character placed in between a start and stop bits, this is called a framing. Okay, this one byte in between we are placing one start bit, and stop bit in between we are placing this character. Okay, that's why we are calling it as completely one start bit data, and stop bit we are calling it as framing. And block oriented data transfer uses a synchronous method. Okay, if I want to transfer a block oriented data, then we need to use this synchronous method. And the start bit always one bit, and the stop bit can be one bit or two bits. Okay, in our UART 8051 microcontroller, we are using only one stop bit, and one start bit. Okay, here that stop bit can be one or two. Okay, in our asynchronous communication we'll see how the communication start with the always start bit with the logic 0, and always communication stop with the stop bit with the logic 1 bit. Okay, here the logic 0 telling us that communication is started, logic 1 means communication stopped. Okay, here in between I am just transmitting character oriented transmission. Our asynchronous communication is a character oriented transmission. Here I am transmitting a is my character, I am transmitting this data, and I need to represent with the binary 01000001, and this my hex value is 41. I just represented with the just binary 0100 is a 4, and 1 is 0001, and the LSB I'm just transmitting first and the until MSB, and this is my end of the communication. Okay, this is the way we are transmitting the data from the sender to receiver, always with the asynchronous method. Always we are starting the communication with the start bit, ending the communication with the stop bit, and in between we are placing the data. This is our asynchronous communication. And here extension to the start and stop bit, assuming that we are transmitting a text file of the ASCII characters using one stop bit, we have total 10 bits for each character. Okay, here if you see 8 bit of the data and 2 extra, one start bit, one stop bit, we are transmitting 10 bits in each transmission. That's why here this gives you 25% of overhead, that is 8 bit character with the 2 extra bits. Okay, here completely out of this 8 bits we are adding 2 more extra bit. That's why we are creating 25% of the overhead in our serial communication. In some system, in order to maintain data integrity, polarity of the character is included in the data frame. Okay, here in our data frame now we consider it as 10 bits. Okay, if I add the parity also one of the bit, then we are considering it as totally 11 bits. Okay, UART chip allows the programming of the parity bit, odd, even, and no parity. And finally, if I use the in few UART communication, we might use this parity also. Totally 11 bit of UART communication. And here we'll discuss on the data transfer. Okay, here we'll discuss mainly difference between the bits per second and baud rate. Okay, here the bits per second is the number of bits transmitted per second is the bits per second. Here the baud rate is number of symbols transmitted per second is the baud rate. Okay, whenever the one symbol equal to one bit, then bits per second and baud rate are the same. Okay, these are mainly difference between the bits per second and baud rate. Bits per second is the number of bits transmitted per second. Baud rate is the number of symbols transmitted per second. Whenever the symbol one symbol equal to one bit, then both bit per second and baud rates are both are same. These are mainly terminologies in our communication. Okay, next we'll discuss about the RS-232 standards. For example, if I want to transmit a distance over a long distance, then we need this RS-232 universal standard voltage logics. A interfacing standard is RS-232 was set by the Electronic Industry Association EIE in 1960. This is a universal standard. If I want to communicate between the microcontroller to the PC or the microcontroller to the external any serial communication devices, then we need this RS-232 standards mandatory. Okay, the standard was set long before the advent of the TTL logic family. Its input and output voltages are not TTL compatible. Okay, here usually the RS-232, a logic 1 represents by -3 to -25 volts, and while a logic 0 bit is +3 to +25, making -3 to +3 is undefined voltages. Okay, this is the RS-232 standard. Logic 1, our TTL logic 1 means 5 volts, and in RS-232 it is converting like -3 to -25. In our TTL logic 0 means 0 volts, it is converting like my +3 to +25 volts. Okay, this is the mainly standard we should follow if I want to transmit the data over a long distance of communication. Okay, this RS-232 logics we need to just understand. Logic 1 means our microcontroller logic 1 means 5 volts, and we are representing and we are converting it as -3 to -25, and logic 0 volts we are converting it as +3 to +25 volts. This is the standard. Okay, if I want to convert to this standard, we need max 232 IC that we will discuss in the next slides. Okay, how we are going to convert to the TTL to the RS232 standard, that we are going to discuss in the next slides. Okay, here is our DB9 connector. Okay, normally if I want to connect to the PC, this DB9 mainly we are using. Since not all the pins are used in PC cable, IBM introduced DB9 version of the serial IO standard. Okay, DB9, this is introduced by IBM, and here we have the DB9 means 9 pins, and here mainly in our 805 and microcontroller we are using only the 3 pins: receive data RxD pin, TxD pin, and ground. Only 2, 3, and 5 pins are we are using, and other pins are control pins. Here data carrier detect. For example, we need to test the cable whether it's working or not using this DCD, data carrier detect, and this is for the data serially. If I want to receive, I can use this pin. If I want to transmit the data serially, I can use this pin. And data terminal ready, for example whether the each microcontroller or PC whether it is ready or not, by using to identify by using this signal. And signal ground. Okay, this is for the to connect the common ground, we are using this pin. And data set ready, for example if I want to transmit the data ready between the sender and receiver, mainly this signal can be used. And requested to send the data, RTS means requested to send the data from the sender to receiver, mainly this signal can be used. Clear to send, for example whatever the previous this is for the next data send, we are using to this clear the previous data, so that this clear to send. And ring indicator, in few of the communication we saw some ring indicator without data exchanging, then we will get the ring indicator before the data transmission, then we will get this ring. In case of in our telecommunication we used to get the ring before our communication. This is the mainly to identify the ring. Okay, this is mainly our DB9 standard in our communications. But in our serial communication we are using mainly RxD pin, TxD pin, and ground pin. Okay, this is our RS232 standard. And here we'll just talk about the DTE, means data terminal equipment, either microcontroller or the PC, we are calling it as data terminal equipment. Data communication equipment we are calling it as modems. Okay, it will just convert from the one format to another format, then we are using it as modems. Okay, here if you see, always the DTE to another DTE, always the cross connection. Okay, for example the one microcontroller is sending the data, other microcontroller should receive the data. And similar way other microcontroller is sending the data, the other microcontroller should receive the data. These are mainly the cross connection between the TXD or XD, and the common ground between the two DTEs, data terminal equipments. And as we discussed here, if I want to convert the TTL to the RS232 logics. Okay, if I want to transmit over the long distance communication, this DB9 connection will be used, and a similar connection will be used at the receiver side. Okay, here microcontroller max 232 DB9. Again, the receiver end also I should use the DB9 pin. Again, max 232. Again, I will connect the another microcontroller. Okay, this is the way of communication between the microcontrollers or the PC. From here also we can connect to the PC. Okay, here we need to understand what is the RS232 logics. For example, if I want to convert the TTL to RS232 logics, as we discussed here, for example, this logic 1 should be converted to the minus 3 volts to the 25 volts, and the logic 0 means 0 volts should be converted to the plus 3 to plus 25 volts. Mainly here we are using the max 232 IC. Here the 11 pin I am connecting to the TXD pin, 12 pin I am connecting to the RxD pin. And here we have the two conversions. We have one TTL2 and RS232. Again we have 10 and 9. For the other UART we can connect this 10 and 9, and 7 and 8 we can connect to the another DB9 pin. Okay, here we have the in max 232 we have the two TTL2 two RS232 conversions. For example, in our 8051 we have only one UART. We are using this 11 and 12 pin and 14 and 13 pin. Okay, here this TTL inputs I am giving it here, and it will convert to the RS232. And again this RS232 TTL it will convert it will convert the both the ways, vice versa. Okay, it will convert to the TTL to RS232. Whenever I am transmitting the data, whenever I am receiving the data, it will convert to the RS232 TTL. This is a both way conversion. Okay, it will convert from the this voltages to this voltages. Logic 1 it will represent as minus 3 to minus 25. Logic 0 0 volts the TTL side, it will be converted to the plus 3 volts to 5 volts. These are mainly to convert the TTL to RS232 logics. RS232 TTL, we are using this max 232 IC. Okay, based on by using these capacitors only, we are converting the voltages to the minus 3 to minus 25 volts and plus 3 to plus 25 volts. Whatever the TTL logic 0 to 0 means 0 volts, logic 5 means 5 volts, and these TTL logics we are converting to minus 3 to minus 25 plus 3 to plus 25 by using this max 232 IC. Okay, here we have the 8051 microcontroller. We need to connect this max 232 IC. At the end we need to connect DB9 connector. Similarly, if I want to connect another microcontroller, then we need again DB9 connector max 232 IC. Again at the end we need to connect the microcontroller. This is a way we are communicating using the standard or RS232 communication. And here we'll discuss the standard baud rates. Is a 110 is the baud rate, and 150, 300, 600, 1200, 2400, 4800, 9600 is the universal standard, and 19200 also one of the universal standard. And here these are the standards. If I want to communicate with the PC, always we should set this these many baud rates, but usually we are using this 9600 baud rate, and we'll see how we are going to calculate the baud rate in our serial communication. Okay, here in our external communication we are always giving the 11.0592 megahertz, and this is our machine cycle frequency, always divided by 12 is my 921.6 kilohertz, and this is my UART is dividing by 32. The finally I will get the 28800 hertz to the serial communication, to the UART communication. Okay, this is my UART frequency. If I want to operate with the specified baud rate, mainly this UART communication will be used. Okay, mainly for example, if I want to communicate with the any device, first we need to set the baud rate, and after that we can able to communicate infinite times. Okay, here if I want to calculate the particular baud rate, for example, this is my frequency, final frequency to the UART 28800. Here I am dividing with 3, then I will get the 9600 baud rate. Okay, here I am just dividing with the particular value so that I will get the baud rate. Okay, here frequency divided by I'm just dividing with the 2. Here I am telling us that minus 3 I need to load with the th1 value. Okay, here we need to discuss about the auto reload mode. Whenever this timer is overflowed, okay, here we'll discuss about the auto reload mode. Whenever the THX value is overloaded, TLX value is overloaded, automatically this TH1 value will be copied to the TL1 value. Okay, this is the mainly working of the auto reload mode. Here I am loading the TH1 value is FD. Okay, we'll discuss more on once again. Okay, here this FD minus 3 means here FD to FE, FE to FF, FF to 0. My timer is this TL value will be loaded. Okay, here the th value always loaded with ff. Whenever the tl value overflowed from the fd to 00, fd to fe, fe to ff, ff to 0, my tl1 value is overflow, automatically this th1 value will be copied to the tl1. Okay, using this fd only. Okay, here minus 3 means fd. Why? Because fd to fe, fe to ff, ff to 00 overflow, th1 value will be overflowed. Okay, here that's why we are loading with th1 value with minus 3. Okay, if I am dividing with the 12, I got the 2400 baud rate, that's why I am always minus with the 12. Okay, f4 to ff is 11, and ff to the 0 totally 12, that's why I am always doing the minus 12, nothing but f4. Here similar way divided by 24 means e8. Okay, I will show you another method to calculate the this th1 value, and in the next slides. Okay, here this is for the understanding. Whenever I am just dividing with the 3, I will get the 9600 baud rate. Whenever I am dividing with the 12, I will get the 2400. This is my normal frequency at the UART 28800, and if I divide by 3, and that minus 3 value should be loaded to the FD, or the converted hex value is minus 3 nothing but FD. This is another conversion. Minus 2 minus 3 negative value, if I just load it to the positive value is FD to the th1 value. We can also load the minus 12 to the th1 value. This is also another method. Other way we can just load the FD. Minus 3 also we can load the decimal value, the x value is FD. See here, the 9600 is minus 3 FD, and 4800 is a -6 FA. Here we can remember for the 9600 is FD. Okay, mainly in our all universal communications we are using this 9600 baud rate. Okay, here we'll discuss about the SBUF register. Okay, right now we'll be mainly discussing about the registers of the serial communication. What are all the important registers? This is the SBUF serial buffer. Okay, it is a 8-bit register. For example, this is a mainly if I want to transmit the data from the microcontroller to external device, always we should place the data onto the SBUF. Then SBUF will take care of the transmission from the microcontroller to the external device. Similarly, if I want to receive the data from the external devices, we should receive through this SBUF register. Okay, here we'll just read the SBUF is the 8-bit register used solely for the serial communication. For byte data be transmitted via TX line, it should be placed SBUF register. For example, if I want to transmit any data from the microcontroller to the external device, we should place to this SBUF register. The moment a byte returned to the SBUF, the frame with the start and stop bit and transferred serially via TX line, and it will be framed with start and stop bit, this 8-bit data, and it will add the one start bit and stop bit, and it will be transmitted from the TXD line. And similarly for the RX also, SBUF holds the byte of data when it is received by the 8051 RxD line. When the bits are received serially via RxD pin, the 8051 deframes it, eliminating the start bit and stop bit, making the byte out of the received data, and then it is placed to the SBUF. See here, mainly if I want to transmit the data, we need to place into the SBUF. Then 8051 automatically add the start and stop bit, and it will transmit via TXD line. Okay, in case of reception, okay, it will deframe the this start and stop bit. Finally, whatever the 8-bit data will be copied to the SBUF. These are mainly working principle of this SBUF. Then we will program how to transmit the data and also how to receive the data. And this is a working of the SBUF register. Next is the SCON register. Here it is a 8-bit register. It is a byte addressable. It is a bit addressable. Okay, here bit or byte addressable, both we can access. Here we can access bitwise or bytewise. This is a byte addressable only, and this is a bit or byte addressable. And SCON is a 8-bit register used to program start bit and stop bit and data bits of data frame, and among data bits of data frame among other things. Okay, here mainly it is a 8-bit register. Okay, here SM0 SM1 is the mode selection. Okay, we'll discuss in the next slide. We have the 4 modes: mode 0, mode 1, mode 2, mode 3 in our serial communication. This SM2 is a multi-processing mode. Okay, here currently this we can make it as 0. We have using the single processing mode. And REN receive enable. For example, if I want to receive the data from externally, this should say, bit should be set to 1. And the TB8 or B8, as we discussed the parity bit, always I am storing it here, the extra bit whatever we discussed here, right? The parity bit always 1. Okay, one extra bit, that's why here this is the TB8 RB8 is the one extra bit in our serial communication. This is a parity bit, we are storing it here, TB8 and RB8, 0 to 7 bits we are transmitting the data. And if I want to use the 8 bit also, we can use this TB8 and RB8. Okay, currently for the parity I am not using it, I am just setting to 00. And TI or this is a transmission interrupt and receiver interrupt. Whenever the successful reception, my RA flag set to 1. Whenever the successful transmission by the microcontroller, this TA flag will set to 1. These two flags set by the hardware. For example, when I am placing the data to the SBUF, once this data is successfully transmitted, this TA flag rise to 1. Okay, similar way, whenever the successfully received by the SBUF, then this RA flag will be set to 1. Okay, these two flags will set by the hardware. We can also clear, this is the read write flags. We can from the software we can clear these flags. Okay, for example, for the mode selection we can go to the next slide. Here 00 means 8-bit shift register mode. Here the clock always fixed, oscillator divided by 12. And 01 is 8-bit UART and set by the timer 1. Okay, here the mode whatever the baud rate and frequency is set by the timer 1. Okay, here the variable baud rate, here the mode 1 and mode 3 are the variable baud rate, and mode 0 mode 2 are the fixed baud rates. Okay, here always 8-bit UART set by the timer 1. Here the 9-bit mode means always here we are using the parity bit also in case of mode 2 and mode 3. Okay, here always I am using a one start bit and one stop bit in our serial communication. That's why I'm always using this one. Okay, always mode 1 means 0 1. Okay, I want to just use the for the communication. Okay, I am always using the mode 1. 0 1 is my mode 1, and this multi-processing mode I am setting it as 0. For the receive enable always we should set to 1. If I want to receive the data I am always should set to 1. 0 1 0 1 means 5, and this t-bit or bit for the parity only we need to use, otherwise I am just setting to 0 0 only. And this ta and ra initially I am setting to 0. Whenever the successful transmission this will set to 1, whenever successful reception it will set to 0, it will set to 1. Okay, initially I am making 0 0. Okay, if, we should initialize with 5 0. For example, if I want to use the mode 1 we should initialize with 0 0 1 0 1 4 zeros. The lower 4 bits I am filling with 0, and mode 1 means 0 1 is my mode 1, and this my for the multi processing mode SM2 always I am initializing REN I am setting to 1. Okay, here always 0x50 is my, always we should load with SCON 0x50. Okay, we should load this SCON with always mode 1 with one start bit and one stop bit with 8 bit. Okay, always we should load with 0x50. Okay, similar way we'll discuss if I want to double the baud rate, mainly this pcon register can be used. Okay, here the SMOD mainly here we'll discuss. Okay, this is the one method for the baud rate calculation. Divide by 3, then I will get the 9600. Then I can directly load this th1 value with -3. This is also one method. The other method, what is the corresponding hex value, also we can load. This is the one method of calculation. Similar way we can calculate using this formula, baud rate equal to 2 power s mod. Okay, currently initially this s mod will be 0. 2 power 0 is 1 divided by 32 is my UART division. This my 12 is my timer division. This my machine cycle division. 12 is my machine cycle division, and 32 is my normally UART division. Okay, here and F oscillator means nothing but 11.0592 megahertz, and 255 minus th1 value, max value is 255. That's why I'm always subtracting with th1 value. Okay, here if I want to calculate the th1 value, always for example if I want to get that 9600, so that I can calculate the th1 value, we know already the frequency, we know the baud rate. S mod always 0 initially. Okay, for example if I want to double the baud rate, this S mod I can set to 1. For example if I am setting this one to 1, 2 power 1 is 2. I am multiplying whatever the existing baud rate with 1 into 2. Okay, 9600 multiplied to I will get the 919200. Similar way 4800 multiplied to 9600. 2400 multiplied to 4800. 1200 multiplied to 2400. Okay, if you see here S mod is 1 divided by 2, our UART is doing divide by 16, and S mod is 0, it is dividing with 32. That's why we are getting this frequency. Due to that we are doubling the completely baud rate based on this frequency as we calculated here, right? Frequency divided by 3, then I am getting the 9600. That minus 3 value I am loading with th1 value. Okay, here similar way we can calculate using this formula. Okay, if I am just using that S mod is 1, so that I can calculate the corresponding th1 value, so that we can generate the respective baud rate. Okay, here general flag 0, general flag 1 are these two are general flags, and always I am this for the future flags always I am setting to 0 0. And here the PD power down mode, for example if I want to, normally our power consumption is 5 volts. If I want to reduce to 2 volts, this power down mode can be used. Okay, this is ideal mode if I want to put my processor to the sleep mode, so that I can use this mode. Okay, if I want to reduce the power consumption to the 2 volts, so that I can put my microcontroller to power down mode. These two are power saving modes, and we have, by using this pcon register, we have the power control as well as the baud rate doubling. We have these many facilities in our pcon register. These are mainly working principle of the pcon. Okay, here we'll discuss mainly on the how to program the, if I want to transmit a one character serially, so that we need to program these many steps. First one, always we need to load my t mod with the 8-bit auto reload mode. Okay, always timer one we are using here. See here, th1 always our baud rate depends on the th1 value. That's why I'm always using the t mod register is loaded with the value 20. 20 means 8-bit auto reload mode, timer 1 auto reload mode, mode 2 timer 1 auto reload mode to set the baud rate. And the th1 value should be loaded with the some value to set the baud rate. For example, fd is nothing but 9600. Okay, here I will just load with the fd. Now scon register, as we discussed now, with 50. Okay, here we have loaded with 50. This is a mode 1, and here ren bit I'm setting to 1. Here re1 bit I'm setting to 1. Okay, that's why I'm always selecting with the mode 1 with 8-bit one start bit and stop bit. And we need to start the timer 1. We need to use the tr1 bit and place the data into the sbuff and check the ta flag whether it is raised or not. If it is raised, then we need to our sbuff, whatever the content is successfully transmitted, we need to clear for the next transmission. Okay, here mainly this t mode register we need to initialize with 20. And th1 value, whatever the baud rate, whatever we calculated here, fd I can load it. And the next scon always 50. And I can start the timer and I will place the data. Okay, for example, in case of transmission, first we need to place the data into the sbuff, and after that I can check whether the transmission is completed or not by using this flag. Okay, we have this ta flag. Whenever the successfully transmitted whatever the placed data, then this will be raised to 1. Okay, whenever it is raised to 1, my content is already transmitted, so that I can clear for the next transmission. Okay, similarly I will write the program as we discussed here. Okay, I'm going to write the same program. First we need to initialize the t mode register with the 0x20, nothing but timer 1 mode 2 is the auto reload mode, mode 2 auto reload mode. Okay, next one is scon. We should load with scon equal to 0x50, nothing but 8-bit data, 8-bit data, one start bit, one start bit, one stop bit. Okay, this is just extension of the program. Okay, next here I can load the th1 value before the scon. Th1 equal to 0x fd. Th1 value 0x fd is nothing but 9600 baud rate, 9600. This is my 9600 is my baud rate. Here see, I just loaded with the th1 value with 9600. fd is nothing but 9600. Okay, next after that just initialize the t mode with the 8-bit auto reload mode with the timer 1. And after that I loaded with the this th1 value. Next after that I load with the scon. Scon is 0x50, means nothing but 8-bit data, one start bit and another is stop bit. Okay, next scon also loaded with the value, and after that I need to start the timer 1. Okay, tr1 equal to 1 means I started my timer. This is just I have initialized all the register with the 9600 baud rate, and I started with the my timer is started. Now I can place the data to the sbuff. If I want to transmit the data, here I am just writing the while of one loop. I want to transmit the data cyclically infinite times. That's why I am writing this open and close. Okay, here while of one I am writing within this loop I am writing. Here I am placing the data to the sbuff equal to, here I am just placing a character a, nothing but 41 I am placing. I placed the data, and I need to check whether my transmission is completed or not. Okay, here I am just checking my ta flag. Okay, whenever my transmission is completed, then automatically this flag set by the controller to 1. Okay, until 1 I am waiting here, and after that I should clear the flag for the next transmission. Okay, here as per the program steps I was written here. Okay, here see, I just placed the data in this step. I placed the data, and here I need to monitor the ta flag. Whenever the ta flag set to 1, nothing but my transmission is completed. If it is 0, I am always waiting here. If it is 1, this will be set by the hardware. Whenever it is 1, my whatever the placed data is successfully transmitted. I am just waiting here. Once it is successfully transmitted and I'm going to the next step, I'm clearing the 0 to the next transmission for the next transmission. This will be done by the software. clearing will be done by the software and set by the hardware. Okay, this is the mainly just program for the transmission. Okay, similarly we'll build and we'll generate the executable, and once the executable is generated we can just flash it here. Okay, here I will just remove the LCD. Why? Because this 3.0 and 3.1 pin we are using for the communication, that's why I just removed the LCD. Okay, here I can connect the virtual terminal is my serial communication. Okay, this TX pin I should connect to the RX. Similar this TX pin I can connect to the RX. Okay, this is a reverse connection. If microcontroller is transmitting, our terminal is receiving. This is nothing but our PC, and here this is transmitting, I should receive. Okay, this is the just communication connection, and just I will flash, will check whether we are able to receive the same this continuously a value or not on the onto the this terminal 11.0592. Okay, in case of serial communication we should change this frequency always 11.0592 megahertz, and I should select the same executable as we generated now. Then I have the same executable 11 1036, and just I am running with the same executable, and I should transmit the A always infinite times. Okay, as we written the program while of one is infinite times, I'm just placing the A value and I'm checking whether it is transmitted or not. If it is transmitted, I'm just clearing for the next transmission, and again I will place the A and I will check whether A is transmitted or not. If transmitted, I'm clearing. Okay, this will continue forever infinite times. That's why for infinite times I'm transmitting value way. This is my output of the program. And similar way, if I want to write for the reception, and all the program steps are same, only the these steps are different. Okay, here we need to check the whether it is completely received or not. If it is received, we need to place the data to the particular register, and after that we need to clear the register content. Okay, if, in case of this for the TX program, now I am going to write for the RX program. Okay, the baud rate is always same, and the whatever the reception is different. Here I need to check the whether it is received successfully or not. Whenever this flag set by the hardware to 1 means successfully received. Okay, until successful reception I am waiting here. Until successful reception I am waiting it here. Okay, once it is received, I am going to available data at the sbuf. Okay, I am going to copy to the port 1. Port 1 I am just copying the data, whatever the received data I am copying. Okay, whenever this RA flag is 1, I am going to the next step. If the RA flag is 0, there is no successful reception. Until successful reception I am waiting here. Once it is received, I am just copying to the port 1, and here I am clearing for the next reception. Okay, this is only the change in the reception. Okay, just I'm building the thing. I'm just getting okay, here this just for the comment I written. Okay, just I have executed my executable, and right now I'm just flashed the same executable with the same frequency, and just now I'm executing with the same one. Okay, here I need to transmit some data that should be visible here, right, in port 1. Okay, I will take some LEDs. Whatever the received data, A means 41 I should receive, right? The similar way I can take the LEDs, group of LEDs. I will check whether my 41 value is received or not. Okay, here I am just taking the green LEDs, a group of LEDs. Okay, here port 1 I am connecting to the here, and port 1.0, port 1.1, port 1.2 should connect to here, port 1.3, port 1.4, port 1.5, port 1.6, port 1.7. Next, the right side completely we can connect to the ground terminal, ground, and similar way just we can connect to the grounds. Okay, now if I just transmit from the PC, I should receive the data using this program. I should transmit to the this port. This port 1 I should transmit the data. I should place the data across the port 1. Okay, if you see the if you understand the program, once the successfully received from the other node, Okay, the other node nothing but PC. From the PC I'm transmitting the data. Once it is received successfully, I'm just copying the data to the port 1. For example, if I just transmit the A character from the external PC to the from the terminal to the PC, then the A value should be written here. A is nothing but 0x41. 0x41 means 0100 and 0001. Okay, this value should be observed across the port. If I just transmit the value B, then I should see 42 value. Okay, similarly we'll check whether same data is coming or not. Okay, here I am just executing the thing. Here this is the terminal, we can give the data. Here from the keypad I am typing capital A now, and my port data should be set to 41. Initially my all the port pins are logic 1, that's why all the LEDs are glown now. Okay, if I just send the 41, nothing but only the 41 should be displayed. Here I am just sending the character A, nothing but 41. Only the 0100 and 0001, only second LED and last LED should be glown. Okay, if I am just giving the capital A now from the keyboard, okay, see now it is 41. Capital A I have given, that is received by the microcontroller. What is the received data placed across this port 1? Similarly, if I type the B and 42 means this is a second LED, here also this second LED. From the last to second, this second LED 42 means this second LED, here this should enable. If I'm just sending capital B now, see 42 nothing but 0 0 1 double 0 0 0 1 0. Okay, nothing but 42 is displayed. Okay, this is a nothing but whatever the received data, this is a program for, I'm just waiting until one successful reception. I'm just copying the data to port 1. Whatever the received current data, I'm just copying to port 1. This is a mainly program for the RX. Okay, similarly we written for the TX also. Okay, this is for the RX program, just we need to remember. Okay, just I will copy the RX program and I will go for the TX also. How we written for the TX? Okay, this is for the TX program. TX program, this for the RX program. Just we want to just check first. In case of TX, we should place the data to the SBUF and check whether the successfully whether this A is transmitted or not. If successfully transmitted, then I am just clearing this TA flag. This for the transmission. Okay, first we need to place the data. After that we need to check whether it is successfully transmitted or not. If transmitted, clear. Okay, this for the transmission. In case of reception, first we need to check whether the successfully the data is received to the SBUF or not. If RA flag to set to 1, my I received the successfully data. Otherwise I will wait here only. Okay, once the data is received, I am just copying to the port 1 and I am clearing for the next reception. This is a mainly working principle of the communication. Okay, here I am just setting the baud rate only the once. Here see, I am just initializing the baud rate once, then it will be forever. Okay, to the until successful communication, always I am just loaded with this baud rate. Okay, the always baud rate should be set only the once, this will be retained forever. This is a mainly working principle of the serial communication. Okay, thank you friend.
Today we are mainly discussing about on serial communication programming continuation. Already we discussed about the what and all the important registers in serial communication and how to transmit the data serially and also how to receive the data serially in the previous session. Today we are mainly going to take the two problem statements that we are going to solve using the embedded C programming. And the first program is write a C program to receive bytes of data serially via serial port and put them on LCD. Set baud rate at 9600, 8-bit data, one start bit and one stop bit. Okay, already we know the steps for programming for the receiving the data, and before that we need this LCD programming. Okay, first we will add the LCD programming. This already we learned in the previous sessions. That's why I'm going to take this LCD programming directly from the previous session. Okay, this I am just copying from the previous session and I am trying to paste in this completely in the project, and I have built my project. Okay, here if you see here, always we are just displaying welcome to my project in the first time, and after some time I'm just clearing the welcome to my project. I'm after that I'm displaying YT Training Institute onto the LCD. Okay, here mainly in our program statement, we need to receive the data serially via serial port and put them on to the LCD. These are mainly our program. That's why we have taken this LCD program from the previous session, and right now I have executed. I does not see any errors. Okay, here I am going to display onto this LCD. Okay, right now here I have some initial circuitry. Okay, here we have the power supply circuitry and reset circuitry, crystal oscillator circuitry, and here our LCD interfacing. Okay, right now I have interfaced with the same LCD program. Just I am playing. Okay, here welcome to my project YT Training Institute. This is my LCD program, and here in my problem statement, always telling us that we should receive the data. Okay, that's why we should always use this port 3.0 pin if I want to receive the data. For the serial communication, we should use this 3.0 and 3.1 pin. That's why this data pins of LCD we need to move to the port 1 from the port 3 to port 1. Okay, that's why I'm going to change in the programming as well as in the hardware. Okay, here I'm just mentioning to the 90 means nothing but port 1 address. Here I'm changing to port 1 address due to here I'm just using this port 3 for the serial communication. That's why I'm just moving the data pins of LCD to the port 1. Okay, here I just build my code. Similar way we need to change the hardware design as well. Okay, here we need to delete the existing connections, and we should connect to the port 1 instead of port 3. Just I am deleting all the data pins of the LCD, and I am going to connect port 1 to the completely data pins. Here I am just connecting to the D0, next one D1, next one is D2, next one is D2 is connected, and 1.3 I am connecting to D3, 1.4 I am connecting to D4, 1.6 I am connecting to D5. Next one is D6 and D7. Okay, just I have changing my connections, and as per program I'm just connecting my hardware. Okay, here if I just play, I should display the same text onto the LCD. Welcome to my project YT Training Institute. Okay, now I can connect my serial communication to the external devices by using this 3.0 and 3.1 pin. Okay, here I am going to connect one. Here we have the virtual terminal. Here we have one virtual terminal. For example, if I want to connect any external serial devices, this is the one of the serial device. Here we can transmit the data from this device and also receive the data to this device from the microcontroller. Okay, here always we should connect to the cross connection. If microcontroller is transmitting, this virtual terminal is reception, and here I am receiving virtual terminal is the transmission. Okay, here if you just double click, always initial baud rate is 9600, 8-bit data, one stop bit, start bit always only one bit. Okay, here I just interface the this virtual terminal also to the microcontroller. Right now we should write the programming for the serial reception. Already we know the steps for the serial reception. First we need to initialize with tmod with 20 by setting this timer 1 mode to 8-bit auto reload mode. Okay, first we should initialize tmod with 20. Next th1 we should set the baud rate. If the th1 value is fd, then we can generate 9600 baud rate as per this baud rate calculations, so that I can just initialize with th1 with fd. Next scon with 50. Okay, as per the problem statement, 8-bit data, one start bit and one stop bit, nothing but scon is 50. Next I should start the timer. Okay, until these four steps we set the baud rate of the serial communication as per the 9600 baud rate, 8-bit start and start bit, one stop bit and one start bit. Okay, next here we should wait for the data reception. Okay, we should monitor this RA flag. When this RA flag is 1, our data completely received into this SBUF. Okay, whatever the received data we should display onto the LCD, and after that we should clear the RA flag for the next character reception. Okay, similar way we'll write the programming. Okay, here in the first, why? Because the baud rate should be initialized only once. That's why I'm writing after the main. This st tmod equal to 0x20 is my this timer 1 mode 2 auto reload mode. Auto reload mode. Okay, next one is th1 equal to 0xfd. Okay, nothing but 9600 baud rate. 9600 baud rate. Okay, now I have set my baud rate. Next, I am just initializing my scon equal to 0x50. Nothing but 8-bit data as per my problem statement. 8-bit data, one start bit, one stop bit. Okay, this is my initial configuration. Now I can start my timer. Timer 1 equal to 1. Timer run 1 equal to 1. Just this is to set my baud rate with the 9600 for the serial communication. Okay, due to this just initialization. Okay, just as per my steps 20 th1 ifd and scon is 50, and I started my timer. Okay, here I should check always. Here I have to check in my while one program I can write my always I should monitor my RA flag. If RA flag is 1, my data received successfully into the SBUF. Okay, similar way we can write, and after some time I will just clear my YT Training Institute. I will just clear and I will start with 80. Whatever the received data, I'm going to display the data from 80 onwards. 80 means the first row. Okay, after YT Training Institute, I'm just after some time, I'm just clearing this complete text. Whatever the received data, I'm just want to display from the 80. That's why I have given after clearing, I'm just given the address of 80. From 80 onwards, I'm going to display the received data here. Here I am just typing RI double equal to 0 semicolon. Here whenever my RI flag is 1, here as per my programming statement, whenever it is raised means 1. Whatever the successfully our microcontroller is received the whatever the serial character successfully to this SBUF register. Okay, that's why I'm just sending my whatever the received data to the LCD directly. Okay, LCD data. Okay, here I can just pass the SBUF data. Okay, SBUF contains whatever the received characters. If the successfully data received, I am going to come to the next step. Okay, I am just always waiting here until successful reception. Until successful reception. Okay, once it is received successfully into the SBUF, I'm just passing to the LCD data. Okay, here whatever the received data always ASCII character. What I am going to display onto the LCD also always ASCII characters. That's why we don't want to convert any conversion. That's why I'm just directly displaying onto whatever the received data to the SBUF. I'm just transmitting to the LCD. Okay, next one I will just clear my RI flag for the next reception. Okay, here I just written my program as per the just as per the problem statement. If you just read whatever the received data serially that we are going to display onto the LCD with this baud rate. Okay, if I want to set this baud rate, I should always feed the frequency 11.0592. Okay, as we discussed in the previous sessions. Okay, here the baud rate should be always whatever the clock frequency should be always 11.0592. Then only we can generate this fixed baud rate 9600 baud rate. That's why I'm setting my clock frequency always 11.0592. Okay, that's why we can generate that exact baud rate. Okay, here welcome to my project YT Training Institute. After that, I will clear everything. I will start pointing this 80 location, 0x80 location. Okay, 1 minute. We should compile once again. I think the changes are not reflected. We should clear the YT Training Institute, and after that we should see the empty screen. YT Training Institute. See, right now we are able to transmit from the here. Okay, from the hyper terminal, I am transmitting the data. Microcontroller should receive. Uh, Whenever the successful data is received, then it should pass to the LCD. Just now I am going to type ABCD from the terminal. Whatever the typed data, it should be received by the microcontroller. That received data should be displayed onto the LCD. Okay, let us I'm just going to write the A from the keyboard. Capital A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. Okay, until 16 characters I have displayed, and my address I should change to the A C0. Then only I can display onto the second row. For example, if I am just typing now, it won't display. Why? Because the address always increment by one. Whenever I am adjusting new character to the LCD, always address should be incremented by one. Now I am just displayed 80 to 8F, 16 characters. Now it will be 90. 90 means there is no address to the LCD. Okay, that's why we should give the C0 to display the 17 character. Okay, similar way I should display the 32 characters. Once these 32 characters are overflow, then I should display again to the start. Okay, here that's why I'm going to take one variable to check how many characters are received. Just I'm going to take one more variable here and assign it char I. Okay, here I'm just always increment. Here every successful reception I'm going to increment this I value by one. Nothing but here I'm just incrementing whatever the received characters I'm just counting. If it is 17 character, if I double equal to 17, nothing but I should change the address of the LCD to the C0. Okay, 80 initially I have given. I displayed 16 characters. Whenever the 17th character, I should display onto the second row. Okay, here I have just given the second row. Similar way, if my character is overloaded, completely these 32 characters are filled. Okay, I should display the next character to the first of the LCD. That's why I'm just going to write I double equal to 33 character. I should change the address to the again 80. Okay, here I will just clear I whatever the counting to 0. Again I am just start counting from 0. Whenever it is 17, I am going to change the address to the C0. Again whenever 33, I am going to change to 0. Okay, this is the program I have written. I should always display onto the LCD whatever the received characters. Okay, let us just restart. Whatever my program changes will be reflected here. Welcome to my project YT Training Institute. After that, I will clear complete LCD. Okay, here I will display 1 to 16. 17 characters I should display here as per my program. Whenever the 17 characters, I am changing my address of the LCD to C0 means second row. Okay, I'm going to display next characters until 32. 33 characters I am just changing to again to the first row. 80 means first row. Okay, similar way we will just verify. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q. Here after 16 characters, 17th character I display onto the second row. This is the correct one. R S T U V W X Y Z. Here I will just type small letters A B C D E F G. If I type the G always after 32 characters, I am changing to the 33 nothing but to the changing the address to the 80 starting of the LCD. Whatever my G command, it should display here G data. Okay, just now I am typing G. See here it's displayed onto the again 80. Okay, this is the way whatever the received completely last 16 characters, I am going to display onto the LCD by using this program. Okay, here as per this whatever my expected output, as per my problem statement, we have displayed the content, whatever the received data I just displayed onto the LCD. Okay, successfully we have done this implementation for as per the embedded C by using the embedded C. Similar way we'll write the another program, and we will implement using this embedded C. Write an 8051 C program to monitor bit port 2.5. If it is low, whatever the logic low across this 2.5, we should turn on the LED, otherwise turn off the LED. Connect LED across 2.5, send the LED status, current LED status via the serial port onto the LCD. Here we need both the communications. Here we need serial communication as well as LCD program. Here I have the already LCD program, and also we return the initial baud rate for the program. Here I does not require any I value. From here I will start my program. Okay, here I will just clear my program from the while of 1 onwards. Okay, from here I am going to just display. First I am just setting my baud rate. Why? Because I should transmit whatever my LED status via serial port. That's why I'm just initializing my baud rate with 9600 baud rate with the same configuration with one start bit and one stop bit. And after that I am initializing my LCD communication, and here welcome to my project. I am displaying onto the first LCD, and after some time I'm just clearing 0x01 means clearing. Next, after the 0x80 I am just giving the next first row. I'm just displaying just YT training. In the second row I'm just displaying institute, and after some delay again I'm clearing 80. I will mention like LED status. Okay, here I am going to display in the first row LED status. In the second row, whatever the current status I will display. Here I am going to display the LED status with the colon. Okay, in the second row I will display whether it is LED on or off. Here I need two more pins. Okay, I should connect LED across 2.5, LED across 2.6, and switch across 2.3. Okay, I am going to take one more switch. Okay, here first we'll write the program easily. Okay, after that we'll try to design the hardware. If my switch double equal to 0, if my logic low across the switch, I'm going to turn on the LED. LED I'm just passing the logic 1 means turn on, LED on. Just this I will just mention it as comment. Similar way else part, I should turn off the LED. Else, okay, here I will turn off the LED. Turn off means logic 0, nothing but 0 volts to the that particular pin. Here I will define the two pins here. Okay, similar way I will just copy. Okay, for the SF for special function register, if I want to use only dedicated pin for the dedicated functionality, we should use this S bit in our serial normally in our embedded C programming. Here 2.5 I will connect to the switch, 2.6 I will connect to the LED. Okay, here I will type LED. Here I will type switch. Okay, here in my program, in my while of one program, I have used here switch nothing but whatever I defined here 2 point pin. Whenever the 2.5 pin, whenever the logic low, I am just setting my LED 1, else LED 0. Okay, similar way I am just turning on the LED, otherwise turning off the LED. Okay, as per my program I have implemented. Now here I connected my LED 2.6, send the current status via serial port as well as LCD data. Okay, here I will send first to the LCD. Here I will take the same text now. I will change the later on. Okay, here the second row I'm displaying whatever the status nothing but LED on. Okay, here see whenever I'm setting the this pin particularly that LED will on, whatever the status I am displaying on to the LCD LED on. Similarly I will display second row, C0 means second row. First row I will display always LED status. The second row, whatever the status I am displaying on the second row. Okay, here LED off. Okay, I have displayed onto the LCD. Similar way I should extend further. I should send via serial port. Okay, I will try to extend the program. Okay, we know the program how to transmit in the previous session. Okay, we will just place the data onto the SBUF, and once it is transmitted, we are going to clear the TA flag. Okay, similar way I'm going to write two more programs. Okay, I'm just copying this two functions. I should define two more extra functions to transmit serial data continuously. Okay, here whatever, for example, if I transmit one character of data, here send serial character. Here I will just change my program fully. Okay, here I just want to send the one serial character. Here to send one serial character from the microcontroller, first we should place the data into the SBUF. Okay, here whatever my argument is B, sorry. Okay, that B I'm just replacing to the SBUF. Whatever the for example, to this API I'm just calling with, I just want to transmit a character. Okay, just I will pass like this. Okay, for example, if I want to transmit a character from the microcontroller, just I will pass this a character, single quote, always a character is single quote. Okay, this a character I am passing to B. Whatever the B I am just whatever the content of A I am just whatever the a character I am passing to the SBUF. Here I will check whether this a character is transmitted or not. TI double equal to 0. Here I am waiting until this TA flag always set by the microcontroller hardware. Okay, whenever it is 1, my content is successfully transmitted. Then I will just clear the flag for the next transmission. Okay, this is for the send on character. And similar way I will extend for the string. Okay, here I will just mention send serial string. Okay, here I just written my another function with the pointer as a argument. Here I am just passing, let us assume here I can pass this function one string directly from the main function. Okay, here just I am taking an example LED on, let us assume I'm just passing this string to this function. Okay, here I'm just passing to each and one character to this serial character. Okay, if I want to send this complete string, so that I am just trying to point out letter by letter, that letter I am going to pass to this function. Okay, let us just discuss one by one step here. Just I am passing complete string to here, LED on. Here I am going to point out the first character as capital L. Okay, L is not a null character. Always our embedded C programming, always whatever my C language also always add one null character at the end. Okay, to the string. First it will always point out this L. L is not a null character. That's why I'm going to the inside, and whatever the L value I am just L character I am passing to this function. Yeah, see serial send serial character. Okay, I'm just passing this L value to the SBUF, and whether it is transmitted or not I'm checking. If it is transmitted, I'm just clearing the flag. Okay, similar way E I will just point out. Here I'm just incrementing the pointer. Okay, here I will just point out the E, and similar E I will pass it here. I will transmit, and after that I will increment my pointer. I'm just pointing to D. D is not a null. I'm just passing to the here, and I'm transmitting D also until N. I will transmit. At the end I have the null character. While of null is here, it is always failing, I will exit from the loop. Okay, this is the way we are written this program. This is a reason we written the this extra two functions, and these two functions I will declare at the top. Here I done the definition for these two programs. For the declaration I will do it at the top. Here declaration of these two programs. Here just we need API name and the argument. Just I have just mentioned this one, and here we defined there is no issues. Here I, if I want to transmit a string of data, so that I can pass to this one as we discussed now. Similar way here I will pass here send serial string. Okay, here I'm just passing the same status as we have here. Okay, this LED on, I'm just passing the same text. Okay, here similar way I will take the, in the else part also I will just write the same. Okay, here similar way I'm just sending LED off to the serial communication. Okay, if I pass it to the this function string, I'm just pointing out each and every character I'm passing to here, and this will transmit the data from the microcontroller to the to the external devices. Okay, this program I think we fulfilled. As per our problem statement, we will check whether this 2.5 pin always, if it is low, we are turning on the LED. Here, as per my program, if you see, if it is low, low active low across this switch, and I'm just turning on LED, and I'm whatever the content, whatever the current status, I'm displaying onto the LCD as well as serial communication. Similar way, for example, if it is high, then I am just clearing my LED else part, and similar way I'm displaying the current status over LCD as well as serial port. And here we have some one issue. Then here see semicolon we missed, and just I have added, and I got the executable from the this microvision tool, so that we will flash, so that we can display the, okay, before that we should design this switch and LED to the microcontroller. After that we can just start the simulation. Okay, from here I am going to take the switch from the library. Okay, this switch is the correct one. I am just going to interface it here to the 2.5. Okay, other end I should connect to the ground. Okay, here I have connected to the ground. Similar way I will take LED, one animated LED. Okay, similar way I'm just taking one animated LED, just that also I'm going to connect to here. 2.6 I'm going to connect to the anode, and the other end cathode I'm connecting to the ground. Okay, here the we have the ground, and I have designed the hardware whenever the switch is open. Okay, initially what I will do, initially my port pin is logic 1. That's why I will initially send the logic 0 to the port pin. Initially I should not turn on the LED. That's why I will just turn off the LED initially. Turn off. Okay, here nothing but turn off. Sorry, text, whatever the text I written wrong. Okay, here LED on means logic 1 means LED on, logic 0 means LED off. Okay, here we written the program, and initially my LED I will just turn off. Okay, see here initially LED is turned off, and here see LED off. Here in the serial communication also, if I just pass, here always I am sending LED off, LED off, LED off. Okay, here if you see whatever my current status of LED is off, whatever the LED status I am displaying onto the LCD as well as serial port. Okay, if I just again play my program, if I press the switch, I should transmit LED on to the LCD as well as serial port. If I'm just turning on my switch, means whenever this low, active low, I should send the logic 1 to the LED. Similar way I just displayed onto the LCD as well as serial port. Okay, if I pass here, here in the previous time I displayed LED off. Right now see LED on, LED on, it is displaying. Okay, this way we are just displaying whatever the content as per my program. It is just displaying whenever the LED is off, whatever the current status I am just displaying onto the LCD as well as serial communication port. Okay, as per my program, I am just seeing my output here. Okay, similar way, for example, I will tell you one more command. For example, every time, every this new string, after this string is transmitted, I want to display the into the next character always. For example, this string I want to display into the next line. Okay, after this string is transmitted, I want to come to the next new line of this hyper terminal. So we have one command. Okay, serial character also we can send, right? I will just pass the serial character function with the 0x0d, nothing but new line to the hyper terminal. Okay, it will just create the new line 0x0d. I'm just passing, after passing this string to the serial communication, I'm just passing this command as well. This command nothing but it will create a new line. Okay, LED on new line, it will come to the new line. That way we can see the visualization is very good. Okay, that I will show you now, the whatever the changes. Okay, just I am going to display. If you see LED on new line, LED on new line, new line, new line, this way it will display. Okay, for example, if I just turn off the LED, the text we can see very clearly. If I'm just changing my LED status, LED off, see here LED off. Okay, after every string transmission I'm just sending the 0D command, nothing but new line. Okay, it is creating new line in the virtual terminal, that we are going to see always. Okay, this is a mainly program whatever we have implemented using the embedded C programming easily. Okay, if we know the previous session LCD program, so that we can just return the program very easily as per my problem statement. Okay, thank you friends, thank you for discussing about an interrupt programming using 8051 microcontroller. Interrupt is one of the feature in our microcontroller. If you want to write this interrupt programming, we should be aware of the port programming, timer programming, and serial communication programming. Once we know these three programming, we'll be able to write this interrupt programming very easily. And today we are going to discuss about the some registers: interrupt enable register, interrupt priority register, and tcon register. And also we are going to take the few problem statement that we are going to solve using the embedded C in our interrupt programming. And first of all we are going to discuss about the interrupt versus polling. And whenever any device need a service, we are going to fulfill by using any of the method, interrupt or polling. Okay, first of all, already we written the program for the polling. While of tf0 double equal to 0 semicolon, until my timer overflow I am waiting in this while loop. And until my for example I have loaded 50 milliseconds to the timer, until my timer overflow I'm waiting this place. And this we are calling it as polling. Until any device service completion we are waiting at this point of time. That's why we are calling it as polling. Similar way, while ta double equal to 0 semicolon, until my sbuff transmission I am waiting at this place, and we are fulfilling this device service. And similar way, while ra double equal to 0 semicolon, until successful reception I am waiting at this place, and we are fulfilling this service. And here, if you want to fulfill the three services, we should execute one after another service, so that this we are executing round robin fashion. First we need to complete this service, timer service, after that transmission interrupt service, after that receive interrupt service. Okay, this we are doing in the polling method. Okay, right now we'll be mainly discuss about the interrupt context. Here we are not going to waste any microcontroller time. We can execute another program. Whenever the interrupt comes, I am going to serve those interrupts. For example, I am going to always my execution start from the main programming. I am going to execute step by step in my main programming. Whenever the interrupt comes, I am going to stop at this time. I am going to serve the whatever the requested interrupt. Okay, here I am going to stop the this place the execution, and I am going to complete the current instruction execution. And the next instruction address always stored in the program counter. Okay, here my next instruction address is already available in the program counter. This I am going to copy to the stack pointer. Okay, the next PC address is always holding the interrupt point. Okay, here it will copy the next instruction whatever the PC to the interrupt first address. Okay, here we are calling it as interrupt programming, we are calling it as interrupt service routine. Okay, whenever interrupt comes, I am going to copy the next instruction address from the program counter to stack pointer. And the PC always fetches the interrupt address. Okay, here the PC holds the interrupt address. It is going to fetch from the interrupt vector table. Okay, whenever the here we have the six interrupts. Whenever the reset comes, our program counter will be reset to 4 zeros h. Whenever the external hardware interrupt 0 comes, always our PC holds 0003H. And whenever the timer 0 interrupt, whenever the TF0 overflow, this flag set to 1, our program counter holds with 000B. Similar way, external interrupt 1, external hardware interrupt 1, when our PC will be reset to 0013. Similarly, whenever the timer 1 overflows, TF1 flag set to 1, our program counter holds this address 001B. Similar way, serial communication interrupt TI or RI, our always program counter holds this 0023. Okay, whenever any interrupt comes, I'm going to stop the execution at this point of time. I'm going to copy the current program counter address to the stack pointer. The next address I'm going to fetch it from the interrupt vector table, and that I am going to execute the complete interrupt service routine, and nothing but interrupt program I'm going to complete. Once it is completed, I'm going to retrieve the already stored address from the stack pointer to the PC. Okay, here I am retrieving my address from the stack pointer to PC. Again, I am coming back to this point of time. Again, I am going to execute again step by step from here. Okay, this is the mainly working principle of the interrupt. Okay, here the polling, we should wait until this service completion, but here we no need to wait, we will execute the main programming until interrupt comes. Okay, whenever the interrupt comes, I will stop the execution, I am going to serve the interrupt, I am coming back to the main program. This is the mainly working principle of the interrupt. Okay, here always we have the fixed interrupt, we have the fixed addresses. Okay, reset, we are not going to enable any of the interrupt. In case of external interrupt 0, timer 0, external interrupt 1, timer 1, serial communication interrupt, we should enable the interrupt in the by using IE register. Once it is enabled, whenever the interrupt condition is met, we are going to execute the particular interrupt service routine and again coming back to the main program. These are mainly working principle of the this interrupt context. Okay, here always I am going to count from here, always we are going to enable or disable the interrupt from here. And here this is a external hardware interrupt. Okay, here there is no need of enabling this interrupt. Always this will be whenever I am going to press this external switch, I am going to reset my program counter to 0. This is the this interrupt, there is no need of any enabling in our software. For other remaining 5 interrupts, we should enable in our by using IE register. Once it is enabled, whenever that condition met, for example, this interrupt 0, whenever the any act to low signal to this port 3.2 pin, then only I am able to serve this interrupt. Whenever the this timer 0 overflow flag set to 1, then only I am able to serve this interrupt. Whenever this external hardware this pin having the act to low signal across this port 3.3, then I am going to serve this interrupt. Okay, again similar with TF1 flag, whenever it is set to 1, then only I am going to serve this interrupt. Similar way, whenever the RA flag or TA flag set to 1, then only I am going to serve this interrupt. Okay, here if we want to serve the any interrupt, we should enable the all the interrupts before serving the any interrupt. We should enable the interrupt. Okay, that we are going to discuss. We are going to take the one problem statement that we are going to solve using the all the methods. We are going to write the programming for the timer interrupt as well as the external hardware interrupt as well as the serial communication interrupt. Okay, here always our interrupt addresses always holds from the always 40H to the 0029. This addressing range always holds the interrupt vector addressing. From 30 onwards, we are going to store our always main program. All the interrupt services I am going to store 40H to the 0029 address. Until this time, until this addressing, we are using for the interrupt vector tabling. See here, 40H. Always I am writing the program from origin 0. Here I am always using long jump main. I am going to come to here from the 30 onwards. Always I am going to write my assembly program like this. If in case of whether we, if in case of we have the interrupts, we are going to jump from the LGM to the here. If we don't have any interrupts, we can use it for the this ranging also, we can use it for the special purpose. Okay, here this is a mainly interrupt versus polling, and here we are wasting the microcontroller time. Here we are not going to waste any of the microcontroller time. Here there is no priority in the all the device services, we should execute one after another. Here we have the priority. We have, for example, we have this six interrupts. Whenever this interrupt comes for external interrupt one, I'm executing the timer 0 interrupt. Okay, this timer 0 will be interrupted by the interrupt 0 interrupt. Okay, this is a high priority, low priority compared to the interrupt 0. This is a high to low priorities. All interrupt 0 having highest priority. After the timer 0 having the next priority. This one is the next priority, next priority, next priority. Okay, this is the priority, initial priority order. Okay, here by interrupt service routine always execute the always in the priority, which is the highest priority interrupt that we are going to execute always first. Okay, for example, these two interrupts comes at once, I am going to execute interrupt 0 first. For example, I am executing the timer 0 interrupt. At this time, I received the interrupt 0 interrupt. So that I will stop the execution at this interrupt. I am going to serve this interrupt. Again, I am coming back to this interrupt. This is a mainly execution of the interrupt in our any of the microcontroller. Okay, here we should discuss about the IE register if you want to enable the interrupt. For example, if I want to serve any interrupt, first we should enable the interrupt by using the interrupt enable register. Here we have the all the five interrupts as we discussed here. We have the six interrupt also. This will be used in the 8052, 8952 nothing but 8052. We have the timer 2 also. This is the timer 2 interrupt. Okay, here the interrupt 0 external interrupt 0 interrupt, and this is the timer 0 interrupt, external interrupt 1 interrupt, and here is the timer 1 interrupt, here serial communication interrupt, and here the timer 2 interrupt. This is a EA, enable all interrupt, enable or disable the all the interrupts. For example, if this bit I'm going to set to 1, I'm going to enable the interrupt 0, external interrupt 0 interrupt. For example, if I am setting to this one to 0, I am disabling this interrupt. Similarly, if I am going to set to 1, I am going to enable the timer 0 interrupt. Otherwise, it will be disabled. If I am going to set this bit to 1, I am going to enable the external interrupt 1. Otherwise, it will be 0. Similarly, if I am going to set this bit to 1, timer 1 will be enabled. Otherwise, 0. If I am going to set this bit to 1, I am going to enable the serial interrupt. Otherwise, it will be disabled. Similarly, for the timer 2 also, if I am setting this one to 1 in case of 8052, okay, then only I am going to enable this interrupt, otherwise will be disabled. For example, if I enable the all the interrupts but this bit I am setting to 0, in that case also all the interrupts will be disabled. This is a flag to enable the all the interrupts. For example, if I want to enable the one particular interrupt, I should set this bit to 1 as well as the EA bit also should be 1. Then only I am going to enable the that particular interrupt. Okay, for example, if I want to enable the this timer 0 interrupt, I should set this flag to 1 as well as EA flag also should set to 1. Then only this interrupt 0 should be enabled. Okay, that we are going to write the timer programming now using the interrupt context. Okay, here always our timer programming, timer interrupt always comes whenever this TF flag set to 1, then only I am going to execute the interrupt service routine. See here, whenever the TF0 flag for the timer 0, whenever this TF0 flag set to 1, then only I am going to execute, I am going to fetch the interrupt vector table. From that, I am going to pick the address and I am going to execute the interrupt service routine. Similarly, whenever the TF1 flag set to 1, then I am going to fetch the address from the using the PC program counter. I am going to fetch from this interrupt vector table. Okay, whenever this TF1 flag set to 1, then I need to serve the timer 1 interrupt. Okay, this is a mainly working principle of the timer. For example, I have loaded with 100 microseconds. Let us take the one example.
and that 100 microsecond my timer is overflow, this flag set to 1, then I met my interrupt condition, so that I should execute the interrupt service routine. Okay, whenever this flag set to 1, so that I met my interrupt condition, so that I should go to the interrupt service routine, I should execute my interrupt service routine, I should come back to the main program. This is a mainly working principle of the timer. Okay, whenever my let us remove the code again. Here we are going to write this code from the scratch. Okay, write a C program. Here right now we are going to write the for the timer interrupt. Whenever my timer 0 overflows or the timer 1 overflows, then only I am going to execute the ISR for the timer 0. And here write a C program that continuously gets a single bit of data from 1.7 and it's sent to 1.0. Okay, this we can write into the always in the main context, while continuously creating the square wave of 200 microseconds period on the port 2.0 pin. Use timer 0, create the square wave, assumes the frequency 11.0592. Okay, here first we will use the timer 0 mode 2. Why? Because within this 200 microseconds I should only create the delay for the only 100 microseconds. Why? Because here one half of the period is 100 microseconds. Why? Because for the active low I will keep the 100 microsecond. For the active high, for the this 2.5 pin, active low is 100 microseconds, active high is 100 microseconds, so that we will create the square wave of 200 microseconds. Okay, that's why we should create the time delay of 100 microseconds. That's why I am going to load the 100 microseconds timing value to the this timer 0 mode 2 value. Okay, 100 always we should divide with 1.085 microseconds. For example, if I want to generate 200 microseconds delay, 200 divided by 1.085 microseconds. Okay, similar way we need to do the same. Okay, here I got the 92 value. Okay, always we should subtract from the 256. My timer 0 mode 2, what is my maximum range is 256. That's why I'm subtracting 256 minus 92. Always my timer overflows whenever my timer reaches all FF, then only my timer will be overflow. That's why I'm going to subtract from the 256 value. That's why I'm loading with A4 to FF. Whenever my timer overflow, my TF flag set to 1. Then only I am going to execute the interrupt service routine. Okay, I am going to write the this port 2.0 in the interrupt context. This square wave always I am going to execute in the interrupt context. This I am going to write in the main context. Okay, right now I am going to write the timer interrupt programming. First, we should be aware of the timer programming. First we should set the T mode to 0x02. Okay, nothing but timer 0 mode 2 mode 2, nothing but auto reload mode. Okay, this is my timer 0 mode 2, nothing but here if you use this T mode, we are going to set the particular timer mode of operation. Okay, next th1. Okay, th0, we are using the timer 0, that's why we should load with a4 as we calculated in the excel. A4 tl0 also I am loading with 0x a4. Why? Because whenever this TL value overflow, automatically this TH value will be copied to this TL value in case of auto reload mode. Okay, next I should enable the interrupt. Okay, I should use the IE register. Okay, here we should write the some specific hex value, so that I am going to the IE register. Here I should enable that particular timer 0 interrupt, right? Here this bit should I should set to 1 always. EA flag should set to 1, and also this flag the second bit. Okay, second bit means nothing but timer 1. Okay, what is my value? This is my 82. Okay, this is my 82 value. Okay, if I just this is my binary representation, this is my corresponding hex value. Okay, this flag I should set to 1. If I want to enable the timer 0 interrupt, this flag I should set to 1, as well as EA flag also. 1 triple 0 double 0 1 0. Okay, similar I written in the binary format, and that equivalent hex is 0x82. Okay, if I want to enable this timer 0 interrupt, I should write the 82. Here enable the timer 0 interrupt. Okay, here I have enabled the timer 0 interrupt so that I can start my timer. After enabling that, I can start my timer. Okay, in my while loop, I'm going to write the main programming. Always I should execute the main programming. Whenever the interrupt comes, I should jump to that programming. Okay, here in my main context, I'm going to copy the data from the port 1.7 to 1.0. Okay, here I will take 2 bits as bit. Here I will call it as in port 1.1 cap of 7, and one is the out out bit. Okay, here this is my out bit. I'm calling it as port 1.0, right? We can just go to the this one. 1.7 is the in bit. I should send to the 1.0 pin. Okay, here I am just defining with 1.0 pin. Okay, this is my in pin. Whatever the value across this pin, I am copying to the out. Okay, this is my always my main program. Always my execution always will be in the while one loop. Always I'm just copying this into out. Whenever the interrupt comes, I should go to the interrupt service routine. Okay, here I'm going to write my interrupt service routine. Void here my I will call it as timer 0 underscore interrupt. Okay, here this is my function name. We can write any of the naming. Here we should write the what is the interrupt number we should write. Then only I will go to that respect to ISR. Okay, here reset we should not consider. This is my interrupt 0 is my this one. Now naming in the embedded C. Okay, this is my naming in the embedded C. Okay, this is my interrupt 0. This is my interrupt 1, interrupt 2, interrupt 3, interrupt 4. This is my embedded C interrupt naming convention. This is my interrupt 0, this is my interrupt 1, interrupt 2, interrupt 3, interrupt 4. Right now I am writing for the timer 0. This is my interrupt 0, interrupt 1. I should write the interrupt 1 here. Interrupt 1. Okay, here nothing but timer 0. Okay, if I want to write the interrupt service for the interrupt 0, external interrupt 0, so that I should write the interrupt 0. Okay, okay, this naming already this is predefined in the embedded C. Okay, here for the external interrupt 0, okay, this interrupt, okay, this we should remember. Okay, for the external interrupt 0, I am calling it as interrupt 1. Okay, for the timer 0 interrupt, I am calling it as interrupt. Okay, here interrupt 0, sorry, starting with interrupt 0. Okay, here interrupt 1 similar way, and next one is external interrupt 1 is interrupt 2, interrupt 2, this is my interrupt 1. Okay, here we'll write the same, otherwise we'll forget always. Here for the again for the timer 1 interrupt, nothing but interrupt 3. Okay, this naming should we should remember always, 3. And last one is a serial interrupt equal to interrupt 4. Okay, this naming we should remember always, we should call it as 4. Okay, this I am just commenting for the currently. Okay, we should always remember this naming. Okay, for the right now I'm going to write the right now I'm going to write the programming for the timer 0 interrupt. That's why I'm writing interrupt 1. Okay, and here we should always generate the square wave. That's why I'm defining one more pin with the wave equal to port 2 kappa 5. Okay, here I am going to define as per my problem statement. Here 2.5 I should generate the square wave every 100 microsecond. I should execute this interrupt. Okay, this interrupt will be called every 100 microseconds as per this interrupt. Okay, here I am always toggling my pin equal to wave. Okay, here I written my program. I should clear my overflow flag here. Okay, okay, I will explain the execution of the program now, and similar way we'll execute in Keil as well as the Proteus. Okay, right now I am going to compile. Let's see if we have any issues. No. Okay, here see, always I am going to select my timer 0 mode 2. Here I have loaded my 100 microsecond value. 100 microsecond value. Okay, whenever this 100 microsecond elapses, my TF0 flag set to 1. Okay, TF0 flags equal to 1. Okay, this will be set to 1 whenever this 100 microseconds is elapsed. Okay, I'm going to this interrupt programming. I'm going to toggle from initially it will be 1. I'm going to toggle to 0. Okay, again I'm going to reset my interrupt flag to 0, whatever my TF0 flag. Okay, if you see here, whenever this TF0 flag set to 1, then only my interrupt will be triggered. I'm going to execute this interrupt. Whenever the exiting of this interrupt, I'm going to clear the TF0 flag. Again, my timer is auto reload mode. Okay, whenever this TL0 is overflow, always this TH value will be copied to TL. Again, this will rolls from A4 to FF. Again, it is overflow. Again, every 100 millisecond, this will be called. I'm going to toggle this pin always. Okay, okay, always I am going to toggle this pin always 1 to 0, 0 to 1. Always I am going to toggle this 2.5 pin. That means we are generating the square wave using this port 2.5 pin. Okay, and parallelly in my main execution I am always doing the copy whatever the data in from whatever the data in our port 1.7 I'm copying to the out pin. Okay, we'll discuss the same. We'll try to execute the same whether as per my program we are executing or not. Okay, here similar way we'll save our program. Let's see. Okay, here I'm just saved my program, and again I compile, no errors, and yeah, I'm just debugging the same. Okay, here we need port 1 and port 2. Okay, here I took the interrupt table also, and we'll see whether we have enabled our particular interrupt or not. Here I need port 2. Okay, as we discussed initially, if you want to write any program, we should be aware of the port programming, timer programming, and the next we'll discuss about the serial communication also. Okay, here I am going to execute my step by step program. T mode I just selected as timer 0. This is my timer 0 mode 2, 8-bit auto reload mode. 8-bit auto reload mode. Okay, if I just loaded with 0x to 0, I just shifted to my timer 0 to the mode to 8-bit auto reload mode. Here I have loaded, I need to load TL0, TH0. TH0 I have loaded, TL0 also I loaded. Okay, next I am just initially my timer is stopped state. Now, right now I am going to start my timer. Okay, T or 0 is 1. See here, I started my timer. Whenever my timer overflow, this TL will roll from A5 to FF. Then I'm going to execute this ISR once. Okay, and I'm going to clear this TF flag to 0. Again, my automatically whatever the TH value will be loaded here. Again, whenever it is overflow, every 100 millisecond, I'm going to call this timer interrupt. Okay, let us execute one by one. Here this TL value in case of auto reload mode, always this value will be rolls from whatever the loaded value to the max value. Whenever it is overflow, nothing but we finished the 100 microseconds. Okay, until 100 microseconds I am executing some other program here. Okay, this is the mainly use of the interrupt. Okay, here I am going to execute other programming this 100 microseconds. Whenever this 100 microsecond, this is rolling from A4 to FF. Now it is D, D3, D, next E, E0 to EF, F0 to FF. See, whenever it is reaches FF, and again automatically reloaded this A4 to here. Right now I am in the interrupt 1. Okay, I just finished the 100 microseconds. I came to here. I am going to clear this TF flag now. Okay, I have cleared my TF flag. Again I will come to here. I am always executing this program. Again this will roll from A4 to FF. Again I will come back to here. Okay, every 100 microseconds I am toggling this bit. 0 to 1 1 to 0 0 to 1 1 to 0, so that we are generating square wave, exact square wave across this 2.5 pin, and parallelly we are copying this 1.7 bit to 1.0 bit. Okay, this is my 1.0 1.1 1.2 1.3 1.4 1.5 1.6 1.7. Okay, here this bit I am just changing. Let's see the automatically whatever this value should be copied to the 1.0 pin, this pin. Okay, here see whatever the value across this pin I'm copying to here. This is my main programming. Always I'm executing the main programming. Whenever any interrupt comes, I should execute this once. I'm coming back to here. Okay, always execution of the exit of the interrupt, we should clear the interrupt flags always. Okay, why otherwise we will be always staying in this interrupt only. That's why I'm clearing the interrupt flag. This is a mainly interrupt programming we should write always. Okay, here I am going to see the same output here in the 2.5. Okay, I'm going to check whether we are really generating the square wave or not. Okay, here I'm just taking the oscilloscope, and just I'm connecting to the 2.5, and we should check whether we are really generating the square wave or not. See here, I will just zoom out. See, I'm just generating exact square wave across this channel 1 2.5. This 2.5 pin I connected to the oscilloscope of the first channel, so that we are going to see the square wave always across the this 2.5 pin. Okay, here with 100 microseconds we are generating the square wave exactly as per my program requirement. We have fulfilled using the timer interrupt. Okay, this is mainly about the timer interrupt. Okay, similar way we'll discuss about the external interrupt. Either can be the interrupt 0 or interrupt 1. First we should discuss about this tcon register. Okay, for in case of this external interrupt, we can execute either in case of level triggering or the edge triggering. Always it should depend on the external clock. It should always whether active low, or always we should detect the active low, then only I will execute the interrupt service routine. Okay, here initially my port 3.2 pin and port 3.3 pin both are initially logic high. Whenever the it is detected the logic low, then only I will go to the that interrupt service routine. Okay, this is a mainly working principle of the external interrupts. Okay, this IT0 IE0 mainly to select the level triggering or edge triggering for the external interrupt 0. These two are for the external interrupt 1. For example, this IT0 is the it will decide whether it is level triggering. I want to execute this interrupt 0, external interrupt 0, level triggering or the edge triggering. Okay, similar way for the edge triggering, if you want to enable this flag should set to 1. Okay, in case of edge triggering, these two flags I should set to 1. In case of level triggering, these two flags set to 0. Okay, there is no change in the tcon register, then initially we'll treat it as level triggering. Whenever these two flags set to 1, I will consider it as a edge triggering. Okay, similar way for the this is for the external interrupt 0, these two flags for the external interrupt 1. These two flags set to 1, I will consider it as a edge triggering. If these two flags are 0, I will consider it as a level triggering. Okay, we'll see the how we are going to execute. This is a external interrupt 0, nothing but port 3.2 pin. Whenever my IT0 is 0, I will consider it as level triggering. That to active low. Okay, here we have the tri-state, here we have the inverter. Always it should consider active low signal. And how much periodicity will be there for the level triggering, that we'll check in the next slides. Okay, right now for the level triggering, this IT0 flag is 0. Okay, if I am not using any of the tcon register, if I am loading any of the flags to in the tcon, so that initially I will be in the level triggering. Okay, whenever this IT1 and IE1 is 1, I am going to consider the edge triggering. Edge triggering always a high to low transition. Okay, always we should consider the high to low transition. Level triggering also it should be low level. Okay, low level, then only I will consider whenever the low level detected, I will consider the interrupt condition is met, I should execute the my ISR always located in the 0003 or the 0013 for the interrupt 1. Okay, the similar way here whenever this based on this IT0 IE0 flag, then we are deciding either it is a level triggering or the edge triggering. Similar way for the interrupt 1. Okay, Here for the level triggering, I should always get the active low signal for the at least 4 machine cycle. Then only I will consider it as external interrupt condition is met. Okay, for the port 3.2 pin or the 3.3 pin, for example, I have enabled my interrupt. Whenever that 3.2 pin, if it is detected the active low signal for the 4 machine cycle, then I should jump to that particular ISR. Okay, this is for the level triggering. In case of edge triggering, at least one machine cycle should be high, one machine cycle should be low. Then only I will consider it as okay. The edge triggering is detected across the port 3.2 pin or the port 3.3 pin. Then we will serve based on the which interrupt is enabled, and we are going to serve those interrupts. Okay, right now I am going to write the programming for the assume that interrupt one pin is connected to a switch, okay, that normally is high. Initially port 3.2 pin, right now we are going to write for that interrupt one nothing but 3.3 pin. Okay, interrupt one means 3.3 pin. Whenever the 3.3 pin initially always will be high, whenever it is go slow nothing but whenever the interrupt is condition is met, and we should execute the our interrupt ISR. Okay, in the ISR context, I am going to turn on the LED, and LED should be connected across port 1.3. Okay, right now I am going to write the external interrupt programming. As of now, we written for the timer interrupt. Right now I am going to write for the external interrupt. Okay, here I am going to change my program name. Here I will call it as external interrupt 1. Okay, this is my any name we can give it here, but here it should be based on our. Right now I am going to write for the interrupt 1. Sorry, this is for the interrupt 1. Okay, this is my interrupt 0, timer 0, interrupt 1, timer 1. Okay, here I am going to write the programming for the interrupt 2 now. Okay, right now I should write the in my ISR interrupt 2 nothing but external interrupt 1. Okay, here I written the programming ISR for the external interrupt 2 nothing but interrupt to nothing but this is my ISR naming convention. Interrupt to nothing but external interrupt 1. Yeah, okay, we written the ISR as well as the main program. Okay, right now we should write the programming as per the problem statement. Here I'm going to connect the switch always across this one. Okay, here port 3.3 pin I should not going to define anything initially. It will treat as the interrupt. Okay, right now I am not going to define any pin to here. I'm going to define only one pin across 1.3 pin. Okay, as bit LED, I'm just going to connect LED equal to port 1 cap of 3. Okay, here I'm just going to connect the LED across 1.3. Okay, whenever it is go slow, automatically I'm going to execute the interrupt programming. Okay, here always I should load the interrupt enable register always. Okay, I should enable the interrupt 2 nothing but external interrupt 1 I should enable using the IE register. Okay, I am going to the IE register again. Okay, here I should enable the interrupt 1 external interrupt 1 nothing but 1 triple 0 Okay, here 0100. Okay, here I am just setting this bit to 1 as well as EA. Then only this external interrupt 1 bit will be set to 1. Here nothing but 84. Okay, this 84 value if I load, nothing but I am just enabling the external interrupt 1. Okay, 84. Okay, whenever this condition is met, whenever the external interrupt condition is met, nothing but whenever here external interrupt 1 condition met means whenever the level triggering or edge triggering is detected. Whenever the active low for the level triggering, for the edge triggering one clock pulse high, one machine cycle active low. Okay, one machine cycle active high, one machine cycle active low. Okay, this whenever this clock is detected, and automatically I'm going to execute the ISR. Okay, right now I'm considering it as a level triggering. There is no need of initialization in the IT0 IE0. Okay, here there is no need of initialization here, and initially I am considering it as level triggering. Whenever the active low comes across this 3.3 pin, I should execute this interrupt. Okay, here I just written my program. Okay, here initially I am setting my LED to 0. Okay, to check whether I whether I'm just turning on the LED or not. Okay, here I'm just setting my LED to 1. Sorry, here I'm just turning on my LED whenever the interrupt comes, whenever the any active low signal detected. Right now we are writing for the level triggering. Okay, if you want to write for the edge triggering, we should initialize this tcont IT0 IE0 flags to 1. Then we will execute the edge triggering. Okay, initially it will treat as level triggering. Okay, here I have enabled the interrupt whenever this condition is met. Okay, here I am writing my while of one condition. Always I am going to execute this program always. Okay, here I am going to here while of one I'm going to write nothing, I'm going to write here. Okay, always I will be executing this while of one. Okay, here always my execution start from main, and always I am in the while one loop. Okay, whenever the interrupt comes, whenever the active low detected across the port 3 point pin, I'm going to change the LED to 1. Okay, this logic I'm just setting to 1. Okay, check whether as per the program whether it is working or not. We'll try to debug now. Okay, always I should stay in the, okay, I need this interrupt table right now. Okay, and as well as the, and I need port 1 and port 3. I need port 3 also, so that I'm just taking the port 3. Okay, port 3.3 pin, whenever the active low is detected, then only I will go to here. Otherwise I should be stay in the main function. See here always I'm staying across this always main function. When the interrupt comes, whenever the active load detected across the port 3.3 pin, 3.0, 3.1, 3.2, 3.3 pin, whenever it is active load detected, right now I should go to the interrupt. I should turn on this LED. Okay, this 1.3 LED I should turn on now. I should go to the interrupt. I should execute this loop. Nothing but I should turn on the LED. See here, I just turn on the LED. For example, this active low I should remove. Okay, if I am just exiting from the this interrupt, I should remove this interrupt condition. Okay, whatever the interrupt condition I have to remove. Otherwise, I should always stay. I will come to the main. Again, the interrupt is detected. I will go to the again interrupt context. See here, I'm coming to the main program. Again, I will check whether my active low signal is detected across the port 3.3 pin. Okay, still active low. I should go to interrupt again. See here, I'm just going to the interrupt again. Okay, again I'm coming back to the main. Okay, if I want to stay always in the main programming, I should remove the active low across the port 3.3 pin. I will always stay across the port always in the main programming. Okay, this is the mainly working principle of the external interrupt. Okay, similar way we'll execute in the interrupt in our Proteus. Here I need 1.3. I should connect LED. Okay, this design I am just removing. 1.3 I am just connecting LED. Here we just type the LED, then automatically we will see so many LEDs. Okay, here I am just taking and connecting to the 1.3. Okay, the other one I should connect to the ground. Okay, I have connected my LED. Now I should create the active low pulse across the 3.3 pin. Okay, that's why here I am connecting switch across the 3.3 pin. Okay, whenever if I just press my switch here, right now we are working on the interrupt one, nothing but we are connecting 1.3 pin. Okay, whenever this active low comes, automatically it should go to the interrupt. I should turn on the LED. This is the program we written here. Whenever the active low detected, nothing but whenever the interrupt is detected, automatically I should go to the ISR. I should execute this piece of code, nothing but I should turn on the LED. Okay, if I just press this switch, I should turn on the LED. Okay, this is the mainly working principle of the external interrupt. Okay, similarly if I want to write the for the edge triggering for the interrupt one, I should set this IT one flag and IE1 flag. These are the bit or byte addressable, so that I can just write here IT1 in the main programming, IT1 equal to 1. Similar way we can write, I think capital we should write IT1 equal to 1. Okay, this will work as it is in the edge triggering high to low. Okay, similar way IE1 equal to This edge flag is also 1. Okay, if you write this two statement, then we are going to execute the edge triggering. These are mainly working principle of the external interrupts. Okay, similarly, we will take one problem statement for the serial communication. Okay, here already we are aware of whenever the serial interrupt comes, whenever this successful transmission, this TA interrupt will come. Automatically, this TA flag set by the hardware, automatically transmission interrupt will be triggered, and we are going to execute this ISR 002C. Our PC holds the this ISR address. Similar way, this serial communication we have only one interrupt. That's why here we are doing the OR operation. Either I can get the transmission interrupt or the receiver interrupt, only one at a time. Okay, that's why here for the TA or RI we have only the one interrupt. And for the serial communication we are going to take one problem statement that we are going to solve using the embedded C. Okay, right now I'm going to write for the receiver interrupt. Okay, here we'll see how we are going to enable the receiver interrupt. Here we should be aware of the port programming, serial communication programming, as well as the timer programming. Okay, here write a C programming interrupts to do the following. Okay, receive data serially and send it to the port 1 in the serial interrupt context. Okay, here we should receive the data serially and send it to the port 1. This should we should write in the interrupt context. Get the single bit of data from 2.7 and send it to the 2.0 in the main program. Okay, assume crystal oscillator frequency 11.0592 megahertz. Set the baud rate to 9600 baud rate. Okay, if you know the serial reception program, so that we can just write the interrupt programming also very easy way. Okay, similar way here, just I am removing all other code, and the interrupt we should change, right now we are in the serial reception. Nothing but what is my serial interrupt 4. I should write the interrupt 4 here. Nothing but this is my interrupt, serial interrupt. Okay, this is ISR will be treated as serial interrupt. Okay, this is my serial interrupt. Okay, here we can just change the here our program name can be anything. Okay, here I can just change my programming to the serial interrupt. Okay, this programming naming can be anything. This should be always, if it is serial interrupt I should always write the interrupt 4. If it is timer 1 interrupt I should write the interrupt 3. Okay, here I written the ISR as well as the main programming. Right now we just will read the problem statement. For the interrupt context we'll write in the next time. Okay, the second statement will write this is the main programming. Okay, get the single bit of data from 2.7 and send it to the 2.0. Okay, right now I will consider it as bit in is 2.7, port 2 cap of 7, and the other one is 2.0. Yeah, out bit is 2.0. As bit out is port 2 cap of 0. Okay, this is the two bits I have written. And okay, first we should set my baud rate to the 9600 baud rate. That's why I'm just selecting T mode always, timer 1 mode 2, 0x20. This is my timer 1, timer 1 mode 2, mode 2 auto reload mode, auto. This is my timer 1 auto reload mode, timer 1 mode 2 auto reload mode. This is my comment I'm writing here. Nothing but okay, here I'm just loading with FD th1 equal to FD, nothing but 9600 baud rate. This should be 0x. Actually I'm loading it. This is nothing but 9600 baud rate. Okay, next SCON I should write SCON with 0x50, nothing but 8-bit data, 8-bit 8-bit data, one start bit, one stop bit. Okay, this is the mainly nothing but 50. Okay, and here I just initialized my thing. Okay, next here before that I should enable the interrupt. Okay, I have set my baud rate and also serial configuration mode also I have selected, T mode also selected. Next here I should write the IE register. In the IE register I should enable the interrupt, then only I can serve the this interrupt. Okay, that's why I am going to the IE register again. I should enable the this IE register to the particular serial interrupt. 1001, nothing but 9, all zeros I can mention. Okay, this is my 9, remaining all zeros. Okay, I'm not going to enable any of the interrupt. This 4 bits I'm just setting to 0. This bit I have set to 1, and the remaining two zeros and 1. Okay, this is my nothing but 90. If I just initialize with 90, I'm enabling the serial interrupt. Okay, whenever the ta flag or ri flag set, then I'm going to execute this isr. Once it is exit of the program, I'm just going to clear the flag. Okay, this is my serial, enable the serial interrupt, enable the serial interrupt. Okay, here I have enabled my serial interrupt. Okay, next I will start my timer one here. Okay, I'm just setting had set my baud rate as per the 9600. Here I have just set my baud rate. Here in the while of one, I'm just writing my main program. Always I'm just writing my main program. I'm just copying in bit to the out bit. This is my main programming as per the problem statement, out to the in. Okay, here the main programming always I have written, and I'm just copying to that. And whenever the successfully received, and I am going to come here, I'm going to copy the data from the uh, serial buffer to the port 1. Okay, this part I should do it here. Okay, port 1 I should copy whatever the received data from the external. Okay, from the sbuff. Sbuff holds the always received data. See, I am always executing the main program. I am always copying the in bit to the out bit. Okay, whatever the value is in there, is there in the this 2.7 data, I am always copying to the out in the main programming. Always I am executing this one. Whenever the data serially received, and I am going to copy the sbuff to the, I am going to execute the ISR. Whenever the RI flag set to 1, okay, here RI flag is set to 1. I'm going to come here, and the end of the program I'm going to reset RI flag for the next reception. Okay, next ISR to be triggered. Otherwise, I will always stay in the always interrupt context. That's why I'm just clearing that flag, and let us execute once. Okay, here I have cleared my flag. Okay, I have executed as per the program. Okay, let us debug in the directly in the our proteus. Okay, let us execute step by step here, and I will see the all the interrupt table also. T mode, I have selected my T mode, timer 0. This is my timer 1, sorry. I should take the timer 1. Okay, here we'll see whether I'm going to enable the receive interrupt or not. One by one we can just check. Okay, here at th1 I just th1 I have loaded with ff. I should load with fd we loaded, and to mode to 8-bit auto reload mode, and scon with 50. Here we can take scon with 50. We should set scon with 50 8-bit variable baud rate. This is my configuration, and IE I am just setting to the 9. Okay, here I have enabled the receive interrupt and as well as the transmit interrupt. Okay, whenever this interrupt condition is met, nothing but this ri flags is set to 1. When the sbuff is received successfully, this ri flag set to 1, then I will come to interrupt. Okay, this is the mainly working of the serial communication, and otherwise I will always stay in the port, always in the main programming. I should open the port 2 now. Okay, I should open the port 2, whatever the 2.7 bit, right? 2.7 bit I'm copying to the 2.0. If I execute now, whatever the value across this logic low, that will be copied to the 2.0. See, okay, here it's copied to the 2.0. Okay, this is a mainly execution across the main program. Okay, if I just set this bit to 1, the 2.0 bit also will be set to 1. Okay, this is a main program execution. Whenever the interrupt comes, whenever the data serially received, I should go to here, I should copy to the port 1, I should clear the interrupt. Okay, this is mainly serial interrupt working. Okay, right now we had the executable. Right now I am going to design my hardware, and I am going to feed the data from the terminal, and that data will be received across the port 1. Okay, here I am going to connect a group of LEDs across the port 1. Okay, here I will take LEDs array. Why? Because I should receive the whatever the received data to the port 1. That's why I'm just taking the group of LEDs. Here we should type the LED. Here we'll get group of LEDs here. Okay, here we have somewhere we have the group of LEDs that we can take. Here we have the group of LEDs. You can take any one, red or green. Okay, here I am just interfacing all the LEDs to the array. Okay, this thing I'm just interfacing one by one. 1.0, 1.1. Okay, here similar way we should connect all the 8 pins to the 8 LEDs to the left side. Okay, similar way we should connect all the LEDs. Okay, two more bits are left. Okay, I have connected 8 LEDs here, 1.0 to 1.7, and here I should connect the ground right side. The other end always I should connect to the ground. Okay, here whatever the data received by microcontroller to the SBUF, and that data I should copy to here in the interrupt context. That we return the program, and similar way we should verify here. Okay, here in the serial port I will connect. Okay, here virtual terminal I will interface. This is the TX, I should connect to the RX. This TX I should connect to the RX. Okay, here I have flashed as we executed here. Initially, my port bits are all are one. If I just press the capital A, I should receive in the interrupt context. Okay, whenever the successfully received by SBUF, this RA flag set to 1. Whenever it is RA flag set to 1, I will come to interrupt context. I will just copy the whatever the value to the port 1. If I just type the capital A nothing but 41, and this LED should set to 1, and this LED should set to 1. Okay, let us see here 40, this LED and this LED set to 1. Okay, next if I just press the B, and this one 42, nothing but the second LED. Okay, here I am just whatever whenever the interrupt comes, 1 minute, sorry, and we should change the baud rate to 11.0592. That's why we see some mismatch in the data. 11.0592, nothing but this is my serial baud rate, always I should set. Okay, that's why it does not see capital A here. See, right now this second LED, this LED should glow. This is my 40 01 0040 001. Okay, this LED and this LED is on. 41 01 00 001. This is my 41 capital A value. Capital B value means 42. Okay, 01 00 0010. Okay, this is my capital B. Whatever the received data, I am going to send it to, across this port 1. This is my interrupt context we were written. Whenever the RA flag set to 1, nothing but we received the data successfully to the SBUF, that we are copied to the whenever the interrupt comes, the this flag set to 1, my interrupt will be triggered. I should copy this one, I should clear for the next reception. Again I will coming back to the main program, I will execute. Whenever the interrupt comes, I should copy to the port 1. Okay, this program we have written successfully, and we have executed successfully in our Proteus. Okay, that's all friend. And one more thing, IP register we want to discuss at the end. Okay, this is the IP register. This is the initial priority as we discussed in the initially. Okay, highest to lowest. This is the highest priority. Interrupt 0, external interrupt 0. Next timer 0 is the next priority. Next interrupt 1 is the external interrupt 1 is the next priority. Next priority is the timer 1 interrupt. And the last priority is the TAR RI. This is the initial priority upon a power on. Okay, if I want to change the initial priority, for example, if the interrupt 0 and timer 0 comes at once, initially it will serve the interrupt 0. For example, I should serve the timer 0 first, so that this timer 0 flag I should set to 1. This is my interrupt 0 priority change. This is my interrupt 1 and timer 0 priority change. This is my interrupt 1 priority change. This is my timer 1 interrupt priority change. And here the serial communication interrupt priority change. This is my timer 2 for the 8052. Okay, this is the mainly if I want to change the existing priority, so that we can use the IP register. This is the mainly use case of the IP register, enter priority register. This is my initial priority. For example, initially if these two interrupts are triggered, I will serve the interrupt 0. Okay, in case if I just set the TF0, this flag I'm going to set to 1. Okay, if I just get that these two interrupts, timer 0 interrupt will be served. Why? Because this priority I am just setting to the highest priority to the timer 0. Whenever this two interrupt comes, I will serve the this timer 0 interrupt. Why? Because this priority I changed to 1. Okay, this is a mainly working principle of the interrupt priority register. Okay, IP register. Okay, this is also bit or byte addressable, and we can access bitwise as well as the complete bytewise also. Okay, in IE register we access bytewise. If you want, we can access bitwise also. EX0 we can set to 1, EA also we can set to 1. Okay, this also we can set bit by bit or the byte by byte. Okay, thank you friends, thank you for watching.